world can continue to get weird. Again, I don't think it's avoidable. It's physics. But we can help lift people, scale, do things with it. They don't have to rewrite their code every time a new device comes out. And I think that's pretty cool.
The following is a conversation with Chris Lackman, his third time on this podcast. As I've said many times before, he's one of the most brilliant engineers in modern computing, having created the LLM compiler infrastructure project, the Clang compiler, the Swift programming language, a lot of key contributions to TensorFlow and TPUs as part of Google. He served as vice president of autopilot software at Tesla, was innovator and leader at Apple, and now he co-created a new full-stack AI infrastructure for distributed training, inference, and deployment on all kinds of hardware called Modular, and a new programming language called Mojo that is a superset of Python, giving you all the usability of Python but with the performance of C, C++. In many cases, Mojo code has demonstrated over 30,000x speed up over Python. If you love machine learning, if you love Python, you should definitely give Mojo a try. This programming language, this new AI framework and infrastructure, and this conversation with Chris is mind-blowing. I love it. It gets pretty technical at times, so I hope you hang on to the ride. This is the Lex Fridman podcast. To support it, please check out our sponsors in the description. Now, dear friends, there's Chris Lackman. It's been, I think, 2 years since we last talked. In that time, you somehow went and co-created a new programming language called Mojo. So it's optimized for AI. It's a superset of Python. Let's look at the big picture. What is the vision for Mojo?
For Mojo? Well, so, I think you have to zoom out. So I've been working on a lot of related technologies for many, many years. So I've worked on LLVM and a lot of things in mobile and servers and things like this. But the world's changing. And what's happening with AI is we have new GPUs and new machine learning accelerators and other ASICs and things like that make AI go real fast. At Google, we worked on TPUs. It's one of the biggest, largest scale deployed systems that exist for AI. And really what you see is if you look across all of the things that are happening in the industry, there's this new compute platform coming. And it's not just about CPUs or GPUs or TPUs or NPUs or IPUs or whatever, all the PUs, right? It's about how do we program these things, right? And so for software folks like us, right, it doesn't do us any good if there's this amazing hardware that we can't use. And one of the things that you find out really quick is that having the theoretical capability of programming something and then having the world's power and the innovation of all the smart people in the world get unleashed on something can be quite different. And so really where Mojo came from was starting from a problem of we need to be able to take machine learning, take the infrastructure underneath it and make it way more accessible, way more usable, way more understandable by normal people and researchers and other folks that are not themselves like experts in GPUs and things like this. And then through that journey, we realized, hey, we need syntax for this. We need to do programming.
So one of the main features of the language, I say so fully in jest, is that it allows you to have the file extension to be an emoji or the fire emoji, which is one of the first emojis used as a file extension I've ever seen in my life. And you ask yourself the question, why in the 21st century are we not using Unicode for file extensions? Because it's an epic decision. I think clearly the most important decision in but you could also just use MOJO as a file extension.
Well, so take a step back. Come on, Lex, do you think that the world's ready for this? This is a big moment in the world, right?
We're releasing this onto the world.
This is innovation.
It really is kind of brilliant. Emojis is such a big part of our daily lives. Why is it not in programming?
Well, and you take a step back and look at what file extensions are, right? They're basically metadata, right? And so why are we spending all the screen space on them, all this stuff? Also, you have them stacked with text files and PDF files and whatever else. Like, if you're gonna do something cool, you want it to stand out, right? And emojis are colorful, they're visual, they're beautiful, right?
What's been the response so far from
Is there support on like Windows on operating system in displaying like File Explorer?
Yeah.
Do they-
The one problem I've seen is the Git doesn't escape it right.
Mhm.
And so it thinks that the fire emoji is unprintable, so it like prints out weird hex things if you use the command line Git tool. But everything else, as far as I'm aware, works fine. And I have faith that Git can be improved. So
And so
I'm not worried.
GitHub is fine.
GitHub is fine. Yeah, GitHub is fine. Visual Studio Code, Windows, like all this stuff, totally ready because people have internationalization in their normal part of their past. So this is just like the next step, right? It's somewhere between, oh wow, that makes sense. Cool. I like new things. To, oh my God, you're killing my baby. Like, what are you talking about? This can never be, like, I can never handle this. How am I going to type this? Like all these things. And so this is something where I think that the world will get there. You don't have to bet the whole farm on this. I think we can provide both paths, but I think it'll be great.
When can we have emojis as part of the code?
Yeah, so I mean, lots of languages provide that. So I think that we have partial support for that. It's probably not fully done yet, but yeah, you can do that. For example, in Swift, you can do that for sure. So an example we gave at Apple was the dog cow. Yeah, so that's a classical Mac heritage thing. So you use the dog and the cow emoji together next to your variable name. But of course, the internet went and made pilot proof for everything. So, you know, if you want to name your function pilot proof, then you can totally go to town and see how that gets through code review.
Okay, so let me just ask a bunch of random questions. So is Mojo primarily designed for AIs, or is it a general purpose programming?
Yeah, good question. So it's AI first. And so AI is driving a lot of the requirements. And so Modular is building and designing and driving Mojo forward. And it's not because it's an interesting project theoretically to build, it's because we need it. And so at Modular, we're really tackling the AI infrastructure landscape and the big problems in AI, the reasons that it is so difficult to use and scale and adopt and deploy, and like all the big problems in AI. And so we're coming at it from that perspective. Now, when you do that, when you start tackling these problems, you realize that the solution to these problems isn't actually an AI-specific solution. And so what we're doing is we're building Mojo to be a fully general programming language. And that means that you can obviously tackle GPUs and CPUs and like these AI things, but it's also a really great way to build NumPy and other things like that. Or, you know, just if you look at what many Python libraries are today, often they're a layer of Python for the API, and they end up being C and C++ code underneath them. That's very true in AI. That's true in lots of other domains as well. And so anytime you see this pattern, that's an opportunity for Mojo to help simplify the world and help people have one thing.
To optimize through simplification by having one thing. So you mentioned Modular. Mojo is the programming language. Modular is the whole software stack.
So just over a year ago, we started this company called Modular. Yeah. Okay, what Modular is about is it's about taking AI and up-leveling it into the next generation, right? And so if you take a step back, what's gone on in the last 5, 6, 7, 8 years is that we've had things like TensorFlow and PyTorch, and these other systems come in. You've used them, you know this. And what's happened is these things have grown like crazy. They get tons of users. It's in production deployment scenarios. It's being used to power so many systems. And AI is all around us now. It used to be controversial years ago, but now it's a thing. But the challenge with these systems is that they haven't always been thought out with current demands in mind. And so you think about it, where were LLMs 8 years ago? Well, they didn't exist, right? AI has changed so much, and a lot of what people are doing today are very different than when these systems were built. And meanwhile, the hardware side of this has gotten into a huge mess. There's tons of new chips and accelerators, and every big company is announcing a new chip every day, it feels like. And so between that, you have like this moving system on one side, moving system on the other side, and it just turns into this gigantic mess, which makes it very difficult for people to actually use AI, particularly in production deployment scenarios. And so what Modular's doing is we're helping build out that software stack to help solve some of those problems, so then people can be more productive and get more AI research into production. Now, what Mojo does is it's a really, really, really important piece of that. And so that is, you know, part of that engine and part of the technology that allows us to solve these problems.
So Mojo is a programming language that allows you to do the high level programming, the low level programming. They do all kinds of programming in that spectrum that gets you closer and closer to the hardware.
So take a step back. So like, what do you love about Python?
Oh boy, where do I begin? What is love? What do I love about Python?
You're a guy who knows love. I know this.
Yes. How intuitive it is. How it feels like I'm writing natural language English. How when I can not just write but read other people's code, somehow I can understand it faster. It's more condensed than other languages, like ones I'm really familiar with, like C++ and C. There's a bunch of sexy little features.
Yeah.
We'll probably talk about some of them, but list comprehensions and stuff like this.
So and don't forget the entire ecosystem of all packages.
Oh yeah, there's probably huge.
Because there's always something. If you want to do anything, there's always a package.
Yeah, so it's not just the ecosystem of the packages and the ecosystem of the humans that do it. That's an interesting dynamic, because I think something about the usability and the ecosystem makes this thing viral, and it grows, and then it's a virtuous cycle, I think.
Well, and there's many things that went into that. Like, so I think that ML was very good for Python. And so I think that TensorFlow and PyTorch and these systems embracing Python really took and helped Python grow. But I think that the major thing underlying it is that Python's like the universal connector. Right? It really helps bring together lots of different systems so you can compose them and build out larger systems without having to understand how it works. But then what is the problem with Python?
Well, I guess you could say several things, but probably that it's slow.
I think that's usually what people complain about, right? And so I mean, other people complain about tabs and spaces versus curly braces or whatever, but I mean, those people are just wrong, because it is actually just better to use indentation.
Wow, strong words. So actually, I have a small tangent. Let's actually take that. Let's take all kinds of tangents.
Oh, come on, Lex, you can push me on. I can take it.
Design. Listen, I've recently left Emacs for VS Code.
Okay.
The kind of hate mail I had to receive, because on the way to doing that, I also said I've considered Vim.
Yep.
And chose not to, and went with VS Code. And
You're touching on deep religions, right?
Anyway, tabs is an interesting design decision, and so you've really written a new programming language here. Yes, it is a superset of Python, but you can make a bunch of different interesting decisions here.
Totally, yeah.
And you chose actually to stick with Python as in terms of some of the syntax.
Well, so let me explain why. Right. So, I mean, you can explain this in many rational ways. I think that the indentation is beautiful, but that's not a rational explanation, right? So, but I can defend it rationally, right? So, first of all, Python 1 has millions of programmers.
Yeah.
It is huge. It's everywhere. It owns machine learning. Right? So, factually, it is the thing. Right? Second of all, if you look at it, C code, C++ code, Java, whatever, Swift, curly brace languages also run through formatting tools and get indented. And so if they're not indented correctly, first of all, it will twist your brain around. It can lead to bugs. There's notorious bugs that have happened across time where the indentation was wrong or misleading and it wasn't formatted right. And so it turned into an issue, right? And so what ends up happening in modern large-scale code bases is people run automatic formatters. So now what you end up with is indentation and curly braces. If you're going to have, the notion of grouping, why not have one thing, right? And get rid of all the clutter and have a more beautiful thing, right? Also, you look at many of these languages, it's like, okay, well, you can have curly braces, or you can omit them if there's one statement, or you just like enter this entire world of complicated design space that objectively you don't need if you have Python-style indentation. So
yeah, I would love to actually see statistics on errors made because of indentation. Like how many errors are made in Python versus in C++ that have to do with basic formatting, all that kind of stuff. I would love to see.
I think it's probably pretty minor, because once you get like you use VS Code, I do too. So if you get VS Code set up, it does the indentation for you, generally, right? And so you don't, it's actually really nice to not have to fight it. And then what you can see is the editor is telling you how your code will work by indenting it. Pretty cool.
I honestly don't think I don't remember having an error in Python because I indented stuff wrong.
Yeah. So I mean, I think that there's, again, this is a religious thing, and so I can joke about it, and I love to kind of, I realize that this is such a polarizing thing, and everybody wants to argue about it, and so I like poking at the bear a little bit, right? But That's frankly, right, come back to the first point, Python 1. Like, it's huge, it's an AI, it's the right thing. For us, like, we see Mojo as being an incredible part of the Python ecosystem. We're not looking to break Python or change it or quote unquote fix it. We love Python for what it is. Our view is that Python is just not done yet. And so if you look at, you mentioned Python being slow. Well, there's a couple of different things that go into that, which we can talk about if you want. But one of them is that it just doesn't have those features that you would use to do C-like programming. And so if you say, okay, well, I'm forced out of Python into C for certain use cases, well, then what we're doing is we're saying, okay, well, why is that? Can we just add those features that are missing from Python back up to Mojo? And then you can have everything that's great about Python, all the things you're talking about that you love, plus not be forced out of it when you do something a little bit more computationally intense or weird or hardware-y or whatever it is that you're doing.
Well, a million questions I want to ask, but high level again, is it compiled or is it an interpreted language? So Python is just in time compilation with Mojo.
So Mojo, a complicated answer, does all the things. So it's interpreted, it's JIT compiled, and it's statically compiled. And so this is for a variety of reasons. One of the things that makes Python beautiful is that it's very dynamic. And because it's dynamic, one of the things they added is that it has this powerful metaprogramming feature. And so if you look at something like PyTorch or TensorFlow and even a simple use case, like you define a class that has the plus method. You can overload the dunder methods like dunder add, for example, and then the plus method works on your class. And so it has very nice and very expressive dynamic metaprogramming features. In Mojo, we want all those features to come in. Like, we don't want to break Python, we want it all to work. But the problem is we can't run those super dynamic features on an embedded processor or on a GPU, right? Or if you could, you probably don't want to just because of the performance. And so we entered this question saying, okay, how do you get the power of this dynamic metaprogramming into a language that has to be super efficient in specific cases? And so what we did was we said, okay, well, take that interpreter. Python has an interpreter in it, right? Take that interpreter and allow it to run at compile time. And so now what you get is you get compile time metaprogramming. And so this is super interesting, super powerful, because one of the big advantages you get is you get Python-style expressive APIs. You get the ability to have overloaded operators. And if you look at what happens inside of like PyTorch, for example, with automatic differentiation and computer mode, like all these things, they're using these really dynamic and powerful features at runtime. But we can take those features and lift them so that they run at compile time.
See, the C++ has metaprogramming with templates, but it's really messy.
It's super messy. It's always, it was accidentally, different people have different interpretations. My interpretation is that it was made accidentally powerful. It was not designed to be Turing complete, for example, but that was discovered kind of along the way, accidentally. And so there have been a number of languages in the space. And so they usually have templates, code instantiation, code copying features of various sorts. Some more modern languages, or some more newer languages, let's say, like, they're fairly unknown, like Zig, for example, says, okay, well, let's take all of those types that you can run it, all those things you can do at runtime, and allow them to happen at compile time. And so one of the problems with C++, which is one of the problems with C++,
there we go,
is
wrong words. We're gonna offend everybody.
Oh, that's okay. Everybody hates me for a variety of reasons, anyways. I'm sure, right? I've written enough.
The way they show love.
I have written enough C++ code to earn a little bit of grumpiness with C++. But one of the problems with it is that the metaprogramming system templates is just a completely different universe from the normal runtime programming world. And so if you do metaprogramming and programming, it's just like a different universe, different syntax, different concepts, different stuff going on. And so, again, one of our goals with Mojo is to make things really easy to use, easy to learn, and so there's a natural stepping stone. And so as you do this, you say, okay, well, I have to do programming at runtime, I have to do programming at compile time. Why are these different things?
How hard is that to pull out? Because that sounds, to me, as a fan of metaprogramming in C++ even, how hard is it to pull that off? That sounds really, really exciting, because you can do the same style programming at compile time and at runtime. That's really, really exciting.
Yep. And so, in terms of the compiler implementation details, it's hard. I won't be shy about that. It's super hard. It requires, I mean, what Mojo has underneath the covers is a completely new approach to the design of the compiler itself. And so this builds on these technologies like MLIR that you mentioned. It also includes other like caching and other interpreters and JIT compilers and other stuff like
So you
that.
have like an
that run
interpreter inside the
within the compiler, yeah. And so it really takes the standard model of programming languages and kind of twists it and unifies it with the runtime model, which I think is really cool. And to me, the value of that is that, again, many of these languages have metaprogramming features, like they grow macros or something, right? Lisp.
Oh. What the fuck is this shit?
Right?
Go.
I know. Your roots, right? You know.
What in the fuck?
And this is a powerful thing, right? And so. You know, if you go back to Lisp, one of the most powerful things about it is that it's the metaprogramming of the program.
Heard about this fucking programming language so many fucking times. Yeah.
On one axis, you have more hardware coming in. On the other hand, you have an explosion of innovation in AI. And so what happened with both TensorFlow and PyTorch is that the explosion of innovation in AI led to, it's not just about matrix multiplication and convolution. These things have now like 2,000 different operators. And on the other hand, you have, I don't know how many pieces of hardware there are out there. It's a lot. Part of my thesis, part of my belief of where computing goes, if you look out 10 years from now, is it's not going to get simpler. Physics isn't going back to where we came from. It's only going to get weirder from here on out. Right. And so to me, the exciting part about what we're building is it's about building that universal platform, which the world can continue to get weird. Because again, I don't think it's avoidable. It's physics. But we can help lift people, scale, do things with it. They don't have to rewrite their code every time a new device comes out. And I think that's pretty cool.
The following is a conversation with Chris Ladner, his third time on this podcast. As I've said many times before, he's one of the most brilliant engineers in modern computing.
Weird.
The following is a conversation with Chris Ladner, his
Oh,
third
what the
time
fuck
on
is
this
that
podcast.
shit? No wonder.
As I've said many times before, he's one of the most brilliant engineers in modern computing, having created LLM compiler infrastructure project, the Clang compiler, the Swift programming language, a lot of key contributions to TensorFlow and TPUs for Google. He served as vice president of Autopilot software at Tesla, was a software innovator and leader at Apple, and now he co-created a new full-stack AI infrastructure with distributed training, inference, and deployment on all kinds of hardware called Modular, and a new programming language called Mojo that is a superset of Python, giving you all the usability of Python, but with the performance of C, C++. In many cases, Mojo code has demonstrated over 30,000x speed up over Python. If you love machine learning, if you love Python, you should definitely give Mojo a try. This programming
Mojo?
language, this new AI
Like
framework,
that
and
fucking
infrastructure,
YouTube channel.
and this conversation
Yeah.
with Chris
I've got
is
Mojo.
mind-blowing.
What is Mojo?
I love it.
Sex
It
appeal?
gets pretty technical at times, so I hope
gotta
you
take a
hang
whiz.
on for the ride.
What kind of whiz,
This
Rabbi?
is the Lex Figure Podcast. To support it, please check out our sponsors in the description. Now, dear friends, here's Chris.
It's like a
Blattner.
5. What kind of?
It's been,
I
I
don't know.
think, 2 years
5.5.
since we last talked, and in that time, you somehow went and co-created a new programming
It's an
language
average piss,
called
lady.
Mojo.
Mind your own business.
So
I don't
it's
ask you what your
optimized
piss
for
looks
AI.
like.
It's a superset of Python.
This one time,
Let's look at the
Oprah
big picture. What is the
had
vision
this thing.
for Mojo?
She like
Mojo.
made me
Well, so,
start
I mean, I
thinking
think you have
about
to zoom
piss
out.
color
So I've been
and like how.
working on a lot of related
Dehydrated
technologies
you
for
can be.
many, many years.
So
I've
what's
worked on
super
LLM
hydrated?
and a lot of things and mobile
Super
and servers and things like this.
A
But the
zero?
world's changing.
Zero
What's
should be
happening
you don't
with
have
AI
to
is
do
we
anything.
have new GPUs and new machine learning accelerators.
Oh,
and
wait, P
ASICs,
can be
things like that that
How
make AI
badly
go
you have to pee, and
real
then the
fast.
color.
At Google, I worked on TPUs. That's one of the biggest, largest scale
All right.
deployed systems
We're
that
gonna-
exist for AI.
We're gonna have
And
all this shit.
really what you see is
Standardized,
if you look
kids.
across all of the things that are happening in the industry, there's this new compute platform coming. And it's not just about
Some lady's gonna. Yeah. I don't-
CPUs or
I just
GPUs
had a
or
5.5.
TPUs or NPUs or IPUs or whatever, all the PUs,
Damn,
right? It's about how do we program these things, right? And so
take a
for
whiz.
software folks like us,
Whiz,
right,
kid.
it doesn't do us any good if there's this amazing hardware that we can't use. And one of the things you find out really quick is that having the theoretical capability of programming something and then having the world's power and the innovation of all the smart people in the world get unleashed on something can be quite different. And so really where Mojo came from was starting from a problem of we need to be able to take machine learning, take the infrastructure underneath it and make it way more accessible, way more usable, way more understandable by normal people and researchers and other folks that are not themselves like experts in GPUs and things like this. And then through that journey, we realized, hey, we need syntax for this. We need to do programming language.
So one of the main features of the language, I say so fully in jest, is that it allows you to have the file extension to be
Yeah, I
an
think it's like a
emoji,
5.5.
the fire emoji, which is one of the first emojis used as a file extension I've ever seen in my life. And then you ask yourself the question, why in the 21st century are we not using Unicode for file extensions? This, I mean, it's an epic decision. I think clearly the most important decision in most, but you could also just use MOJO as the file extension.
Well, so take a step back. I mean, come on, Lex, do you think that the world's ready for this? This is a big moment in the world, right?
We're releasing this onto the world.
This is innovation.
I mean, it really is kind of brilliant. Emojis are such a big part of our daily lives. Why isn't it not in programming?
Well, and like you take a step back and look at what file extensions are, right? They're basically metadata, right? And so why are we spending all the screen space on them and all this stuff? Also, you have them stacked up next to text files and PDF files and whatever else. Like, if you're gonna do something cool, you want to stand out, right? And emojis are colorful, they're visual, they're beautiful,
Yeah.
right?
What's been the response so far from is there support on like Windows on the operating system in displaying like file explorer?
Yeah.
Can
The one problem I've seen is that Git doesn't escape it right.
Uh-huh.
And so it thinks that the fire emoji is unprintable, and so it like prints out weird hex things if you use the command line Git tool. But everything else, as far as I'm aware, works fine. And I have faith that Git can be improved. So I'm not worried.
GitHub is fine.
GitHub is fine. Yeah, GitHub is fine. Visual Studio Code, Windows, like all this stuff, totally ready because people have internationalization in their normal part of their past. So this is just like taking the next step, right? It's somewhere between, oh wow, that makes sense. Cool. I like new things, to, oh my God, you're killing my baby. Like, what are you talking about? This can never be, like, I can never handle this. How am I going to type this? Like all these things. And so this is something where I think that the world will get there. You don't have to bet the whole farm on this. I think we can provide both paths, but I think it'll be great.
When can we have emojis as part of the code?
Yeah, so I mean, lots of languages provide that. So I think that we have partial support for that. It's probably not fully done yet, but yeah, you can do that. For example, in Swift, you can do that for sure. So an example we gave at Apple was the dog cow. Yeah, so it's a classical Mac heritage thing, and so you use the dog and the cow emoji together, and that could be your variable name. But of course, the internet went and made pile of poop for everything. So, if you want to name your function pile of poop, then you can totally go to town and see how that gets through code review.
Okay, so let me just ask a bunch of random questions. So is Mojo primarily designed for AIs, or is it a general purpose program?
Yeah, good question. So it's AI first. And so AI is driving a lot of the requirements. And so Modular is building and designing and driving Mojo forward. And it's not because it's an interesting project theoretically to build, it's because we need it. And so at Modular, we're really tackling the AI infrastructure landscape and the big problems in AI, and the reasons that it is so difficult to use and scale and adopt and deploy, and like all these big problems in AI. And so we're coming at it from that perspective. Now, when you do that, when you start tackling these problems, you realize that the solution to these problems isn't actually an AI-specific solution. And so while we're doing this, we're building Mojo to be a fully general programming language. And that means that you can obviously tackle GPUs and CPUs and like these AI things, but it's also a really great way to build NumPy and other things like that. Or, just if you look at what many Python libraries are today, often they're a layer of Python for the API, and they end up being C and C++ code underneath them. That's very true in AI. That's true in lots of other domains as well. And so anytime you see this pattern, that's an opportunity for Mojo to help simplify the world and help people have one thing.
To optimize through simplification by having one thing. You mentioned Modular. Mojo is the programming language. Modular is the whole software stack.
So just over a year ago, we started this company called Modular. Yeah. What Modular is about taking AI and up-leveling it into the next generation, right? And so if you take a step back, what's gone on in the last 5, 6, 7, 8 years is that we've had things like TensorFlow and PyTorch, and these other systems come in. You've used them, you know this. And what's happened is these things have grown like crazy. We get tons of users. It's in production deployment scenarios. It's being used to power so many systems. I mean, AI is all around us now. It used to be controversial years ago, but now it's a thing. But the challenge with these systems is that they haven't always been thought out with current demands in mind. And so you think about it, where were LLMs 8 years ago? Well, they didn't exist, right? AI has changed so much, and a lot of what people are doing today are very different than when these systems were built. And meanwhile, the hardware side of this has gotten into a huge mess. There's tons of new chips and accelerators, and every big company is announcing a new chip every day, it feels like. And so between that, you have like this moving system on one side, moving system on the other side, and it just turns into this gigantic mess, which makes it very difficult for people to actually use AI, particularly in production deployment scenarios. And so what Modular is doing is we're helping build out that software stack to help solve some of those problems, so that then people can be more productive and get more AI research into production. Now, what Mojo does is it's a really, really, really important piece of that. And so that is, part of that engine and part of the technology that allows us to solve these problems.
So Mojo is a programming language that allows you to do high-level programming, the low-level programming. They do all kinds of programming in that spectrum that gets you closer and closer to the hardware.
So take a step back. So Lex, what do you love about Python?
Oh boy, where do I begin? What is love? What do I love about Python?
You're a guy who knows love. I know this.
Yes. How intuitive it is. How it feels like I'm writing natural language English. How when I can not just write but read other people's code, somehow I can understand it faster. It's more condensed than other languages, like ones I'm really familiar with, like C++ and C. There's a bunch of sexy little features.
Yeah.
We'll probably talk about some of them, but list comprehensions and stuff like this.
So and don't forget the entire ecosystem of all the packages.
Oh yeah, that's probably huge.
Because there's always something. If you want to do anything, there's always a package.
Yeah, so it's not just the ecosystem of the packages and the ecosystem of the humans that do it. That's an interesting dynamic.
That's
because
huge.
I think something about the usability and the ecosystem makes the thing viral. It grows, and then it's a virtuous cycle.
Well, and there's many things that went into that. Like, so I think that ML was very good for Python. And so I think that TensorFlow and PyTorch and these systems embracing Python really took and helped Python grow. But I think that the major thing underlying it is that Python's like the universal connector. Right? It really helps bring together lots of different systems so you can compose them and build out larger systems without having to understand how it works. But then, what is the problem with Python?
Well, I guess you could say several things, but probably that it's slow.
I think that's usually what people complain about, right? And so I mean, other people complain about tabs and spaces versus curly braces or whatever, but I mean, those people are just wrong because it is actually just better to use indentation.
Wow, strong words. So actually, a small tangent. Let's actually take that. Let's take all kinds of tangents.
Oh, come on, Lex, you can push me on. I can take it.
Design. Listen, I've recently left Emacs for VS Code. And
Okay.
the kind of hate mail I had to receive, because on the way to doing that, I also said I've considered Vim.
Yep.
And chose not to, and went with VS Code. And
You're
just
touching on deep religions, right?
anyway, tabs is an interesting design decision, and so you've really written a new programming language here. Yes, it is a superset of Python, but you can make a bunch of different interesting decisions here.
Totally, yeah.
And you chose actually to stick with Python as in terms of some of the syntax.
Well, so let me explain that, right? So, I mean, you can explain this in many rational ways. I think that the indentation is beautiful, but that's not a rational explanation, right? So, but I can defend it rationally, right? So, first of all, Python 1 has millions of programmers.
Yeah.
It is huge. It's everywhere. It owns machine learning, right? So, factually, it is the thing, right? Second of all, if you look at it, C code, C++ code, Java, whatever, Swift, curly brace languages also run through formatting tools and get indented. And so if they're not indented correctly, first of all, we'll twist your brain around. It can lead to bugs. There's notorious bugs that have happened across time where the indentation was wrong or misleading and it wasn't formatted right, and so it turned into an issue, right? And so what ends up happening in modern large-scale code bases is people run automatic formatters. So now what you end up with is indentation and curly braces. If you're going to have, the notion of grouping, why not have one thing, right? And get rid of all the clutter and have a more beautiful thing, right? Also, you look at many of these languages, it's like, okay, well, you can have curly braces, or you can omit them if there's one statement, or you just enter this entire world of complicated design space that objectively you don't need if you have Python style indentation. So,
Yeah, I would love to actually see statistics on errors made because of indentation. Like how many errors are made in Python versus in C++ that have to do with basic formatting, all that kind of stuff. I would love to see.
I think it's probably pretty minor because once you get like you use VS Code, I do too. So if you get VS Code set up, it does the indentation for you, right? And so you don't, it's actually really nice to not have to fight it. And then what you can see is the editor is telling you how your code will work by indenting it, which I think is pretty cool.
I honestly don't think I don't remember having an error in Python because I indented stuff wrong.
So I mean, I think that there's, again, this is a religious thing, and so I can joke about it, and I love to kind of, I realize this is such a polarizing thing, and everyone wants to argue about it, so I like poking at the bear a little bit, right? But frankly, like, come back to the first point, Python 1. Like, it's huge, it's an AI, it's the right thing. For us, like, we see Mojo as being an incredible part of the Python ecosystem. We're not looking to break Python or change it or quote-unquote fix it. We love Python for what it is. Our view is that Python is just not done yet. And so if you look at, you mentioned Python being slow. Well, there's a couple of different things that go into that, which we can talk about if you want. But one of them is that it just doesn't have those features that you would use to do C-like programming. And so if you say, okay, well, I'm forced out of Python into C for certain use cases, well, then what we're doing is we're saying, okay, well, why is that? Can we just add those features that are missing from Python back up to Mojo? And then you can have everything that's great about Python, all the things you're talking about that you love, plus not be forced out of it when you do something a little bit more computationally intense or weird or hardware-y or whatever it is that you're doing.
Well, a million questions I want to ask, but high level again, is it compiled or is it an interpreted language? So Python is just-in-time compilation. What's Mojo?
So Mojo, a complicated answer, does all the things.
Mm-hmm.
So it's interpreted, it's JIT compiled, and it's statically compiled. And so this is for a variety of reasons. So one of the things that makes Python beautiful is that it's very dynamic. And because it's dynamic, one of the things they added is that it has this powerful metaprogramming feature. And so if you look at something like PyTorch or TensorFlow or Or I mean, even a simple use case like you define a class that has the plus method. Right? You can overload the dunder methods like dunder add, for example, and then the plus method works on your class. And so it has very nice and very expressive dynamic metaprogramming features. In Mojo, we want all those features to come in. Like we don't want to break Python, we want it all to work. But the problem is you can't run those super dynamic features on an embedded processor or on a GPU. Right? Or if you could, you probably don't want to just because of the performance. And so we entered this question of saying, okay, how do you get the power of this dynamic metaprogramming into a language that has to be super efficient in specific cases? And so what we did was we said, okay, we'll take that interpreter. Python has an interpreter in it, right? Take that interpreter and allow it to run at compile time. And so now what you get is you get compile time metaprogramming. And so this is super interesting, super powerful, because one of the big advantages you get is you get Python-style expressive APIs. You get the ability to have overloaded operators. And if you look at what happens inside of like PyTorch, for example, with automatic differentiation, eager mode, like all these things, they're using these really dynamic and powerful features at runtime. But we can take those features and lift them so that they run at compile time.
So the C++ has metaprogramming with templates, but it's really messy.
It's super messy. It's always, it was accidentally, I mean, different people have different interpretations. My interpretation is that it was made accidentally powerful. It was not designed to be Turing complete, for example, but that was discovered kind of along the way, accidentally. And so there have been a number of languages in the space. And so they usually have templates, code instantiation, code copying features of various sorts. Some more or some more newer languages, let's say, like, you know, they're fairly unknown, like Zig, for example, says, okay, well, let's take all of those types you can run it, all those things you can do at runtime, and allow them to happen at compile time. And so one of the problems with C++, which is one of the problems with C++,
Here we go.
is
Wrong words. You're gonna offend everybody.
Oh, it's okay. I mean, everybody hates me for a variety of reasons, anyways. I'm sure, right? I've written enough.
That's the way they show love.
I've written enough C++ code to earn a little bit of grumpiness with C++. But one of the problems with it is that the metaprogramming system templates is just a completely different universe from the normal runtime programming world. And so if you do metaprogramming and programming, it's just like a different universe, different syntax, different concepts, different stuff going on. And so, again, one of our goals with Mojo is to make things really easy to use, easy to learn. And so there's a natural stepping stone. And so as you do this, you say, okay, well, I have to do programming at runtime. I have to do programming at compile time. Why are these different things?
How hard is that to pull it off? Because that sounds, to me as a fan of metaprogramming in C++ even, how hard is it to pull that off? That sounds really, really exciting, because you can do the same style programming at compile time and at runtime. That's really, really exciting.
Yep. And so, I mean, in terms of the compiler implementation details, it's hard. I won't be shy about that. It's super hard. It requires, I mean, what Mojo has underneath the covers is a completely new approach to the design of the compiler itself. And so this builds on these technologies like MLIR that you mentioned, but it also includes other like caching and other interpreters and JIT compilers and other stuff like
So you
that.
have like an interpreter inside the
within the compiler, yes. And so it really takes the standard model of programming languages and kind of twists it and unifies it with the runtime model, right? Which I think is really cool. And to me, the value of that is that, again, many of these languages have metaprogramming features, like they grow macros or something, right? Lisp, right? Yes, I know your roots, right? You know, and this is a powerful thing, right? And so, you know, if you go back to Lisp, one of the most powerful things about it is that it said that the metaprogramming and the programming are the same, right? And so that made it way simpler, way more consistent, way easier to understand, reason about, and it made it more composable. So if you go to library, you can use it both at runtime and compile time, which is pretty cool.
Yeah, and then for machine learning, I think metaprogramming, I think we could generally say, is extremely useful. And so you get features. I mean, I'll jump around, but there's the feature of auto-tuning and adaptive compilation just blows my mind.
Yeah. Well, so okay, so let's come back to that.
Sure.
So,
All right.
So what is machine learning? Like what is a machine learning model? Like you take a PyTorch model off the internet, right? It's really interesting to me because what PyTorch and what TensorFlow and all these frameworks are kind of pushing compute into is they're pushing into like this abstract specification of a compute problem, which then gets mapped in a whole bunch of different ways. Right? And so this is why it became a metaprogramming problem. And so you want to be able to say, cool, I have this neural net, now run it with batch size 1,000. Right? Do a mapping across batch. Or okay, I want to take this problem, now run it across 1,000 CPUs or GPUs. Right? And so like this problem of like just describe the compute and then map it and do things and transform it are like actually it's very profound, and that's one of the things that makes machine learning systems really special.
Maybe can you describe auto tuning and how do you pull off? I mean, I guess adaptive compilation is what we're talking about, is metaprogramming.
Yeah.
How do you pull off auto tuning? I mean, is that as profound as I think it is? It just seems like a really like we'll mention list comprehensions. To me, from a quick glance at Mojo, which by the way I have to absolutely like dive in. As I realize how amazing this is, I absolutely must dive in. That looks like just an incredible feature for machine learning people.
Yeah. Well, so what is auto tuning? So take a step back. Auto tuning is a feature in Mojo. It's not so very very little of what we're doing is actually research. Like many of these ideas have existed in other systems and other places, and so what we're doing is we're pulling together good ideas, remixing them, and making them into hopefully a beautiful system, right? And so auto tuning, the observation is that turns out hardware systems algorithms are really complicated. Turns out maybe you don't actually want to know how the hardware works, right? A lot of people don't, right? And so there are lots of really smart hardware people, I know a lot of them, where they know everything about, okay, the cache size is this, and the number of registers is that, and if you use this length of vector, it's going to be super efficient because it maps directly onto what it can do, and like all this kind of stuff. Or the GPU has SMs and it has a warp size of whatever, right? All the stuff that goes into these things, or the tile size of a TPU is 128, like these factoids, right? My belief is that most normal people, and I love hardware people also, I'm not trying to offend literally everybody in the internet, but most programmers actually don't want to know this stuff, right? And so if you come at it from the perspective of how do we allow people to build both more abstracted but also more portable code, because it could be that the vector length changes or the cache size changes, or it could be that the tile size of your matrix changes, or the number, an A100 versus an H100 versus a Volta versus a whatever GPU have different characteristics, right? A lot of the algorithms that you run are actually the same, but the parameters, these magic numbers you have to fill in, end up being really fiddly numbers that an expert has to go figure out. And so what auto tuning does is says, okay, well, guess what? There's a lot of compute out there. Right? So instead of having humans go randomly try all the things or do a grid search or go search some complicated multidimensional space, how about we have computers do that? Right? And what auto tuning does is you can say, hey, here's my algorithm. If it's a matrix operation or something like that, you can say, okay, I'm going to carve it up into blocks. I'm going to do those blocks in parallel, and I want this with 128 things that I'm running on, I want to cut it this way or that way or whatever. And you can say, hey, go see which one's actually empirically better on the system.
And then the result of that, you cache for that system.
Yep.
You save it.
And so come back to twisting your compiler brain, right? So not only does the compiler have an interpreter that's used to do metaprogramming, that compiler, that interpreter, that metaprogramming now has to actually take your code and go run it on a target machine. see which one it likes the best, and then stitch it in and then keep going. Right.
So part of the compilation is machine specific.
Yeah. Well, so I mean, this is an optional feature, right? So you don't have to use it for everything. But yeah, if you're so one of the things that we're in the quest of is ultimate performance.
Yes.
Right. And ultimate performance is important for a couple of reasons, right? So if you're an enterprise, you're looking to save costs and compute and things like this. Ultimate performance translates to fewer servers. Like if you care about the environment, hey, better performance leads to more efficiency. Right? I mean, you could joke and say Python's bad for the environment, right? And so if you move to Mojo, it's like at least 10x better just out of the box and keep going, right? But performance is also interesting because it leads to better products. And so in the space of machine learning, right, if you reduce the latency of a model so that it runs faster, so every time you query the server running the model, it takes less time, well, then the product team can go and make the model bigger. Well, that actually makes it so you have a better experience as a customer. And so a lot of people care about that.
So for auto tuning, for like tile size, you mentioned 128 for TPU, you would specify like a bunch of options to try just in the code, just simple statement, and then you can just set and forget and know depending wherever it compiles, it'll actually be the fastest way.
And yeah, exactly. And the beauty of this is that it helps you in a whole bunch of different ways, right? So if you're building, so often what will happen is that you've written a bunch of software yourself, right? You wake up one day, you say, I have an idea, I'm going to go cut up some code. I get to work, I forget about it, I move on with life. I come back 6 months or a year or 2 years or 3 years later, you dust it off and you go use it again in a new environment.
Mm-hmm.
And maybe your GPU is different. Maybe you're running on a server instead of a laptop, maybe whatever, right? And so the problem now is you say, okay, well, I mean, again, not everybody cares about performance, but if you do, you say, okay, well, I want to take advantage of all these new features. I don't want to break the old thing though, right? And so the typical way of handling this kind of stuff before is, if you're talking about C++ templates, or you're talking about C with macros, you end up with if-defs, you get like all these weird things get layered in, make the code super complicated, and then how do you test it? Right? It becomes this crazy complexity, multidimensional space that you have to worry about. And, that just doesn't scale very well.
Actually, let me just jump around before I go to some specific features. Like the increase in performance here that we're talking about can be just insane. You're right that Mojo can provide a 35,000x speed up over Python. How does it do that?
Yeah, so I can even do more, but we'll get to that. So first of all, when we say that, we're talking about what's called CPython. It's the default Python that everybody uses. When you type Python 3, that's like typically the one you use, right? CPython is an interpreter. And so interpreters, they have an extra layer of like bytecodes and things like this that they have to go read, parse, interpret, and slow from that perspective. And so one of the first things we do is we move to a compiler. And so just moving to a compiler, getting the interpreter out of the loop is 2 to 5 to 10x speed up, depending on the code. So just out of the gate, just using more modern techniques. Right? Now, if you do that, one of the things you can do is you can start to look at how CPython started to lay out data. And so one of the things that CPython did, and this isn't part of the Python spec necessarily, but this is just sets of decisions, is that if you take an integer, for example, it'll put it in an object. So in Python, everything's an object. And so they do the very logical thing of keeping the memory representation of all objects the same. So all objects have a header, they have like payload data, and what this means is that every time you put an object, you're passing around a pointer to the data. Well, this has overhead. Right? It turns out that modern computers don't like chasing pointers very much and things like this. It means that you have to allocate the data. It means you have to reference count it, which is another way that Python uses to keep track of memory. And so this has a lot of overhead. And so if you say, okay, let's try to get that out of the heap, out of a box, out of an indirection, and into the registers. Mm-hmm. That's another 10x.
So it adds up more. if you're reference counting every single thing you create, that adds up.
Yeah, and if you look at people complain about the Python GIL, this is one of the things that hurts parallelism. That's because of the reference count. Right? And so the GIL and reference counting are very tightly intertwined in Python. It's not the only thing, but it's very tightly intertwined. And so then you lean into this and you say, okay, cool. Well, modern computers, they can do more than one operation at a time. And so they have vectors. What is a vector? Well, a vector allows you to take one, instead of taking one piece of data, doing an add or a multiply, and then picking up the next one, you can now do 4 or 8 or 16 or 32 at a time. Right? Well, Python doesn't expose that because of reasons. And so now you can say, okay, well, you can adopt that. Now you have threads. Now you have like additional things, like you can control the memory hierarchy. And so what Mojo allows you to do is it allows you to start taking advantage of all these powerful things that have been built into the hardware over time. And the library gives very nice features. So you can say, just parallelize this, do this in parallel, right? So it's very, very powerful weapons against slowness, which is why people have been, and I think having fun, like just taking code and making it go fast, because it's just kind of an adrenaline rush to see like how fast you can get things.
Before I talk about some of the interesting stuff with parallelization and all that, let's first talk about like the basics. We talked to indentation, right? So this thing looks like Python. It's sexy and beautiful like Python, as we mentioned.
Yep.
Is it a typed language? So what's the role of types?
Yeah, good question. So Python has types. It has strings, it has integers, it has dictionaries, and like all that stuff, but they all live at runtime, right? And so because all those types live at runtime in Python, you don't have to spell them. Python also has like this whole typing thing going on now, and a lot of people use it.
Yeah.
I'm not talking about that. That's kind of a different thing. We can go back to that if you want. But typically the you just say I have a def, and my def takes two parameters. I'm going to call them A and B, and I don't have to write a type. Okay, so that is great. But what that does is that forces what's called a consistent representation. So these things have to be a pointer to an object with the object header, and they all have to look the same. And then when you dispatch a method, you go through all the different paths, no matter what the receiver, whatever that type is. So what Mojo does is it allows you to have more than one kind of type. And so what it does is allows you to say, okay, cool, I have an object, and objects behave like Python does. And so it's fully dynamic, and that's all great. And for many things, classes, like that's all very powerful and very important. But if you want to say, hey, it's an integer, and it's 32 bits, or it's 64 bits, or whatever it is, or it's a floating point value, it's 64 bits, well, then the compiler can take that, and it can use that to do way better optimization. And it turns out, again, getting rid of the indirections, that's huge. It means you can get better code completion because you have, because the compiler knows what the type is, and so knows what operations work on it. And so that's actually pretty huge. And so what Mojo does is allows you to progressively adopt types into your program. So you can start, again, it's compatible with Python. And so then you can add however many types you want, wherever you want them. And if you don't want to deal with it, you don't have to deal with it. Right? And so one of our opinions on this is that it's not that types are the right thing or the wrong thing. It's that they're a useful thing.
Which is kind of optional. It's not strict typing. Like, you don't have to specify a type.
Exactly.
Okay, so it's starting from the thing that Python's kind of reaching towards right now with trying to inject types into it.
With a very different approach, but yes. Yeah.
What's the different approach? I'm actually one of the people that have not been using types very much in Python.
That's okay. Why did you say?
It just, because I know the importance. It's like adults use strict typing. And so I refuse to grow up in that sense. It's a kind of rebellion. But I just know that it probably reduces the amount of errors, even just forget about performance improvements. It probably reduces errors when you do strict typing.
Yeah, so I mean, I think it's interesting if you look at that, right? And the reason I'm giving you a hard time,
yes,
is that there's this cultural norm, this pressure, this like there has to be a right way to do things. Like,
yes,
only grown-ups only do it one way, and if you
yes,
don't do that, you should feel bad.
Yes.
Right? Like some people feel like Python's a guilty pleasure or something.
Mm-hmm.
And it's like when it gets serious, I need to go rewrite it, right?
Yeah, exactly.
Well, I mean, cool, I understand history and I understand kind of where this comes from, but I don't think it has to be a guilty pleasure.
Yeah.
Right? And
Yeah.
so if you look at that, you say, why do you have to rewrite it? Well, you have to rewrite it to deploy. Well, why do you want to deploy? Well, you care about performance, or you care about predictability, or you want, a tiny thing server that has no dependencies, or, you have objectives that you're trying to attain. So what if Python can achieve those objectives? So if you want types, well, maybe you want types because you want to make sure you're passing in the right thing. Sure, you can add a type. If you don't care, you're prototyping some stuff, you're hacking some things out, you're like pulling some random code off the internet, it should just work, right? And you shouldn't be like pressured. You shouldn't be mad about doing the right thing or the thing that feels good. Now, if you're in a team, right, you're working at some massive internet company and you have 400 million lines of Python code, well, they may have a house rule that you use types,
Yeah.
right, because it makes it easier for different humans to talk to each other and understand what's going on, and bugs at scale, right? And so there are lots of good reasons why you might want to use types, but that doesn't mean that everybody should use them all the time, right? So what Mojo does is it says, cool, well, allow people to use types, and if you use types, you get nice things, you get better performance and things like this, right? But Mojo is a full compatible superset of Python. Right. And so that means it has to work without types. It has to support all the dynamic things, it has to support all the packages, it has to support for comprehension, list comprehensions and things like this, right? And so that starting point, I think, is really important. And I think that, again, you can look at why I care so much about this, and there's many different aspects of that, one of which is the world went through a very challenging migration from Python 2 to Python 3. Right. This migration took many years, and it was very painful for many teams. Right.
Yeah.
And there's a lot of things that went on in that. I'm not an expert in all the details, and I honestly don't want to be. I don't want the world to have to go through that.
Yeah.
Right. And people can ignore Mojo, and if it's not their thing, that's cool. But if they want to use Mojo, I don't want them to have to rewrite all their code.
Yeah, I mean, the superset part is it's just, I mean, there's so much brilliant stuff here. That definitely is incredible. We'll talk about that.
Yeah,
But first
well,
of all, how's the typing
yeah.
implemented differently in Python versus Mojo?
Yeah.
So this heterogeneous flexibility, you said, is differently implemented.
So I'm not a full expert in the whole backstory on types in Python. So I'll give you that. I can give you my understanding. My understanding is basically, like many dynamic languages, the ecosystem went through a phase where people went from writing scripts to writing large scale, huge code bases in Python, and at scale, it kind of helps to have types. People want to be able to reason about interfaces. What do you expect, a string or an int, or like what these basic things, right? And so what the Python community started doing is it started saying, okay, let's have tools on the side, checker tools, right, that go and like enforce invariants, check for bugs, try to identify things. These are called static analysis tools generally. And so these tools run over your code and try to look for bugs. What ended up happening is there's so many of these things, so many different weird patterns and different approaches on specifying the types and different things going on, that the Python community realized and recognized, hey, there's the thing here. And so what they started to do is they started to standardize the syntax for adding types to Python. Now, one of the challenges that they had is that they're coming from kind of this fragmented world where there's lots of different tools, they have different trade-offs and interpretations, and the types mean different things. And so if you look at types in Python, according to the Python spec, the types are ignored. Right, so according to the Python spec, you can write pretty much anything in a type position, okay? And you can write any expression, okay? Now, that's beautiful because you can extend it, you can do cool things, you can build your own tools, you can build your own house linter or something like that, right? But it's also a problem because any existing Python program may be using different tools and they have different interpretations. And so if you adopt somebody's package into your ecosystem, try to run the tool you prefer, it may throw out tons of weird errors and warnings and problems just because it's incompatible with how these things work. Also because they're added late and they're not checked by the Python interpreter, it's always kind of more of a hint than it is a requirement. Also, the CPython implementation can't use them for performance, and so it's really...
I mean, that's the big one, right? So you can't utilize for the compilation, for the just-in-time compilation. Okay.
Yep, exactly. And this all comes back to the design principle of they're kind of hints. They're kind of, the definition's a little bit murky. It's unclear exactly the interpretation in a bunch of cases. And so because of that, you can't actually, even if you want to, it's really difficult to use them to say like, it is going to be an int, and if it's not, it's a problem, right? A lot of code would break if you did that. So in Mojo, right, so you can still use those kind of type annotations, it's fine. But in Mojo, if you declare a type and you use it, then it means it is going to be that type. And the compiler helps you check that and enforce it, and it's safe. And it's not a like best effort hint kind of a thing.
So if you try to shove a string type thing into an integer,
you get an error
from the compiler compile time. Nice. Okay, what kind of basic types are there?
Yeah, so Mojo is pretty hardcore in terms of what it tries to do in the language, which is the philosophy there is that we again, if you look at Python, right? Python's a beautiful language because it's so extensible, right? And so all of the different things in Python, like for loops and plus and like all these things, can be accessed through these underbar methods. Okay, so you have to say, okay, if I make something that is super fast, I can go all the way down to the metal. Why do I need to have integers built into the language? Right? And so what Mojo does is it says, okay, well, we can have this notion of structs. So you have classes in Python. Now you can have structs. Classes are dynamic. Structs are static. Cool. We can get high performance. We can write C++ kind of code with structs if you want. These things mix and work beautifully together. But what that means is that you can go and implement strings and ints and floats and arrays and all that kind of stuff in the language, right? And so that's really cool because, you know, to me as a idealizing compiler language type of person, what I want to do is I want to get magic out of the compiler and put it in the libraries. Because if somebody can, you know, if we can build an integer that's beautiful and it has an amazing API and it does all the things you'd expect an integer to do, but you don't like it, maybe you want a big integer, maybe you want a like sideways integer, I don't know, like what all the space of integers are, then you can do that and it's not a second-class citizen. And so if you look at certain other languages, like C++, one I also love and use a lot, int is hard-coded the language, but complex is not. And so isn't it kind of weird that you have this std complex class, but you have int, and complex tries to look like a natural numeric type and things like this, but integers and floating point have these like special promotion rules and other things like that that are magic and they're hacked into the compiler. And because of that, you can't actually make something that works like the built-in types.
Cottage cheese.
Is there something provided as a standard? Because because it's AI first, numerical types are so important here. So is there something like a nice standard implementation of integer and float?
Yeah, so we're still building all that stuff out. So we provide integers and floats and all that kind of stuff. We also provide like buffers and tensors and things like that you'd expect in an ML context. Honestly, we need to keep designing and redesigning and working with the community to build that out and make that better. That's not our strength right now. Give us 6 months or a year, and I think it'll be way better. But the power of putting it in the library means that we can have teams of experts that aren't compiler engineers that can help us design and refine and drive this forward.
So one of the exciting things we should mention here is that this is new and fresh. This cake is unbaked. It's almost baked. You can tell it's delicious, but it's not fully ready to be consumed.
Yep, that's very fair. It is very useful, but it's very useful if you're a super low-level programmer right now. And what we're doing is we're working our way up the stack. And so the way I would look at Mojo today in May in 2023 is that it's like a 0.1. So I think that a year from now, it's going to be way more interesting to a variety of people. But what we're doing is we decide to release it early so that people can get access to it and play with it, and we can build it with the community. We have a big roadmap, fully published, being transparent about this, and a lot of people are involved in this stuff. And so what we're doing is we're really optimizing for building this thing the right way. And building it the right way is kind of interesting working with the community because everybody wants it yesterday. And so it's sometimes it's kind of, there's some dynamics there. But
Yeah,
I think it's the right thing.
So there's a Discord also, so the dynamics is pretty interesting. Sometimes the community probably can be very chaotic and introduce a lot of stress. Guido famously quit over the stress of the walrus operator. I mean, it broke. Maybe that
straw that broke the camel's back.
Yeah, exactly. And so, like, it can be very stressful to develop. But can you just add tangent upon a tangent? Is it stressful to work through the design of various features here, given that the community is so richly involved?
Well, so I've been doing open development and community stuff for decades now. Somehow this has happened to me. So I've learned some tricks, but the thing that always gets me is I want to make people happy, right? And so this is maybe not all people all happy all the time, but generally I want people to be happy, right? And so the challenge is that, again, we're tapping into some deep-seated long tensions and pressures, both in the Python world, but also in the AI world, in the hardware world, and things like this. And so people just want us to move faster. Right? And so, again, our decision was, let's release this early. Let's get people used to it or access to it and play with it, and let's build it in the open, which we could have, had the language monk sitting in the cloister up on the hilltop, like beavering away trying to build something. But in my experience, you get something that's way better if you work with the community. Right. And so yes, it can be frustrating, can be challenging for lots of people involved. And if you mentioned our over 10,000 people on the Discord, 11,000 people or something. Keep in mind, we released Mojo like 2 weeks ago.
Yeah.
So
it's very active.
So it's very cool. But what that means is that 10, 11,000 people all will want something different, right? And so what we've done is we've tried to say, okay, cool, here's our roadmap. Here, and the roadmap isn't completely arbitrary. It's based on here's the logical order in which to build these features or add these capabilities and things like that. And what we've done is we've spun really fast on like bug fixes. And so we actually have very few bugs, which is cool. I mean, actually for the project in the state, but then what we're doing is we're dropping in features very deliberately.
I mean, this is fun to watch because you got the two gigantic communities of like hardware, like systems engineers, and then you have the machine learning Python people that are like higher level.
Yeah. And
it's just two like army, like
they've been at war. Yeah, they've been at war, right? And so here's
like
the
a Tolkien
test.
novel or something. Okay.
Well, so here's the test. Again, like it's super funny for something that's only been out for 2 weeks, right? People are so impatient, right? But okay, cool. Let's fast forward a year. Like in a year's time, Mojo will be actually quite amazing and solve tons of problems and be very good. People still have these problems, right? And so you look at this and you say, and the way I look at this at least is to say, okay, well, we're solving big, long-standing problems. To me, again, working on many different problems, I want to make sure we do it right. Right? There's like a responsibility you feel because if you mess it up, right, there's very few opportunities to do projects like this and have them really have impact on the world. If we do it right, then maybe we can take those feuding armies and actually some of those wounds.
Yeah, this
Right?
is like this feels like a speech by George Washington or Abraham Lincoln or something.
And you look at this and it's like, okay, well, how different are we?
Yeah.
We all want beautiful things. We all want something that's nice. We all want to be able to work together. We all want our stuff to be used, right? And so if we can help heal that. Now, I'm not optimistic that all people will use Mojo and they'll stop using C++. Like that's not my goal, right? But if we can heal some of that, I think that'd be pretty cool.
Yeah, and we start by putting the people who like braces into the gulag. No.
So there are proposals for adding braces to Mojo, and we tell them no.
Okay. Politely. Yeah, anyway, so there's a lot of amazing features on the roadmap, and those already implemented. It'd be awesome if I could just ask you a few things.
Yeah, go for it.
So the other performance improvement comes from immutability. So what's this var and this let thing that we got going on?
Well,
And what's immutability?
Yeah, so one of the things that is useful, and it's not always required, but it's useful, is knowing whether something can change out from underneath you. Right? And so in Python, you have a pointer to an array, right? And so you pass that pointer to an array around to things. If you pass into a function, they may take that and scroll it away in some other data structure. So you get your array back and you go to use it. And now somebody else is like putting stuff in your array. How do you reason about that? It gets to be very complicated and leads to lots of bugs, right? And so one of the things that, again, this is not something Mojo forces on you, but something Mojo enables is a thing called value semantics. And what value semantics do is they take collections like arrays, like dictionaries, also tensors and strings and things like this that are much higher level and make them behave like proper values. And so it makes it look like if you pass these things around, you get a logical copy of all the data. And so if I pass you an array, it's your array. You can go do what you want to it. You're not going to hurt my array. Now, that is an interesting and very powerful design principle. It defines away a ton of bugs. You have to be careful to implement it in an efficient way.
Is there a performance hit that's significant?
Generally not, if you implement it the right way, but it requires a lot of very low level getting the language right bits.
I assume there'd be a huge performance hit because it's the benefit is really nice because you don't get into
Absolutely. Well, the trick is you can't do copies, so you have to provide the behavior of copying without doing the copy.
Yeah, how do you do that? How do you do that?
It's not magic. It's just it's actually pretty cool. Well, so first, before we talk about how that works, let's talk about how it works in Python. Right. So in Python, you define a person class, or maybe a person class is a bad idea. You define a database class, right? And a database class has an array of records, something like that, right? And so the problem is that if you pass in a record or a class instance into a database, it'll take a hold of that object, and then it assumes it has it. And if you're passing an object in, you have to know that that database is going to take it, and therefore you shouldn't change it after you put it in the database, right? This
You just kind of have to know that.
You just have to kind of know that, right? And so you roll out version 1 of the database, you just kind of have to know that. Of course, Lex uses its own database, right?
Yeah.
Right? Because you built it. You understand how this works, right? Somebody else joins the team. They don't know this,
Yes.
right? And so now they suddenly get bugs. You're having to maintain the database. You shake your fist. You argue. The 10th time this happens, you're like, okay, we have to do something different, right? And so what you do is you go change your Python code and you change your database class to copy the record every time you add it. And so what ends up happening is you say, okay, I will do what's called a defensive copy inside the database. And then that way, if somebody passes something in, I will have my own copy of it and they can go do whatever and they're not going to break my thing. Okay, this is usually the two design patterns. If you look in PyTorch, for example, this is cloning a tensor. Like there's a specific thing and you have to know where to call it. And if you don't call it in the right place, you get these bugs, and this is state of the art, right? So a different approach, so it's used in many languages, so I've worked with it in Swift, is you say, okay, well, let's provide value semantics. And so we want to provide the view that you get a logically independent copy, but we want to do that lazily. And so what we do is you say, okay, if you pass something into a function, it doesn't actually make a copy. What it actually does is it just increments a reference to it. And if you pass it around, you stick in your database, you can go in the database, you own it, and then you come back out of the stack, nobody's copied anything, you come back out of the stack, and then the caller lets go of it. Well, then you've just handed it off to the database, you've transferred it, and there's no copies made. Now, on the other hand, if your coworker goes and hands you a record and you pass it in, you stick it in the database, and then you go to town and you start modifying it, what happens is you get a copy lazily on demand. And so what this does is gives you copies only when you need them. And it also, so it defines away the bugs, but it also generally reduces the number of copies in practice. And so
But the implementation details are tricky here.
So this is, yes.
Something with reference counting, but to make it performant across a number of different kinds of objects.
Yeah, well, so you need a couple of things. And so there's many, so this concept has existed in many different worlds. And so it's not novel research at all, right? The magic is getting the design right so that you can do this in a reasonable way, right? And so there's a number of components that go into this. One is when you're passing around, so we're talking about Python and reference counting and the expense of doing that. When you're passing values around, you don't want to do extra reference counting for no good reason. And so you have to make sure that you're efficient and you transfer ownership instead of duplicating references and things like that, which is a very low-level problem. You also have to adopt this, and you have to build these data structures. And so if you say, Mojo has to be compatible with Python, so of course the default list is a reference semantic list that works the way you'd expect in Python, but then you have to design a value semantic list. And so you just have to implement that, and then you implement the logic within. And so the role of the language here is to provide all the low-level hooks that allow the author of the type to be able to get and express this behavior without forcing it into all cases or hard coding this into the language itself.
But there's a ownership, so you're constantly transferring, you're tracking who owns this thing.
Yes, and so there's a whole system called ownership, and so this is related to work done in the Rust community. Also, the Swift community has done a bunch of work, and there's a bunch of different other languages that have all kind of. C++ actually has copy constructors and destructors and things like that, and so. And I mean, C++ has everything. So it has move constructors and has like this whole world of things. And so this is a body of work that's kind of been developing for many, many years now. And so Mojo takes some of the best ideas out of all these systems and remixes it in a nice way so that you get the power of something like the Rust programming language, but you don't have to deal with it when you don't want to, which is a major thing in terms of teaching and learning and being able to use and scale these systems.
How does that play with argument conventions? What are they? Why are they important? How does the value semantics, how does the transfer ownership work with the arguments when they're passed into functions?
So if you go deep into systems programming land, so it's not something for everybody, but if you go deep into systems programming land, what you encounter is these types that get weird. So if you're used to Python, you think about everything, I can just copy it around, I can go change it and mutate it and do these things, and it's all cool. If you get into systems programming land, you get into these things like I have an atomic number, or I have a mutex, or I have a uniquely owned database handle, things like this, right? So these types you can't necessarily copy. Sometimes you can't necessarily even move them to a different address. And so what Mojo allows you to do is it allows you to express, hey, I don't want to get a copy of this thing. I want to actually just get a reference to it. And by doing that, what you can say is okay, if I'm defining something weird, like a atomic number or something, it's like it has to be. So an atomic number is an area in memory that multiple threads can access at a time without synchronous, without locks.
Yeah, you never seen
right?
a pimp like this.
And so like the definition of an atomic number is multiple different things have to be poking it. Therefore, they have to agree on where it is. Right? And so you can't just like move it out from underneath one because it kind of breaks what it means. And so that's an example of a type that you can't copy, you can't move it. Like once you create it, it has to be where it was, right? Now, if you look at many other examples, like a database handle, right? So, okay, well, what happens? How do you copy a database handle? Do you copy the whole database? That's not something you necessarily want to do. There's a lot of types like that where you want to be able to say that they are uniquely owned. So there's always one of this thing, or if I create a thing, I don't copy it. And so what Mojo allows you to do is it allows you to say, hey, I want to pass around a reference to this thing without copying it. And so it has borrowed conventions. So you can say you can use it, but you don't get to change it. You can pass it by mutable reference. And so if you do that, then you get a reference to it, but you can change it. And so it manages all that kind of stuff.
So it's just a really nice implementation of like C++ has, the different kinds of pointers.
Yeah, it has pointers.
Smart, different kinds of implementations of smart pointers
Yeah.
that you can explicitly define. This allows you, but you're saying that's more like the weird case versus the common case.
Well, it depends on where. I mean, I
Yes.
don't think I'm a normal person, so
Yes.
I mean, I'm not one to call other people weird.
Yeah.
But but if you talk to a typical Python programmer, you're
Yeah.
typically not thinking about this, right? This is a lower level of abstraction. Now, if you talk to a C++ programmer, certainly if you talk to a Rust programmer, again, they're not weird, they're delightful. Like these are all good people, right? Those folks will think about it all the time, right? And so I look at this as there's a spectrum between very deep, low-level systems. I'm going to go poke the bits and care about how they're laid out in memory, all the way up to application and scripting and other things like this. And so it's not that anybody's right or wrong. It's about how do we build one system that scales.
By the way, the idea of an atomic number has been something that always brought me deep happiness, because the flip side of that, the idea that threads can just modify stuff asynchronously. Just the whole idea of concurrent programming is a source of infinite stress for me.
Well, so this is where you jump into, again, you zoom out and get out of programming languages or compilers and you just look at what the industry has done. My mind is constantly blown by this, right? And you look at what, Moore's Law. Moore's Law is this idea that like computers for a long time, single thread performance just got faster and faster and faster and faster for free. But then physics and other things intervened, and power consumption, like other things started to matter. And so what ended up happening is we went from single core computers to multi-core. Then we went to accelerators, right? And this trend towards specialization of hardware is only going to continue. And so for years, us programming language nerds and compiler people have been saying, okay, well, how do we tackle multi-core? Right? For a while, it was like multi-core is the future. We have to get on top of this thing. And then it was multi-core is the default. What are we doing with this thing? And then it's like, there's chips with hundreds of cores in them. what happened, right?
Yeah.
And so I'm super inspired by the fact that, in the face of this, those machine learning people invented this idea of a tensor, right? And what is a tensor? A tensor is an arithmetic and algebraic concept. It's like an abstraction around a gigantic parallelizable data set, right? And because of that, and because of things like TensorFlow and PyTorch, we're able to say, okay, we'll express the math of the system. This enables you to do automatic differentiation. This enables you to do like all these cool things. And it's an abstract representation. Because you have that abstract representation, you can now map it onto these parallel machines without having to control, okay, put that byte here, put that byte there, put that byte there. And this has enabled an explosion in terms of AI, compute, accelerators, like all the stuff. And so that's super, super exciting.
What about the deployment, the execution across multiple machines?
Yep.
So you write that the modular compute platform dynamically partitions models with billions of parameters and distributes their execution across multiple machines, enabling unparalleled efficiency. By the way, the use of unparalleled in that sentence, anyway, enabling unparalleled efficiency, scale, and reliability for the largest workloads. So how do you do this abstraction of distributed deployment of large?
Yeah, so one of the really interesting tensions, so there's a whole bunch of stuff that goes into that. I'll pick a random walkthrough. If you go back and replay the history of machine learning, right? I mean, the brief most recent history of machine learning, because this is, as you know, very deep. I knew Lex when he had an AI podcast. Right. Yeah. So if you look at just TensorFlow and PyTorch, which is pretty recent history in the big picture, right? But TensorFlow is all about graphs. PyTorch, I think, pretty unarguably ended up winning. And why did it win? Mostly because of usability. Right, and the usability of PyTorch is, I think, huge. And I think, again, that's a huge testament to the power of taking abstract theoretical, technical concepts and bring it to the masses, right? Now, the challenge with what the TensorFlow versus the PyTorch design point was that TensorFlow is kind of difficult to use for researchers, but it was actually pretty good for deployment. PyTorch is really good for researchers. It kind of not super great for deployment, right? And so I think that we as an industry have been struggling. And if you look at what deploying a machine learning model today means, is that you'll have researchers who are, I mean, wicked smart, of course, but they're wicked smart at model architecture and data and calculus, and like they're wicked smart in various domains. They don't want to know anything about the hardware deployment or C++ or things like this, right? And so what's happened is you get people who train the model, they throw it over the fence, and then you have people that try to deploy the model. Well, every time you have a team A does X, they throw it over the fence, and team Y does team B does Y, like you have a problem, because of course it never works the first time. And so you throw it over the fence, they figure out, okay, it's too slow, won't fit, doesn't use the right operator, the tool crashes, whatever the problem is, then they have to throw it back over the fence. And every time you throw a thing over a fence, it takes 3 weeks of project managers and meetings and things like this. And so what we've seen today is that getting models in production can take weeks or months. It's not atypical. Right? I talk to lots of people, and you talk about like VP of software at some internet company trying to deploy a model, and they're like, why do I need a team of 45 people? It's so easy to train a model. Why can't I deploy it, right? And if you dig into this, every layer is problematic. So if you look at the language piece, I mean, this is tip of the iceberg. It's a very exciting tip of the iceberg for folks, but you've got Python on one side and C++ on the other side. Python doesn't really deploy. I mean, it can theoretically, technically in some cases, but often a lot of production teams will want to get things out of Python because they get their performance and control and whatever else. So Mojo can help with that. If you look at serving, so you talk about gigantic models. Well, a gigantic model won't fit on one machine, right? And so now you have this model, it's written in Python, it has to be rewritten in C++. Now it also has to be carved up so that half of it runs on one machine, half of it runs on another machine. Or maybe it runs on 10 machines. So now suddenly the complexity is exploding, right? And the reason for this is that if you look into TensorFlow, PyTorch, these systems, they weren't really designed for this world, right? They were designed for, back in the day when we were starting and doing things, where it was a different, much simpler world. If you want to run ResNet 50 or some ancient model architecture like this, it was a completely different world.
Trained on one GPU,
exactly.
Doing
AlexNet,
on one GPU.
yeah, AlexNet, right? The major breakthrough, and the world has changed, right? And so now the challenge is that TensorFlow, PyTorch, these systems, they weren't actually designed for LLMs. Like that was not a thing. And so where TensorFlow actually has amazing power in terms of scale and deployment and things like that. And I think Google is, I mean, maybe not unmatched, but they're like incredible in terms of their capabilities and gigantic scale. Many researchers using PyTorch, right? And so PyTorch doesn't have those same capabilities. And so what Modular can do is it can help with that. Now, if you take a step back and you say, like, what is Modular doing, right? So Modular has like a bitter enemy that we're fighting against in the industry. And it's one of these things where everybody knows it, but nobody is usually willing to talk about it.
The bitter enemy.
The bitter thing that we have to destroy, that we're all struggling with, and it's like all around, it's like fish can't see water, is complexity.
Sure. Yes. Complexity.
Right.
That was very philosophical of you. As you said.
And so if you look at it, yes, it is on the hardware side.
Yes.
All these accelerators, all these software stacks that go with the accelerator, all these, like, there's massive complexity over there. You look at what's happening on the modeling side, massive amount of complexity. Like, things are changing all the time. People are inventing. Turns out the research is not done, right? And so people want to be able to move fast. Transformers are amazing, but there's a ton of diversity even within transformers. And what's the next transformer, right? And you look into serving, also huge amounts of complexity. It turns out that all the cloud providers, right, have all their very weird but very cool hardware for networking, all this kind of stuff, and it's all very complicated. People aren't using it. If you look at classical serving, right, there's this whole world of people who know how to write high-performance servers with zero copy networking, and like all this fancy asynchronous I/O and like all these fancy things in the serving community. Very little that has pervaded into the machine learning world. right? And why is that? Well, it's because, again, these systems have been built up over many years. They haven't been rethought. There hasn't been a first principles approach to this. And so what Modular is doing is we're saying, okay, we've built many of these things, right? So I've worked on TensorFlow and TPUs and things like that. Other folks on our team have worked on PyTorch Core. We've worked on Onyx Runtime. We've worked on many of these other systems. And so built systems like the Apple accelerators and all that kind of stuff. Like our team is quite amazing. And so one of the things that roughly everybody at Modular is grumpy about is that when you're working on one of these projects, you have a first order goal. Get the hardware to work, get the system to enable one more model, get this product out the door, enable this specific workload, or make it solve this problem for this product team, right? And nobody's been given a chance to actually do that step back. And so we as an industry, we didn't take 2 steps forward. We took like 18 steps forward in terms of all this really cool technology across compilers and systems and runtimes and heterogeneous compute, like all this kind of stuff. And like all this technology has been, I wouldn't say beautifully designed, but it's been proven in different quadrants. Like, you look at Google with TPUs, massive, huge exaflops of compute strapped together into machines that researchers are programming in Python in a notebook. That's huge. That's amazing.
That's incredible.
Right? It's incredible. And so you look at the technology that goes into that, and the algorithms are actually quite general. And so lots of other hardware out there and lots of other teams out there don't have the sophistication or maybe the years working on it or the budget or whatever that Google does, right? And so they should be getting access to the same algorithms, but they just don't have them, right? And so what Modular's doing is we're saying, cool, this is not research anymore. Like we've built auto-tuning in many systems. We've built programming languages, right? And so like have implemented C++, have implemented Swift, have implemented many of these things. And so, it's hard, but it's not research. And you look at accelerators. Well, we know there's a bunch of different weird kinds of accelerators, but they actually cluster together, right? And you look at GPUs. Well, there's a couple of major vendors of GPUs, and they maybe don't always get along, but their architectures are very similar. You look at CPUs. CPUs are still super important for the deployment side of things. And you see new architectures coming out from all the cloud providers and things like this, and they're all super important to the world, right? But they don't have the 30 years of development that the entrenched people do, right? And so what Modular can do is we're saying, okay, all this complexity, like it's not bad complexity, it's actually innovation, right? And so it's innovation that's happening, and it's for good reasons, but I have sympathy for the poor software people, right? I mean, again, I'm a generally software person too. I love hardware, but software people want to build applications and products and solutions that scale over many years. They don't want to build a solution for one generation of hardware with one vendor's tools, right? And because of this, they need something that scales with them. They need something that works on cloud and mobile, right? Because their product manager said, "Hey, I want it to have lower latency and it's better for personalization," or whatever they decide, right? Products evolve. And so the challenge with the machine learning technology and the infrastructure we have today in the industry is that it's all these point solutions. And because there are all these point solutions, it means that as your product evolves, you have to switch to different technology stacks or switch to a different vendor. And what that does is that slows down progress.
So basically, a lot of the things we've developed in those little silos for machine learning tasks, you want to make that the first-class citizen of a general-purpose programming language that can then be compiled across all these kinds of hardware.
Well, so it's not really about a programming language. I mean, the programming language is a component of the mission, right? And the mission is, our not literal, but our joking mission is to save the world from terrible AI software.
Excellent. I love
Okay. So if you look at this mission, you need a syntax. One existed. Right, so if Python was already good enough, then cool, we would have just used it. Right? We're not just doing very large-scale, expensive engineering projects for the sake of it. Like, it's to solve a problem, right? It's also about accelerators. It's also about exotic numerics and bfloat16 and matrix multiplications and convolutions and like this kind of stuff. Within the stack, there are things like kernel fusion. It's an esoteric but really important thing that leads to much better performance and much more general research hackability together, right?
And so, that's enabled by the ASICs. That's enabled by certain hardware. So it's like, where's the dance between? There's several questions here. Like, how do you add a piece of hardware to this stack?
Yeah.
If a new piece of, like, if I have this genius invention of a specialized accelerator,
Yeah.
how do I add that to the modular framework? And also, how does modular as a standard start to define the kind of hardware that should be developed?
Yeah. So let me take a step back and talk about status quo. Okay.
Right.
And so if you go back to TensorFlow 1, PyTorch 1, this kind of time frame, and these have all evolved and gotten way more complicated. So let's go back to the glorious simple days, right? These things basically were CPUs and CUDA. And so what you do is you say, go do a dense layer, and a dense layer has a matrix multiplication in it, right? And so when you say that, you say, go do this big operation, a matrix multiplication, and if it's on a GPU, kick off a CUDA kernel. If it's on a CPU, go do like an Intel algorithm or something like that with the Intel MKL, okay? Now, that's really cool if you're either NVIDIA or Intel, right? But then more hardware comes in, right? And on one axis, you have more hardware coming in. On the other hand, you have an explosion of innovation in AI. And so what happened with both TensorFlow and PyTorch is that the explosion of innovation in AI has led to, it's not just about matrix multiplication and convolution. These things have now like 2,000 different operators. And on the other hand, you have, I don't know how many pieces of hardware there are out there. It's a lot. Okay, it's not even hundreds. It's probably thousands. Okay, and across all of Edge and across like all the different things
That are used at scale.
Yeah, exactly. I mean,
Also, it's not just like
AI is
a handful.
everywhere. Yeah,
It's not a handful of TPU alternatives.
Correct.
It's
every phone, often with many different
right.
chips inside of it from different vendors. From
Right.
like it's AI is everywhere. It's a thing, right?
Why are they all making their own chips? Like, why is everybody making their own thing?
Well, so because
Was that a good thing?
so Chris's philosophy on hardware.
Yeah.
Right. So my philosophy is that there isn't one right solution. Right. And so I think that again, we're at the end of Moore's law. Specialization happens.
Yeah.
If you're training GPT-5, you want some crazy supercomputer data center thingy. If you're making a smart camera that runs on batteries, you want something that looks very different. If you're building a phone, you want something that looks very different. If you have something like a laptop, you want something that looks maybe similar but a different scale, right? And so AI ends up touching all of our lives, robotics, right? And like lots of different things. And so as you look into this, these have different power envelopes. There's different trade-offs in terms of the algorithms. There's new innovations in sparsity and other data formats and things like that. And so hardware innovation, I think, is a really good thing. Right? And what I'm interested in is unlocking that innovation. There's also like analog and quantum and like all the really weird stuff, right?
Mm-hmm.
And so if somebody can come up with a chip that uses analog computing and it's 100x more power efficient, think what that would mean in terms of the daily impact on the products we use. That'd be huge. Now, if you're building an analog computer, you may not be a compiler specialist. Right? These are different skill sets, right? And so you can hire some compiler people if you're running a big company, maybe. But it turns out these are really like exotic new generation of compilers. Like this is a different thing, right? And so if you take a step back out and come back to what is the status quo? Status quo is that if you're Intel or you're NVIDIA, you keep up with the industry and you chase and okay, there's 1900 now, there's 2000 now, there's 2100, and you have a huge team of people that are like trying to keep up and tune and optimize. And even when one of the big guys comes out with a new generation of their chip, they have to go back and rewrite all these things, right? So really, it's only powered by having hundreds of people that are all like frantically trying to keep up. And what that does is that keeps out the little guys, and sometimes the not so little guys, the big guys that are also just not in those dominant positions. And so what has been happening, and so a lot of, you talk about the rise of new exotic crazy accelerators, is people have been trying to turn this from a let's go write lots of special kernels problem into a compiler problem. Mm-hmm. And so I contributed to this as well. we as an industry went into it like, let's go make this compiler problem phase, let's call it. And much of the industry is still in this phase, by the way, so I wouldn't say this phase is over. And so the idea is to say, look, okay, what a compiler does is it provides a much more general, extensible, hackable interface for dealing with the general case, right? And so within machine learning algorithms, for example, people figured out that, hey, if I do a matrix multiplication and I do a ReLU, right, the classic activation function, it is way faster to do one pass over the data and then do the ReLU on the output where I'm writing out the data, because ReLU is just a maximum operation, right? Maximum 0. And so it's an amazing optimization. Take matmul, ReLU, squish together in one operation. Now I have matmul ReLU. Well, wait a second. If I do that, now I just went from having 2 operators to 3. But now I figure out, okay, well, there's a lot of activation functions. What about leaky ReLU? What about like a million things that are out there, right? And so as I start fusing these in, now I get permutations of all these algorithms, right? And so what the compiler people said is they said, hey, well, cool. Well, I will go enumerate all the algorithms, and I will enumerate all the pairs, and I will actually generate a kernel for you. And I think that this has been very, very useful for the industry. This is one of the things that powers Google TPUs. PyTorch 2's like rolling out really cool compiler stuff with Triton, this other technology and things like this. And so the compiler people are kind of coming into their fore and saying like, awesome, this is a compiler problem, we'll compiler it. Here's the problem. Not everybody's a compiler person. I love compiler people, trust me, right? But not everybody can or should be a compiler person. It turns out that there are people that know analog computers really well, or they know some GPU internal architecture thing really well, or they know some crazy sparse numeric interesting algorithm that is the cusp of research, but they're not compiler people. And so one of the challenges with this new wave of technology trying to turn everything to a compiler is, again, it has excluded a ton of people. And so you look at what does Mojo do, what does the modular stack do, is it brings programmability back into this world. Like it enables, I wouldn't say normal people, but like a new, a different kind of delightful nerd that cares about numerics or cares about hardware or cares about things like this, to be able to express that in the stack and extend the stack without having to actually go hack the compiler itself.
So extend the stack on the algorithm side,
yeah,
and then on the hardware side.
Yeah. So again, go back to like the simplest example of int, right? And so what both Swift and Mojo and other things like this did is we said, okay, pull magic out of the compiler and put it in the standard library. Right, and so what Modular is doing with the engine that we're providing and like this very deep technology stack, right, which goes into heterogeneous runtimes and like a whole bunch of really cool things. This whole stack allows that stack to be extended and hacked and changed by researchers and by hardware innovators and by people who know things that we don't know, because Modular has some smart people, but we don't have all the smart people, it turns out.
What are heterogeneous runtimes?
Yeah, so what is heterogeneous, right? So heterogeneous just means many different kinds of things together.
Mm-hmm.
And so the simplest example you might come up with is a CPU and a GPU.
Mm-hmm.
And so it's a simple heterogeneous computer to say, I will run my data loading and pre-processing and other algorithms on the CPU. And then once I get it into the right shape, I shove it into the GPU. I do a lot of matrix multiplications and convolutions and things like this. And then I get it back out and I do some reductions and summaries, and they shove it across the wire across the network to another machine. Right? And so you've got now what are effectively two computers, a CPU and a GPU, talking to each other, working together in a heterogeneous system. But that was 10 years ago. Okay, you look at a modern cell phone. Modern cell phone, you've got CPUs. And they're not just CPUs, there's like big dot little CPUs, and so there's multiple different kinds of CPUs that are kind of working together. They're multi-core. You've got GPUs, you've got neural network accelerators, you've got dedicated hardware blocks for media, so for video decode and JPEG decode and things like this. And so you've got this massively complicated system. And this isn't just cell phones. Every laptop these days is doing the same thing. And all of these blocks can run at the same time and need to be choreographed. Right. And so, again, one of the cool things about machine learning is it's moving things to like data flow graphs and higher level abstractions and tensors and these things that it doesn't specify. Here's how to do the algorithm. It gives the system a lot more flexibility in terms of how to translate or map it or compile it onto the system that you have. And so what you need, the bottomest part of the layer there is a way for all these devices to talk to each other. And so this is one thing that I'm very passionate about. I'm a nerd, but all these machines and all these systems are effectively parallel computers running at the same time, sending messages to each other. And so they're all fully asynchronous. Well, this is actually a small version of the same problem you have in a data center. Right? In a data center, you now have multiple different machines, sometimes very specialized, sometimes with GPUs or TPUs in one node, and sometimes with disks in another node. And so you get a much larger scale heterogeneous computer And so what ends up happening is you have this like multi-layer abstraction of hierarchical parallelism, hierarchical asynchronous communication, and making that, again, my enemy is complexity. By getting that away from being different specialized systems at every different part of the stack and having more consistency and uniformity, I think we can help lift the world and make it much simpler and actually get used.
But how do you leverage the strengths of the different specialized systems? So looking inside the smartphone,
Yeah.
like there's what, like, I don't know, 5-6 computers essentially inside
Yeah,
the smartphone. How do you, without trying to minimize the explicit, making it explicit which computer is supposed to be used for which operation?
Yeah, so there's a pretty well-known algorithm, and what you're doing is you're looking at two factors. You're looking at the factor of sending data from one thing to another, right? Because it takes time to get it from that side of the chip to that side of the chip, and things like this. And then you're looking at what is the time it takes to do an operation on a particular block. So take CPUs. CPUs are fully general. They can do anything, right? But then you have a neural net accelerator that's really good at matrix multiplications. Okay, and so you say, okay, well, if my workload is all matrix multiplications, I start up, I send the data over to the neural net thing, it goes and does matrix multiplications. When it's done, it sends me back the result. All is good, right? And so the simplest thing is just saying, do matrix operations over there, right? But then you realize you get a little bit more complicated because you can do matrix multiplications on a GPU, you can do it on a neural net accelerator, you can do it on CPU, and they'll have different trade-offs and costs. And it's not just matrix multiplication. And so what you actually look at is you look at, I have generally a graph of compute. I want to do a partitioning. I want to look at the communication, the bisection bandwidth, and like the overhead and the sending of all these different things, and build a model for this, and then decide, okay, it's an optimization problem. Where do I want to place this compute?
It's the old school theoretical computer science problem of scheduling. And then how does, presumably it's possible to somehow magically include AutoTune into this?
Absolutely. So, I mean, in my opinion, this is an opinion. This is not everybody would agree with this, but in my opinion, the world benefits from simple and predictable systems at the bottom that you can control. But then once you have a predictable execution layer, you can build lots of different policies on top of it, right? And so one policy can be that the human programmer says, do that here, do that here, do that here, do that here, and like fully manually controls everything. And the system should just do it, right? Then you quickly get in the mode of like, I don't want to have to tell it to do it.
Yeah.
And so the next logical step that people typically take is they write some terrible heuristic. Oh, if it's a matrix multiplication, do it over there. Or if it's floating point, do it on the GPU. If it's an integer, do it on the CPU. Like something like that.
This
right?
sucks.
And then you then get into this mode of like people care more and more and more, and you say, okay, well, let's actually like make the heuristic better. Let's get into AutoTune. Let's actually do search of the space to decide, well, what is actually better, right? Well, then you get into this problem where you realize this is not a small space. This is a many-dimensional, hyperdimensional space that you cannot exhaustively search. So, do you know of any algorithms that are good at searching very complicated spaces for?
Don't tell me you're going to turn this into a machine learning problem.
So then you turn into a machine learning problem, and then you have a space of genetic algorithms and reinforcement learning, and like all these.
But can you include that into the stack, into the modular stack?
Yeah. And so,
Where does it sit? Where does it live? Is it a separate thing, or is it part of the compilation?
So you start from simple and predictable models, and so you can have full control, and you can have coarse grain knobs that like nudge the system, so you don't have to do this. But if you really care about getting the best, the last ounce out of a problem, then you can use additional tools. And there, the cool thing is you don't want to do this every time you run a model. You want to figure out the right answer and then cache it. And once you do that, you can say, okay, cool. Well, I can get up and running very quickly. I can get good execution out of my system. I can decide if something's important, and if it's important, I can go throw a bunch of machines at it and do a big, expensive search over the space using whatever technique I feel like. It's really up to the problem. And then when I get the right answer, cool, I can just start using it.
I don't hear anything.
And so you can get out of this this trade-off between, okay, am I going to like spend forever doing a thing, or do I get up and running quickly and get a quality result? Like these are actually not in contention with each other if the system's designed to scale.
You started and did a little bit of a whirlwind overview of how you get 35,000x speed up or more over Python. Jeremy Howard did a really great presentation about sort of the basic, like look at the code. Here's how you get the speed up. Like you said, that's something we could probably developers can do for their own code to see how you can get these gigantic speed ups. But can you maybe speak to the machine learning task in general? How do you make some of this code fast and specifics? Like, what would you say is the main bottleneck for machine learning tasks? So, are we talking about matmul, matrix multiplication? How do you make that fast?
So, I mean, if you just look at the Python problem, right, you can say, how do I make Python faster? And there's been a lot of people that have been working on how to make Python 2x faster, 10x faster, or something like that, right? And there have been a ton of projects in that thing, right? Mojo started from what can the hardware do? Like, what is the limit of physics?
Yeah.
What is the speed of light? What is like, how fast can this thing go? And then, how do I express that? Right. And so it wasn't anchored relatively on make Python a little bit faster. It's saying, cool, I know what the hardware can do. Let's unlock that. Right now, when you
can you just say how gutsy that is to be in the meeting, and as opposed to trying to see how do we get the improvement, it's like, what can the physics do?
I mean, maybe I'm a special kind of nerd, but you look at that. What is the limit of physics? How fast can these things go? Right. When you start looking at that, typically it ends up being a memory problem. Right? And so today, particularly with these specialized accelerators, the problem is that you can do a lot of math within them, but you get bottleneck sending data back and forth to memory, whether it be local memory or distant memory or disk or whatever it is. And that bottleneck, particularly as the training sizes get large, as you start doing tons of inferences all over the place, like that becomes a huge bottleneck for people, right?
No way.
So again, what happened is we went through a phase of many years where people took the special case and hand-tuned it, and tweaked it and tricked it out, and they knew exactly how the hardware worked, and they knew the model, and they made it fast. Didn't generalize. And so you can make, ResNet 50 or AlexNet or something, exception V1. Like you can do that, right? Because the models are small. They fit in your head, right? But as the models get bigger, more complicated, as the machines get more complicated, it stops working. Right? And so this is where things like kernel fusion come in. So what is kernel fusion? This is this idea of saying, let's avoid going to memory, and let's do that by building a new hybrid kernel, a numerical algorithm that actually keeps things in the accelerator instead of having to write it all the way out to memory. What's happened with these accelerators now is you get multiple levels of memory. Like in a GPU, for example, you'll have global memory and local memory and like all these things. If you zoom way into how hardware works, the register file is actually a memory. So the registers are like an L0 cache. And so a lot of taking advantage of the hardware ends up being fully utilizing the full power in all this capability. And this has a number of problems, right? One of which is, again, the complexity of disaster, right? There's too much hardware. Even if you just say, let's look at the chips from one line of vendor, like Apple or Intel or whatever it is, each version of the chip comes out with new features. And they change things so that it takes more time or less time to do different things. And you can't rewrite all the software whenever a new chip comes out. Right. And so this is where you need a much more scalable approach. This is what Mojo and what the modular stack provides. Provides this infrastructure, this system for factoring all this complexity, and then allowing people to express algorithms, auto tuning, for example, express algorithms in a more portable way, so that when a new chip comes out, you don't have to rewrite it all. So to me, like, I kind of joke, like, what is a compiler? Well, there's many ways to explain that. You convert thing A into thing B, and you convert source code to machine code. Like you can talk about many things that compilers do. But to me, it's about a bag of tricks. It's about a system and a framework that you can hang complexity. It's a system that can then generalize and it can work on problems that are bigger than fit in one human's head. Right? And so what that means, what a good stack and what the modular stack provides is the ability to walk up to it with a new problem, and it'll generally work quite well. And that's something that a lot of machine learning infrastructure and tools and technologies don't have. Typical state of the art today is you walk up, particularly if you're deploying, if you walk up with a new model, you try to push it through the converter, and the converter crashes. That's crazy. The state of ML tooling today is not anything that a C programmer would ever accept, right? And it's always been this kind of flaky set of tooling that's never been integrated well, and it's been never worked together, and because it's not designed together. It's built by different teams. It's built by different hardware vendors. It's built by different systems. It's built by different internet companies. They're trying to solve their problems, right? And so that means that we get this fragmented, terrible mess of complexity.
So, I mean, the specifics, and Jeremy showed this. There's the vectorize function, which I guess is built into Mojo.
Vectorize, as you showed, is built into the library.
Into the library. It's there in the library. Vectorize, parallelize. Vectorize is more low level, parallelize is higher level. There's the tiling thing, which is how he demonstrated the auto tune, I think.
So think about this in like levels, hierarchical levels of abstraction. Right? And so at the very, if you zoom all the way into a compute problem, you have one floating point number, right? And so then you say, okay, I can do things one at a time in an interpreter. It's pretty slow, right? So I can get to doing one at a time in a compiler. You can see, and I can get to doing 4 or 8 or 16 at a time with vectors. That's called vectorization. Then you can say, hey, I have a whole bunch of different, what a multi-core computer is it's basically a bunch of computers, right? So they're all independent computers that can talk to each other and they share memory. And so now what Parallelize does is it says, okay, run multiple instances of this on different computers. And now they can all work together on a problem, right? And so what you're doing is you're saying, keep going out to the next level out. And as you do that, how do I take advantage of this? So tiling is a memory optimization, right? It says, okay, let's make sure that we're keeping the data close to the compute part of the problem instead of sending it all back and forth through memory every time I load a block.
And the size of the block size is all. That's how you get to the auto tune to make sure it's optimized.
Yeah. Well, so all of these, the details matter so much to get good performance. This is another funny thing about machine learning and high performance computing that is very different than C compilers we all grew up with, where, if you get a new version of GCC or a new version of Clang or something like that, maybe something will go 1% faster, right? And so compiler engineers work really, really, really hard to get 0.5% out of your C code, something like that. But when you're talking about an accelerator or an AI application, or you're talking about these kinds of algorithms, these are things people used to write in Fortran, for example, right? If you get it wrong, it's not 5% or 1%. It could be 2x or 10x, right? If you think about it, you really want to make use of the full memory you have, the cache, for example. If you use too much space, it doesn't fit in the cache, now you're going to be thrashing all the way back out to main memory. And these can be 2x, 10x, major performance. So this is where getting these magic numbers and these things right is really actually quite important.
So you mentioned that Mojo is a superset of Python. Can you run Python code as if it's Mojo code?
Yes. Yes. And this has two sides of it. So Mojo's not done yet. So I'll give you a disclaimer. Mojo's not done yet. But already we see people that take small pieces of Python code, move it over, they don't change it, and you can get 12x speedups. Like somebody was just tweeting about that yesterday, which is pretty cool, right? And again, interpreters, compilers, right? And so without changing any code, also this is not JIT compiling or doing anything fancy. This is just basic stuff straight over. Now, Mojo will continue to grow out, and as it grows out, it will have more and more and more features. And our North Star is to be a full superset of Python, and so you can bring over basically arbitrary Python code and have it just work. And it may not always be 12x faster, but it should be at least as fast and way faster in many cases. Right. Now it'll take time to do that. And Python is a complicated language. There's not just the obvious things, but there's also non-obvious things that are complicated. Like we have to be able to talk to CPython packages, to talk to the C API, and there's a bunch of pieces.
So you have to, just to make explicit the obvious, it may not be so obvious until you think about it. So, to run Python code, that means you have to run all the Python packages and libraries.
Yeah.
So that means what? What's the relationship between Mojo and CPython, the interpreter that's presumably would be tasked with getting those packages to work?
Yep. So in the fullness of time, Mojo will solve for all the problems, and you'll be able to move Python packages over and run them in Mojo
without the CPython.
without CPython someday.
Yeah.
Right. So not today, but someday. And that'll be a beautiful day because then you'll get a whole bunch of advantages and you'll get massive speed ups and things like that.
So you can do that one at a time, right? You can make packages one at a time.
Exactly. But we're not willing to wait for that. Python is too important. The ecosystem is too broad. We want to both be able to build Mojo out. We also want to do it the right way without without intense time pressure. We're obviously moving fast, but and so what we do is we say, okay, well, let's make it so you can import an arbitrary existing package, arbitrary, including like you write your own on your local disk or whatever. It's not like a standard package, like an arbitrary package, and import that using CPython. So CPython already runs all the packages. Right, and so what we do is we built an integration layer where we can actually use CPython. Again, I'm practical to actually just load and use all the existing packages as they are. The downside of that is you don't get the benefits of Mojo for these packages. Right, and so they'll run as fast as they do in the traditional CPython way.
I try to get more information out of
But
them.
what that does is that gives you an incremental migration path.
Actually,
And so
this
if you say, hey,
J-Rod
cool,
I
well,
gotta
here's
have
a,
J-Rod.
the Python ecosystem is vast. I want all of it to just work. But there's certain things that are really important. And so if I'm doing weather forecasting or something, well, I want to be able to load all the data. I want to be able to work with it, and then I have my own crazy algorithm inside of it. Well, normally I'd write that in C++. If I can write in Mojo and have one system that scales, well, that's way easier to work with.
Is it hard to do that, to have that layer that's running CPython? Because is there some communication back and forth?
Yes, it's complicated. I mean, this is what we do. So, I mean, we make it look easy, but it is complicated. But what we do is we use the CPython existing interpreter. So it's running its own bytecodes, and that's how it provides full compatibility. And then it gives us CPython objects, and we use those objects as is. And so that way we're fully compatible with all the CPython objects and all the it's not just the Python part, it's also the C packages, the C libraries underneath them, because they're often hybrid. And so we can fully run and we're fully compatible with all that. And the way we do that is that we have to play by their rules, right? And so we keep objects in that representation when they're coming from that world.
What's the representation that's being used?
In memory. I have to know a lot about how the CPython interpreter works. It has, for example, reference counting, but also different rules on how to pass pointers around and things like this. Super low level fiddly, and it's not like Python, it's like how the interpreter works, okay? And so that gets all exposed out, and then you have to define wrappers around the low level C code. Right? And so what this means is you have to know not only C, which is a different world from Python, obviously, not only Python,
With the wrappers.
but the interpreter and the wrappers and the implementation details and the conventions, and it's just this really complicated mess. And when you do that, now suddenly you have a debugger that debugs Python. You can't step into C code.
This is Kitty Cat.
So you have this two-world problem, right? And so by pulling this all into Mojo, what you get is you get one world. You get the ability to say, cool, I have untyped, very dynamic, beautiful, simple code. Okay, I care about performance for whatever reason, right? There's lots of reasons you might care. And so then you add types, you can parallelize things, you can vectorize things, you can use these techniques, which are general techniques to solve a problem. And then you can do that by staying in the system. And if you're you have that one Python package that's really important to you, you can move to Mojo. You get massive performance benefits on that, and other advantages. If you like static types, it's nice if they're enforced. Some people like that, right? Rather than being hints. So there's other advantages too. And then you can do that incrementally as you go.
So one different perspective on this would be why Mojo instead of making CPython faster or redesigning CPython?
Yeah. Well, I mean, you could argue Mojo is redesigning CPython, but why not make CPython faster and better and other things like that? There's lots of people working on it. So actually, there's a team at Microsoft that is really improving. I think CPython 3.11 came out in October or something like that, and it was 15% faster, 20% faster across the board, which is pretty huge given how mature Python is and things like this. And so that's awesome. I love it. Doesn't run on GPU. It doesn't do AI stuff, like it doesn't do vectors, doesn't do things. I'm 20% is good, 35,000 times better, right? So like they're definitely. I'm a huge fan of that work, by the way, and it composes well with what we're doing, and so it's not like we're fighting or anything like that. It's actually just general. It's goodness for the world, but it's just a different path, right? And again, we're not working forwards from making Python a little bit better. We're working backwards from what is the limit of physics.
What's the process of porting Python code to Mojo? Is there what's involved in that process? Is there tooling for that?
Not yet. So we're missing some basic features right now, and so we're continuing to drop out new features like on a weekly basis. But at the fullness of time, it was a year and a half, maybe 2 years.
Is it an automatable process?
So when we're ready, it'll be very automated. Yes.
Is it automatable? Like, is it possible to automate in the general case the Python to Mojo conversion?
Yeah. Well,
you're saying it's possible.
Well, and this is why, among other reasons why we use tabs.
Yes.
Right. So first of all, by being a superset,
yeah,
it's like C versus C++. Can you move C code to C++?
Yes.
Yeah. Right. And you can move C code to C++, and then you can adopt classes. You can adopt templates. You can adopt other references or whatever C++ features you want after you move C code to C++. Like, you can't use templates in C, right? And so if you leave it as C, fine, you can't use the cool features, but it still works, right? And C and C++ could work together. And so that's the analogy, right? Now, here, right, there's not a Python is bad and then Mojo is good. Right? Mojo just gives you superpowers, right? And so if you want to stay with Python, that's cool. But the tooling should be actually very beautiful and simple, because we're doing the hard work of defining a superset.
Right. So you're right. So there's several things to say there, but also the conversion tooling should probably give you hints as to like how you can improve the code.
And then exactly. Once you're in the new world, then you can build all kinds of cool tools to say like, hey, should you adopt this feature? Or like, and we haven't built those tools yet, but I fully expect those tools will exist, and then you can quote unquote modernize your code, or however you want to look at it, right? So one of the things that I think is really interesting about Mojo is that there have been a lot of projects to improve Python over the years. Everything from getting Python to run on the Java virtual machine, PyPy, which is a JIT compiler. There's tons of these projects out there that have been working on improving Python in various ways. They fall into one of two camps. So PyPy is a great example of a camp that is trying to be compatible with Python. Even there, not really. It doesn't work with all the C packages and stuff like that. But they're trying to be compatible with Python. There's also another category of these things where they're saying, well, Python is too complicated, and I'm going to cheat on the edges, and it's like integers in Python can be an arbitrary size integer. If you care about fitting going fast in a register in a computer, that's really annoying, right? And so you can choose two paths on that, right? You can say, well, people don't really use big integers that often, therefore I'm going to just not do it, and it'll be fine. Not a Python superset.
Yeah.
Or you can do the hard thing and say, okay, this is Python. You can't be a superset of Python without being a superset of Python. And that's a really hard technical problem, but it's, in my opinion, worth it, right? And it's worth it because it's not about any one package. It's about this ecosystem. It's about what Python means for the world. And it also means we don't want to repeat the Python 2 to Python 3 transition. Like, we want people to be able to adopt this stuff quickly. And so by doing that work, we can help lift people.
Yeah, the challenge, it's really interesting technical philosophical challenge of really making a language a superset of another language. It's breaking my brain a little bit.
Well, it paints you into corners. So again, I'm very happy with Python. So all joking aside, I think that the indentation thing is not the actual important part of the problem.
Yes.
Right? But the fact that Python has amazing dynamic metaprogramming features and they translate to beautiful static metaprogramming features, I think is profound. I think that's huge, right? And so Python, I've talked with Guido about this. It's like it was not designed to do what we're doing. That was not the reason they built it this way, but because they really cared and they were very thoughtful about how they designed the language, it scales very elegantly in this space. But if you look at other languages, for example, C and C++, right? If you're building a superset, you get stuck with the design decisions of the subset, right? And so C++ is way more complicated because of C and the legacy than it would have been if they would have theoretically designed a from scratch thing. And there's lots of people right now that are trying to make C++ better and resyntax C++. It's going to be great. We'll just change all the syntax. But if you do that, now suddenly you have 0 packages. You don't have compatibility.
So what are the, if you could just linger on that, what are the biggest challenges of keeping that superset status? What are the things you're struggling with? Is it all boiled down to having a big integer?
No, I mean,
What are the other things?
Usually it's the long tail weird things. So let me give you a war story.
Okay.
So war story in the space is you go way back in time. Project I worked on is called Clang.
Mm-hmm.
Clang, what it is a C++ parser, right? And when I started working on Clang, it must have been like 2006 or something. 2007, 2006 when I first started working on it, right? It's funny how time flies.
Yeah.
I started that project and I'm like, okay, well, I want to build a C parser, C++ parser for LLVM. It's going to be the word GCC is yucky. This is me in earlier times. It's yucky. It's unprincipled. It has all these weird features, like all these bugs. Like it's yucky. So I'm going to build a standard compliant C and C++ parser. It's going to be beautiful. Be amazing, well engineered, all the cool things an engineer wants to do. And so I started implementing, building it out, and then I got to include standard.io.h. And all of the headers in the world use all the GCC stuff. Okay.
Yeah.
And so again, come back away from theory back to reality, right? I was at a fork on the road. I could have built an amazingly beautiful academic thing that nobody would ever use. Or I could say, well, it's yucky in various ways. All these design mistakes, accents of history, the legacy. At that point, GCC was like over 20 years old. Which, by the way, now LLVM's over 20 years old.
Yeah.
Right? And so it's funny how
time
catches up to you, right? And so you say, okay, well, what is easier, right? I mean, as an engineer, it's actually much easier for me to go implement long tail compatibility weird features, even if they're distasteful, and just do the hard work and like figure it out, reverse engineer it, understand what it is, write a bunch of test cases, like try to understand behavior. It's way easier to do all that work as an engineer than it is to go talk to all C programmers and argue with them and try to get them to rewrite their code.
Yeah.
Right. And
because that breaks a lot more things.
Yeah. And you have realities like nobody actually even understands how the code works because it was written by the person who quit 10 years ago. Right. And so this software is kind of frustrating that way, but that's how the world works. Right?
Yeah. Unfortunately, it can never be this perfect, beautiful thing.
Well, there are occasions in which you get a build, like, you invent a new data structure or something like that, or there's this beautiful algorithm that just like makes you super happy. Right? I love that moment. But when you're working with people, when you're working with code and dusty deck code bases and things like this, right? It's not about what's theoretically beautiful. It's about what's practical, what's real, what people actually use. And I don't meet a lot of people that say, I want to rewrite all my code just for the sake of it.
Mm-hmm. By the way, there could be interesting possibilities, and we'll probably talk about it, where AI can help rewrite some code. That might be farther out future, but it's a really interesting one. Yeah. How that could create more, be a tool in the battle against this monster of complexity that you mentioned.
Yeah.
You mentioned Guido, the benevolent dictator for life of Python. What does he think about Mojo? Have you talked to him much about it?
I have talked with him about it. He found it very interesting. We actually talked with Guido before it launched, and so he was aware of it before it went public. I have a ton of respect for Guido for a bunch of different reasons. You talk about Walrus operator, and like Guido is pretty amazing in terms of steering such a huge and diverse community and like driving it forward. And I think Python is what it is thanks to him. Right? And so to me, it was really important starting to work on Mojo to get his feedback and get his input and get his eyes on this. Right now, a lot of what Guido was and is, I think, concerned about is how do we not fragment the community?
Yeah,
we don't want a Python 2 to Python 3 thing. Like that was really painful for everybody involved. And so we spent quite a bit of time talking about that and some of the tricks I learned from Swift, for example. So in the migration from Swift, we managed to like not just convert Objective-C into a slightly prettier Objective-C, which we did. We then converted, not entirely, but almost an entire community to a completely different language, right? And so there's a bunch of tricks that you learn along the way that are directly relevant to what we do. And so this is where, for example, you leverage CPython while bringing up the new thing. Like that approach is, I think, proven and comes from experience. And so Guido was very interested in, like, okay, cool. Like, I think that Python is really his legacy. It's his baby. I have tons of respect for that. Incidentally, I see Mojo as a member of the Python family. We're not trying to take Python away from Guido and from the Python community. And so to me, it's really important that we're a good member of that community. And so, yeah, I think that, again, you would have to ask Guido this, but I think that he was very interested in this notion of like, cool, Python gets beaten up for being slow. Maybe there's a path out of that. Right. And that, if the future is Python, right? I mean, look at the far outside case on this, right? And I'm not saying this is Guido's perspective, but there's this path of saying like, okay, well, suddenly Python can suddenly go all the places it's never been able to go before. Right. And that means that Python can go even further and can have even more impact on the world.
So in some sense, Mojo could be seen as Python 4.0.
I would not say that. I think that would drive a lot of people really crazy.
Because of the PTSD of the 3.0, 2.0.
I'm willing to annoy people about Emacs versus Vim,
But
about
not that
Tails
one.
versus Spaces.
Not that one.
I don't know. That might be a little bit far even for me. Like my skin may not be that thick.
But the point is, the step to being a superset and allowing all of these capabilities, I think, is the evolution of a language. It feels like an evolution of a language. So he's interested by the ideas that you're playing with, but also concerned about the fragmentation. So what are the ideas you've learned? What are you thinking about? How do we avoid fragmenting the community where the Pythonistas and the I don't know what to call the Mojo people.
Magicians.
Magicians, I like it.
There you go.
Can coexist happily and share code and basically just have these big code bases that are using CPython and more moving towards Mojo.
Yeah. Well, so again, these are lessons I learned from Swift, and here we face very similar problems, right? In Swift, you have Objective-C, super dynamic. They're very different syntax, right? But you're talking to people who have large-scale code bases. I mean, Apple's got the largest scale code base of Objective-C code, right? And so, none of the companies, none of the iOS developers, none of the other developers want to rewrite everything all at once. And so you want to be able to adopt things piece at a time. And so a thing that I found that worked very well in the Swift community was saying, okay, cool. And this is when Swift was very young. And you say, okay, you have a 1 million line of code Objective-C app. Don't rewrite it all. But when you implement a new feature, go implement that new class using Swift. Mm-hmm. Right. And so now this turns out is a very wonderful thing for an app developer, but it's a huge challenge for the compiler team and the systems people that are implementing this, right? And this comes back to what is this trade-off between doing the hard thing that enables scale versus doing the theoretically pure and ideal thing, right? And so Swift adopted and built a lot of different machinery to deeply integrate with the Objective-C runtime. And we're doing the same thing with Python, right? Now, what happened in the case of Swift is that Swift as a language got more and more mature over time, right? And incidentally, Mojo is a much simpler language than Swift in many ways. And so I think that Mojo will develop way faster than Swift for a variety of reasons. But as the language gets more mature, in parallel with that, you have new people starting new projects, right? And so when the language is mature and somebody's starting a new project, that's when they say, okay, cool, I'm not dealing with 1 million lines of code. I'll just start and use the new thing for my whole stack. Now, the problem is, again, you come back to we're communities and we're people that work together. You build a new subsystem or a new feature, a new thing in Swift, or you build a new thing in Mojo. Then you want to end up being used on the other side, right? And so then you need to work on integration back the other way. And so it's not just Mojo talking to Python, it's also Python talking to Mojo. right? And so what I would love to see, I don't want to see this next month, right? But what I want to see over the course of time is I would love to see people that are building these packages, like, NumPy or, TensorFlow or what, these packages that are half Python, half C++. And if you say, okay, cool, I want to get out of this Python C++ world into a unified world, and so I can move to Mojo, but I can't give up all my Python clients.
Mhm.
They're like, these libraries get used by everybody, and they're not all going to switch all at once, and maybe never, right? Well, so the way we should do that is we should vend Python interfaces to the Mojo types.
Mhm.
And that's what we did in Swift, and it worked great. I mean, it was a huge implementation challenge for the compiler people, right? But there's only a dozen of those compiler people, and there are millions of users. And so it's a very expensive, capital intensive, like skill set intensive problem. But once you solve that problem, it really helps adoption. It really helps the community progressively adopt technologies. And so I think that this approach will work quite well with the Python and the Mojo world.
So for a package, port it to Mojo and then create a Python interface.
Yep.
So how do when you're on these packages, NumPy, PyTorch, TensorFlow?
Yeah.
How do they play nicely together? So is Mojo supposed to be? Let's talk about the machine learning ones. Is Mojo kind of vision to replace PyTorch and TensorFlow? To incorporate it? What's the relationship in this?
All right, so
Dang.
so take a step back. So I wear many hats. So you're angling it on the Mojo side. Mojo is a programming language, and so it can help solve the C++, Python feud that's happening.
The fire emoji got me. I'm sorry. We should be talking modular. Yes.
Yes. Okay. So the fire emoji is amazing. I love it. It's a big deal. The other side of this is the fire emoji is in service of solving some big AI problems, right? And so the big AI problems are, again, this fragmentation, this hardware nightmare, this explosion of new potential, but it's not getting felt by the industry, right? And so when you look at how does the modular engine help TensorFlow and PyTorch, right? It's not replacing them, right? In fact, when I talk to people, again, they don't like to rewrite all their code. You have people that are using a bunch of PyTorch, a bunch of TensorFlow. They have models that they've been building over the course of many years, right? And when I talk to them, there's a few exceptions, but generally they don't want to rewrite all their code, right? And so what we're doing is we're saying, okay, well, you don't have to rewrite all your code. What happens is the modular engine goes in there and goes underneath TensorFlow and PyTorch. It's fully compatible. And it just provides better performance, better predictability, better tooling. It's a better experience that helps lift TensorFlow and PyTorch and make them even better. I love Python. I love TensorFlow. I love PyTorch, right? This is about making the world better because we need AI to go further.
But if I have a process that trains a model and I have a process that performs inference on that model and I have the model itself, what should I do with that in the long arc of history? In terms of if I use PyTorch to train it, should I rewrite stuff in Mojo? Would that, if I care about performance?
Oh, so I mean, again, it depends. So if you care about performance, then writing it in Mojo is going to be way better than writing it in Python. But if you look at LLM companies, for example, if you look at OpenAI, rumored, and you look at many of the other folks that are working on many of these LLMs and other like innovative machine learning models. On the one hand, they're innovating in the data collection and the model, billions of parameters and the model architecture and the RLHF and the like all the cool things that people are talking about. But on the other hand, they're spending a lot of time writing CUDA kernels, right? And so you say, wait a second, how much faster could all this progress go if they were not having to handwrite all these CUDA kernels, right? And so there are a few technologies that are out there, and people have been working on this problem for a while, and they're trying to solve subsets of the problem, again, kind of fragmenting the space. And so what Mojo provides for these kinds of companies is the ability to say, cool, I can have a unifying theory, right? And again, the better together, the unifying theory, the two-world problem or the three-world problem or the n-world problem, like this is the thing that is slowing people down. And so as we help solve this problem, I think it'll be very helpful for making this whole cycle go faster.
So obviously we talked about the transition from Objective-C to Swift, to design this programming language. And you've also talked quite a bit about the use of Swift for machine learning context. Why have you decided to move away from maybe an intense focus on Swift for the machine learning context versus sort of deciding a new programming language that happens to be a superset.
You're saying this is an irrational set of life choices I make?
Did you go to the desert? And did you meditate on it? Okay, all right. No, it was bold. It was bold and needed, and I think it's just bold. And sometimes to take those leaps is a difficult leap to take.
Yeah, well, so, okay. I mean, I think there's a couple of different things. So, actually, I left Apple back in 2017, like January 2017. So it's been a number of years that I left Apple. And the reason I left Apple was to do AI. Okay, so, and again, I won't comment on Apple and AI, but at the time, right, I wanted to get into and understand the technology, understand the applications, the workloads, and so I was like, okay, I'm going to go dive deep into applied and AI, and then the technology underneath it, right? I found myself at Google,
and that was like when TPUs were
waking
up.
Exactly, and so I found myself at Google, and Jeff Dean, who's a rock star, as you know, right? And in 2017, TensorFlow is like really taking off and doing incredible things. And I was attracted to Google to help them with the TPUs, right? And TPUs are an innovative hardware accelerator platform. Have now, I think, proven massive scale and like done incredible things, right? And so one of the things that this led into is a bunch of different projects, which I'll skip over, right? One of which was this Swift for TensorFlow project, right? And so that project was a research project. And so the idea of that is say, okay, well, let's look at innovative new programming models where we can get a fast programming language, we can get automatic differentiation into language. Let's push the boundaries of these things in a research setting, right? Now, that project, I think, lasted 2-3 years. There's some really cool outcomes of that. So one of the things that's really interesting is I published a talk at an LLVM conference in 2018, and it seems like so long ago, about graph program abstraction, which is basically the thing that's in PyTorch 2. And so PyTorch 2, with all this DynamoRio thing, it's all about this graph program abstraction thing from Python bytecodes. And so a lot of the research that was done ended up pursuing and going out through the industry and influencing things, and I think it's super exciting and awesome to see that. But the Swift for TensorFlow project itself did not work out super well. And so there's a couple of different problems with that, one of which is that you may have noticed Swift is not Python. There's a few people that write Python code.
Yes.
And so it turns out that all of ML is pretty happy with Python.
It's actually a problem that other programming languages have as well, that they're not Python. We'll probably maybe briefly talk about Julia, which is a very interesting, beautiful programming language, but it's not Python.
Exactly. Well, and so if you're saying, I'm going to solve a machine learning problem where all the programmers are Python programmers, and you say the first thing you have to do is switch to a different language, well, your new thing may be good or bad or whatever, but if it's a new thing, the adoption barrier is massive.
It's still possible.
Still possible? Yeah, absolutely. The world changes and evolves, and there's definitely room for new and good ideas, but it just makes it so much harder. Right? And so, lesson learned, Swift is not Python, and people are not always in search of like learning a new thing for the sake of learning a new thing. And if you want to be compatible with all the world's code, turns out, meet the world where it is. Right? Second thing is that, a lesson learned is that Swift as a very fast and efficient language, kind of like Mojo, but a different take on it still, really worked well with eager mode. And so eager mode is something that PyTorch does, and it proved out really well, and it enables really expressive and dynamic and easy to debug programming. TensorFlow at the time was not set up for that. Let's say that was not.
Timing is also important in this world.
Yeah. TensorFlow is a good thing, and it has many strengths, but you could say Swift for TensorFlow is a good idea, except for the Swift and except for the TensorFlow part. So
Swift because it's not Python, and TensorFlow because it's not.
It wasn't set up for eager mode at the time. Yeah,
it was 1.0.
Exactly. And so one of the things about that is that in the context of it being a research project, I'm very happy with the fact that we built a lot of really cool technology. We learned a lot of things. I think the idea on to have influence in other systems like PyTorch. A few people use that, I hear, right? And so I think that's super cool. And for me personally, I learned so much from it, right? And I think a lot of the engineers that worked on it learned a tremendous amount. And so, I think that that's just really exciting to see. And I'm sorry that the project didn't work out. I wish it did, of course, right? But it's a research project, and so you're there to learn from it.
But it's interesting to think about the evolution of programming as we come up with these whole new set of algorithms in machine learning and artificial intelligence, and what's going to win out. Because it could be a new programming language.
Yeah.
It could be, I just mentioned Julia. I think there's a lot of ideas behind Julia that Mojo shares. What are your thoughts about Julia in general?
So I will have to say that when we launched Mojo, one of the biggest things I didn't predict was the response from the Julia community. And so I was not, okay, let me take a step back. I've known the Julia folks for a really long time. They're an adopter of LLVM a long time ago. They've been pushing state of the art in a bunch of different ways. Julia is a really cool system. I had always thought of Julia as being mostly a scientific computing focused environment, right? And I thought that was its focus. I neglected to understand that one of their missions is to help make Python work end to end. And so I think that was my error for not understanding that. And so I could have been maybe more sensitive to that. But there's major differences between what Mojo is doing and what Julia is doing. So as you say, Julia is not Python, right? And so one of the things that a lot of the Julia people came out and said is okay, well, if we put a ton of more energy and a ton more money or engineering or whatever into Julia, maybe that would be better than starting Mojo. Maybe that's true, but it still wouldn't make Julia into Python. So if you work backwards from the goal of let's build something for Python programmers without requiring them to relearn syntax, then Julia just isn't there, right? That's a different thing, right? And so if you anchor on I love Julia and I want Julia to go further, then you can look at it from a different lens. But the lens we were coming at was, hey, everybody is using Python. Syntax isn't broken. Let's take what's great about Python and make it even better. And so it's just a different starting point. So I think Julia is a great language. The community is a lovely community. They're doing really cool stuff, but it's just a slightly different angle.
But it does seem that Python is quite sticky. Is there some philosophical almost thing you could say about why Python, by many measures, seems to be the most popular programming language in the world?
Well, I can tell you things I love about it. Maybe that's one way to answer the question, right? So huge package ecosystem, super lightweight and easy to integrate. It has very low startup time.
So what startup time? You mean learning curve or what?
Yeah, so if you look at certain other languages, you say Go, and it just takes Java, for example, it takes a long time to JIT compile all the things, and then the VM starts up and the garbage collector kicks in, and then it revs its engines, and then it can plow through a lot of internet stuff or whatever, right? Python is scripting. It just goes, right? Python has very low compile time. So you're not sitting there waiting. Python integrates into notebooks in a very elegant way that makes exploration super interactive, and it's awesome, right? Python is also, it's almost the glue of computing. Because it has such a simple object representation, a lot of things plug into it. That dynamic metaprogramming thing we were talking about also enables really expressive and beautiful APIs. Right? So there's lots of reasons that you can look at technical things that Python has done and say okay, wow, this is actually a pretty amazing thing. And any one of those you can neglect. People will all just talk about indentation and ignore the fundamental things. But then you also look at the community side, right? So Python owns machine learning. Machine learning is pretty big.
Yeah, and it's growing.
And it's growing, right? And it's growing in importance, right? And
there's a reputation of prestige to machine learning, to where if you're a new programmer, you're thinking about which programming language do I use? Well, I should probably care about machine learning. Therefore, let me try Python. And kind of builds and builds and builds.
And even go back before that. My kids learn Python. Right? Not because I'm telling them to learn Python, but because
were they rebelling against you or what?
Well, no, right? Well, they also learn Scratch, right, and things like this too. But it's because Python is taught everywhere, right? Because it's easy to learn, right, and because it's pervasive, right? And
back in my day, we learned Java and C++. Uphill both directions, but yes, I guess Python is the main language of teaching software engineering in schools now.
Yeah, well, and if you look at this, there's these growth cycles, right? If you look at what causes things to become popular and then gain in popularity, there's reinforcing feedback loops and things like this. And I think Python has done, again, the whole community has done a really good job of building those growth loops and help propel the ecosystem. And I think that, again, you look at what you can get done with just a few lines of code. It's amazing.
So this kind of self-building loop is interesting to understand, because when you look at Mojo, what it stands for, some of the features, it seems sort of clear that this is a good direction for programming languages to evolve in the machine learning community. But it's still not obvious that it will, because of this, whatever the engine of popularity, of virality. Is there something you could speak to, like how do you get people to switch?
Yeah, well, I mean, I think that the viral growth loop is to switch people to Unicode.
Yes.
I think the Unicode file extends are what I'm betting on. I think that's going to be the thing.
Yeah. Tell the kids that you can use the fire emoji. They'd be
Exactly.
like, what?
Exactly. So, well, in all seriousness, like, I mean, I think there's really, I'll give you two opposite answers. One is, I hope if it's useful, if it solves problems, and if people care about those problems being solved, they'll adopt the tech. Right, that's kind of the simple answer. And when you're looking to get tech adopted, the question is it solving an important problem people need solved? And is the adoption cost low enough that they're willing to make the switch and cut over and do the pain up front so that they can actually do it, right? And so hopefully Mojo will be that for a bunch of people. And people building these hybrid packages are suffering. And it's really painful. And so I think that we have a good shot of helping people. But the other side is, like, it's okay if people don't use Mojo. Like, it's not my job to say, like, everybody should do this. Like, I'm not saying Python is bad. Like, I hope CPython, like all these implementations, because the Python ecosystem is not just CPython. It's also a bunch of different implementations with different trade-offs. And this ecosystem is really powerful and exciting, as are other programming languages. It's not like TypeScript or something is going to go away, right? And so there's not a winner-take-all thing. And so I hope that Mojo is exciting and useful to people, but if it's not, that's also fine.
But I also wonder what the use case for why you should try Mojo would be. So practically speaking,
Yeah.
It seems like so there's entertainment. There's the dopamine hit of saying, holy shit, this is 10 times faster. This little piece of code is 10 times faster in Mojo.
Out of the box before you get to 35,000.
Exactly. I mean, just even that. I mean, that's the dopamine hit that every programmer sort of dreams of. Is the optimization. It's also the drug that can pull you in and have you waste way too much of your life optimizing and over optimizing, right? But so what do you see would be like common? It's just very hard to predict, of course, but if you look 10 years from now and Mojo's super successful,
Yeah.
what do you think would be the thing where people like try it and then use it regularly and it kind of grows and grows and grows?
Well, so you talk about dopamine hit. And so, again, humans are not one thing. And some people love rewriting their code and learning new things and throwing themselves in the deep end and trying out a new thing. In my experience, most people don't. Like, they're too busy. They have other things going on. By number, most people don't like this. I want to rewrite all my code. But even those people, the too busy people, the people that don't actually care about the language, they just care about getting stuff done, those people do like learning new things, right? And so you talk about the dopamine rush of 10x faster. Wow, that's cool. I want to do that again. Well, it's also like, here's the thing I've heard about in a different domain, and now I don't have to rewrite all my code. I can learn a new trick, right? Well, that's called growth, And so one thing that I think is cool about Mojo, and again, those will take a little bit of time for example, the blog posts and the books and like all that kind of stuff to develop, and the language needs to get further along. But what we're doing, you talk about types, like you can say, look, you can start with the world you already know, and you can progressively learn new things and adopt them where it makes sense. If you never do that, that's cool. You're not a bad person. if you get really excited about it and want to go all the way in the deep end and want to rewrite everything and like whatever, that's cool, right? But I think the middle path is actually the more likely one, where it's you come out with a new idea and you discover, wow, that makes my code way simpler, way more beautiful, way faster, way whatever. And I think that's what people like. Now, if you fast forward and you said like 10 years out, right? I can give you a very different answer on that, which is, I mean, if you go back and look at what computers looked like 20 years ago, every 18 months they got faster for free. Right, 2x faster every 18 months. It was like clockwork. It was free, right? You go back 10 years ago, and we entered in this world where suddenly we had multi-core CPUs and we had GPUs. And if you squint and turn your head, what a GPU is it's just a many-core, very simple CPU thing, kind of, right? And so, and 10 years ago, it was CPUs and GPUs and graphics. Today, we have CPUs, GPUs, graphics, and AI, because it's so important, because the compute is so demanding, because of smart cameras and the watches and all the different places the AI needs to work in our lives. It's caused this explosion of hardware. And so part of my thesis, part of my belief of where computing goes, if you look out 10 years from now, is it's not going to get simpler. Physics isn't going back to where we came from. It's only going to get weirder from here on out, right? And so to me, the exciting part about what we're building is it's about building that universal platform, which the world can continue to get weird, because again, I don't think it's avoidable, it's physics, but we can help lift people, scale, do things with it. They don't have to rewrite their code every time a new device comes out. And I think that's pretty cool. And so if Mojo can help with that problem, then I think that it will be hopefully quite interesting and quite useful to a wide range of people, because there's so much potential, and like there's so much, maybe analog computers will become a thing or something, right? And we need to be able to get into a mode where we can move this programming model forward, but do so in a way where we're lifting people and growing them instead of forcing them to rewrite all their code and exploding them.
Do you think there'll be a few major libraries that go Mojo first?
Well, so I mean, the modular engine's on Mojo. So again, come back to, like, we're not building Mojo because it's fun. We're building Mojo because we had to solve these accelerators.
That's the origin story. But I mean ones that are currently in Python.
Yeah, so I think that a number of these projects will. And so one of the things, again, this is just my best guess, like each of the package maintainers also has, I'm sure, plenty of other things going on. People really don't like rewriting code just for the sake of rewriting code. But sometimes, like, people are excited about like adopting a new idea.
Yeah.
It turns out that while rewriting code is generally not people's first thing, turns out that redesigning something while you rewrite it and using a rewrite as an excuse to redesign can lead to the 2.0 of your thing that's way better than the 1.0. Right. And so I have no idea. I can't predict that. But there's a lot of these places where, again, if you have a package that is half C and half Python, right, you just solve the pain, make it easier to move things faster, make it easier to debug and evolve your tech. Adopting Mojo kind of makes sense to start with, and then it gives you this opportunity to rethink these things.
So the two big gains are that there's a performance gain, and then there's the portability to all kinds of different devices.
And there's safety, right? So you talk about real types. And I'm not saying this is for everybody, but that's actually a pretty big thing. Right?
Yeah, types are,
and so there's a bunch of different aspects of what value Mojo provides. And so I mean, it's funny for me. Like, I've been working on these kinds of technologies and tools for too many years now. But you look at Swift, right? And we talked about Swift for TensorFlow, but Swift as a programming language, right? Swift's now 13 years old from when I started it.
Yeah.
So because I started in 2010, if I remember, and so. That project, and I was involved with it for 12 years or something, right? That project has gone through its own really interesting story arc, right? And it's a mature, successful, used by millions of people system, right? Certainly not dead yet, right? But also going through that story arc, I learned a tremendous amount about building languages, about building compilers, about working with the community, and things like this. And so that experience, like, I'm helping channel and bring directly into Mojo, and other systems, same thing. Like, apparently, I like building and iterating and evolving things. And so you look at this LLVM thing that I worked on 20 years ago, you look at MLIR, right? And so a lot of the lessons learned in LLVM got fed into MLIR. And I think that MLIR is a way better system than LLVM was. And, Swift is a really good system, and it's amazing, but I hope that Mojo will take the next step forward in terms of design.
In terms of running Mojo, people can play with it. What's Mojo Playground?
Yeah.
And from the interface perspective and from the hardware perspective, what's this incredible thing running on?
Yeah. So right now, here we are 2 weeks after launch.
Yes.
We decided that, okay, we have this incredible set of technology that we think might be good, but we have not given it to lots of people yet. And so we were very conservative and said, let's put it in a workbook so that if it crashes, we can do something about it. We can monitor and track that, right? And so, again, things are still super early, but we're having like one person a minute sign up with over 70,000 people 2 weeks in. It's kind of crazy.
So you can sign up to the playground and you can use it in the cloud.
Yeah.
In your
Yeah.
browser.
And so what that's running on, right?
Notebook.
Yeah, what that's running on is that's running on Cloud VM. And so you share a machine with a bunch of other people, but it turns out there's a bunch of them now because there's a lot of people. And so what you're doing is you're getting free compute and you're getting to play with this thing in kind of a limited, controlled way so that we can make sure that it doesn't totally crash and be embarrassing, right?
Yeah.
So now a lot of the feedback we've gotten is people want to download it locally, so we're working on that right now. And so that's
the goal, to be able to download locally.
yeah,
to it.
yeah, that's what everybody expects. And so we're working on that right now. And so we just want to make sure that we do it right. And I think this is one of the lessons I learned from Swift also, by the way, is that when we launched Swift, gosh, it feels like forever ago. It was 2014. And it was super exciting. The team had worked on Swift for a number of years in secrecy. Okay. And we, 4 years into this development, roughly, of working on this thing, at that point, about 250 people at Apple knew about it. Okay. So it was secret. Apple's good at secrecy, and it was a secret project. And so we launched this at WWDC, a bunch of hoopla and excitement, and said, developers are going to be able to develop and submit apps to the App Store in 3 months. Okay. Well, several interesting things happened, right? So first of all, we learned that it had a lot of bugs. It was not actually production quality, and it was extremely stressful in terms of like trying to get it working for a bunch of people. And so what happened is we went from 0 to, I don't know how many developers Apple had at the time, but a lot of developers overnight, and they ran into a lot of bugs, and it was really embarrassing, and it was very stressful for everybody involved, right? It was also very exciting because everybody was excited about that. The other thing I learned is that when that happened, roughly every software engineer who did not know about the project at Apple, their head exploded when it was launched because they didn't know it was coming. And so they're like, wait, what is this? I signed up to work for Apple because I love Objective-C. Why is there a new thing, right? And so now what that meant practically is that the push from launch to, first of all, the fall, but then to 2.0 and 3.0 and like all the way forward was super painful for the engineering team and myself. It was very stressful. The developer community was very grumpy about it because they're like, okay, well, wait a second, you're changing and code and like you have to fix the bugs. And it was just like a lot of tension and friction on all sides. There's a lot of technical debt in the compiler because you have to run really fast. You have to go implement the thing and unblock the use case and do the thing. And it's not right, but you never have time to go back and do it right. And I'm very proud of the Swift team because they've come, they came so far and made so much progress over this time since launch. It's pretty incredible. And Swift is a very, very good thing. But I still want to do that again, right? And so
iterate more through the development process.
And so what we're doing is we're not launching it when it's hopefully 0.9 with no testers. We're launching it and saying it's 0.1. Right. And so we're setting expectations of saying like, okay, well, don't use this for production. Right. If you're interested in what we're doing, we'll do it in an open way and we can do it together, but don't use it in production yet. Like we'll get there, but let's do it the right way. And I'm also saying we're not in a race. The thing that I want to do is build the world's best thing.
Yeah.
Right. Because if you do it right and it lifts the industry, it doesn't matter if it takes an extra 2 months. Yeah. Like 2 months is worth waiting. And so doing it right and not being overwhelmed with technical debt, things like this is like, again, war wounds, lessons learned, whatever you want to say, I think is absolutely the right thing to do, even though right now people are very frustrated that, you can't download it or that it doesn't have feature X or something like this. And so,
well, what have you learned in a little bit of time since it's been released into the wild that people have been complaining about feature X or Y or Z? What have they been complaining about? What they have been excited about? Almost like detailed things versus big vision. I think everyone would be very excited about the big vision.
Yeah. Well, so I mean, I've been very pleased. I mean, in fact, I mean, we've been massively overwhelmed with response, which is a good problem to have. It's kind of like a success disaster,
Yeah.
in a sense, right? So what, I mean, if you go back in time when we started Modular, which was just not yet a year and a half ago, so it's still a pretty new company, new team, small but very good team of people. Like, we started with extreme conviction that there's a set of problems that we need to solve, and if we solve it, then people will be interested in what we're doing, right? But again, you're building in basically secret, right? You're trying to figure it out. The creation's a messy process. You're having to go through different paths and understand what you want to do and how to explain it. Often when you're doing disruptive and new kinds of things, just knowing how to explain it is super difficult, right? And so when we launched, we hoped people would be excited, but I'm an optimist, but I'm also like, don't want to get ahead of myself. And so when people found out about Mojo, I think their heads exploded a little bit, right? And here's I think a pretty credible team that's built some languages and some tools before, and so they have some lessons learned and are tackling some of the deep problems in the Python ecosystem and giving it the love and attention that it should be getting. And I think people got very excited about that. And so if you look at that, I mean, I think people are excited about ownership and taking a step beyond Rust, right? There's people that are very excited about that. There's people that are excited about, just like, I made Game of Life go 400 times faster, right? And things like that. And that's really cool. There are people that are really excited about I really hate writing stuff in C++. Same.
Like systems engineers, they're like stepping up. Like,
Yeah. So that's me, by the way. Also,
Yeah.
I really want to stop writing C++. But
I get third person excitement when people tweet, "Yeah, I made this code, Game of Life, or whatever, faster." And you're like,
yeah, and also, like, well, I would also say that let me cast blame out to people who deserve it.
sure,
These terrible people who convinced me to do some of this.
Yeah.
Jeremy Howard,
yes.
that guy.
Well, he's been pushing for this kind of thing. He's
wanted this for
Mojo.
years.
Yeah, he's wanted this for a long,
He's
long
wanted
time.
this for years. And so
For people who don't know Jeremy Howard, he's like one of the most legit people in the machine learning community. He's a grassroots. He really teaches. He's an incredible educator. He's an incredible teacher, but also legit in terms of a machine learning engineer himself.
yeah,
And
so,
he's been running the Fast.ai and looking, I think, for exactly what you
exactly.
Mojo.
And so, I mean, the first time, so I met Jeremy pretty early on, but the first time I sat up and I'm like, this guy is ridiculous, is when I was at Google and we were bringing up TPUs and we had a whole team of people and there was this competition called Dawn Bench of who can train ImageNet fastest, right?
Yes.
And Jeremy and one of his researchers crushed Google by not through sheer force of the amazing amount of compute and the number of TPUs and stuff like that. That he just decided that progressive image resizing was the right way to train the model and fewer epochs faster and make the whole thing go vroom, right?
Yep.
And I'm like, this guy is incredible. Right? So you can say, anyways, come back to where's Mojo coming from? Chris finally listened to Jeremy. It's all his fault.
But there's a kind of very refreshing, pragmatic view that he has about machine learning that I don't know if it's like this mix of a desire for efficiency, but ultimately grounded in a desire to make machine learning more accessible to a lot of people. I don't know what that is. I guess that's coupled with efficiency and performance. But it's not just obsessed about performance.
Well, so a lot of AI and AI research ends up being that it has to go fast enough to get scale. So a lot of people don't actually care about performance, particularly on the research side, until it allows them to have a bigger data set, right? And so suddenly now you care about distributed compute and like all these exotic HPC. Like, you don't actually want to know about that. You just want to be able to do more experiments faster and do so with bigger data sets, right? And so Jeremy has been really pushing limits. And one of the things I'll say about Jeremy, and there's many things I could say about Jeremy because I'm a fan boy of his, but it fits in his head. And Jeremy actually takes the time, where many people don't, to really dive deep into why is the beta parameter of the atom optimizer equal to this, right? And he'll go survey and understand what are all the activation functions and the trade-offs, and why is it that everybody that does, this model pick that thing?
So the why, not just trying different
The why.
values, like really what is going on here.
Right. And so as a consequence of that, like he makes time, but he spends time to understand things at a depth that a lot of people don't. And as you say, he then brings it and teaches people. And his mission is to help lift, his website says, making AI uncool again. Like, it's about, forget about the hype. It's actually practical and useful. Let's teach people how to do this, right? Now, the problem Jeremy struggled with is that he's pushing the envelope, right? Research isn't about doing the thing that is staying on the happy path or the well-paved road, right? And so a lot of the systems today have been these really fragile, fragmented things. They're special case in this happy path. And if you fall off the happy path, you get eaten by an alligator.
So what about, so Python has this giant ecosystem of packages, and there's a package repository. Do you have ideas of how to do that well in Mojo?
Yeah.
How to do a repository of packages?
Well, so that's another really interesting problem that I knew about, but I didn't understand how big of a problem it was. Python packaging. A lot of people have very big pain points and a lot of scars with Python packaging.
Oh, you
And
mean, so there's several things to say.
building and distributing
Yes.
and managing dependencies and versioning and all this stuff.
So from the perspective of if you want to create your own package.
Yes. And then, or you want to build on top of a bunch of other people's packages and then they get updated and stuff like this. Now, I'm not an expert in this, so I don't know the answer. I think this is one of the reasons why it's great that we work as a team and there's other really good and smart people involved. But one of the things I've heard from smart people who've done a lot of this is that the packaging becomes a huge disaster when you get the Python and C together. And so if you have this problem where you have code split between Python and C, now not only do you have to package the C code, you have to build the C code. C doesn't have a package manager, right? C doesn't have a dependency versioning management system, right? And so I'm not experienced in the state of the art and all the different Python package managers, but my understanding is that's a massive part of the problem. And I think Mojo solves that part of the problem directly heads on. Now, one of the things I think we'll do with the community, and this isn't, again, we're not solving all the world's problems at once, we have to be kind of focused to start with, is that I think that we will have an opportunity to reevaluate packaging, right? And so I think that we can come back and say, okay, well, given the new tools and technologies and the cool things we have that we've built up, because we have not just syntax, we have an entirely new compiler stack that works in a new way. Maybe there's other innovations we can bring together and maybe we can help solve that problem.
So almost a tangent to that question from the user perspective of packages. It was always surprising to me that it was not easier to sort of explore and find packages. You know, with pip install, and it feels it's an incredible ecosystem. It's just interesting that it wasn't made. It's still, I think, not made easier to discover packages to do, like search and discovery, as YouTube calls it.
Well, I mean, it's kind of funny because this is one of the challenges of these like intentionally decentralized communities. And so I don't know what the right answer is for Python. I mean, there are many people that would, or I don't even know the right answer for Mojo. There are many people that would have much more informed opinions than I do. But it's interesting if you look at this, right? Open source communities. There's Git. Git is a fully decentralized, and anybody can do it any way they want. But then there's GitHub, right? And GitHub, centralized, commercial in that case, right? Thing really help pull together and help solve some of the discovery problems and help build a more consistent community. And so maybe there's opportunities for
something like a GitHub for community.
Yeah.
Although even GitHub, I might be wrong on this, but the search and discovery for GitHub is not that great. Like I still use Google search.
Yeah, well, I mean, maybe that's because GitHub doesn't want to replace Google search, right? And I think there is room for specialized solutions to specific problems. So,
Sure.
I don't know. I don't know the right answer for GitHub either. They can go figure that out.
But the point is to have an interface that's usable, that's accessible to people of all different skill levels.
well, and again, like what are the benefit of standards, right? Standards allow you to build these next level up ecosystem, next level up infrastructure, and next level up things. And so, again, come back to I hate complexity. C plus Python is complicated. It makes everything more difficult to deal with. It makes it difficult to port, move code around, work with. All these things get more complicated. And so, I mean, I'm not an expert, but maybe Mojo can help a little bit by helping reduce the amount of C in this ecosystem and make it therefore scale better.
Any kind of packages that are hybrid in nature would
Yeah.
be a natural fit to move to Mojo.
Which is a lot of them, by the way.
Yeah.
So,
A lot of them, especially, they're doing some interesting stuff competition-wise. Let me ask you about some features.
Yeah.
So we talked about, obviously, indentation. That's a typed language or optionally typed. What's the right way to say it?
it's either optionally or progressively, or
Progressively.
I think so. People have very strong opinions on the right word to use.
Yeah.
I don't know.
I look forward to your letters. So there's the var versus let, but let is for constants.
Yeah.
Var is an optional.
Yeah, var makes it mutable, so you can reassign.
Then there's function overloading.
Oh, okay. Yeah.
I mean, there's a lot of source of happiness for me, but function overloading, that's, I guess, is that for performance, or is that, why does Python not have function overloading?
So I can speculate. So Python is a dynamic language. The way it works is that Python and Objective-C are actually very similar worlds if you ignore syntax. And so Objective-C is straight line derived from Smalltalk, a really venerable, interesting language that much of the world has forgotten about, but the people that remember it love it generally. And the way that Smalltalk works is that every object has a dictionary in it, and the dictionary maps from the name of a function, or the name of a value within an object, to its implementation. And so the way you call a method in Objective-C is you say, go look up, and the way I call foo is I go look up foo, I get a pointer to the function back, and then I call it. Okay, that's how Python works, right? And so now the problem with that is that the dictionary within a Python object, all the keys are strings, and it's a dictionary, so you can only have one entry per name.
You think it's as simple as that?
I think it's as simple as that. And so now, why do they never fix this? Like, why do they not change it to not be a dictionary? Why do they not do other things? Well, you don't really have to in Python because it's dynamic. And so you can say, I get into the function. Now, if I got past an integer, do some dynamic tests for it. If it's a string, do another thing. There's another additional challenge, which is even if you did support overloading, you're saying, okay, well, here's a version of a function for integers and a function for strings. Well, you'd have, even if you could put it in that dictionary, you'd have to have the caller do the dispatch. Mm-hmm. And so every time you call the function, you'd have to say, like, is it an integer or is it a string? And so you'd have to figure out where to do that test. And so in a dynamic language, overloading is something you don't have to have. So, but now you get into a typed language, and in Python, if you subscript with an integer, then you get typically one element out of a collection. If you subscript with a range, you get a different thing out, right? And so often in typed languages, you'll want to be able to express the fact that, cool, I have different behavior depending on what I actually pass into this thing. If you can model that, it can make it safer and more predictable and faster and like all these things.
It somehow feels safer, yes, but also feels empowering. Like in terms of clarity, like you don't have to design whole different functions.
Yeah, well, this is also one of the challenges with the existing Python typing systems is that in practice, like you take subscript, like in practice, a lot of these functions, they don't have one signature. Right? They actually have different behavior in different cases. And so this is why it's difficult to like retrofit this into existing Python code and make it play well with typing. You kind of have to design for that.
Okay, so there's a interesting distinction that people that program Python might be interested in is def versus fn. So it's two different ways to define a function. And fn is a stricter version of def. What's the coolness that comes from the strictness?
So here you get into what is the trade-off with the superset.
Yes.
Okay, so a superset, you have to, or you really want to be compatible. If you're doing a superset, you've decided compatibility with existing code is the important thing, even if some of the decisions they made were maybe not what you would choose. Okay, so that means you put a lot of time in compatibility, and it means that you get locked into decisions in the past, even if they may not have been a good thing. Right now, systems programmers typically like to control things, right? And they want to make sure that, not in all cases, of course, and even systems programmers are not one thing, right? But often you want predictability. And so one of the things that Python has, for example, as you know, is that if you define a variable, you just say x equals 4. I have a variable named x. Now I say some long name equals 17. Print out some long name. Oops, but I typoed it. Right. Well, the Python compiler doesn't know in all cases what you're defining and what you're using, and did you typo the use of it or the definition? Right. And so for people coming from typed languages, again, I'm not saying they're right or wrong, but that drives them crazy because they want the compiler to tell them you typoed the name of this thing.
Mm-hmm.
Right. And so what FN does is it turns on, as you say, it's a strict mode. And so it says, okay, well, you have to actually intentionally declare your variables before you use them. That gives you more predictability, more error checking, and things like this. But you don't have to use it. And this is a way that Mojo is both compatible, because defs work the same way that defs have always worked, but it provides a new alternative that gives you more control and allows certain kinds of people that have a different philosophy to be able to express that and get that.
But usually, if you're writing Mojo code from scratch, you'll be using FM.
It depends. Again, it depends on your mentality, right? It's not that def is Python and FN is Mojo. Mojo has both, and it loves both, right? It really depends on.
That was just strict.
Yeah, exactly. Are you playing around and scripting something out? And is it a one-off throwaway script? Cool. Like Python is great at that.
I will still be using FM, but yeah.
Well, so
I love strictness.
okay. Well, so
Control, power.
you also like suffering, right?
Yes.
So,
They go hand in hand.
how many pull-ups?
I've lost count at this.
Yeah, exactly.
At this point.
So and that's cool. I love you for that.
Yeah.
And I love other people
But
who
if-
like strict things, right? But I don't want to say that that's the right thing, because Python's also very beautiful for hacking around and doing stuff and research and these other cases where you may not want that.
See, I just feel like maybe I'm wrong in that, but it feels like strictness leads to faster debugging. So in terms of going from, even on a small project, from 0 to completion, it just, I guess it depends how many bugs you generate usually.
Well, so I mean, it's again lessons learned and looking at the ecosystem. It's really, I think it's, if you study some of these languages over time, like the Ruby community, for example. Ruby is a pretty well-developed, pretty established community, but along their path, they really invested in unit testing. And so I think that the Ruby community has really pushed forward the state-of-the-art of testing because they didn't have a type system that caught a lot of bugs at compile time, right? And so you can have the best of both worlds. You can have good testing and good types, right, and things like this. But I thought that was really interesting to see how certain challenges get solved. And in Python, for example, the interactive notebook kind of experiences and stuff like this are really amazing. If you typo something, it doesn't matter. It just tells you that's fine, right? And so I think that the trade-offs are very different if you're building a large-scale production system versus you're building and exploring in a notebook.
So speaking of control, the hilarious thing, if you look at code I write just for myself for fun, it's like littered with asserts everywhere.
Yeah.
It's a kind of
Yeah, you'd like types.
it's basically saying in a dictatorial way, this should be true now, otherwise everything stops.
Well, and that is the sign. And again, I love you, man, but that is a sign of somebody who likes control.
Yeah.
And so, yes, I think that you'll like
How did
FN.
this turn into a
I think you'll like
therapy?
Mojo.
Therapy session. Yes, I definitely will. Speaking of asserts, exceptions are called errors. Why is it called errors?
So we use the same. We're the same as Python, right? But we implement it a very different way, right? And so if you look at other languages, like we'll pick on C++, our favorite, right? C++ has this thing called zero-cost exception handling. Okay, so, and this is, in my opinion, something to learn lessons from.
It's a nice polite way of
Okay.
saying it.
And
Yeah.
so zero cost exception handling, the way it works is that it's called zero cost because if you don't throw an exception, there's supposed to be no overhead for the non-error code, and so it takes the error path out of the common path. It does this by making throwing an error extremely expensive. And so if you actually throw an error with a C++ compiler using exceptions, it has to go look up in tables on the side and do all this stuff. And so throwing an error can be like 10,000 times more expensive than returning from a function, right? Also, it's called zero cost exceptions, but it's not zero cost by any stretch of the imagination because it massively bloats out your code, your binary. It also adds a whole bunch of different paths because of structures and other things like that that exist in C++. And it reduces the number of optimizations, it has like all these effects. And so this thing that was called zero cost exceptions, it really ain't. Okay. Now, if you fast forward to newer languages, and this includes Swift and Rust and Go and now Mojo, well, in Python, it's a little bit different because it's interpreted, and so like it's got a little bit of a different thing going on. But if you look at compiled languages, many newer languages say, okay, well, let's not do that zero cost exception handling thing. Let's actually treat throwing an error the same as returning a variant, returning either the normal result or an error. Now, programmers generally don't want to deal with all the typing machinery and like pushing around a variant. And so you use all the syntax that Python gives us, for example, try and catch, functions that raise and things like this. You can put a raises decorator on your function, stuff like this. And if you want to control that, and then the language can provide syntax for it. But under the hood, the way the computer executes it, throwing an error is basically as fast as returning something.
Interesting. So it's exactly the same way from the compiler perspective.
And so this is actually, I mean, it's a fairly nerdy thing, right? Which is why I love it. But this has a huge impact on the way you design your APIs, right? So in C++, huge communities turn off exceptions because the cost is just so high, right? And so the zero cost is so high, right? And so that means you can't actually use exceptions in many libraries. Right. And even for the people that do use it, well, okay, how and when do you want to pay the cost? If I try to open a file, should I throw an error? Well, what if I'm probing around looking for something, right? And I'm looking it up in many different paths. Well, if it's really slow to do that, maybe I'll add another function that doesn't throw an error, returns an error code instead. And now I have two different versions of the same thing. And so it causes you to fork your APIs. And so one of the things I learned from Apple and I still love is the art of API design is actually really profound. I think this is something that Python's also done a pretty good job at in terms of building out this large-scale package ecosystem. It's about having standards and things like this. And so, we wouldn't want to enter a mode where, there's this theoretical feature that exists in the language, but people don't use it in practice. Now, I'll also say one of the other really cool things about this implementation approach is that it can run on GPUs and it can run on accelerators and things like this. And that standard zero cost exception thing would never work on an accelerator. And so this is also part of how Mojo can scale all the way down to like little embedded systems and to running on GPUs and things like that.
Can you actually say about is there some high level way to describe the challenge of exceptions and how they work in code during compilation? So just this idea of percolating up a thing, an error.
Yeah. So the way to think about it is think about a function that doesn't return anything, just as a simple case, right? And so you have function 1 calls function 2, calls function 3, calls function 4. Along that call stack, there are try blocks, right? And so if you have function 1 calls function 2 has a try block, and then within it, it calls function 3, right? Well, what happens if function 3 throws? Well, actually, start simpler. What happens if it returns? Well, if it returns, it's supposed to go back out and continue executing and then fall off the bottom of the try block and keep going, and all's good. If the function throws, you're supposed to exit the current function and then get into the except clause, right? And then do whatever code's there and then keep following on and going on. And so the way that a compiler like Mojo works is that the call to that function, which happens in the except block, calls the function, and then instead of returning nothing, it actually returns, a variant between nothing and an error. And so if you return normally, fall off the bottom or do a return, you return nothing. And if you throw an error, you return the variant that is I'm an error, right? So when you get to the call, you say, okay, cool, I call the function. Hey, I know locally I'm in a try block, right? And so I call the function and then I check to see what it returns. Aha, if it's that error thing, jump to the except block.
And that's all done for you behind the scenes.
Exactly. And so the compiler does all this for you. And I mean, one of the things, if you dig into how this stuff works in Python, it gets a little bit more complicated because you have finally blocks, which now you need to go into, do some stuff, and then those can also throw and return.
Wait, what? Nested?
Yeah, and like this stuff matters for compatibility. Like there's
nest them?
There's with clauses, and so with clauses are kind of like finally blocks with some special stuff going on, and so there's
Nesting in general, nesting of anything, nesting of functions should be illegal.
Well,
it just feels like it adds a level of complexity.
I'm merely an implementer, and so this is again
You don't ask
one of the trade-offs you get when you decide to build a superset is you get to implement a full fidelity implementation of the thing that you decided is good, and so yeah, I mean we can complain about the reality of the world, shake our fists, but
It always feels like you shouldn't be allowed to do that, like to declare functions inside functions.
oh wait, what happened to Lex, the Lisp guy?
No, I understand that, but Lisp is what I used to do in college.
So now you've grown up.
You know, we've all done things in college we're not proud of. No, I love Lisp. I love Lisp.
Okay, wait, yeah, I was gonna say you're afraid of me irritating the whole internet. Like,
no, I love Lisp. It worked. It worked as a joke in my head. And
right. So nested functions are, joking aside, actually really great and for certain things, right? And so these are also called closures. Closures are pretty cool, and you can pass callbacks. There's a lot of good patterns, and so.
So speaking of which, I don't think you have nested functions implemented yet in Mojo.
We don't have Lambda syntax, but we do have
Lambda syntax.
nested functions. Yeah.
So there's a few things on the roadmap that you have that it would be cool to sort of just fly through, because it's interesting to see, you know, how many features there are in a language, small and big.
Yep.
You have to implement.
Yeah.
So first of all, there's tuple support, and that has to do with some very specific aspects of it, like the parentheses or not parentheses. That.
Yeah, this is just totally a syntactic thing.
A syntactic thing. Okay, but it's cool still. So keyword arguments and functions.
Yeah, so this is where in Python you can say call a function x equals 4.
Yeah.
And x is the name of the argument.
That's a nice sort of self-documenting feature.
Yeah, I mean, and again, this isn't rocket science to implement. It's just the laundry.
It's just on the list.
The bigger features are things like traits.
Mm-hmm.
So traits are when you want to define abstract. So when you get into typed languages, you need the ability to write generics. And so you want to say, I want to write this function, and now I want to work on all things that are arithmetic-like. Well, what does arithmetic-like mean? Well, arithmetic-like is a categorization of a bunch of types. And so, you can define them in many different ways, and I'm not going to go into ring theory or something. But you can say it's arithmetic-like if you can add, subtract, multiply, divide it, for example, right? And so what you're saying there's a set of traits that apply to a broad variety of types. And so there are all these types of arithmetic-like, all these tensors and floating point and integer, and like there's this category of types. And then I can define on an orthogonal axis algorithms that then work against types that have those properties. And so this is it's a widely known thing. It's been implemented in Swift and Rust and many languages. So it's not Haskell, which is where everybody learns their tricks from. But we need to implement that, and that'll enable a new level of expressivity.
So classes.
Yeah, classes are a big deal.
It's a big deal still to be implemented. Like you said, Lambda syntax. And there's like detailed stuff like whole module import, support for top level code at file scope. So, and then global variables also. So being able to have variables outside of a top level.
Well, and so this comes back to where Mojo came from and the fact that it's 0.1, right? And so Modular's building an AI stack, right? And an AI stack has a bunch of problems working with hardware and writing high performance kernels and doing this kernel fusion thing I was talking about and getting the most out of the hardware. And so we've really prioritized and built Mojo to solve Modular's problem. Right now, our North Star is build out and support all the things, and so we're making incredible progress. By the way, Mojo's only like 7 months old, so that's another interesting thing.
But I mean, part of the reason I wanted to mention some of these things is like there's a lot to do, and it's pretty cool how you just kind of. Sometimes you take for granted how much there is in a programming language, how many cool features you kind of rely on, and this is kind of a nice reminder when you lay it as a to-do list.
Yeah, and so I mean, but also you look into it's amazing how much is also there, and you take it for granted that a value, if you define it, it will get destroyed automatically. Like that little feature itself is actually really complicated, given the way the ownership system has to work, and the way that works within Mojo is a huge step forward from what Rust and Swift have done.
But can you say that again? When a value, when you define it, gets destroyed automatically.
Yeah, so like say you have a string, right? So you just find a string on the stack, okay, or whatever that means, like in your local function, right? And so you say, like whether it be in a def, and so you just say x equals hello world, right? Well, if your string type requires you to allocate memory, then when it's destroyed, you have to deallocate it. So in Python and Mojo, you define that with the del method, right? Where does that get run? Well, it gets run sometime between the last use of the value and the end of the program. Like in this, you now get into garbage collection, you get into like all these long debated, you talk about religions and trade-offs and things like this. This is a hugely hotly contested world. If you look at C++, the way this works is that if you define a variable or a set of variables within a function, they get destroyed in a last in, first out order. So it's like nesting, okay? This has a huge problem because if you have a big scope and you define a whole bunch of values at the top, and then you use them, and then you do a whole bunch of code that doesn't use them, they don't get destroyed until the very end of that scope, right? And so this also destroys tail calls. So good functional programming, right? This has a bunch of different impacts on, you talk about reference counting optimizations and things like this, a bunch of very low-level things. And so what Mojo does is it has a different approach on that from any language I'm familiar with, where it destroys them as soon as possible. And by doing that, you get better memory use, you get better predictability, you get tail calls that work, you get a bunch of other things, you get better ownership tracking. There's a bunch of these very simple things that are very fundamental, that are already built in there in Mojo today, that are the things that nobody talks about generally, but when they don't work right, you find out and you complain about.
Is it trivial to know what's as soon as possible to delete a thing that's not going to be used again?
Yeah, well, I mean, it's generally trivial. It's after the last use of it. So if you define X as a string, and then you have some use of X somewhere in your code.
Within that scope, you mean? Within the scope that's accessible?
Yeah, exactly. So you can only use something within its scope. Yeah. And so then it doesn't wait until the end of the scope to delete it. It destroys it after the last use.
So there's kind of some very ego machine that's just sitting there and deleting.
Yeah, and it's all in the compiler, so it's not at runtime, which is also cool. And so, and this is actually non-trivial because you have control flow.
Yeah, right.
And so it gets complicated pretty quickly, and so like getting this right was not.
Also, you have to insert delete like in a lot of places.
Potentially, yeah, exactly. So the compiler has to reason about this, and this is where, again, it's experience building languages and not getting this right. So again, you get another chance to do it, and you get basic things like this right. But it's extremely powerful when you do that, right? And so there's a bunch of things like that that kind of combine together, and this comes back to you get a chance to do it the right way, and make sure that every brick you put down is really good, so that when you put more bricks on top of it, they stack up to something that's beautiful.
But there's also, like, how many design discussions do there have to be about particular details, like implementation of particular small features? Because the features that seem small, I bet some of them might be like really require really big design decisions.
Yeah. Well, so I mean, let me give you another example of this. Python has a feature called async await. So it's a new feature. I mean, in the long arc of Python history, it's a relatively new feature, right? That allows way more expressive asynchronous programming. Okay. Again, this is Python's a beautiful thing, and they did things that are great for Mojo for completely different reasons. The reason the async await got added to Python, as far as I know, is because Python doesn't support threads. Okay, and so Python doesn't support threads, but you want to work with networking and other things like that that can block. I mean, Python does support threads; it's just not its strength. And so they added this feature called async await. It's also seen in other languages like Swift and JavaScript and many other places as well. Async await in Mojo is amazing. We have a high-performance heterogeneous compute runtime underneath the covers that then allows non-blocking I/O, so you get full use of your accelerator. That's huge, turns out. It's actually really an important part of fully utilizing the machine. You talk about design discussions. That took a lot of discussions, right? And it probably will require more iteration. And so my philosophy with Mojo is that we have a small team of really good people that are pushing forward, and they're very good at the extremely deep, knowing how the compiler and runtime and like all the low-level stuff works together. But they're not perfect. Same thing as the Swift team, right? And this is where one of the reasons we released Mojo much earlier is so we can get feedback. And we've already like renamed a keyword due to community feedback. And we use an ampersand, and now it's named now. We're not renaming existing Python keywords because that breaks compatibility, right? We're renaming things we're adding and making sure that they are designed well. We get usage experience, we iterate and work with the community, because again, if you scale something really fast and everybody writes all their code and they start using it in production, then it's impossible to change. And so you want to learn from people, you want to iterate and work on that early on. And this is where design discussions is actually quite important.
Could you incorporate an emoji like into the main language?
Do
Do
you have a favorite one?
Well, I really like in terms of humor, I like Rawful, whatever, rolling on the floor laughing. So that could be like a. What would that be? The use case for that, like an exception, throw an exception of some sort. I don't know.
You should totally file a feature request.
Or maybe a heart one. It has to be a heart one.
People have told me that I'm insane, so this is I'm liking this.
I'm gonna use the viral nature of the internet to actually get this passed.
I mean, it's funny you come back to the flame emoji file extension, right? We have the option to use the flame emoji, which just even that concept cause, for example, the people at GitHub say, "Now I've seen everything." Like,
yeah, there's something. It's reinvigorating. It's like, oh, that's possible. That's really cool. For some reason that makes everything else really exciting.
The world is ready for this stuff, right? And so when we have a package manager, we'll clearly have to innovate by having the compiled package thing be the little box with the bow on it, right? I mean, it has to be done.
It has to be done. Is there some stuff on the roadmap that you're particularly stressed about or excited about that you're thinking about a lot?
I mean, as of today's snapshot, which will be obsolete tomorrow, the lifetime stuff is really exciting. And so lifetimes give you safe references to memory without dangling pointers. And so this has been done in languages like Rust before. And so we have a new approach, which is really cool. I'm very excited about that. That'll be out to the community very soon. The traits feature is really a big deal, and so that's blocking a lot of API design, and so there's that. I think that's really exciting. A lot of it is these kind of table stakes features. One of the things that is, again, also lessons learned with Swift is that programmers in general like to add syntactic sugar, and so it's like, oh, well, this annoying thing, like in Python, you have to spell unbar add. Why can't I just use plus? Def plus, come on. Why can't I just do that, right? And so, trivial bit of syntactic sugar, it makes sense, it's beautiful, it's obvious. We're trying not to do that. And so, for two different reasons, one of which is that, again, lesson learned with Swift. Swift has a lot of syntactic sugar, which may be a good thing, maybe not, I don't know. But because it's such an easy and addictive thing to do, sugar, like, makes your blood get crazy, right? Like, the community will really dig into that and want to do a lot of that, and I think it's very distracting from building the core abstractions. Second is, we want to be a good member of the Python community, right? And so we want to work with the broader Python community, and yeah, we're pushing forward a bunch of systems programming features, and we need to build them out to understand them. But once we get a long ways forward, I want to make sure that we go back to the Python community and say, okay, let's do some design reviews. Let's actually talk about this stuff. Let's figure out how we want this stuff all to work together. And syntactic sugar just makes all that more complicated. So
And list comprehension is yet to be implemented.
Yeah.
And my favorite, dictionaries.
Yeah, there's some
Can't wait for
basic stuff.
dictionaries.
0.1.
0.1.
Yeah, but nonetheless, it's actually still quite interesting and useful.
As you mentioned, modular is very new. Mojo is very new. It's a relatively small team.
Yeah.
That's building up this
We're just
gigantic stack.
Yeah.
This incredible stack that's going to perhaps define the future of development of our AI overlords.
we just hope it will be useful.
As do all of us. So what have you learned from this process of building up a team? Maybe one question is, how do you hire
Yeah.
great programmers, great people that operate in this compiler, hardware, machine learning, software, interface design space?
Yeah.
And maybe are a little bit fluid in
Yeah.
what they can do.
So
Language design too.
So building a company is just as interesting in different ways as building a language. Like different skill sets, different things, but super interesting. And I've built a lot of teams in a lot of different places. If you zoom in from the big problem into recruiting, well, so here's our problem. Okay, I'll be very straightforward about this. We started Modular with a lot of conviction about we understand the problems, we understand the customer pain points. We need to work backwards from the suffering in the industry, and if we solve those problems, we think it'll be useful for people. But the problem is that the people we need to hire, as you say, are all these super specialized people that have jobs at big tech worlds, right? And I don't think we have product market fit in the way that a normal startup does, or we don't have product market fit challenges. Because right now everybody's using AI and so many of them are suffering and they want help. And so again, we started with strong conviction. Now, again, you have to hire and recruit the best, and the best all have jobs. And so what we've done is we said, okay, well, let's build an amazing culture. Start with that. That's usually not something a company starts with. Usually you hire a bunch of people and then people start fighting and it turns into a gigantic mess. And then you try to figure out how to improve your culture later. My co-founder, Tim, in particular, is super passionate about making sure that that's right. And we've spent a lot of time early on to make sure that we can scale.
Can you comment, sorry, before we get to the second,
Yeah.
What makes for a good culture?
There's many different cultures, and I've learned many things from many
You worked
different
with
people.
several very unique, almost famously unique cultures.
And some of them I learned what to do, and some of them I learned what not to do. Okay, and so we want an inclusive culture. I believe in amazing people working together, and so I've seen cultures where you have amazing people and they're fighting each other. I see amazing people and they're told what to do, like thou shalt line up and do what I say. It doesn't matter if it's the right thing, do it, right? And neither of these is and I've seen people that have no direction. They're just kind of floating in different places, and they want to be amazing. They just don't know how. And so a lot of it starts with have a clear vision. Right? And so we have a clear vision of what we're doing. And so I kind of grew up at Apple in my engineering life, right? And so a lot of the Apple DNA rubbed off on me. My co-founder, Tim, also is a strong product guy. And so what we learned is, I was taught at Apple that you don't work from building cool technology. You don't work from come up with a cool product and think about the features you'll have in the big check boxes and stuff like this. Because if you go talk to customers, they don't actually care about your product. They don't care about your technology. What they care about is their problems, right? And if your product can help solve their problems, well, hey, they might be interested in that, right? And so if you speak to them about their problems, if you understand and you have compassion, you understand what people are working with, then you can work backwards to building an amazing product.
So the vision starts by defining the problem.
And then you can work backwards in solving technology.
Got it.
And at Apple, it's, I think, pretty famously said that, for every, there's 100 no's for every yes. I would refine that to say that there's 100 not yets for every yes.
Yes.
But famously, if you go back to the iPhone, for example, right, the iPhone 1, many people laughed at it because it didn't have 3G, it didn't have copy and paste. Right. And then a year later, okay, finally it has 3G, but it still doesn't have copy and paste. It's a joke. Nobody will ever use this product, blah, 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 blah. Right. Well, year 3, it had copy and paste, and people stopped talking about it. Right. And so being laser focused and having conviction and understanding what the core problems are and giving the team the space to be able to build the right tech is really important. Also, I mean, you come back to recruiting, you have to pay well, right? So we have to pay industry leading salaries and have good benefits and things like this. That's a big piece. We're a remote first company, and so we have to. So remote first has a very strong set of pros and cons. On the one hand, you can hire people from wherever they are, and you can attract amazing talent even if they live in strange places or unusual places. On the other hand, you have time zones. On the other hand, you have like everybody on the internet will fight if they don't understand each other, and so we've had to learn how to like have a system where we actually fly people in, and we get the whole company together periodically, and then we get work groups together, and we plan and execute together. And
Is there
that's-
like an intimacy to the in-person brainstorming?
Yeah.
that I guess you lose, but maybe you don't. Maybe if you get to know each other well and you trust each other, maybe you can do that.
Yeah. Well, so when the pandemic first hit, I mean, I'm curious about your experience too. The first thing I missed was having whiteboards.
Yeah.
Right. Those design discussions where like I can high intensity work through things, get things done, work through the problem of the day, understand where you're on, figure out and solve the problem, move forward.
Yeah.
But we figured out ways to work around that now with all these screen sharing and other things like that we do. The thing I miss now is sitting down at a lunch table with the team.
Yeah.
The spontaneous things like those the coffee bar things and the bumping into each other and getting to know people outside of the transactional solve a problem over Zoom thing.
And I think there's just a lot of stuff that I'm not an expert at this. I don't know who is. Hopefully there's some people. But there's stuff that somehow is missing on Zoom. Even with the whiteboard, if you look at that, if you have a room with one person at the whiteboard and there's like 3 other people at a table, there's first of all, there's a social aspect to that where you're just shooting the shit a little bit, almost like
As people are just kind of coming in and
that, but also while like it's a breakout discussion that happens for like seconds at a time, maybe an inside joke. It's like this interesting dynamic that happens. That Zoom,
you're bonding.
You're bonding, but through that bonding, you get the excitement. There's certain ideas that are like complete bullshit, and you'll see that in the faces of others that you won't see necessarily on Zoom. Like something, it feels like that should be possible to do without being in person.
Well, I mean, being in person is a very different thing. It's worth it, but you can't always do it. And so, again, we're still learning, and we're all still learning as like humanity with this new reality, right? But what we found is that getting people together, whether it be a team or the whole company or whatever, is worth the expense because people work together and are happier after that. Like it just like there's a massive period of time where you like go out and things start getting frayed, put people together, and then you realize that we're all working together. We see things the same way. We work through the disagreement or the misunderstanding. We're talking across each other, and then you work much better together. And so things like that, I think, are really quite important.
What about people that are kind of specialized in very different aspects of the stack working together? What are some interesting challenges there?
Yeah, well, so I mean, there's lots of interesting people, as you can tell. I'm, hard to deal with too. But
you're one of the most lovable people.
So there's different philosophies in building teams. For me, and so some people say hire 10x programmers, and that's the only thing, whatever that means, right? What I believe in is building well-balanced teams that have people that are different in them. Like if you have all generals and no troops, or all troops and no generals, or you have all people that think in one way and not the other way, what you get is you get a very biased and skewed and weird situation where people end up being unhappy. And so what I like to do is I like to build teams of people where they're not all the same. We do have teams and they're focused on like runtime or compiler, GPU or accelerator or whatever the speciality is, but people bring a different take and have a different perspective. And I look for people that complement each other. And particularly if you look at leadership teams and things like this, you don't want everybody thinking the same way. You want people bringing different perspectives and experiences. And so I think that's really important.
That's team, but what about building a company as ambitious as Modular? So what are some interesting questions there?
Oh, I mean, so many. One of the things I love about, so Modular is the first company I built from scratch. One of the first things that was profound was I'm not cleaning up somebody else's mess. right? And so if you look at
And that's
so
liberating to some degree.
it's super liberating, and also many of the projects I've built in the past have not been core to the product of the company. Swift is not Apple's product, right? MLIR is not Google's revenue machine or whatever. Right? It's not. It's important, but it's like working on the accounting software for the retail giant or something, right? It's like enabling infrastructure and technology. And so modular, the tech we're building is here to solve people's problems. Like it is directly the thing we're giving to people. And so this is a really big difference in what it means for me as a leader, but also for many of our engineers is they're working on the thing that matters. And that's actually pretty, I mean, again, for compiler people and things like that, that's usually not the case, right? And so that's also pretty exciting and quite nice. But the one of the ways that this manifests is it makes it easier to make decisions. And so one of the challenges I've had in other worlds is it's like, okay, well, community matters somehow for the goodness of the world, like, or open source matters theoretically, but I don't want to pay for a t-shirt, right? Or some swag. Like, well, t-shirts cost $10 each. You can have 100 t-shirts for $1,000. To a megacorp, $1,000 is uncountably, can't count that low,
Yes.
right? But justifying it and getting a t-shirt, by the way, if you'd like a t-shirt.
Well, I would 100% like a t-shirt. Are you joking?
A fire emoji t-shirt.
I will treasure this.
Is that a good
I
thing?
will pass it down to my grandchildren.
And so, it's very liberating to be able to decide, I think that Lex should have a t-shirt. Right? And it becomes very simple. I like Lex.
This is awesome. So I have to ask you about one of the interesting developments with large language models is that they're able to generate code recently really well.
Yes.
To a degree that maybe I don't know if you understand, but I struggle to understand because it forces me to ask questions about the nature of programming, of the nature of thought, because the language models are able to predict the kind of code I was about to write so well.
Yep.
That it makes me wonder, like, how unique my brain is and where the valuable ideas actually come from. Like, how much do I contribute in terms of ingenuity, innovation to code I write, or design and that kind of stuff. When you stand on the shoulders of giants, are you really doing anything? And what LLMs are helping you do is they help you stand on the shoulders of giants in your program. There's mistakes. They're interesting that you learn from, but it would love to get your opinion first, high level, of what you think about this impact of large language models when they do program synthesis, when they generate code.
Yeah. Well, so I don't know where it all goes.
Yeah.
I'm an optimist, and I'm a human optimist. Right? I think that things I've seen are that a lot of the LLMs are really good at crushing leak code projects, and they can reverse the linked list like crazy. Well, it turns out there's a lot of instances of that on the internet, and it's a pretty stock thing. And so if you want to see standard questions answered, LLMs can memorize all the answers, and that can be amazing. And also they do generalize out from that, and so there's good work on that. But I think that in my experience, building something like you talk about Mojo, or you talk about these things, or you talk about building an applied solution to a problem, it's also about working with people. It's about understanding the problem. What is the product that you want to build? What are the use cases? What are the customers? You can't just go survey all the customers because they'll tell you that they want a faster horse. Maybe they need a car, right? And so a lot of it comes into, I don't feel like we have to compete with LLMs. I think they'll help automate a ton of the mechanical stuff out of the way. And just like, I think we all try to scale through delegation and things like this, delegating rote things to an LLM, I think is an extremely valuable and approach that will help us all scale and be more productive.
But I think it's a fascinating companion.
But I'd say I don't think that means that we're going to be done with coding.
Sure. But there's power in it as a companion. And
absolutely.
So from there, I would love to zoom in onto Mojo a little bit. Do you think about that? Do you think about LLMs generating Mojo code and helping sort of, like, When you design a new programming language, it almost seems like, man, it would be nice to sort of almost as a way to learn how I'm supposed to use this thing for them to be trained on some of the Mojo code.
So I do lead an AI company, so maybe there will be a Mojo LLM at some point. But if your question is like, how do we make a language to be suitable for LLMs?
Yeah.
I think that the cool thing about LLMs is you don't have to, right? And so if you look at what is English or any of these other terrible languages that we as humans deal with on a continuous basis, they're never designed for machines, and yet they're the intermediate representation. They're the exchange format that we humans use to get stuff done, right? And so these programming languages, they're an intermediate representation between the human and the computer, or the human and the compiler, roughly, right? And so I think the LLMs will have no problem learning whatever keyword we pick.
Maybe the fire emoji is gonna.
Oh, maybe that's going to break it. It doesn't tokenize.
No, the reverse of that, it will actually enable it, because one of the issues I could see with being a superset of Python is there would be confusion about the gray area, so it would be mixing stuff. But
Well, I'm a human optimist. I'm also an LLM optimist. I think that we'll solve that problem.
we'll solve the GPT.
But you look at that and you say, okay, well, reducing the rote thing, right? Turns out compilers are very particular, and they really want things. They really want the indentation to be right. They really want the colon to be there on your else, or else it'll complain, right? I mean, compilers can do better at this, but LLMs can totally help solve that problem. So I'm very happy about the new predictive coding and Copilot type features and things like this, because I think it'll all just make us more productive.
It's still messy and fuzzy and uncertain, unpredictable. So, but is there a future you see, given how big of a leap GPT-4 was, where you start to see something like LLMs inside a compiler? Or no?
I mean, you could do that. Yeah, absolutely. I mean, I think that'd be interesting.
Is that wise?
Well, I mean, it would be very expensive. So compilers run fast and they're very efficient, and LLMs are currently very expensive. There's on-device LLMs and there's other things going on, and so maybe there's an answer there. I think that one of the things that I haven't seen enough of is that, so LLMs to me are amazing when you tap into the creative potential of the hallucinations, right? And so if you're doing creative brainstorming or creative writing or things like that, the hallucinations work in your favor. If you're writing code that has to be correct because you're going to ship it in production, then maybe that's not actually a feature. And so I think that there has been research and there has been work on building algebraic reasoning systems and kind of like figuring out more things that feel like proofs. And so I think that there could be interesting work in terms of building more reliable at scale systems, and that could be interesting. But if you chase that rabbit hole down, the question then becomes, how do you express your intent to the machine? And so maybe you want an LLM to provide the spec, but you have a different kind of net that then actually implements the code.
Right, so it's to use the documentation and inspiration versus the actual implementation.
Yeah, potentially.
Since a successful modular will be the thing that runs, I say so jokingly, our AI overlords, but AI systems that are used across, I know it's a cliche term, but Internet of Things, so across.
So I'll joke and say, like, AGI should be written in Mojo.
Yeah, AGI should be written in Mojo. You're joking, but it's also possible that it's not a joke. That a lot of the ideas behind Mojo is, seems like the natural set of ideas that would enable at scale training and inference of AI systems. So I just have to ask you about the big philosophical question about human civilization. So folks like Eliezer Yudkowsky are really concerned about the threat of AI.
Yeah.
Do you think about the good and the bad that can happen at scale deployment of AI systems?
Well, so I've thought a lot about it, and there's a lot of different parts to this problem, everything from job displacement to Skynet, things like this. And so you could zoom into subparts of this problem. I'm not super optimistic about AGI being solved next year. I don't think that's going to happen personally.
So you have a kind of Zen-like calm about, because there's a nervousness because the leap of GPT-4 seemed so big.
Sure. It's
like
huge.
we're there's some kind of transitionary period. You're thinking,
Well,
or everything-
I mean, there's a couple of things going on there. One is, I'm sure GPT-5 and 7 and 19 will be also huge leaps. They're also getting much more expensive to run. And so there may be a limiting function in terms of just expense on the one hand and train. Like that could be a limiter that slows things down. But I think the bigger limiter is outside of like Skynet takes over, and I don't spend any time thinking about that because if Skynet takes over and kills us all, then I'll be dead. So I don't worry about that. So, I mean, that's just, okay. I have other things to worry about. I'll just focus on, I'll focus and not worry about that one. But I think that the other thing I'd say is that AI moves quickly, but humans move slowly and we adapt slowly. And so what I expect to happen is just like any technology diffusion, like the promise and then the application takes time to roll out. And so I think that I'm not even too worried about autonomous cars defining away all the taxi drivers. Remember, autonomy was supposed to be solved by 2020.
Boy, do I remember.
So like I think that on the one hand we can see amazing progress, but on the other hand we can see that the reality is a little bit more complicated, and it may take longer to roll out than you might expect.
Well, that's in the physical space. I do think in the digital space is the stuff that's built on top of LLMs that runs, the millions of apps that could be built on top of them, and that could be run on millions of devices, millions of types of devices.
Yeah.
I just think that the rapid effect it has on human civilization could be truly transformative to it.
And there I think it depends on, are you an optimist or a pessimist or a masochist?
Just to clarify, optimist about human civilization.
Me too. And so I look at that as saying, okay, cool, what will AI do? Right. And so some people say, oh my God, it's going to destroy us all. How do we prevent that? I kind of look at it from is it going to unlock us all? Right. You talk about coding. Is it going to make so I don't have to do all the repetitive stuff? Well, suddenly that's a very optimistic way to look at it. And you look at what a lot of these technologies have done to improve our lives. And I want that to go faster.
What do you think the future of programming looks like in the next 10, 20, 30, 50 years?
Yeah.
With LLMs and with Mojo, with modular, like the vision for devices, the hardware to the compilers to the different stacks of software.
Yeah. Well, so what I want, I mean, coming back to my arch nemesis, right? It's complexity, right? So again, me being the optimist, if we drive down complexity, we can make these tools, these technologies, these cool hardware widgets accessible to way more people, right? And so what I'd love to see is more personalized experiences, more things, the research getting into production instead of being lost at NeurIPS, right? And like these things that impact people's lives by entering products. And so one of the things that I'm a little bit concerned about is right now, the big companies are investing huge amounts of money and are driving the top line of AI capability forward really quickly. But if it means that you have to have $100 million to train a model or more, $100 billion, right? Well, that's going to make it very concentrated with very few people in the world that can actually do this stuff. I would much rather see lots of people across the industry be able to participate and use this. Right? And you look at this, I mean, a lot of great research has been done in the health world, and looking at like detecting pathologies and doing radiology with AI and like doing all these things. Well, the problem today is that to deploy and build these systems, you have to be an expert in radiology and an expert in AI. And if we can break down the barriers so that more people can use AI techniques, and it's more like programming Python, which roughly everybody can do if they want to, right? Then I think that we'll get a lot more practical application of these techniques and a lot more nichier, cool but narrower domains. And I think that's going to be really cool.
Do you think we'll have more or less programmers in the world than now?
Well, so I think we'll have more programmers, but they may not consider themselves to be programmers.
Maybe a different name for it.
Right? I mean, do you consider somebody that uses, I think that arguably the most popular programming language is Excel.
Yeah.
Right?
Yep.
And so do they consider themselves to be programmers? Maybe not. I mean, some of them make crazy macros and stuff like that. But what you mentioned Steve Jobs, it's the bicycle for the mind. that allows you to go faster, right? And so I think that as we look forward, right, what is AI? I look at it as hopefully a new programming paradigm. It's like object-oriented programming, right? If you want to write a cat detector, you don't use for loops. It turns out that's not the right tool for the job, right? And so right now, unfortunately, I mean, it's not unfortunate, but it's just kind of where things are. AI is this weird, different thing that's not integrated into programming languages and normal tool chains, and all the technology is really weird and doesn't work right, and you have to babysit it, and every time you switch somewhere it's different. It shouldn't be that way. When you change that, when you fix that, suddenly, again, the tools, technologies can be way easier to use. You can start using them for many more things. And so that's why I would be excited about it.
What kind of advice could you give to somebody in high school right now, or maybe early college, who's curious about programming and feeling like the world is changing really quickly here?
Yeah, well,
What kind of stuff to learn? What kind of stuff to work on? Should they finish college? Should they go work at a company? Should they build a thing? What do you think?
well, so I mean, one of the things I'd say is that you'll be most successful if you work on something you're excited by. And so don't get the book and read the book cover to cover and study and memorize and recite and flashcard, and go build something. Like, go solve a problem. Go build the thing that you wanted to exist. Go build an app. Go train a model. Like, go build something and actually use it, and set a goal for yourself. And if you do that, then there's the success, there's the adrenaline rush, there's the achievement, there's the unlock that I think is where, if you keep setting goals and you keep doing things and building things, learning by building is really powerful. In terms of career advice, I mean, everybody's different. It's very hard to get generalized advice. I'll speak as, a compiler nerd. If everybody's going left, sometimes it's pretty cool to go right.
Yeah.
And so just because everybody's doing a thing, it doesn't mean you have to do the same thing and follow the herd. In fact, I think that sometimes the most exciting paths through life lead to being curious about things that nobody else actually focuses on, right? And it turns out that understanding deeply parts of the problem that people want to take for granted makes you extremely valuable and specialized in ways that the herd is not. And so, again, I mean, there's lots of rooms for specialization, lots of rooms for generalists. There's lots of room for different kinds and parts of the problem. But I think that it's, just because everybody's doing one thing doesn't mean you should necessarily do it.
And now the herd is using Python, so if you want to be a rebel, go check out Mojo and help Chris and the rest of the world fight the arch nemesis of complexity, because simple is beautiful.
There you go.
Chris, you're an incredible person. You've been so kind to me ever since we met. You've been extremely supportive. I'm forever grateful for that. Thank you for being who you are, for being legit, for being kind, for fighting this really interesting problem of how to make AI accessible to a huge number of people, huge number of devices.
Yeah, well, so Lex, you're a pretty special person too. And so I think that, one of the funny things about you is that besides being curious and pretty damn smart, you're actually willing to push on things. And I think that you've got an agenda to make the world think, which I think is a pretty good agenda.
It's a pretty good one. Thank you so much for talking today, Chris.
Yeah, thanks, Lex.
Thanks for listening to this conversation with Chris Latner. To support this podcast, please check out our sponsors in the description. And now, let me leave you with some words from Isaac Asimov. I do not fear computers. I fear the lack of them. Thank you for listening, and hope to see you next time.
The ribosome, who I mentioned a little while back, can make an elephant one molecule at a time. Ribosomes are slow. They run at about 1 molecule a second, but ribosomes make ribosomes. So you have trillions of them, and that makes an elephant. In the same way, these little assembly robots I'm describing can make giant structures at heart because the robot can make the robot. So more recently, two of my students, Amira and Miana, had a Nature Communication paper showing how this robot can be made out of the parts it's making. so the robots can make the robots, so you build up the capacity of robotic assembly.
The following is a conversation with Neil Gershenfeld, the director of MIT's Center for Bits and Atoms, an amazing laboratory that is breaking down boundaries between the digital and physical worlds, fabricating objects and machines at all scales of reality, including robots and automata that can build copies of themselves and self-assemble into complex structures. His work inspires millions across the world as part of the Maker movement to build cool stuff, to create, the very act that makes life so beautiful and fun. This is the Lex Friedman Podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Neil Gershenfeld. You have spent your life working at the boundary between bits and atoms, so the digital and the physical. What have you learned about engineering and about nature reality from working at this divide, trying to bridge this divide?
I learned why von Neumann and Turing made fundamental mistakes. I learned the secret of life.
Yeah.
I learned how to solve many of the world's most important problems, which all sound presumptuous, but all of those are things I learned at that foundry.
Okay, so Turing and von Neumann, let's start there. Some of the most impactful, important humans who have ever lived in computing. Why were they wrong?
So I worked with Andy Gleason, who is Turing's counterpart. So just for background, if anybody doesn't know, Turing is credited with the modern architecture of computing, among many other things. Andy Gleason was his US counterpart. And you might not have heard of Andy Gleason, but you might have heard of the Hilbert problems. And Andy Gleason solved the fifth one. So he was a really notable mathematician. During the war, he was Turing's counterpart. Then von Neumann is credited with the modern architecture of computing, and one of his students was Marvin Minsky. So I could ask Marvin what Donnie was thinking, and I could ask Andy what Alan was. And what came out from that, what I came to appreciate as background, I never understood the difference between computer science and physical science. But Turing's machine, that's the foundation of modern computing, has a simple physics mistake, which is the head is distinct from the tape. So in the Turing machine, there's a head that programmatically moves and reads and writes a tape. The head is distinct from the tape, which means persistence of information is separate from interaction with information. Then von Neumann wrote deeply and beautifully about many things, but not computing. He wrote a horrible memo called the first draft of a report on the EDVAC, which is how you program a very early computer. In it, he essentially roughly took Turing's architecture and built it into a machine. So the legacy of that is the computer somebody's using to watch this is spending much of its effort moving information from storage transistors to processing transistors, even though they have the same computational complexity. So in computer science, when you learn about computing, there's a ridiculous taxonomy of about 100 different models of computation, but they're all fictions. In physics, a patch of space occupies space. It stores state, it takes time to transit, and you can interact. That is the only model of computation that's physical. Everything else is a fiction. So I really came to appreciate that a few years back when I did a keynote for the annual meeting of the supercomputer industry, and then went into the halls and spent time with the supercomputer builders and came to appreciate, let's see, if you're familiar with the movie The Metropolis, people would frolic upstairs in the gardens, and down in the basement, people would move levers. And that's how computing exists today, that we pretend software is not physical. It's separate from hardware. And the whole canon of computer science is based on this fiction that bits aren't constrained by atoms, but all sorts of scaling issues in computing come from that boundary, but all sorts of opportunities come from that boundary. And so you can trace it all the way back to Turing's machine making this mistake between the head and the tape. Von Neumann, he never called it von Neumann's architecture. He wrote about it in this dreadful memo. And then he wrote beautifully about other things we'll talk about. Now, to end a long answer, Turing and von Neumann both knew this. So all of the canon of computer scientists credits them for what was never meant to be a computer architecture. Both Turing and von Neumann ended their life studying exactly how software becomes hardware. So von Neumann studied self-reproducing automata, how a machine communicates its own construction. Turing studied morphogenesis, how genes give rise to form. They ended their life studying the embodiment of computation, something that's been forgotten by the canon of computing, but developed sort of off to the sides by a really interesting lineage.
So there's no distinction between the head and the tape, between the computer and the computation. It is all computation.
Right. So I never understood the difference between computer science and physical science. And working at that boundary helped lead to things like my lab was part of doing, with a number of interesting collaborators, the first faster than classical quantum computations. We were part of a collaboration creating the minimal synthetic organism where you design life in a computer. Those both involve domains where you just can't separate hardware from software. The embodiment of computation is embodied in these really profound ways.
So the first quantum computation, synthetic life, so in the space of biology, the space of physics at the lowest level, and the space of biology at the lowest level. So let's talk about CBA, Center of Bits and Atoms. What's the origin story of this MIT, legendary MIT center that you're a part of creating?
In high school, I really wanted to go to vocational school where you learn to weld and fix cars and build houses. And I was told, no, you're smart. You have to sit in a room. And nobody could explain to me why I couldn't go to vocational school. I then worked at Bell Labs, this wonderful place before deregulation, legendary place. And I would get union grievances because I would go into the workshop and try to make something. And they would say, no, you're smart. You have to tell somebody what to do. And it wasn't until MIT, and I'll explain how CBA started, but I could create CBA, that I came to understand this is a mistake that dates back to the Renaissance. So in the Renaissance, the liberal arts emerged. And liberal doesn't mean politically liberal. This was the path to liberation, birth of humanism. And so the liberal arts were the trivium, quadrivium, roughly language, natural science. And at that moment, what emerged was this sort of dreadful concept of the illiberal arts. So anything that wasn't the liberal arts was for commercial gain and was just making stuff and wasn't valid for serious study. And so that's why we're left with learning to weld wasn't a subject for serious study. But the means of expression have changed since the Renaissance. So micro machining or embedded coding is every bit as expressive as painting a painting or writing a sonnet. So never understanding this difference between computer science and physical science, the path that led me to create CBA with colleagues was I was what's called a junior fellow at Harvard. I was visiting MIT through Marvin because I was interested in the physics of musical instruments. This will be another slight digression. In Cornell, I would study physics, and then I would cross the street and go to the music department where I played the bassoon, and I would trim reeds and play the reeds, and they'd be beautiful, but then they'd get soggy. And then I discovered in the basement of the music department at Cornell was David Gordon, who you might not have heard of, but is legendary in electronic music because he was really the first electronic musician. So Bob Moog, who invented Moog synthesizers, was a physics student at Cornell, like me, crossing the street. And eventually he was kicked out and invented electronic music. David Gordon was the first musician who created electronic music. So he's legendary for people like Phil Glass and Steve Reich. And so that got me thinking about, I would behave as a scientist in the music department, but not in the physics department, but not in the music department. Got me thinking about what's the computational capacity of a musical instrument. And through Marvin, he introduced me to Todd Mackover at the Media Lab, who was just about to start a project with Yo-Yo Ma that led to a collaboration to instrument a cello, to extract Yo-Yo's data and bring it out into computational environments.
What is the computational capacity of a musical instrument? As we'll continue on this tangent, and we shall return to CBA.
Yeah. So one part of that is to understand the computing. And if you look at like the finest time scale and length scale you need to model the physics, it's not heroic. You know, a good GPU can do teraflops today. That used to be a national class supercomputer. Now it's just a GPU. And that's about, if you take the time scales and length scales relevant for the physics, that's about the scale of the physics computing. For Yo-Yo, what was really driving it was he's completely unsentimental about the Strad. It's not that it makes some magical wiggles in the sound wave. It's performance as a controller, how he can manipulate it as an interface device.
Interface between what and what exactly?
Him and sound.
Okay.
And so what it led to was, I had started by thinking about ops per second, but Yo-Yo's question was really resolution and bandwidth. It's how fast can you measure what he does, and the bandwidth and the resolution of detecting his controls and then mapping them into sounds. And what he found was, if you instrument everything he does and connect it to almost anything, it sounds like Yo-Yo. That the magic is in the control, not in ineffable details in how the wood wiggles. And so with Yo-Yo and Todd, that led to a piece. And towards the end, I asked Yo-Yo what it would take for him to get rid of his Strad and use our stuff. And his answer was just logistics. It was, at that time, our stuff was like a rack of electronics and lots of cables and some grad students to make it work. Once the technology becomes as invisible as the Strad, then sure, absolutely, he would take it. And by the way, as a footnote on the footnote, an accident in the sensing of Yo-Yo's cello led to a $100 million a year auto safety business to control airbags in cars.
How did that work?
I had to instrument the bow without interfering with it. So I set up local electromagnetic fields where I would detect how those fields interact with the bow he's playing. But we had a problem that his hand, whenever his hand got near these sensing fields, I would start sensing his hand rather than the materials on the bow. And I didn't quite understand what was going on with that interference. So my very first grad student ever, Josh Smith, did a thesis on tomography with electric fields, how to see in 3D with electric fields. Then through Todd and at that point research scientist in my lab, Joe Paradiso, it led to a collaboration with Penn and Teller, where we did a magic trick in Las Vegas to contact Houdini. And sort of these fields are sort of like, contacting spirits. So we did a magic trick in Las Vegas, and then the crazy thing that happened after that was Phil Rittmuller came running into my lab. He worked with, this became with Honda and NEC, airbags were killing infants in rear-facing child seats. Cars need to distinguish a front-facing adult where you'd save the life versus a bag of groceries where you don't need to fire the airbag versus a rear-facing infant where you would kill it. And so the seat need to, in effect, see in 3D to understand the occupants. And so we took the Penn and Teller magic trick derived from Josh's thesis from Yo-Yo's cello to an auto show. And all the car companies said, great, when can we buy it? And so that became Elysis, and it was a $100 million a year business making sensors. There wasn't a lot of publicity because it was in the car, so the car didn't kill you. So they didn't sort of advertise, we have nice sensors so the car doesn't kill you, but it became a leading auto safety sensor.
And that started from the cello and the question of the computational capacity of musical instruments.
Right. So now to get back to MIT, I was spending a lot of outside time at IBM Research that had gods of the foundations of computing. There's just amazing people there. And I'd always expected to go to IBM to take over a lab, but at the last minute pivoted and came to MIT to take a position in the Media Lab and start what became the predecessor to CBA. Media Lab is well known for Nicholas Negroponte. What's less well known is the role of Jerry Wiesner. So Jerry was MIT's president, before that Kennedy's science advisor, grand old man of science. At the end of his life, he was frustrated by how knowledge was segregated. And so he wanted to create a department of none of the above, a department for work that didn't fit in departments. And the Media Lab, in a sense, was a cover story for him to hide a department. As MIT's president, towards the end of his tenure, if he said, I'm going to make a department for things that don't fit in departments, the departments would have screamed. But everybody was sort of paying attention to Nicholas creating the Media Lab, and Jerry kind of hid in it a department called Media Arts and Sciences. It's really the department of none of the above. And Jerry explaining that and Nicholas then confirming it is really why I pivoted and went to MIT. Because my students who help create quantum computing or synthetic life get degrees from Media Arts and Sciences, this department of none of the above. So that led to coming to MIT with Todd and Joe Paradiso and Mike Hawley. We started a consortium called Things That Think, and this was around the birth of Internet of Things and RFID. But then we started doing things like work we can discuss that became the beginnings of quantum computing and cryptography and materials and logic and microfluidics. And those needed much more significant infrastructure and were much longer research arcs. So with a bigger team of about 20 people, we wrote a proposal to the NSF to assemble one of every tool to make anything of any size, was roughly the proposal.
One of any tool to make anything of any size.
Yeah. So they're usually nanometers, micrometers, millimeters, meters are segregated, input and output is segregated. We wanted to look just very literally at how digital becomes physical and physical becomes digital. And fortunately, got NSF on a good day, and they funded this facility of one of almost every tool to make anything. And so with a group of core colleagues that included Joe Jacobson, Ike Trang, Scott Manalis, we launched CBA.
And so you're talking about nanoscale, microscale, nanostructures, microstructures, macrostructures, electron microscopes and focused ion beam probes for nanostructures, laser, micro machining, and X-ray microtomography for microstructures, multi-axis machining and 3D printing for macrostructures, just some examples. What are we talking about in terms of scale? How can we build tiny things and big things all in one place?
Yeah, so a well-equipped research lab has the sort of tools we're talking about, but they're segregated in different places. They're typically also run by technicians where you then have an account and a project and you charge. All of these tools are essentially when you don't know what you're doing, not when you do know what you're doing, in that they're when you need to work across length scales, where we don't, once projects are running in this facility, we don't charge for time, you don't make a formal proposal to schedule, and the users really run the tools, and it's for work that's kind of inchoate that needs to span these disciplines and length scales. And so work in the project today, work in CBA today ranges from developing zeptojoule electronics for the lowest power computing to micromachining diamond to take 10 million RPM bearings for molecular spectroscopy studies, up to exploring robots to build 100-meter structures in space.
Okay, can we, the three things you just mentioned, let's start with the biggest. What are some of the biggest stuff you attempted to explore how to build it?
Sure. So viewed from one direction, what we're talking about is a crazy random seeming of almost unrelated projects. But if you rotate 90 degrees, it's really just a core thought over and over again, just very literally how bits and atoms relate, how digital, and it's just going from digital to physical in many different domains. But it's really just the same idea over and over again. So to understand the biggest things, let me go back to bring in now Shannon as well as von Neumann. Yeah, so what is digital? The casual, obvious answer is digital in 1 and 0, but that's wrong. There's a much deeper answer, which is Claude Shannon at MIT wrote the best master's thesis ever. In his master's thesis, he invented our modern notion of digital logic. Where it came from was Vannevar Bush was a grand old man at MIT. He created the post-war research establishment that led to the National Science Foundation. And he made an important mistake, which we can talk about. But he also made the differential analyzer, which was the last great analog computer. So it was a room full of gears and pulleys, and the longer it ran, the worse the answer was. And Shannon worked on it as a student, and he got so annoyed in his master's thesis, he invented digital logic. But he then went on to Bell Labs, and what he did there was communication was beginning to expand. There was more demand for phone lines. And so there's a question about how many phone messages you could send down a wire. And you could try to just make it better and better. He asked a question nobody had asked, which is, rather than make it better and better, what's the limit to how good it can be? And he proved a couple things, but one of the main things he proved was a threshold theorem for channel capacity. And so what he showed was, my voice to you right now is coming as a wave through sound. And the further you get, the worse it sounds. But people watching this are getting it as packets of data in a network. When the computer they're watching this gets the packet of information, it can detect and correct an error. And what Shannon showed is, if the noise in the cable to the people watching this is above a threshold, they're doomed. But if the noise is below a threshold, for a linear increase in the energy representing our conversation, the error rate goes down exponentially. Exponentials are fast. There's very few of them in engineering. And the exponential reduction of error below a threshold, if you restore state, is called a threshold theorem. That's what led to digital. That means unreliable things can work reliably. So Shannon did that for communication. Then von Neumann was inspired by that and applied it to computation. And he showed how an unreliable computer can operate reliably by using the same threshold property of restoring state. It was then forgotten many years. We had to rediscover it, in effect, in the quantum computing era, when things are very unreliable again. But now to go back to, how does this relate to the biggest things I've made? So in fabrication, MIT invented computer-controlled manufacturing in 1952. Jet aircraft were just emerging. There was a limit to turning cranks on a milling machine to make parts for jet aircraft. Now, this is a messy story. MIT actually stole computer-controlled machining from the inventor who brought it to MIT, wanted to do a joint project with the Air Force, and MIT effectively stole it from him. So it's kind of a messy history. But that sounds like the birth of computer-controlled machining, 1952. There are a number of inventors of 3D printing. One of the companies spun off my lab by Max Lebowski's Formlabs, which is now a billion-dollar 3D printing company. That's the modern version. But all of that's analog, meaning the information is in the control computer. There's no information in the materials. And so it goes back to Vannevar Bush's analog computer. If you make a mistake in printing or machining, just the mistake accumulates. The real birth of computerized digital manufacturing is 4 billion years ago. That's the evolutionary age of the ribosome. So the way you're manufactured is, there's a code that describes you, the genetic code. It goes to a micro machine, the ribosome, which is this molecular factory that builds the molecules that are you. The key thing to know about that is there are about 20 amino acids that get assembled. And in that machinery, it does everything Shannon and von Neumann taught us. You detect and correct errors. So if you mix chemicals, the error rate is about a part in 100. When you elongate a protein in the ribosome, it's about a part in 10 to the 4. When you replicate DNA, there's an extra level of error correction. It's a part in 10 to the 8. And so in the molecules that make you can detect and correct errors, and you don't need a ruler to make you. The geometry comes from your parts. So now compare a child playing with Lego and a state-of-the-art 3D printer or computerized milling machine. The tower made by a child is more accurate than their motor control because the act of snapping the bricks together gives you a constraint on the joints. You can join bricks made out of dissimilar materials. You don't need a ruler for Lego because the geometry locally gives you the global parts. And there's no Lego trash. The parts have enough information to disassemble them. Those are exactly the properties of a digital code.
The unreliable is made reliable.
Yes, absolutely. So what the ribosome figured out 4 billion years ago is how to embody these digital properties, but not for communication or computation in effect, but for construction. So a number of projects in my lab have been studying the idea of digital materials. And think of a digital material just as Lego bricks. The precise meaning is a discrete set of parts reversibly joined with global geometry determined from local constraints. And so it's digitizing the materials. And so I'm coming back to what are the biggest things I've made. My lab was working with the aerospace industry. So Spirit Aero was Boeing's factories. They asked us for how to join composites. When you make a composite airplane, you make these giant wing and fuselage parts. And they asked us for a better way to stick them together because the joints were a place of failure. And what we discovered was instead of making a few big parts, if you make little loops of carbon fiber and you reversibly link them in joints, and you do it in a special geometry that balances being under constrained and over constrained with just the right degrees of freedom, we set the world record for the highest modulus ultralight material just by, in effect, making carbon fiber Lego. So lightweight materials are crucial for energy efficiency. This let us make that the lightest weight, high modulus material. We then showed that with just a few part types, we can tune the material properties, and then you can create really wild robots that instead of having a tool the size of a jumbo jet to make a jumbo jet, you can make little robots that walk on these cellular structures to build the structures, where they error correct their position on the structure and they navigate on the structure. And so using all of that with NASA, we made morphing airplanes. A former student, Kenny Chung and Ben Jeanette, made a morphing airplane the size of NASA Langley's biggest wind tunnel. With Toyota, we've made super efficiency race cars. We're right now looking at projects with NASA to build these for things like space telescopes and space habitats, where the ribosome, who I mentioned a little while back, can make an elephant one molecule at a time. Ribosomes are slow. They run at about 1 molecule a second, but ribosomes make ribosomes. So you have thousands of them, trillions of them, and that makes an elephant. In the same way, these little assembly robots I'm describing can make giant structures at heart because the robot can make the robot. So more recently, two of my students, Amira and Miana, had a Nature Communication paper showing how this robot can be made out of the parts it's making. So the robots can make the robots, so you build up the capacity of robotic assembly.
You can self-replicate. Can you linger on what that robot looks like? What is a robot that can walk along and do error correction? And what is a robot that can self-replicate from the materials that is given? What does that look like? What are we talking about?
So
this is fascinating.
Yeah, the answer is different at different length scales. So to explain that, in biology, primary structure is the code in the messenger RNA that says what the ribosome should build. Secondary structure are geometrical motifs, or things like helices or sheets. Tertiary structures are functional elements, like electron donors or acceptors. Quaternary structure is things like molecular motors that are moving my mouth or making the synapses work in my brain. So there's that hierarchy of primary, secondary, tertiary, quaternary. Now, what's interesting is if you want to buy electronics today from a vendor, there are hundreds of thousands of types of resistors or capacitors or transistors, huge inventory. All of biology is just made from this inventory of 20 parts, the amino acids. And by composing them, you can create all of life. And so as part of this digitization of materials, we're in effect trying to create something like amino acids for engineering, creating all of technology from 20 parts. As another discretion, I helped start an office for science in Hollywood, and there was a fun thing for the movie The Martian where I did a program with Bill Nye and a few others on how to actually build a civilization on Mars that they described in a way that I like, as I was talking about how to go to Mars without luggage. And at heart, it's sort of how to create life in non-living materials. So if you think about this primary, secondary, tertiary, quaternary structure, in my lab, we're doing that, but on different length scales for different purposes. So we're making micro robots out of like nano bricks, and to make the robots to build large scale structures in space, the elements of the robots now are centimeters rather than micrometers. And so the assembly robots for the bigger structures are, there are the cells that make up the structure, but then we have functional cells. And so cells that can process and actuate, each cell can like move 1 degree of freedom, or attach or detach, or process. Now, those elements I just described, we can make out of the still smaller parts. So eventually there's a hierarchy of the little parts make little robots, make bigger parts of bigger robots, up through that hierarchy.
And in that way, you can move up the length scale.
Right. Early on, I tried to go in a straight line from the bottom to the top, and that ended up being a bad idea. Instead, we're kind of doing all of these in parallel, and then they're growing together. And so to make the larger scale structures, we like there's a lot of hype right now about 3D printing houses, where you have a printer the size of the house. We're right now working on using swarms of these, table scale robots that walk on the structures to place the parts much more efficiently.
But you're saying you can't, for now, go from the very small to the very large.
That'll come. That'll come in stages.
Can we just linger on this idea? Starting from von Neumann's self-replicating automata that you mentioned. It's just a beautiful idea.
So that's at the heart of all of this. In the stack I described, so one student, Will Langford, made these micro robots out of little parts that then we're using for Miana's bigger robots up through this hierarchy. And it's really realizing this idea of the self-reproducing automata. So von Neumann, when I complained about the von Neumann architecture, it's not fair to von Neumann because he never claimed it as his architecture. He really wrote about it in this one fairly dreadful memo that led to all sorts of lawsuits and fights about the early days of computing. He did beautiful work on reliable computation and unreliable devices. And towards the end of his life, what he studied was how, and I have to say this precisely, how a computation communicates its own construction. So
beautiful.
So a computation can store a description of how to build itself. But now there's a really hard problem, which is how, if you have that in your mind, how do you transfer it and wake up a thing that then can contain it? So how do you give birth to a thing that knows how to make itself? And so with Stan Ulam, he invented cellular automata as a way to simulate these. But that was theoretical. My lab is fundamentally how to realize it, how to realize self-reproducing automata. And so, this is something von Neumann thought very deeply and very beautifully about theoretically. And it's right at this intersection. It's not communication or computation or fabrication. It's right at this intersection where communication and computation meets fabrication. Now, the reason self-reproducing automata intellectually is so important, because this is the foundation of life. This is really just understanding the essence of how to life. And in effect, we're trying to create life in non-living material. The reason it's so important technologically is because that's how you scale capacity. That's how you can make an elephant from a ribosome, because the assemblers make assemblers.
So simple building blocks that inside themselves contain the information of how to build more building blocks, and so between each other construct arbitrarily complex objects.
Right. Now, let me give you the numbers. So let me relate this to, right now we're living in AI mania explosion times. Let me relate that to what we're talking about. 100 petaflop computer, which is a current generation supercomputer, not quite the biggest ones, does 10 to the 17 ops per second. Your brain does 10 to the 17 ops per second. It does about 10 to the 15 synapses, and they run at about 100 hertz. So as of a year or two ago, the performance of a big computer matched the brain. So you could view AI as a breakthrough, but the real story is within about a year or two ago, and let's see, that the supercomputer has about 10 to the 15 transistors in the processors, 10 to the 15 transistors in the memory, which is the synapses in your brain. So the real breakthrough was the computers match the computational capacity of a brain, and so we'd be sort of derelict if they couldn't do about the same thing. But now the reason I'm mentioning that is the chip fab making the supercomputer is placing about 10 to the 10 transistors a second. While you're digesting your lunch right now, you're placing about 10 to the 18 parts per second. There's an 8 order of magnitude difference. So in computational capacity, it's done. We've caught up. But there's 8 orders of magnitude difference in the rate at which biology can build versus state-of-the-art manufacturing can build. And that distinction is what we're talking about. That distinction is not analog, but this deep sense of digital fabrication, embodying codes in construction. So a description doesn't describe a thing, but the description becomes the thing.
So you're saying, I mean, this is one of the cases you're making, that this is this third revolution. We've seen the Moore's law in communication. We've seen the Moore's law-like type of growth in computation, and you're anticipating we're going to see that in digital fabrication. Can you actually, first of all, describe what you mean by this term, digital fabrication?
So the casual meaning is the computer controls a tool to make something. And that was invented when MIT stole it in 1952.
Yeah.
There's the deep meaning of what the ribosome does, of a digital description doesn't describe a thing, a digital description becomes the thing. That's where that's the path to the Star Trek replicator. And that's the thing that doesn't exist yet. Now, I think the best way to understand what this roadmap looks like is to now bring in Fab Labs and how they relate to all of this.
What are Fab Labs?
So here's a sequence. With colleagues, I accidentally started a network of what's now 2,500 digital fabrication community labs called Fab Labs, right now in 125 countries. And they double every year and a half. That's called Lass's Law after Sherry Lassiter. We'll explain. So here's the sequence. We started Center for Bits and Atoms to do the kind of research we're talking about. We had all of these machines, and then had a problem. It would take a lifetime of classes to learn to use all the machines. So with colleagues who helped start CBA, we began a class modestly called How to Make Almost Anything.
Yeah.
And there's no big agenda. It was aimed at a few research students to use the machines. And it was completely unprepared for the first time we taught it. We were swamped by, every year since, hundreds of students try to take the class. It's one of the most oversubscribed classes at MIT. Students would say things like, can you teach this at MIT? It seems too useful. It's just how to work these machines. And the students in the class, I would teach them all the skills to use all these tools, and then they would do projects integrating them, and they're amazing. So Kelly was a sculptor, no engineering background. Her project was, she made a device that saves up screams when you're mad and plays them back later. And
Saves up screams when you're mad and plays them
right.
back later.
You scream into this device, and it deadens the sound, records it, and then when it's convenient, releases your scream.
Can we just like pause on the brilliance of that invention, creation, the art? I don't know, the brilliance. Who is this that created
Kelly
this?
Dobson.
Kelly Dobson.
Gone on to do a number of interesting things. Median, who's gone on to do a number of interesting things, made a dress instrumented with sensors and spines. And when somebody creepy comes close, it would defend your personal space.
They're also very
Another project early on was a web browser for parrots, which have the cognitive ability of a young child and lets parrots surf the internet. Another was an alarm clock you wrestle with and keep you awake. And what connects all of these is, so MIT made the first real-time computer, the Whirlwind. That was transistorized as the TX. The TX was spun off from MIT as the PDP. PDPs were the mini computers that created the internet. So outside MIT was DEC, Prime, Wang, David General, the whole mini computer industry. The whole computing industry was there, and it all failed when computing became personal. Ken Olsen, the head of digital, famously said, "You don't need a computer at home." There's a little background to that, but DEC completely missed computing became personal. So I mention all of that because I was asking how to do digital fabrication, but not really why. The students in this How to Make class were showing me that the killer app of digital fabrication is personal fabrication.
Yeah, how do you jump to the personal fabrication?
So Kelly didn't make the screen body because it was for a thesis. She wasn't writing a research paper. It wasn't a business model. It was because she wanted one.
Yes.
It was personal expression, going back to me in vocational school. It was personal expression in these new means of expression. So that's happened every year since.
It literally is called, the course is literally called How to Make Almost Anything.
Yeah.
A legendary course at MIT.
Yeah.
Every year.
And it's grown to multiple labs at MIT with as many people involved as teaching as taking it. And there's even a Harvard lab for the MIT class.
What have you learned about humans colliding with the Fab Lab, about what the capacity of humans to be creative and to build?
I mentioned Marvin. Another mentor at MIT, sadly no longer living, is Seymour Papert. So Papert studied with Piaget. He came to MIT to get access to the early computer. Piaget was a pioneer in how kids learn. Papert came to MIT to get access to the early computers with the goal of letting kids play with them. Piaget helped show kids are like scientists. They learn as scientists, and it gets kind of throttled out of them. Seymour wanted to let kids have a broader landscape to play. Seymour's work led with Mitch Resnick to Lego, Logo, Mindstorms, all of that stuff. As Fab Lab spread, and we started creating educational programs for kids in them, Seymour said something really interesting. He made a gesture. He said it was a thorn in his side that they invented what's called the Turtle, early robot kids could program to connect it to a mainframe computer. Seymour said the goal was not for the kids to program the robot, it was for the kids to create the robot. And so in that sense, the Fab Labs, which were just this accident, he described as sort of this fulfillment of the art of kids learn by experimenting. It was to give them the tools to create, not just assemble things and program things, but actually create. So coming to your question, what I've learned is MIT, a few years back, somebody added up businesses spun off from MIT, and it's the world's 10th economy, falls between India and Russia. And I view that in a way as a bad number because it's only a few thousand people, and these aren't uniquely the 4,000 brightest people. It's just a productive environment for them. And what we found is in rural Indian villages, in African shanty towns, and Arctic hamlets, I find precisely that profile. So Ling sighted a few hours above Tromsø, way above the Arctic circles. It's so far north the satellite dishes look at the ground, not the sky. Hans Christian in the lab was considered a problem in the local school because they couldn't teach him anything. I showed him a few projects. Next time I came back, he was designing and building little robot vehicles. And in South Africa, I mentioned Soshangovi, in this apartheid township, the local technical institute taught kids how to make bricks and fold sheets. It was punitive. But Tupiso in the Fab Lab was actually doing all the work of my MIT classes. And so over and over, we found precisely this same kind of bright, inventive creativity. And historically, the answer was, you're smart, go away. It's sort of like me in vocational school. But in this lab network, what we could then do is, in effect, bring the world to them. Now let's look at the scaling of all of this. So there's one Earth, 1,000 cities, 1 million towns, 1 billion people, 1 trillion things. there was one Whirlwind computer. MIT made the first real-time computer. There were thousands of PDPs. There were millions of hobbyist computers that came from that, billions of personal computers, trillions of Internet of Things. So now if we look at this Fab Lab story, 1952 was the NC Mill. There are now thousands of Fab Labs, and the Fab Lab costs exactly the same cost and complexity of the mini computer. So on the mini computer, it didn't fit in your pocket, it filled a room. But video games, email, word processing, really anything you do, the internet, anything you do with the computer today happened at that era because it got on the scale of a work group, not a corporation. In the same way, Fab Labs are like the mini computers inventing how does the world work if anybody can make anything. Then if you look at that scaling, labs today are transitioning from buying a machine to make machines making machines. So we're transitioning to, you can go to a Fab Lab not to make a project but to make a new machine. So we talked about the deep sense of self-replication. There's a very practical sense of Fab Lab machines making Fab Lab machines. And so that's the equivalent of the hobbyist computer era, what are called the Altair historically. Then the work we spent a while talking about assemblers and self-assemblers, that's the equivalent of smartphones and Internet of Things. That's when, so the assemblers are like the smartphone, where a smartphone today has the capacity of what used to be a supercomputer in your pocket. And then the smart thermostat on your wall has the power of the original PDP computer, not metaphorically, but literally, and now there's trillions of those. In the same sense that when we finally merge materials with the machines in the self-assembly, that's like the Internet of Things stage. But here's the important lesson. If you look at the computing analogy, computing expanded exponentially, but it really didn't fundamentally change. The core things happened in that transition in the mini computer era. So in the same sense, the research now we spent a while talking about is how we get to the replicator. Today, you can do all of that if you close your eyes and view the whole Fab Lab as a machine. In that room, you can make almost anything, but you need a lot of inputs. Bit by bit, the inputs will go down and the size of the room will go down as we go through each of these stages.
So how difficult is it to create a self-replicating assembler, self-replicating machine that builds copies of itself or builds a more complicated version of itself, which is kind of the dream towards which you're pushing in a generic, arbitrary sense?
I had a student, Nadia Peak, with Jonathan Ward, who for me started this idea of how do we use the tools in my lab to make the tools in the lab. In a very clear sense, they are making self-reproducing machines. So one of the really cool things that's happened is there's a whole network of machine builders around the world. So there's Danielle and now in Germany, and Jens in Norway, and each of these people has learned the skills to go into a Fab Lab and make a machine. And so we started creating a network of super Fab. So the Fab Lab can make a machine, but it can't make a number of the precision parts of the machine. So in places like Bhutan or Kerala in the south of India, we started creating super Fab Labs that have more advanced tools to make the parts of the machine so that the machines themselves become even cheaper. So that is self-reproducing machines, but you need to feed it things like bearings or microcontrollers. They can't make those parts. But other than that, they're making their own things. And I should note as a footnote, the stack I described of computers controlling machines to machine making machines to assemblers to self-assemblers, view that as Fab 1, 2, 3, 4. So we're transitioning from Fab 1 to Fab 2, and the research in the lab is 3 and 4. At this Fab 2 stage, a big component of this is sustainability in the material feedstocks. So Alicia, colleague in Chile, is leading a great effort looking at how you take forest products and coffee grounds and seashells and a range of locally available materials and produce the high-tech materials that go into the lab. So all of that is machine building today. Then back in the lab, what we can do today is We have robots that can build structures and can assemble more robots that build structures. We have finer resolution robots that can build micromechanical systems. So robots that can build robots that can walk and manipulate. And we're just now, we have a project at the layer below that where there's endless attention today to billion-dollar chip fab investments. But a really interesting thing we passed through is today the smallest transistors you can buy as a single transistor, just commercially for electronics, is actually the size of an early transistor in an integrated circuit. So we're using these machines, making assemblers to place those parts, to not use a billion-dollar chip fab to make integrated circuits, but actually assemble little electronic components.
To have fine enough, precise enough actuators and manipulators that allow you to place these transistors.
Right, that's a research project in our lab called DICE, on discrete assembly of integrated electronics. And we're just at the point to really start to take seriously this notion of not having a chip fab make integrated electronics, but having not a 3D printer, but a thing that's a cross between a pick and place makes circuit boards in 2D, the printer extrudes in 3D. We're making sort of a micro manipulator that acts like a printer, but it's placing, build electronics in 3D.
But this micro manipulator is distributed, so there's a bunch of them, or is this one centralized thing?
So that's why that's a great question. So I have a prize that's almost but not been claimed for the students whose thesis can walk out of the printer.
Oh, nice.
So you have to print the thesis with the means to exit the printer, and it has to contain its description of the thesis that says how to do that.
It's a really good. I mean, it's a it's a fun example of exactly the thing we're talking about.
And I've had a few students almost get to that. And so, in what I'm describing, there's this stack where we're getting closer, but it's still quite a few years to really go from a. So there's a layer below the transistors where we assemble the base materials that become the transistor. We're now just at the edge of assembling the transistors to make the circuits. We can assemble the micro parts to make the micro robots. We can assemble the bigger robots. And in the coming years, we'll be patching together all of those scales.
So do you see a vision of just endless billions of robots at the different scales, self-assembling, self-replicating and building more complicated structures?
Yes. And the but to the yes but is, let me clarify two things. One is that immediately raises King Charles' fear of gray goo, of runaway mutant self-reproducing things. The reason why there are many things I can tell you to worry about, but that's not one of them, is if you want things to autonomously self-reproduce and take over the world, that means they need to compete with nature on using the resources of nature, of water and sunlight. And in light of everything I'm describing, biology knows everything I told you. Every single thing I explained, biology already knows how to do. What I'm describing isn't new for biology, it's new for non-biological systems. So in the digital era, the economic win ended up being centralized, the big platforms. In this world of machines that can make machines, I'm asked, for example, what's the killer opportunity? Who's going to make all the money? Who to invest in? But if the machine can make the machine, it's not a great business to invest in the machine. In the same way that if you can think globally but produce locally, then the way the technology goes out into society isn't a function of central control, but is fundamentally distributed. Now, that raises an obvious kind of concern, which is, well, doesn't this mean you could make bombs and guns and all of that? The reason that's much less of a problem than you would think is making bombs and guns and all of that is a very well-met market need. Anywhere we go, there's a fine supply chain for weapons. Now, hobbyists have been making guns for ages, and guns are available just about anywhere. So you could go into the lab and make a gun. Today, it's not a very good gun, and guns are easily available. And so generally, if we run these labs in war zones, what we find is people don't go to them to make weapons, which you can already do anyway. It's an alternative to making weapons. coming back to your question, I'd say the single most important thing I've learned is the greatest natural resource of the planet is this amazing density of bright, inventive people whose brains are underused. And you could view the social engineering of this lab work is creating capacity for them. And so, in the end, the way this is going to impact society isn't going to be command and control. It's how the world uses it. And it's been really gratifying for me to see just how it does.
Yeah, but what are the different ways the evolution of the exponential scaling of digital fabrication involves? So you said, self-replicating nanobots, right? This is the gray goo fear. It's a caricature of a fear. But nevertheless, there's interesting, just like you said, that spam and all these kinds of things that came with the scaling of communication and computation. What are the different ways that malevolent actors will use this technology?
Yeah, well, first, let me start with the benevolent story, which is trash is an analog concept. There's no trash in a forest. All the parts get disassembled and reused. Trash means something doesn't have enough information to tell you how to reuse it. It's as simple as there's no trash in a Lego room. When you assemble Lego, the Lego bricks have enough information to disassemble them. So as you go through this Fab 1, 2, 3, 4 story, one of the implications of this transition from printing to assembling. So the real breakthrough technologically isn't additive versus subtractive, which is a subject of a lot of attention and hype. 3D printers are useful. We spun off companies like Formlabs, led by Max for 3D printing. But in a fab lab, it's one of maybe 10 machines. It's used, but it's only part of the machine. The real technological change is when we go from printing and cutting to assembling and disassembling. But that reduces inventories of hundreds of thousands of parts to just having a few parts to make almost anything. It reduces global supply chains to locally sourcing these building blocks. But one of the key implications is it gets rid of technological trash, because you can disassemble and reuse the parts, not throw them away. And so initially that's of interest for things at the end of long supply chains, like satellites on orbit. But one of the things coming is eliminating technical trash through reuse of the building blocks.
So like when you think about 3D printers, you're thinking about addition and subtraction. When you think about the other options available to you in that parameter space, as you call it, that's going to be assembly, disassembly, cutting, you said?
So the 1952 NC mill was subtractive. You remove materials. And 3D printing, additive, and there's a couple claims to the invention of 3D printing, that's closer to what's called net shape, which is you don't have to cut away the material you don't need, you just put material where you do need it. And so that's the 3D printing revolution. But there are all sorts of limitations on 3D printing to the kinds of materials you can print, the kind of functionality you can print. We're just not going to get to making everything in a cell phone on a single printer. But I do expect to make everything in a cell phone with an assembler. And so instead of printing and cutting, technologically, it's this transition to assembling and disassembling. Going back to Shannon and von Neumann, going back to the ribosome 4 billion years ago. Now, you come to malevolent. Let me tell you a story about, I was doing a briefing for the National Academy of Sciences group that advises the intelligence communities. And I talked about the kind of research we do. And at the very end, I showed a little video clip of Valentina in Ghana making a local girl making surface mount electronics in the Fab Lab. And I showed that to this room full of people. One of the members of the intelligence community got up livid and said, "How dare you waste our time showing us a young girl in an African village making surface mount electronics? We're looking at, we need to know about disruptive threats to the future of the United States." And somebody else got up in the room and yelled at him, "And you idiot, I can't think of anything more important than this." But for two reasons. One reason was, because if we rely on like informational superiority in the battlefield, it means other people could get access to it. But this intelligence person's point, bless him, wasn't that. It was getting at the root causes of conflict. Is if this young girl in an African village could actually master surface non-electronics, it changes some of the most fundamental things about recruitment for terrorism, impact of economic migration, basic assumptions about an economy. It's just existential for the future planet.
But we've just lived through a pandemic. I would love to linger on this because the possibilities that are positive are endless.
Yeah.
But the possibilities that are negative are still nevertheless extremely important. But both positive and negative. What do you do with a large number of general assemblers?
Yeah. With the Fab Lab, you could roughly make a biolab and then biotechnology. Now that's terrifying because making self-reproducing gray goo that outcompetes biology, I consider doomed because biology knows everything I'm describing and is really good at what it does. In how to grow almost anything, you learn skills in biotechnology that would let you make serious biological progress.
And when you combine some of the innovations you see with large language models, some of the innovations you see with AlphaFold, so applications of AI for designing biological systems, for writing programs, which can be large language models increasingly so, there seems to be an interesting dance here of automating the design stage of complex systems using AI, and then that's the bits. And you can leap now the innovations you're talking about. You can leap from the complex systems in the digital space to the printing, to the creation, to the assembly at scale of complex systems in the physical space.
Yeah. So something to be scared about is a Fab Lab can make a biolab can make biotechnology. Somebody could learn to make a virus. That's scary. That's unlike some of the things I said I don't worry about. That's something I really worry about. That is scary. Now, how do you deal with that? Prior threats we dealt with command and control. So like early color copiers had unique codes and you could tell which copier made them. Eventually you couldn't keep up with that. There was a famous meeting at Asilomar in the early days of recombinant DNA where that community recognized the dangers of what it was doing and put in place a regime to help manage it. And so that led to the kind of research management. So, MIT has an office that supervises research and it works with the national office. That works if you can identify who's doing it and where. It doesn't work in this world we're describing. So anybody could do this anywhere. And so what we found is you can't contain this. It's already out. You can't forbid because there isn't command and control. The most useful thing you can do is provide incentives for transparency. So, but really the heart of what we do is you could do this by yourself in the basement for nefarious reasons, or you could come into a place in the light where you get help and you get community and you get resources. And there's an incentive to do it in the open, not in the dark. And that might sound naive, but in the sort of places we're working, again, bad people do bad things in these places already, but providing openness and providing transparency is a key part of managing these. And so it transitions from regulating risks as regulation to soft power to manage them.
So there's so much potential for good, so much capacity for good that Fab Labs and the ability and the tools of creation really unlock that potential.
Yeah, and I don't say that as sort of dewy-eyed naive. I say that empirically from just years of seeing how this plays out in communities.
I wonder if it's the early days of personal computers, though, before we get spam, right?
in the end, most fundamentally, literally the mother of all problems is who designed us. So assume success in that we're going to transition to the machines making machines, and all of these new sort of social systems we're describing will help manage them and curate them and democratize them. If we close the gap I just let off with of 10 to the 10 to 10 to the 18 between chip fab and you, we're ultimately, in marrying communication, computation, and fabrication, going to be able to create unimaginable complexity. And how do you design that? And so I'd say the deepest of all questions that I've been working on goes back to the oldest part of our genome. So in our genome, what are called Hox genes, and these are morphogenes. And nowhere in your genome is the number 5. It doesn't store the fact that you have 5 fingers. What it stores is what's called a developmental program. It's a series of steps, and the steps have the character of like grow up a gradient or break symmetry. And at the end of that developmental program, you have 5 fingers. So you are stored not as a body plan, but as a growth plan. And there's 2 reasons for that. One reason is just compression. Billions of genes can place trillions of cells. But the much deeper one is evolution doesn't randomly perturb. Almost anything you did randomly in genome would be fatal or inconsequential, but not interesting. But when you modify things in these developmental programs, you go from like webs for swimming to fingers, or you go from walking to wings for flying. It's a space in which search is interesting. So this is the heart of the success of AI. In part, it was the scaling we talked about a while ago. And in part, it was the representations for which search is effective. AI has found good representations. It hasn't found new ways to search, but it's found good representations of search.
And you're saying that's what biology, that's what evolution has done, is created representations, structures, biological structures through research.
Correct.
Effective.
And so the developmental programs in the genome beautifully encapsulate the lessons of AI. And it's embodied, it's molecular intelligence. It's AI embodied in our genome. It's every bit as profound as the cognition in our brain, but now this is sort of thinking in molecular thinking in how you design. And so I'd say the most fundamental problem we're working on is it's kind of tautological that when you design a phone, you design the phone, you represent the design of the phone. But that actually fails when you get to the sort of complexity that we're talking about. And so there's this profound transition to come. Once I can have self-reproducing assemblers placing 10 to the 18 parts, you need to not sort of metaphorically, but create life, in that you need to learn how to evolve. But evolutionary design has a really misleading, trivial meaning. It's not as simple as you randomly mutate things. It's this much more deep embodiment of AI and morphogenesis.
Is there a way for us to continue the kind of evolutionary design that led us to this place from the early days of bacteria, single-cell organisms, to ribosomes, and the 20 amino acids?
You mean for human augmentation? Or
for life? I mean, what would you call assemblers that are self-replicating and placing parts? What is that? The dynamic, complex things built with digital fabrication. What is that? That's life.
So ultimately, absolutely, if you add up everything I'm talking about, it's building up to creating life in non-living materials. And I don't view this as copying life. I view it as deriving light. I didn't start from how does biology work and then I'm going to copy it. I start from how to solve problems, and then it leads me to, in a sense, rediscover biology. So if you go back to Valentina in Ghana making her circuit board, she still needs a chip fab very far away to make the processor on her circuit board. For her to make the processor locally, for all the reasons we described, you actually need the deep things we were just talking about. And so it really does lead you. So there's a wonderful series of books by Gingery. Book 1 is how to make a charcoal furnace. And at the end of book 7, you have a machine shop. So it's sort of how you do your own personal industrial revolution. ISRU is what NASA calls in situ resource utilization. And that's how do you go to a planet and create a civilization. ISRU has essentially assumed Gingery. You go through the Industrial Revolution and you create the inventory of 100,000 resistors. What we're finding is the minimum building blocks for a civilization is roughly 20 parts. So what's interesting about the amino acids is they're not interesting. They're hydrophobic or hydrophilic, basic or acidic. They have typical but not extremal properties, but they're good enough you can combine them to make you. So what this is leading towards is technology doesn't need enormous global supply chains. It just needs about 20 properties you can compose to create all technology as the minimum building blocks for a technological civilization.
So there's going to be 20 basic building blocks based on which the self-replicating assemblers can work.
Right, and I say that not philosophically, just empirically. Sort of that's where it's heading. And I like thinking about how you bootstrap the civilization on Mars. That problem. There's a fun video and bonus material for the movie where with a neat group of people we talk about it because it has really profound implications back here on Earth about how we live sustainably.
What does that civilization on Mars looks like that's using that ISRU, that's using these 20 building blocks and does self-assembly?
Yeah, go through primary, secondary, tertiary, quaternary. You extract properties like conducting, insulating, semiconducting, magnetic, dielectric, flexural. These are the kind of roughly 20 properties. With those are enough for us to assemble logic, and they're enough for us to assemble actuation. With logic and actuation, we can make micro robots. The micro robots can build bigger robots. The bigger robots can then take the building block materials and make the structural elements that you then do to make construction. And then you boot up through the stages of a technological civilization.
By the way, where in the span of logic and actuation did this sensing come in?
Oh, I skipped over that. But my favorite sensor is a step response. So if you just make a step and measure the response to the electric field, that ranges from user interfaces to positioning to material properties. And if you do it at higher frequencies, you get chemistry. And you can get all of that just from a step in an electric field. So for example, once you have time resolution in logic, something as simple as 2 electrodes let you do amazingly capable sensing. So we've been talking about all the work I do. There's a story about how it happens. Where do ideas come from? And
that's an interesting story. Where do ideas come from?
So I had mentioned Vannevar Bush, and he wrote a really influential thing called The Endless Frontier. So science won World War II. The more known story is nuclear bombs. The less well-known story is the Rad Lab. So at MIT, an amazing group of people invented radar, which is really credited as winning the war. So after the war, grand old man from MIT and was charged with science won the war. How do we maintain that edge? And the report he wrote led to the National Science Foundation and the modern notion we take for granted, but didn't really exist before then, of public funding of research agencies. In it, he made, again, what I consider an important mistake, which is he described basic research leads to applied research, leads to applications, leads to commercialization, leads to impact. And so we need to invest in that pipeline. The reason I consider it a mistake is almost all of the examples we've been talking about in my lab went backwards, that the basic research came from applications. And further, almost all of the examples we've been talking about came fundamentally from mistakes. So essentially everything I've ever worked on has failed, but in failing, something better happened. So the way I like to describe it is ready, aim, fire is you do your homework, you aim carefully at something, a target you want to accomplish, and if everything goes right, you then hit the target and succeed. What I do, you can think of as ready, fire, aim. So you do a lot of work to get ready, then you close your eyes and you don't really think about where you're aiming, but you look very carefully at where you did it, where you aim after you fire. And the reason that's so important is if you do ready, aim, fire, the best you can hope is hit what you aim at. So let me give you some examples. This is a source of great,
full of good lines today. Yeah.
source of great frustration. So I mentioned the early quantum computing. So quantum computing is this power of using quantum mechanics to make computers that for some problems are dramatically more powerful than classical computers. Before it started, there was a really interesting group of people who knew a lot about physics and computing that were inventing what became quantum computing before it was clear there was an opportunity there. It was just studying how those relate. Here's how it fits to the ready, fire, aim. I was doing really short-term work in my lab on shoplifting tags. This was really before there was modern RFID, and so how you put tags in objects to sense them, something we just take for granted commercially. And there was a problem of how you can sense multiple objects at the same time. And so I was studying how you can remotely sense materials to make low-cost tags that could let you distinguish multiple objects simultaneously. To do that, you need nonlinearity so that the signal is modulated. And so I was looking for material sources of nonlinearity, and that led me to look at how nuclear spins interact. Just for spin resonance, the sort of things you use when you go in an MRI machine. And so I was studying how to use that, and it turns out that it was a bad idea. You couldn't remotely use it for shoplifting tags, but I realized you could compute. And so with a group of colleagues thinking about early quantum computing, like David DiVincenzo and Charlie Bennett, was articulating what are the properties you need to compute, and then looking at how to make the tags. Turns out the tags were a terrible idea for sensing objects in a supermarket checkout, but I realized they were computing. So with Ike Chuang and a few other people, we realized we could program nuclear spins to compute. And so that's what we used to do Grover's search algorithm, and then it was used for Shor's factoring algorithm, and it worked out. The systems we did it in, nuclear magnetic resonance, don't scale beyond a few qubits, but the techniques have lived on, and so all the current quantum computing techniques grew out of the ways we would talk to these spins. But I'm telling this whole story because it came from a bad way to make a shoplifting tag.
Starting with an application, mistakes led to
The fundamental science.
Fundamental science.
Yeah.
I mean, can you just link on that? I mean, just in using nuclear spins to do computation. That what gave you the guts to try to think through this from a digital fabrication perspective, actually, how to leap from one to the other.
I wouldn't call it guts. I would call it collaboration. So at IBM, there was this amazing group of, like I mentioned, Charlie Bennett and David DiVincenzo and Rolf Landauer and Nabil Amir, and these were all gods of thinking about physics and computing. So I yelled at the whole computer industry being based on a fiction, Metropolis. Programmers frolicking in the garden while somebody moves levers in the basement. Mm-hmm. There's a complete parallel history of Maxwell to Boltzmann to Szilard to Landauer to Bennett. Most people won't know most of these names, but this whole parallel history, thinking deeply about how computation and physics relate. So I was collaborating with that whole group of people, and then at MIT, I was in this high traffic environment. I wasn't deeply inspired to think about better ways to detect shoplifting tags, but stumbled across companies that needed help with that and was thinking about it. And then I realized those two worlds intersected, and we could use the failed approach for the shoplifting tags to make early quantum computing algorithms.
And this kind of stumbling is fundamental to the Fab Lab idea, right?
Right. Here's one more example. With the student Manu, we talked about ribosomes, and I was trying to build a ribosome that worked on fluids so that I could place the little parts we're talking about. And it kept failing because bubbles would come into our system and the bubbles would make the whole thing stop working. And we spent about half a year trying to get rid of the bubbles. Then Manu said, wait a minute, the bubbles are actually better than what we're doing. We should just use the bubbles. And so we invented how to do universal object with logic with little bubbles and fluid.
Okay, you have to explain this microfluidic bubble logic, please. How does this work?
So yeah,
it's super interesting.
Yeah, and so I'll come back and explain it. But what it led to was we showed fluids could do. It'd been known fluid could do logic, like your old automobile transmissions do logic, but that's macroscopic. It didn't work at little scales. We showed with these bubbles we could do it at little scales. Then I'm going to come back and explain it. But what came out of that is Manu then showed you could make a 50-cent microscope using little bubbles. And then the techniques we developed are what we use to transplant genomes to make synthetic life. All came out of the failure of trying to make the genome, the ribosome. Now, so the way the bubble logic works is in a little channel, fluid at small scales is fairly viscous, sort of like pushing Jello, think of it as. If a bubble gets stuck, the fluid has to detour around it. So now imagine a channel that has two wells and one bubble. If the bubble is in one well, the fluid has to go in the other channel. If the fluid is in the other well, it has to go in the first channel. So the position of the bubble can switch. It's a switch. It can switch the fluid between two channels. So now we have one element, a switch. And it's also a memory because you can detect whether or not a bubble is stored there. Then if two bubbles meet, if you have two channels crossing, a bubble can go through one way or a bubble can go through the other way. But if two bubbles come together, then they push on each other and one goes one way and one goes the other way. That's a logic operation. That's a logic gate. So we now have a switch, we have a memory, and we have a logic gate, and that's everything you need to make a universal computer.
I mean, the fact that you did that with bubbles and microfluid, just kind of brilliant.
Well, so to stay with that example, what we proposed to do was to make a fluidic ribosome, and the project crashed and burned. It was a disaster. This is what came out of it. And so it was precisely ready fire aim, and that we had to do a lot of homework to be able to make these microfluidic systems. The fire part was we didn't think too hard about making the ribosome. We just tried to do it. The aim part was we realized the ribosome failed, but something better had happened. And if you look all across research funding, research management, it doesn't anticipate this. So fail fast is familiar, but fail fast tends to miss ready and aim. You can't just fail. You have to do your homework before the fail part, and you have to do the aim part after the fail part. And so the whole language of research is about like milestones and deliverables. That works when you're going down a straight line, but it doesn't work for this kind of discovery. And to leap to something you said that's really important is, I view part of what the Fab Lab network is doing is giving more people the opportunity to fail.
You've said that geometry is really important in biology. What does fabrication biology look like? Why is geometry important?
So molecular biology is dominated by geometry. That's why the protein folding is so important. That the geometry gives the function. And there's this hierarchical construction of, as you go through primary, secondary, tertiary, quaternary, the shapes of the molecules make the shape of the molecular machines. And they really are exquisite machines. If you look at how your muscles move, if you were to see a simulation of it, it would look like a improbable science fiction cyborg world of these little walking robots that walk on a discrete lattice. They're really exquisite machines. And then from there, there's this whole hierarchical stack of, once you get to the top of that, you then start making organelles that make cells that make organs through the stack of the hierarchy.
Just stepping back, does it amaze you that from small building blocks where amino acids, you mentioned molecules, let's go to the very beginning of hydrogen and helium at the start of this universe, that we're able to build up such complex and beautiful things like our human brain?
So studying thermodynamics, which is exactly the question of, that batteries run out and need recharging. Equipment, cars get old and fail, yet life doesn't. And that's why there's a sense in which life seems to violate thermodynamics, although of course it doesn't.
It seems to resist the march towards entropy somehow.
Right. And so Maxwell, who helped give rise to the science of thermodynamics, posited a problem that was so infuriating it led to a series of suicides. There was a series of advisors and advisees, 3 in a row, that all ended up committing suicide that happened to work on this problem. And Maxwell's demon is this simple but infamous problem where right now in this room we're surrounded by molecules and they run at different velocities. Imagine a container that has a wall and it's got gas on both sides and a little door. And if the door is a molecular sized creature, and it could watch the molecules coming. And when a fast molecule is coming, it opens the door. When a slow molecule is coming, it closes the door. After it does that for a while, one side is hot, one is cold. When something is hot and is cold, you can make an engine. And so you close that, you make an engine, and you make energy. So the demon is violating thermodynamics because it's never touching the molecule. Yet, by just opening and closing the door, it can make arbitrary amounts of energy and power a machine. And in thermodynamics, you can't do that. So that's Maxwell's demon. That problem is connected to everything we just spoke about for the last few hours. So Leo Szilard, around early 1900s, was a deep physicist who then had a lot to do with also post-war anti-nuclear things. But he reduced Maxwell's demon to a single molecule. So the molecule, there's only one molecule, and the question is which side of the partition is it on? That led to the idea of one bit of information. So Shannon credited Szilard's analysis of Maxwell's demon for the invention of the bit. For many years, people tried to explain Maxwell's demon by like the energy in the demon looking at the molecule, or the energy to open and close the door, and nothing ever made sense. Finally, Rolf Landauer, one of the colleagues I mentioned at IBM, finally solved the problem. He showed that you can explain Maxwell's demon by you need the mind of the demon. When the demon opens and closes the door, as long as it remembers what it did, you can run the whole thing backwards. But when the demon forgets, then you can't run it backwards. And that's where you get dissipation, and that's where you get the violation of thermodynamics. And so the explanation of Maxwell's demon is that it's in the demon's brain. So then Rolf's colleague Charlie at IBM then shocked Rolf by showing you can compute with arbitrarily low energy. So one of the things that's not well covered is the big computers used for big machine learning. The data centers use tens of megawatts of power. They use as much power as a city. Charlie shows you can actually compute with arbitrarily low amounts of energy by making computers that can go backwards as well as forwards. And what limits the speed of the computer is how fast you want an answer and how certain you want the answer to be. But we're orders of magnitude away from that. So I have a student, Cameron, working with Lincoln Labs on making superconducting computers that operate near this Landauer limit that are orders of magnitude more efficient. So stepping back to all of that whole tour was driven by your question about life. And right at the heart of it is Maxwell's demon. Life exists because it can locally violate thermodynamics. It can locally violate thermodynamics because of intelligence. And it's molecular intelligence that I would even go out on a limb to say we can already see we're beginning to come to the end of this current AI phase. So depending on how you count, this is, I'd say, the 5th AI boom bust cycle. And you can already, it's exploding, but you can already see where it's heading, how it's going to saturate what happens on the far side. The big thing that's not yet on horizons is embodied AI, molecular intelligence. So to step back to this AI story, there was automation, and that was going to change everything. Then there were expert systems. There was then the first phase of the neural network systems. There have been about 5 of these. In each case, on the slope up, it's going to change everything. In each case, what happens is on the slope down, we sort of move the goalposts and it becomes sort of irrelevant. So a good example is going up, computer chess was going to change everything. Once computers could play chess, that fundamentally changes the world. Now on the downside, computers play chess. Winning at chess is no longer seen as a unique human thing, but people still play chess. This new phase is going to take a new chunk of things that we thought computers couldn't do. Now computers will be able to do. They have roughly our brain capacity. But we'll keep thinking as well as computers. And as I described, while we've been going through these 5 boom busts, if you just look at the numbers of ops per second, bit storage, bits of I/O, that's the more interesting one. That's been steady, and that's what finally caught up to people. But as we've talked about a couple times, there's 8 orders of magnitude to go, not in the intelligence in the transistors or in the brain, but in the embodied intelligence, in the intelligence in our body.
So the intelligent construction of physical systems that would embody the intelligence versus containing within the computation.
Right. And there's a brain centrism that assumes our intelligence is centered in our brain. And in endless ways in this conversation, we've been talking about molecular intelligence. Our molecular systems do a deep kind of artificial intelligence. All the things you think of as artificial intelligence does in representing knowledge, storing knowledge, searching over knowledge, adapting to knowledge, our molecular systems do. But the output isn't just a thought, it's us. It's the evolution of us. And that's, you know, the real horizon to come is now embodying AI, not just a processor and a robot, but you know, building systems that really can grow and evolve.
We've been speaking about this boundary between bits and atoms. So let me ask you about one of the big mysteries of consciousness. Do you think it comes from somewhere between that boundary?
I won't name names, but if you know who I'm talking about, it's probably clear. I once did a drive, in fact, up to the Mussolini era villa outside Torino, in the early days of what became quantum computing, with a famous person who thinks about quantum mechanics and consciousness. And we had the most infuriating conversation that went roughly along the lines of consciousness is weird, quantum mechanics is weird, therefore quantum mechanics explains consciousness. That was roughly the logical process.
You're not satisfied with that process?
No, and I say that very precisely in the following sense. I was a program manager, somewhat by accident, in a DARPA program on quantum biology. And so biology trivially uses quantum mechanics that were made out of atoms. But the distinction is, in quantum computing, quantum information, you need quantum coherence. And there's a lot of muddled thinking about like collapse of the wave function and claims of quantum computing that garbles just quantum coherence. That you can think of it as a wave that has very special properties, but these wave-like properties. And so there's a small set of places where biology uses quantum mechanics in that deeper sense. One is how light is converted to energy in photosystems. It looks like one is olfaction, how your nose is able to tell different smells. Probably one has to do with how birds navigate, how they sense magnetic fields. That involves a coupling between a very weak energy with a magnetic field, coupling into chemical reactions. And there's a beautiful system. Standard in chemistry is magnetic fields like this can influence chemistry, but there are biological circuits that are carefully balanced with two pathways that become unbalanced with magnetic fields. So each of these areas are expensive for biology. It has to consume resources to use quantum mechanics in this way. So again, those are places where we know there's quantum mechanics in biology. In cognition, there's just no evidence. There's no evidence of anything quantum mechanical going on in how cognition works.
Consciousness.
Well, I'm saying cognition. I'm not saying consciousness. But to get cognition to consciousness, so McCullough and Pitts made a model of neurons. That led to perceptrons that then, through a couple boom busts, led to deep learning. One of the interesting things about that sequence is it diverged off. So deep neural networks used in machine learning diverged from trying to understand how the brain works. What makes them work, what's emerged is it's a really interesting story. This may be too much of a technical detail, but it has to do with function approximation. That we talked about exponentials. A deep network needs an exponentially larger shallow network to do the same function. And that exponential is what gives the power to deep networks. But what's interesting is the sort of lessons about building these deep architectures and how to train them have really interesting echoes to how brains work. And there's an interesting conversation that's sort of coming back of neuroscientists looking over the shoulder of people training these deep networks, seeing interesting echoes for how the brain works, interesting parallels with it. And so I didn't say consciousness, I just said cognition. But I don't know any experimental evidence that points to anything in neurobiology that says we need quantum mechanics. And I view the question about whether a large language model is conscious as silly, in that biology is full of hacks and it works. There's no evidence we have that there's anything deeper going on than just this sort of stacking up of hacks in the brain.
And somehow consciousness is one of the hacks or an emergent property of the hacks.
Absolutely. And just numerically, I said big computations now have the degrees of freedom of the brain. And they're showing a lot of the phenomenology of what we think is properties of what a brain can do. And I don't see any reason to invoke anything else.
That makes you wonder what kind of beautiful stuff digital fabrication will create. If biology created a few hacks on top of which consciousness and cognition, some of the things that we love about human beings was created, it makes you wonder what kind of beauty in the complexity creates
so
the digital fabrication.
There's an early peek at that, which is there's a misleading term, which is generative design. Generative design is where you don't tell a computer how to design something, you tell the computer what you want it to do. That doesn't work, that only works in limited subdomains. You can't do really complex functionality that way. The one place it's matured, though, is topology optimization for structure. So let's say you wanted to make a bicycle or a table. You describe the loads on it, and it figures out how to design it. And what it makes are beautiful, organic-looking things. These are things that look like they grew in a forest. And they look like they grew in a forest because that's sort of exactly what they are. That they're solving the ways of how you handle loads in the same way biology does. And so you get things that look like trees and shells and all of that. And so that's a peak at this transition to from we design to we teach the machines how to design.
What can you say about, because you mentioned cellular automata earlier, about from this example you just gave, and in general the observation you can make by looking at cellular automata, that there's from simple rules and simple building blocks can emerge arbitrary complexity. Do you understand what that is, how that can be leveraged?
So understand what it is much easier than it sounds. I complained about Turing's machine making a physics mistake, but Turing never intended it to be a computer architecture. He used it just to prove results about uncomputability. What Turing did on what is computation is exquisite, it's gorgeous. He gave us our notion of computational universality, and something that sounds deep and turns out to be trivial is it's really easy to show almost everything is computationally universal. So Norm Margolis wrote a beautiful paper with Tom Toffoli showing in a cellular automata world is like the game of life, where you just move tokens around. They showed that modeling billiard balls on a billiard table with cellular automata is a universal computer. To be universal, you need a persistent state, you need a nonlinear operation to interact them, and you need connectivity. So that's what you need to show computational universality. So they showed that a CA modeling billiard balls is a universal computer. Chris Moore went on to show that instead of chaos, Turing showed there are problems in computation that you can't solve. That they're harder than you can't predict. They're actually, in a deep reason, that they are unsolvable. Chris Moore showed it's very easy to make physical systems that are uncomputable. That what the physics system does, just bouncing balls and surfaces, you can make systems that solve uncomputable problems. And so almost any non-trivial physical system is computationally universal. So the first part of the answer to your question is, this comes back to how, my comment about how do you bootstrap a civilization. You just don't need much to be computationally universal. So then there isn't today a notion of like fabricational universality or fabricational complexity. The sort of numbers I've been giving you about you eating lunch versus the chip fab, sort of that's in the same spirit of what Shannon did. But once you connect computational universality to kind of fabricational universality, you then get the ability to grow and adapt and evolve.
Because that evolution happens in the physical space.
Yeah, and so that's why, for me, the heart of this whole conversation is morphogenesis. So just to come back to that, what Turing ended his sadly cut short life studying was how genes give rise to form. So how the small amount of it, relatively in effect, small amount of information in the genome can give rise to the complexity of who you are, and that's where what resides is this molecular intelligence, which is first how to describe you, but then how to describe you such that you can exist and you can reproduce and you can grow and you can evolve. And so that's the seat of our molecular intelligence.
The maker revolution in biology.
Yeah, it really is. It really is. And that's where you can't separate communication, computation, and fabrication. You can't separate computer science and physical science. You can't separate hardware and software. They all intersect right at that place.
Do you think of our universe as just one giant computation?
I would even kind of say quantum computing is overhyped in that there's a few things quantum computing is going to be good at. One is breaking crypto systems, where you know how to make new crypto systems. What it's really good at is modeling other quantum systems. So for studying nanotechnology, it's going to be powerful. But quantum computing is not going to disrupt and change everything. But the reason I say that is this interesting group of strange people who helped invent quantum computing before it was clear anything was there. One of the main reasons they did it wasn't to make a computer that can break a crypto system. It was, you could turn this backwards. You could be surprised quantum mechanics can compute, or you can go in the opposite direction and say, if quantum mechanics can compute, that's a description of nature. So physics is written in terms of partial differential equations. That is an information technology from 2 centuries ago. The equations of physics are not, this would sound very strange to say, but the equations of physics, Schrodinger's equations and Maxwell's equations and all of them, are not fundamental. They're a representation of physics that was accessible to us in the era of having a pencil and a piece of paper. They have a fundamental problem, which is if you make a dot on a piece of paper, in traditional physics theory, there's infinite information in that dot. A point has infinite information. That can't be true because information is a fundamental resource that's connected to energy. And in fact, one of my favorite questions you could ask a cosmologist to trip them up is ask, is information a conserved quantity in the universe? was all the information created in the Big Bang, or can the universe create information? And I've yet to meet a cosmologist who doesn't stutter and not clearly know how to handle that existential question. But sort of putting that to the side, in physics theory, the way it's taught, information comes late. You know, you're taught about X, a variable, which can contain infinite information, but physically that's unrealistic. And so physics theories have to find ways to cut that off. So instead, there are a number of people who start with a theory of the universe should start with information and computation as the fundamental resources that explain nature. And then you build up from that to something that looks like throwing baseballs down a slope. And so in that sense, the work on physics and computation has many applications that we've been talking about, but more deeply, it's really getting at new ways to think about how the universe works. And there are a number of things that are hard to do in traditional physics that make more sense when you start with information and computation as the root of physical theory.
So information and computation being the real fundamental thing in the universe.
Right. That information is a resource. You can't have infinite information in finite space. Information propagates and interacts, and from there you erect the scaffolding of physics. Now it happens, the words I just said look a lot like quantum field theories. But there's an interesting way where instead of starting with differential equations to get to quantum field theories, and quantum field theories you get to quantization. If you start from computation and information, you begin sort of quantized, and you build up from there. And so that's the sense in which absolutely I think about the universe. The easy way to understand that is just almost anything is computationally universal, but the deep way is it's a real fundamental way to understand how the universe works.
Let me go a little bit to the personal. And with center bits and atoms, you have worked with the students you worked with have gone on to do some incredible things in this world, including build supercomputers that power Facebook and Twitter and so on. What advice would you give to young people? What advice have you given them how to have one heck of a great career, one heck of a great life?
One important one is if you look at junior faculty trying to get tenure at a place like MIT, the ones who try to figure out how to get tenure are miserable and don't get tenure, and the ones who don't try to figure it out are happy and do get it.
Yeah.
I mean, you have to love what you're doing and believe in it, and nothing else could possibly be what you want to be doing with your life, and it gets you out of bed in the morning. And again, it sounds naive, but within like the limited domain I'm describing now as getting tenure at MIT, that's a key attribute to it. And in the same sense, if you take the sort of outlier students we're talking about, 99 out of 100 come to me and say your work is very fascinating, I'd be interesting to work for you, and 1 out of 100 come and say, here, you're wrong. Here's your mistake. Here's what you should have been doing. And they just sort of say, I'm here and get to work. And again, I don't know how far this resource goes. So, I've said I consider the world's greatest resource this engine of bright, inventive people, of which we only see a tiny little iceberg of it. And everywhere we open these labs, they come out of the woodwork. They come. We didn't create all these educational programs, all these other things I'm describing. We tried to partner everywhere with local schools and local companies, and kept tripping over dysfunction and find we had to create the environment where people like this can flourish. And so I don't know if this is everyone, if it's 1% of society, what the fraction is, but it's so many orders of magnitude bigger than we see today. We've been racing to keep up with it to take advantage of that resource.
Something tells me it's a very large fraction of the population.
I mean, the thing that gives me most hope for the future is that population. Once a year, this whole lab network meets, and it's my favorite gathering. It's in Bhutan this year because it's every body shape, it's every language, every geography, but it's the same person in all those packages. It's the same sense of bright, inventive joy and discovery.
If there's people listening to this and they're just overwhelmed with how exciting this is, which I think they would be, how can they participate? How can they help? How can they encourage young people or themselves to build stuff, to create stuff?
Yeah, that's a great question. So this is part of a much bigger maker movement that has a lot of embodiments. The part I've been involved in is Fab Lab Network. You can think of as a curated part that works as a network. So you don't benefit in a gym if somebody exercises in another gym, but in the Fab Network, you do in a sense benefit when somebody works in another network, another lab, in the way it functions as a network. So you can come to cba.mit.edu to see the research we're talking about. There's a Fab Foundation run by Sherry Lassiter at fabfoundation.org. Fab Labs IO is a portal into this lab network. Fabacademy.org is this distributed hands-on educational program. Fab.city is the platform of cities producing what they consume. Those are all nodes in this network.
So you can learn with Fab Academy, and you can perhaps launch or help launch or participate in launching a Fab Lab.
Well, and in particular, from 1 to 1,000, we carefully counted labs. Now we're going from 1,000 to 1,000,000, where it ceases to become interesting to count them. And in the 1,000 to the 1,000,000, what's interesting about that stage is technologically, you go to a lab not to get access to the machine, but you go to the lab to make the machine. But the other thing interesting in it is we have an interesting collaboration on a Fab Lab in a box. And this came out of a collaboration with SolidWorks on how you can put a Fab Lab in a box, which is not just the tools, but the knowledge. So you open the box, and the box contains the knowledge of how to use it, as well as the tools within it, so that the knowledge can propagate. And so we have an interesting group of people working on, the original Fab Labs. We have a whole team to get involved in the setting up and training. And the Fab Academy is a real in-depth, deep technical program in the training. But in this next phase, how sort of the lab itself knows how to do the lab. We've talked deeply about the intelligence in fabrication, but in a much more accessible one about how the AI in the lab, in effect, becomes a collaborator with you in this nearer term to help get started. And for people wanting to connect, it can seem like a big step, a big threshold, but we've gotten to thousands of these, and they're doubling exactly that way just from people opting in.
And in so doing, driving towards this kind of idea of personal digital fabrication.
Yeah, and it's not utopia, it's not free, but come back to today, we separately have education, we have big business, we have startups, we have entertainment. Sort of each of these things are segregated. When you have global connection to one of these local facilities, in that you can do play and art and education and create infrastructure. You can make many of the things you consume. You could make it for yourself. It could be done on a community scale. It could be done on a regional scale. It really, I'd say, the research we spent the last few hours talking about, I thought was hard. And in a sense, I mean, it's non-trivial, but in a sense, it's just sort of playing out, we're turning the crank. What I didn't think was hard is, if anybody can make almost anything anywhere, how do you live? How do you learn? How do you work? How you play? These very basic assumptions about how society functions. There's a way in which it's kind of back to the future, in that this mode where work is money is consumption, and consumption is shopping by selecting, is only a kind of a few decade old stretch. In some ways, we're getting back to, a Sami village in North Norway is deeply sustainable, but rather than just reverting to living the way we did a few thousand years ago, being connected globally, having the benefits of modern society, but connecting it back to older notions of sustainability. I hadn't remotely anticipated just how fundamentally that challenges how a society functions, and how interesting and how hard it is to figure out how we can make that work.
It's possible that this kind of process will give a deeper sense of meaning to each person.
Let me violently agree in two ways. One way is this community making crosses many sensitive sectarian boundaries in many parts of the world where there's just implicit or explicit conflict, but sort of this act of making seems to transcend a lot of historical divisions. I don't say that philosophically, I just say that as an observation. And I think there's something really fundamental in what you said, which is deep in our brain is shaping our environment. A lot of what's strange about our society is the way that we can't do that. The act of shaping our environment touches something really, really deep that gets to the essence of who we are. That's again why I say that in a way the most important thing made in these labs is making itself.
What do you think, if this shaping of our environment gets to something deep, what do you think is the meaning of it all? What's the meaning of life, man?
I can tell you my insights into how life works. I can tell you in my insights in how to make life meaningful and fulfilling and sustainable. I have no idea what the meaning of life is, but maybe that's the meaning of life.
The uncertainty, the confusion, because there's a magic to it all. Everything you've talked about, from starting from the basic elements with the Big Bang that somehow created the sun, that somehow said FU to thermodynamics and created life, and all the ways that you've talked about, from ribosomes that created the machinery, that created the machine, and then now the biological machine creating through digital fabrication, more complex artificial machines. All of that, there's a magic to that creative process. And we humans are smart enough to notice the magic.
So you haven't said the S word yet.
Which one is that?
Singularity. Yeah, I'm not sure if Ray Kurzweil is listening. If he is, hi Ray. But I have a complex relationship with Ray because a lot of the things he projects I find annoying. But then he does his homework, and then somewhat annoyingly he points out how almost everything I'm doing fits on his roadmaps.
Yeah.
And so, the question is, are we heading towards a singularity? I'd have to say I lean towards sigmoids rather than exponentials.
We've done pretty well with sigmoid.
Yeah, so sigmoids are things grow and they taper, and then there can be one after it and one after it. So, I'll pass on whether there's enough of them that they diverge. But the selfish gene answer to the meaning of life is the meaning of life is the propagation of life, and so it was a step for atoms to assemble into a molecule, for molecules to assemble into a protocell, for the protocell to then form organelles, for the cells to form organs, the organs to form an organism. Then it was a step for organisms to form family units, then family units to form villages. You can view, each of those as a stack in the level of organization. So you could view everything we've spoken about as the imperative of life just the next step in the hierarchy of that, in the fulfillment of the inexorable drive of the violation of thermodynamics. So you could view, I'm an embodiment of the will of the violation of thermodynamics speaking.
The two of us having an old chat, yes.
Yeah.
And so continues, and even then the singularity is just a transition up the ladder.
There's nothing deeper to consciousness than it's a derived property of distributed problem solving. There's nothing deeper to life than embodied AI in morphogenesis. So why so much of this conversation in my life is involved in these fab labs? And initially it just started as outreach, then it started as keeping up with it, then it turned to it was rewarding. Then it turned to we're learning as much from these labs as goes out to them. It began as outreach, but now more knowledge is coming back from the labs than is going into them. And then finally, it ends with what I described as competing with myself at MIT. But a better way to say that is tapping the brain power of the planet. And so, I guess for me personally, that's the meaning of my life.
And maybe that's the meaning for the universe too. It's using us humans and our creations to understand itself. In a way, it's whatever the creative process that created Earth, it's competing with itself.
Yeah. So you could take morphogenesis as a summary of this whole conversation, or you could take recursion. That in a sense, what we've been talking about is recursion all the way down.
And in the end, I think this whole thing is pretty fun. It's short, life is, but it's pretty fun. And so is this conversation. I mentioned to you offline that I'm going through some difficult stuff personally, and your passion for what you do is just really inspiring, and it just lights up my mood and lights up my heart. And you're an inspiration for, I know, thousands of people that work with you at MIT and millions of people across the world. It's a big honor that you were so with me today. This is really fun.
This was a pleasure.
Thanks for listening to this conversation with Neil Gershenfeld. To support this podcast, please check out our sponsors in the description. And now, let me leave you with some words from Pablo Picasso. Every child is an artist. The challenge is staying an artist when you grow up. Thank you for listening, and hope to see you next time.
Let's imagine you have a black rapper who invites people on stage, and let's suppose they invite a black person on stage. You're perfectly happy when the black person full out with their lyrics. They invite a white person on stage. The white person is doesn't sort of mystified, but it comes on stage and full out with what the rapper says, including the infamous N-word, and then the black rapper gets mad. Imagine the white comedian who satirizes that, pokes fun at that, and in poking fun at that, says the infamous N-word. Am I angry? No, I'm not angry. Not angry at all.
The following is a conversation with Randall Kennedy, professor at Harvard Law School and author of many seminal books on race, law, history, culture, and politics, including specifically on affirmative action, criminal justice, policing, and the topic explored extensively in this conversation, the single most powerful word and slur in the English language, the N-word, with a hard R at the end. Randall has written a book with this word as the title, N-word, the strange career of a troublesome word. Please be warned that Randall uses this word throughout this conversation, deliberately and skillfully, to discuss its power and its role in the history of the United States. I don't intend to shy away from controversial topics like these, and I'll work hard to handle them thoughtfully and thoroughly, with respect and with empathy, often with several guests who have very different perspectives on the topic. In the end, I believe in the power of long-form conversations to heal divides by furthering understanding of human nature, of human history, and the full diversity of the human experience. This is the Lex Friedman Podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Randall Kennedy. You wrote a book whose title is The N-Word, spelled out with a hard R at the end. So let's start with the history of this word. What is the history of the N-word?
The word you're referring to is nigger. The book that you're referring to is Nigger, the Strange Career of a Troublesome Word. The word dates back to the 16th, 17th century. It's got a long lineage, in other words. Basically Latin, basically Spanish, basically NIG, black in various formulations. We don't know actually how the term nigger became a slur. So there were words that were close to N-I-G-G-E-R that were used in various ways. For instance, N-I-G-G U-H was used. N-I-G-G-U-R is used. And sometimes it was used in a way that seemed to be just purely descriptive. We do know that by the early 19th century, it had become a slur. It had become a derogatory word about which people complained. But exactly how that came about, no.
So it's been 20 years since you've written the book. What wisdom have you gained about this word since writing the book? And maybe having to interact with people, having to read, having to see, having to feel the response to the book.
This book has generated a lot of controversy. I thought it would. It's probably generated more controversy than I had anticipated. It has certainly generated more different sorts of experiences than I had anticipated. So, for instance, I did not think that writing this book would prompt people to ask me to be an expert witness in cases. And over the past 20 years, I've been an expert witness in a number of different cases. I've been an expert witness in a murder case, in various cases of assault. I've been an expert witness in cases involving tort cases, intentional infliction of emotional distress. I've been an expert witness in a number of employment cases. I had not anticipated that, nor had I anticipated the extent to which people would get in trouble for using my book. Every year, there are teachers who are suspended or who are fired because they will excerpt a chapter of my book. Let's imagine and this is not, I'm not imagining things, this has happened. A teacher is teaching, for instance, the Mark Twain's Huckleberry Finn. The word nigger appears in that book over 200 times. The teacher, trying to be earnest, trying to be sensible, trying to be serious, will excerpt a part of my book to acquaint students with the history of the word and maybe the history of controversy involving the use of the word in this particular novel. The the teacher will give it out, hand it out to the teachers, hand it out to students. And there have been a number of teachers who've been suspended or worse because of that. Students will get upset, go home, tell their parents. Their parents will storm to the school and say that this is terrible. The teacher is, quote, using the word nigger in an offensive way. And oftentimes administrators will basically abandon the teacher. And whenever this comes to my attention, I'll write the superintendent of schools, or I'll write the principal, or sometimes I'll write an opinion editorial piece for the local newspaper. But every year, there are teachers who are disciplined for using my book. I had not anticipated that.
And what is the nature of the letter or the op-ed that you write on why they shouldn't be disciplined, or if they to the degree they should be or shouldn't be?
There's not been one case. There's not been one case that has come to my attention in which it was even remotely sensible for the teacher to be disciplined. And what I say is that, number one, frankly, I go through, what I write is almost a synopsis of my book. Number one, this is an important word in American history. It is a word that is explosive. That's why people get so upset. It's a word that's volatile. It's a word that has typically been used in a terrible way. It's a word that is part of the soundtrack of racial terrorism in the United States. So people ought to know about this word. I mean, if you're interested in knowing the real history of the United States, if you're interested in knowing about lynching, if you're interested in knowing about the way in which Black people have been terrorized in the United States, you need to know this word. You need to know that history. So you need to know why it is that people are upset about the word. But it doesn't end there. You have to know that. And if you know that, then that knowledge should equip you to be careful. It should equip you to know that, to know the range of contexts in which this word appears. But again, it doesn't just end there, because especially young people, you tell that to young people, they nod, they read, they understand that. But then what? But then they turn on their radios and they turn on, they listen to Spotify, they listen to some of their favorite entertainers. They listen to Dr. Dre, they listen to the Ghetto Boys, they listen to, Snoop, and they listen to NWA. What do they hear? They listen to stand-up comedians. They listen to Dave Chappelle. They listen to Cat Williams. What do they hear? They hear the word nigger or nigga being used in a lot of different ways. And so they need to know about that as well. What are people doing? How does one explain the fact that Dick Gregory was a comedian, activist, friend of Martin Luther King Jr., a true activist. I mean, he had a flourishing career as an entertainer that he abandons in order to struggle for racial justice throughout the United States and including the Deep South. How does one explain the fact that he wrote several memoirs, but his first memoir is called Nigger, a memoir? How does one explain that? How does one explain how does one explain Richard Pryor? I mean, Richard Pryor's best album is That Nigger's Crazy. Well, was Richard Pryor trying to put down Black people? How does one explain that? One can only explain that by getting deeper into the word, by understanding that, yes, this is a word that has been used in a derogatory way. This is a word that has been used to put people down. This is a word that has been used to terrorize people. You got to know that. But you also have to know that this is a word that has also been put to other uses. There are artists, there are entertainers who have used this word, like Dick Gregory used it, to put up a mirror to American society and say, look at this word and look at the terrible way in which it's been used. We don't want you to look away. No, don't look away. No euphemism, no asterisk. No N-word. No, nigger. Now we want you to look at that, and we want to talk about that. James Baldwin. There was a documentary about James Baldwin a couple of years ago. Highly lauded documentary. The title that was given to this documentary was "I Am Not Your Negro." That's not what James Baldwin said. Anybody can go to YouTube right now, take a look. James Baldwin said, "I am not your nigger." And then he went on to talk about that. Well, James Baldwin wasn't, again, he wasn't trying to cover up anything. He wanted people to face the facts of American life. And it seems to me that if you're a teacher and you want to have your students face the facts about American life, well, you've got to grapple with the word nigger. Now, let me just quickly say, teachers have a tough job. And if we're talking about students, of course, there's a wide range of students. Am I saying that one ought to give my book to kindergartners? No. Kindergartners are probably not ready for such a book. Third graders? Probably no, not third grade. If we're talking, however, about people in the 10th grade, do I think the 10th graders can read my book? Yeah, sure, absolutely. 11th graders, 12th graders, people in college. There are people in college. There are people in law schools. Teachers in law schools have been disciplined because the word nigger has come out of the teacher's mouth. Why? In a couple of cases recently, teacher would be reading a court opinion. The word appears in the court opinion. The teacher pronounces the word ah. Students get up, leave in a huff, report the teacher. There's some instances in which teachers have been, under those circumstances, have been disciplined. In my view, that's bad. And people ought to say it's bad. It's bad pedagogically. Frankly, in many of these instances, it's not only bad, it's stupid. And I don't mind saying that. I think that some of these instances in which teachers have been disciplined, absolutely stupid. People say, well, the teacher used the word. Excuse me, used the word? It'd be one thing. It'd be one thing if a teacher looked at a student and called the student nigger. Get out of here, nigger. That'd be, fine. Discipline, that's teacher, that's bad. But that's not what's going on. You don't have none of these are cases in which you have an individual who is a stranger to another individual, and this word just sort of comes out. No. What we have here is a class involving a person who is a teacher interacting with students, talking about subjects in which it would be perfectly understandable why this word would emerge as a subject of conversation. Now, under those circumstances, it's somehow wrong for a teacher to utter this word. In my view, the answer is no. And I said that 20 years ago. I say it even more emphatically now.
Still, it is one of the most powerful words in the English language, and there's a kind of responsibility that we as humans should have with words.
Yes.
With statements. That word, if not used skillfully, if not used competently, even when just read from a legal transcript, can do more harm than good.
I agree with what you say. Yes, words are powerful. Words do matter. And so I'm certainly not suggesting that people be lax. I'm not suggesting that people be irresponsible. It's precisely because words matter, however, that we need to be willing to face words and grapple with words and talk about words We'll talk about the history of words, precisely because words matter. And among other things, it seems to me it's important to understand that words can mean different things in different contexts. It's not the case that a word means the same thing in every context. The word discriminating. Sometimes it's a very bad thing. That person discriminates. And when intonation of voice means something. If I say, oh, that person discriminates, and I'm obviously being disapproving, implicitly what I'm saying is that person distinguishes between things on an unjustifiable basis. And that's a bad thing. On the other hand, that person has discriminating taste. Oh, that means something very different. That means that the person differentiates in a way that shows that they understand the difference between excellent, good, and not so good. And we think that that's a good thing. But words can have different, words can mean different things in different contexts. It seems to me that that's something that actually we ought to recognize. We ought to recognize and talk about.
Well, some words enter this territory of being a slur. And it seems like when they cross the line into being a slur, there's the number of contexts in which it's okay to mention it exponentially decreases. Right?
No. I'm gonna resist that a little bit, because the whole idea of slurs change. Yankee was a slur. Yankee was a slur in 18th century United States. Slur today. New York Yankees. I'm a Yankee fan. I'm a Yankee. Queer. And this is in my lifetime. There was a time, you queer, and people would really run away from it, and that was, a bad thing. And then, thank goodness, gay liberation movement. Gay liberation movement, basically, we're not going to run away from this. We're going to grab this, quote, slur, and we're going to affix it to ourselves, and we are going to repurpose it. Now, the word queer is, again, can it be a slur? Yeah, it can be a slur. Doesn't have to be. And it seems to me that it's important for people to know about how a word, a symbol, in some contexts can be a slur, in some contexts doesn't have to be. So the whole idea of what's a slur, that's a complicated idea in and of itself.
It's very complicated. It's, if I may say, almost fascinating how language evolves.
Mm-hmm.
But if we were to kind of have a minute-by-minute evaluation of the most powerful, intensely slur-like words in the world, I think the N-word with a hard R at the end, which is the title of your book, is number one on that list.
Well, probably so. And of course, that's one of the reasons why I wrote a little book about it.
Yeah, but it hasn't, even since you wrote a little book about it, it seems like it's maintained its number one status. You mentioned queer.
Mm-hmm.
Maybe queer was in the top 20, I don't know, for a while, and now it's sliding into the top 1,000, and the N-word is at the top.
You're absolutely right. The origins of this book, I clearly remember. I was at my office, and I was thinking about lecture topics. And I get invited to give lectures from time to time. And I was thinking, well, what might make for an interesting lecture? And all of a sudden, the word nigger popped into my mind. Now, this is a word, I've grown up with this word. I mean, there's never been a time in my life when at least in my conscious life, in which this word's been absent. I mean, in my household, for instance, in my household, my parents are black people. My parents were refugees from the Jim Crow South. I was born in the Deep South, South Carolina. In my household, I heard the word nigger used in every possible way. I heard it used as a slur. I also heard it used with respect to people who were praised. You know, my father, I clearly remember my father, whom I revere. That's the smartest nigger in the world. That's the bravest nigger in the world. That's the baddest nigger I know. He wasn't putting people down. This is the way he talked. And I grew up hearing this word in various ways. And so I was thinking to myself, God, where did this word come from? And one of the first things I did, I clearly remember just jumping up out of my seat, running up to the library, Oxford English Dictionary. When did this word first appear in English? What was the history of the word? And then what really sort of grabbed my attention is I get my computer going, and I asked the computer system, give me every case, every federal court case in which this word appears, thousands of cases. And then I said, oh my goodness, this is really interesting. And then I started just cataloging all the different cases. There came a point, I'd say probably about a month into this, I compared the number of times nigger came up with other sorts of slurs. So, for instance, kike, K-I-K-E, long time, derogatory word for Jews. How many times does this word come up? There was a time in which the word appeared, but nothing like the infamous N-word. Nothing. And then what about wetback? What about, and then I just, let me just take a look at all the other slurs. Nothing came close, not even remotely close to nigger. And I think it has something to do with, the uniqueness of the color line, particularly as it pertains to African Americans. I think that the fact that nigger sort of occupies such a unique status among slurs, I think that's a reflection of the unique stigma that has been imposed on African Americans.
It's hard to know the chicken or the egg, why one word is able to so distinctly and clearly encapsulate this struggle between races that is throughout American history. I mean, it didn't have to probably be so, but it came to be that way.
It became that. Not only that, but of course, the nigger spurred other slurs. So, Arabs, sand niggers, the Irish, the niggers of Europe, women, the niggers of the world.
John Lennon even has a song.
That's right. Well, I think Yoko Ono, had something to do with that song. So, I mean, it is a slur that has spawned other slurs. And again, that's why, as you indicated a moment ago, this is a quite unique term.
But are you conscious? Are you deliberate in you saying this word? So let me just say from a personal experience, maybe my upbringing, where I came from, in my daily life, I don't think I've ever heard that word with a hard R said as often, used clearly in my life. I've heard it today more than I have ever heard in my entire life. And I think there's a few people who listen to this, that will be listening to this and be very uncomfortable I would say not in a bad way, probably in a good way. I'm uncomfortable now, and I am almost introspecting and trying to figure out why I am comfortable. And I think even the title of your book is making me think that.
Mhm.
Just looking into my own mind and trying to understand, wow, words have power. Why does it have so much power? But are you deliberate in that action? And by the way, not only are the people listening to this sweating, this will be on YouTube in part. And YouTube, the people on the other side will be sweating. What do we do with this?
Well, am I deliberate? Yeah, the answer is yes. And let me unpack that a little bit. First, that's right. I mean, am I deliberate? Yeah.
What is
I deliberately wrote a book called Nigger: The Strange Career of a Troublesome Word. And was that deliberate? Yeah, that was quite deliberate.
But the title could have been N-word.
The title could have been N-word. Sure. The title could have been N-word. The title could have been a book about a word that causes pain to many people. I could have named it that. There are many titles I could have used. Did I want a title that would be provocative? Did I want a title that would grab people? The answer to that is yes. I'm a writer. I want people to read what I write. What was I being sensationalistic? Well, I mean, if you want to put it like that, yes. I'm not embarrassed to say that. I mean, I'm sure that when people write books, they think really hard about their titles and they try to get a title that will, grab people's attention. I know people, respect people very deeply who never, as a matter of principle, never utter this word. And I've talked with people, I've had people say, I've read your book, let's talk about it, but let's be very clear, I'm not going to use the word. I've had many conversations with people who've asked me not to use the word. The first time this came up was a book tour. It was 20 years ago when the book first came out, and I was on one of these call-in shows early in the morning. Time came to call in, 7 o'clock. I call in at 5 or 7. Right before I go on, the host of the show says, "Oh, by the way, we have a strict policy here at the station. We never use this word." And I said, "Well, gosh, I wish you had told me this earlier. Does this mean then that you're never going to pronounce fully the title of my book?" She said, "That's right." And I had to make a choice right then and there. Am I going to go on or am I not?
What'd you do?
I went on and I abided by the station's rules. And, fine. We had a perfectly fine conversation. There is a place for euphemism. The American language is a very supple language. There are lots of words that one can use. I do not get angry with people who don't, they say as a matter of principle, they're not going to use the word. Fine. I understand where they're coming from. And often I will defer to their wishes. All I say is I want people to understand where I'm coming from. I'm not just using this word willy-nilly. There's a pedagogical reason. There is a reason for why I'm saying what I'm saying. There is a reason why I use the word.
Can you make the case why using the word is a good idea, and can you steel man the case why it's a bad idea? Maybe you've heard from some critics
Yes.
who said that you saying this word out loud is actually causing a lot of harm. Not like harm because people's feelings are hurt, but increasing the amount of racism and hate.
Yeah. Critics. Let's start with the critics. One, again, going back to when the book was first published, I remember going to the first bookstore I went to. And I talked about the book, had a very, talked, asked questions. And the last comment wasn't a question, but the last comment was made by an elderly black man. I called on him, and he said, "I've listened to what you've had to say, and I appreciate what you've had to say." But he said, "But I remain unconvinced." And I remain unconvinced because when I was coming up, this word was used to put me in the back of the bus. And this word was used to prevent me from voting. And this was the word that was used to justify me never being called as a juror. So to me, this word has only one meaning. It's a terrible meaning. I'm never going to use the word. It hurts me when I hear people use the word, especially those who don't know anything about really about the history of it. And he went on to say, "I think that your book, though well intended, is probably going to be seen by some people as giving them permission to use the word." And then he stopped. And I thought there was a lot of power behind that gentleman's comment. I think that what he said is probably correct insofar as there are probably some people who read the book. There are probably some people who are listening to our conversation right now who will think that I'm giving people permission to use the word. I have said that I'm not. I want people to understand the word. I think that there is a burden that comes from whenever you utter a word like this. But that's a critique, and I think there's strength to that critique. I'm not going to say that that's a ridiculous critique. I think that there's something to that. And by the way, I should say, and that's why I would say to anyone, that's right. If this word comes out of your mouth, you are taking on real responsibility. So for years, it doesn't happen so much now, but there were, I'd say for about the first 5 years after this book was published, I would get an email at least once a week. And it would begin like this. "Dear Professor Kennedy, I read your book and I'm calling to ask you a question." And as soon as I saw that, I knew what the question was going to be. And what the person would say is the following: "I like rap." And then I knew he put stuff. "I like rap. I'm white, and I have black friends, and we listen to rap, and we're driving in the car, and we're listening to the song. We start humming along and singing along, and my black friends sing along, and when nigger or nigga comes up, they sing, and I don't know what to do. Is it wrong for me to sing along?" This happened so often that I'd say about the 10th time I got in such an email, I wrote a form letter because I didn't want to just, take up time writing, sort of crafting letter after letter after letter. So I wrote a form letter, and basically what I said was, number one, I'm flattered that you're asking me, but number one, you should have a conversation with your friend. Number two, no matter what your friend says, let me put something else for you to consider. Let's suppose, for the sake of discussion, that your friend says, "Oh, doesn't bother me. I know where you're coming from. We're just enjoying the music. I don't think that this is a racist utterance, coming out of your mouth." Let's suppose that your friend says that. That doesn't end matters, because let's imagine the following. Let's imagine that you're in a theater and you're waiting for the film to start, and you're just talking with your friends or singing with your friends or just kicking back with your friends, and they're talking about nigger this or nigga this, and you say it. You, the white boy, say it. And the next thing you feel is a fist, a big fist in your mouth that has been launched by a person that you did not see who was right behind you. All this person saw was a white person saying nigga, and the next thing, pow!
Mm-hmm.
That's not, some sort of overheated scenario coming from some law professor's mind. That is a very plausible scenario. So you have to be worried about lots of things, including mistake. So my advice to you is be prudent. I would stay clear of the word unless you're very certain, and unless if you're called on it, you feel you're in a position to defend yourself, defend what you're doing. But the prudent thing would be to stay clear.
There's so many questions I want to ask there. One is about the violence, the legal aspect of that. It's very interesting. You raised that in the book. But, I do want to bring up something I probably disagree with you on, which is you say that there's not a significant difference between the different variations of the N-word.
Mm-hmm.
Or maybe you don't. I just listened to a bunch of your interviews. So there's the version with the ER at the end,
Mm-hmm.
version with a GA at the end, and then GRO at the end. These are all different versions, and I feel like in that list of powerful words, I feel like there's a distinction.
Yes.
I feel like the number one spot is the one with the hard R,
Mhm.
and I don't know. Maybe you can try to shed light, but I feel like the one that ends in GA is really far down the list in terms of modern culture. So we talked about the evolution of the words, and the word queer, for example. It feels like because of rap, because of comedians, because it's become much more. It lost so much of its power.
Well,
or you don't think so?
no, I think there's a difference between nigger and nigga. I mean, people make a distinction between them. And I think that to the extent that lots of people make a distinction between them, I think, just as a sociological fact, they are different. I think that people who get upset if somebody, especially white people, so, if a white person says nigga and they're, they're, sort of criticized about it, and they say, well, I didn't say nigger, I said nigga. Believe me, I think most people who are mad at them are going to stay mad at them. Now you raised the word, so nigger and nigga I would put in a very different category than negro.
Educate me here.
Well, yeah, sure. Happy to. Negro is also controversial. It's also controversial. But Negro has never been viewed by a substantial number of people as a derogatory term, at least with the same amount of animus, the same amount of it's a very different kind of word than nigger or nigga. I mean, after all, Negro, Martin Luther King Jr. All of his great oratory, Negro. You read the work of the great W.E.B. Du Bois, Negro. You read the work of my boss. So for instance, I use the word Negro. Now, I use African American, Black, Afro American, but I also use the word Negro. Now, there are some people who get really mad at me because of when I use the word Negro. And so, for instance, there's students who've gotten really quite exercised, and they'll say, I'll be giving a lecture, and a hand will go up. I'll call on somebody and I'll say, "Listen, are you using the word Negro in its purely because of the historical time period that you're using? So is that why you're using it, or are you using it in your own voice?" And often I'll say, "Well, I'm using it in my own voice," and they'll say, "Well, I'm offended. We think that this is, that's old timey. It's derogatory." When this first came up, I said, "Let's pause for a moment, and I'll take that under advisement, and let me look into this." And I ended up writing an essay about the history of the terms that Black people have used to describe themselves. And it's a long list: Black, colored, Afro-American, African-American, Negro, etc. So I go through all that, and I said, "Now, let me just tell you, I know for certain when I started using the word Negro often in writing. I can date it. 1983, the summer of 1983 is when I started using the word Negro in my professional life as a lawyer. And I did it for a very specific reason. I did it because my boss demanded that I Negro capital N. Now, who was my boss? My boss in the summer of 1983 was Associate Justice of the United States Supreme Court Thurgood Marshall, known as Mr. Civil Rights. Now, it seems to me you're telling me that this word is so out of bounds, that this word is derogatory, nobody should ever use this word. Does the fact that Thurgood Marshall demanded that I use this word, does that complicate things a little bit? And so I think that people, again, ought to know more. I mean, I've encountered students who don't know very much, but who want to lecture me on word usage because they know 3 sentences about current fashion. And hold it, hold it. By the way, I push it further. I sometimes use the word colored. And then some people really don't like that. Colored? Well, there's an organization still very much alive in American life and law, the National Association for the Advancement of Colored People, the NAACP. They haven't changed their name, and as far as I'm concerned, it's a wonderful organization. There are people who have used the word colored. That's what my grandmother used, colored. Perfectly fine as far as I'm concerned. So again, there are lots of different words that one can use different formulations. I understand that people have different preferences. Fine. I have my preferences. At least know where I'm coming from.
Still, words have power, and they have power to hurt.
Mm-hmm.
And there's a lot of reasons that I could see justify the use of the word in its full form, as you're saying, in this conversation as you're using it. One of them is perhaps fighting for the freedom to be able to use those kinds of words. So let me ask you about freedom of speech. Mm-hmm. And the censorship of the word. Should the use of the N-word be censored, for example, on social networks? So we can come up with different places. We can say university campuses, maybe in op-eds, or I don't know. But I think social networks currently is a very interesting place. Mm-hmm. There's a lot of conversations that are happening on them. There's the ability, the technical capability to censor, to remove the ability of people to use the word. Do you think they should be allowed to use the word on Twitter, for example?
Mm-hmm. My response is, it all depends on the way in which the word is being used. If the word is being used to intimidate, if the word is being used to um, terrorize, then no. Along with lots of other words, by the way. I mean, I could use the word, I suppose, gentleman. I mean, I'm sure that I could conjure up a way in which that word could be used in a, intimidating way. So, would I be happy if there was a technology that always blanked this word, Nigger? I would be against that. For one thing, it would erase the name of one of my books, and I think that, I think that the book actually has a lot of useful information, makes some useful points. And by the way, let's imagine a world in which there was a technology that blanked every time Nigger appeared. You would have, what would that do to novels by James Baldwin, by Toni Morrison, what would that do to the speeches of Malcolm X, Martin Luther King Jr.? What would that do to the comedy albums of Richard Pryor, Cat Williams, Dave Chappelle? What would that, if one sort of plays that out, would one want to have all of those blanks in important literary and political performances? No, I don't want such blanks. What I would want the word to be there and for people to understand how to deal with this word. And by the way, you've used the word hurt an awful lot. So let's talk about hurt. I think we need to be more careful with the way in which we deal with hurt, because people can be justifiably hurt. You can have justifiably hurt feelings. And if somebody has justifiably hurt feelings, I then think that we should turn to the person who has hurt those feelings and say, you have acted wrongly because this person's feelings are justifiably hurt in relationship to what you've done. On the other hand, there are people who have hurt feelings, and frankly, it's unjustified. So just imagine the following. Let's imagine that I give a talk about the greatness of Martin Luther King Jr. And then let's imagine that a Ku Klux Klansman comes up to me after my talk and says, "Oh, you have now hurt my feelings." What? Am I supposed to apologize? Am I supposed to be regretful that my talk about the greatness of Martin Luther King Jr. has hurt the feelings of the Klansmen? No, my response is going to be, you need to reevaluate your feelings, because actually your feeling of hurt is unjustified. And no, there's no apology coming from me.
But there's a kind of line, and perhaps the gray area, and maybe the word hurt has been overused. If you try to avoid hurting a small fraction of society that is mentally weak in a way where everything hurts them, that's the wrong way to build a society.
Mm-hmm.
But if we flip that upside down and say trying to maximize the amount of love in the world, and think about decisions we make in terms of language we use to try to maximize the amount of love, and not just short term but long term.
Okay.
And that's where freedom of speech is very powerful, because it's a short term painful thing often, but long term beneficial thing. Just having freedom. And so there's where the question of the N-word starts to come in. How do we think about its use on the internet, on college campuses, in a way that maximizes the amount of love and compassion and camaraderie?
I think that's good. And I would associate myself with your vision. How can we maximize love? No, I love that. I think that's great. So let's take that on. I doubt that the way of doing that is to erase the infamous N-word. I doubt that the way of doing that is to say to people, we understand that your feelings are really hurt, and we're going to do all that we can to avoid this symbolic action. Maybe this word, or maybe this symbol. We're going to do all that we can to suppress it, so that we can have a more loving universe. I doubt that that's the way to do it. I think a better way to do it, would be to fully educate people, including educate people such that, you see that over there? That is the uniform of the Ku Klux Klan. I want you to be educated about the uniform of the Ku Klux Klan, so that you can look at the uniform of the Ku Klux Klan and know what it's about. You're not terrorized by it. You're not immediately. You don't see it and sink to your knees and start wailing and crying. You don't see it and say, "I'm traumatized." No, you don't do any of that. You see it. You understand it. If somebody asks you about it, you're fully prepared to talk about it. It seems to me that attitude, that poise, that strength, that knowledge would be a better way of equipping us to have a more loving world. And by the way, just so you know, I'd say that about the swastika. I would say it about the infamous N-word. I would say it about all of the things that we're talking about. It would be better for people to be educated so that they are not traumatized.
So to you, the N-word should not be removed from Huck Finn, Adventures of Huck Finn, or from the works of James Baldwin and Toni Morrison.
Not at all. In fact, it seems to me that the bowdlerization of these great artists' literary work is, as far as I'm concerned, highly objectionable. Highly objectionable.
When is it okay for a white man to say the N-word with a hard R?
Well, here we need to focus on the word "say." Is it ever okay for anyone? Black, white, pink, yellow, I don't care, red, orange. Is it okay for anyone to use this word in a way to put down people, to terrorize people, to intimidate people? Answer, no. And I'd say that black person. By the way, I've seen black people use this word to try to intimidate, put down other black people. Bad. So I'm against it with a black person, white person, doesn't matter. On the other hand, imagine a white person who is giving a lecture on the history of American racism. A lecture on the history of American racism. And in giving that lecture, quotes the, white racist politicians who, until fairly recently in American life, used the infamous N-word. So imagine a white history professor giving a lecture about the history of American racism and says, In 1948, this is what so-and-so running for the presidency of the United States said, and then quotes a paragraph or two in which the infamous N-word is featured. Is that bad? No, that's not bad. No, that's not bad. Sounds like a perfectly good lecture. And I'm glad that you put the infamous N-word in there so that we can see that as recently as 1948, people who were running for the presidency of the United States openly used the word. That does not bother me. I'll say this too. Now, somebody says, well, nice job, Kennedy, but you've limited it to over here. You put it in an academic setting. What about other settings? It does not bother me. Let's imagine somebody who's a comedian, a white comedian, who is satirizing word usage. Let's imagine a white comedian who is satirizing our current practice and wants to poke fun at the way in which, let's imagine you have a black rapper who invites people on stage. And let's suppose they invite a black person on stage and they're perfectly happy when the black person flout with, their lyrics. They invite a white person on stage. The white person is, doesn't, sort of mystified, but it comes on stage and full out with what the rapper says, including the infamous N-word, and then the black rapper gets mad. Imagine the white comedian who satirizes that, pokes fun at that, and in poking fun at that, says the infamous N-word. Am I angry? No, I'm not angry. Not angry at all.
What if in the process of satirizing, that comedian is not very funny?
You said it's good. Bad joke, you were not funny. I don't object to the use of the infamous N-word. I just say, you're not very funny.
But because there's a line, when the joke is not funny, it just seems like the comedy is used as a cover to actually say something hateful. The interesting thing about comedy, I feel like the funnier you are, the more you can get away with.
Probably.
And that's something to do with the thing we said earlier, which is when you use words that have power, you should do so with skill and competence and the responsibility those words carry.
Again, the cases that I'm most familiar with are the cases involving teachers, professors, academic, and it is said sometimes, why do I object? I object, sometimes people say, because I suspect that this teacher just wanted to say the word, and that all of this is a cover, a pretext. Do I, in my sense of it is, no, I don't think it's a pretext. If it's pretextual, that's bad. But in my experience, I have not seen that. I don't believe that's what's good.
I agree with you on that, but sometimes I do see people that kind of have this flying towards the light desire to say something controversial and edgy, and they don't realize that there's a responsibility there. There's a skill. You shouldn't just say. I mean, actually, when comedians first start out, they'll sometimes go into that territory. They'll say edgy stuff that's totally not funny. And then you realize this is not, like, the edgier the thing, the more skills required to really serve. Like if you're cooking as a chef a poisonous fish, there's a responsibility on how to cook the damn thing so you don't poison the people eating it.
I would agree, but to get back to your question, let's imagine that somebody produces a new set of Lenny Bruce albums. So Lenny Bruce is white. Lenny Bruce used the term nigger in his sets.
Sure did.
Question: would I want Lenny Bruce's albums now to be purged of the infamous N-word? My response, absolutely not.
As another follow-on to the question, what you think? I've seen interviews you've done about this particular book. The title of those interviews on YouTube and elsewhere would use the full word.
Mhm.
What do you think about that? Should I use this word in the title?
In my view, the answer would be yes. Again, there are people, I've been on interviews, I've been on stage with people who had a different conclusion reached, and I respect a different way. Again, there is a place for euphemism. Again, it all depends. I'm not offended. Let's imagine that you posted this and you had asterisks instead of spelling it out. Would I be offended? No, I wouldn't be offended. I would prefer the full spelling, but I would understand where you're coming from. Would it offend me? No, I wouldn't.
Well, here's the weird calculation: is which version of the word in the title, as silly as that is, brings more love to you. It's hard, and basically your answer is, I don't know. your answer is kind of, you have to do it and find out.
I'm not sure. There's certain questions we're not really going to know. There's no sociologist who's going to be able to tell us that. So what do we do then? Then we go to secondary positions. And my secondary position is, I don't know. One thing that I hold on to, however, very strongly is the virtue of openness, the virtue of transparency, the virtue of freedom. And I feel as though if I'm holding on to those things, if I'm trying to engage in a serious conversation in which I'm trying to make other people understand me and I'm listening carefully to other people, I feel at ease. I feel this is going to eventuate in something positive. And, I feel okay.
You are at Harvard.
Yeah.
You're one of the most respected people in the history of Harvard. That said, you did write a book with the N-word in it, and you also have a lot of opinions that challenge the mainstream perspectives on race from all sides. Hopefully we'll get to talk about some of them. But what's your view on Harvard and universities in general and speech?
Yeah.
Did you feel pressure from any direction on first of all, the title of this book, the content of the book, and in general your views on race?
Yeah. I am very laudatory of Harvard University. I've been at Harvard since 1984. I think it is a wonderful place to work. I have, in the various positions I've taken, particularly with respect to this book or all my other books, what has Harvard University done? Harvard University has done nothing but provide support, sustenance, encouragement. I think that people get down on Harvard University. I would say to anybody, imagine the following. Imagine that the ethos of Harvard University became the governing ethos of the United States overnight. Tomorrow, we would wake up in a much better United States of America. I've been supported by Harvard University. I think well of Harvard University. That's not to say that I don't have criticisms of it, but by and large, Harvard University more than by and large. Overwhelmingly, it has provided me, and I think it overwhelmingly provides my colleagues with a work setting in which they can do their work without fear. And, you know, that's a good thing. Are there certain aspects of Harvard University about which I'm critical? Yeah, sure.
By the way, I think a few people, rightfully, wrongfully, would disagree with you that if the ethos of Harvard University took over the country, it would be a better place.
Mhm.
But there's a lot of interesting ways to break that down because Harvard is not one ethos. There's a lot of things going on
Yes.
that are very interesting.
Yes.
But one of the things that's happening is the disproportionate and kind of aggressive growth of the administration versus faculty and students. I think the power of university should always be with the faculty and students. That's where the beauty is. That's where the flourishing happens. And the more you have kind of rules and bureaucracy and all this kind of stuff, the less powerful the university is.
I think that at my university and at many universities, that's right. There's too much bureaucracy, too much regulation, and are there dangers to freedom of expression at my university and at other universities? Answer: yeah, there are. There are. So, and this has really hit home for me. There was a period of time in which I was getting off of I'd gotten off of all boards. I was just doing my work. Forget it. I'm just going to do my work. I'm not going to be associated with any organization. In the last 5 years, that has changed quite dramatically. I have gotten on various. I've reassociated myself with various organizations, mainly organizations involving academic freedom, because of what's going on on university campuses. Again, I have been, at least thus far, this hasn't pinched me where I live, but
You mean in the space of ideas?
in the space of ideas, in the space of speech, in the space of teaching, I haven't been pinched. But I am concerned about things. So, for instance, let's imagine that you're applying for a job. So you want to be an assistant professor. Or let's suppose that you're seeking a promotion. On many university campuses, you are asked to give a DEI statement in which you say, I plan to, one of the reasons why you should hire me, or one of the reasons why you should promote me, is because I'm going to, advance the DEI ambitions.
Diversity, equity, and inclusion, for people who don't know. This is the general set of programs that most universities now have.
Yes, that's right. You've got to sort of, basically, what you're being asked to do. Whether they say it explicitly or not, they don't say this explicitly, but this is what this is what is up. What you're being asked to do is to say, I'm down with the diversity, equity, and inclusion ethos, program, policy, campaign. And here's what I've done that shows that I'm down with this program. And therefore, I'm okay. Well, a lot of what I do would fit very comfortably within that. But let's suppose that I didn't like this. And by the way, there's certain aspects of the DEI, industry that I don't like. You mean to tell me that, I'm being judged at an academic institution? Let's suppose I want to be a chemist. Let's suppose I want to be a physicist. Let's suppose I want to be, I don't care, a critic of literature. I oppose this program. I don't, I don't think this is the way in which higher education should be done. Should I have to, on pain of relinquishing my ability to be hired, Should I have to sign on to this? Just suppose, and let's change it around. Let's not make it a DEI campaign. Let's make it a Make America Great Again campaign. What would we think then? Let's suppose it was something that said, instead of it saying DEI, let's make it say the advancement of American capitalism as we know it. We want you to be down with that. What have you done that shows us that you believe in the advancement of capitalism in America? Would I be happy about? No, I would say this is no. Well, no, with respect to these, as far as I'm concerned, with the DEI statement. Here's another one. I just learned, and in fact, I mean, there's certain things that are happening, and I must say, I mean, I'm in academia, but it's news to me. I didn't know until relatively recently about positionality statements. So these are statements in which somebody writes an article. Let's put, I write an article, and it's not enough for me just to submit my article to some law review or some other sort of journal. No, in addition to me submitting my article, I've got to give a positionality statement in which I say whether I am, gay or straight or what have you, in which I say my race, in which I say my nationality, in which I say my stance toward this ideological position or that ideological position. What?
Is this becoming a kind of a standard?
I don't know how widespread it is. I know there was a very good article in the New York Times a couple of days ago about these positionality statements, and in fact, that's what sort of tipped me off. Somebody had told me there's a law review at my home institution, and I had a friend who sort of mentioned this offhandedly, and who said, "Well, I submitted an article to this journal, and I was a little bit taken aback insofar as they did have me fill out a questionnaire in which I was required to state my race, state this, state that, state the other, and as far as I'm concerned, well, what does that have to do with a proper assessment of somebody's work? This concerns me. I'm concerned about the fact, a little while ago you mentioned the word Negro. I was talking with colleagues a couple months ago, and somebody mentioned that this word had come up in their class, because what happened was one student was reading from a Supreme Court decision, and the word Negro was part of what they read out, and another student held up his hand and said to the student who was reading, "Hey, you should be careful, because I find the word Negro offensive, and you need to be careful about even saying a word that would be offensive to someone." And this person, and the teacher was, what should I say in those circumstances? What should I have said? And I volunteered, and I said, "Well, gosh, that's really interesting to see if that had come up in my class." I would have said, "Well, frankly, I don't see what I don't even see what the big deal is, because I use the word Negro." And Harvard University is not, on some island that is, apart from everything else that's happening in the world. If these things are happening in other places, if they're happening at Stanford, if they're happening at Yale, if they're happening at Columbia, they're going to happen at Harvard. But thus far, and I am most especially experienced in life at Harvard Law School. Harvard Law School is an open environment in which ideas are tested, and they are tested fully. And it's because of that I say I have been fully supported at Harvard Law School, feel that it is an excellent place in which to do work. I'm a fan. I am a fan, and I'm not embarrassed to say it. I am a fan of my workplace, Harvard Law School. I'm very happy to be associated with it.
Zooming out, in general in education, there's something called critical race theory. Can you comment on what are your thoughts about this kind of perspective on race and race in America, to the degree that it's becoming a part of the education program?
Okay, so the first thing I want to say.
What is it?
Well, the first thing I want to say about critical race theory is that critical race theory has become a term. So I'm going to put quotation marks around the term critical race theory. In a minute, I'll talk about critical race theory without quotation marks. But to begin with, I want to talk about critical race theory because the reason why people are talking about critical race theory so much now is because politicians, mainly Republican right-wing politicians, have created a boogeyman, critical race theory with quotation marks around it. They have created a boogeyman, and they have tried to make it seem as though this boogeyman believes all sorts of ideas that Americans should loathe and that Americans should fear. And they've created this boogeyman, and they've created it, and they've done a very good job of creating the boogeyman, and they have mobilized sufficient public support such that there are a number of states that have passed laws prohibiting the teaching of so-called critical race theory. Now, the first thing I want to say about this is that this campaign, these laws, these various policies telling teachers don't teach this and don't teach that, and you can't use this book, you can't use that book. This is a frightening encroachment on freedom of speech, freedom to learn, freedom to listen, freedom to read. That's terrible. And it's one of the most frightening things that has happened in American life in recent memory. So that's the first thing I want to say about so-called critical race theory. Now I'll say something. I'm going to take quotation marks off of the term critical race theory. Critical race theory is a sort of, you could have a nice conversation about actually what it is. One way of viewing it is to say that, well, critical race theory is a community of ideas that comes from a community of people. The community of people would be people in legal academia in the the period starting in probably the middle of the 1980s. It would be associated with people like Derek Bell. It would be associated with people like Kimberly Crenshaw, people like Charles Lawrence, people like Richard Delgado, people like Mary Matsuda. And these are folks who held, embraced a couple of, they articulated a couple of propositions. One of their propositions was that liberal race policy was insufficient. they would say that the racial policies of a person like my old boss, Thurgood Marshall, the liberal racial policies were insufficient to grapple fully with the pervasiveness and the depth and intensity of American racism. Their basic claim, and I think, by the way, it was a good claim, their basic claim was that American racism is more central, more deeply embedded in American life than most people perceive, including liberals. And I think there was a lot of strength to that proposition. But then they also took on some other propositions with which I was in very strong disagreement. So I think it's perfectly fine to say that racism is a force in American life that is deeper, more pervasive, more stubborn, more resilient than I think people often understand, often perceive. But then some of the folks, in critical race theory, push further. One of the propositions that some of the people in critical race theory took was the proposition that America was doomed to always be a country that would be governed according to the dictates of white supremacy. Derek Bell, who was a colleague of mine and a friend of mine, took that position. He talked about the permanence of racism in American life. And he took the position that the various changes that had been wrought in American life were really, mainly cosmetic. They didn't amount to a whole lot. I mean, Derek Bell took the position, the second Reconstruction, the Civil Rights Movement. Well, yeah, it made changes, but at the end of the day, Black people were still, after the second Reconstruction, were still in a position of almost, I don't know, some of them would even say neo-slavery. Well, I think that's ridiculous. The second Reconstruction changed a lot. And as for neo-slavery, what are you talking about? A Black American was president of the United States between the years 2008 and 2016. I mean, what are we talking about here? There's been a tremendous change, and I think people ought to understand that. Now, am I saying that everything is peachy keen and all right? No. The United States is still, to a very large extent, still a pigmentocracy, but that doesn't mean that a lot hasn't changed. A lot has. So I disagree with certain tenets of critical race theory and have been very outspoken in my disagreement. Here's another one, by the way, I need to mention, because we've talked so much in our discussion about freedom of speech, freedom to teach, freedom of listening. Another big problem that I've had with some of the people who talk of themselves as critical race theory people has to do with their attitude towards freedom of speech. Some critical race theory people think that the American legal system is wrong in the latitude that it gives to what they call hate speech, or the latitude that it gives to what they would view as racist beliefs. Some of the people who associate themselves with critical race theory think that racist beliefs ought to be expunged with the aid of state power if need be. Well, I'm against that. And, I think we're at a moment, an ironic moment, in which actually it's the right wing that has embraced some of the ideas that were championed by some of the people who call themselves critical race theorists. They say, oh, we ought to expunge hate speech. Well, the right wing is saying this critical race theory, that's hate speech, so let's expunge it. And so again, I've been very outspoken in my criticism of some of the illiberal dimensions of critical race theory. So I've been a critic of certain features of critical race theory. I have applauded certain features of critical race theory. Critical race theory, there's some aspects of it that I think have been useful. There's some aspects of it that I think have been, profoundly wrong-headed. So that's where I am. And I certainly, above all, I certainly am against any efforts to remove it from, the intellectual universe. It is a part of our intellectual universe. People ought to know about it, and people ought to debate it, and people ought to be free to make up their minds to conclude what they will about the strengths and weaknesses of critical race.
And we'll talk about the pessimistic and the optimistic perspective on race in the history of the 20th century in America. I think you have very interesting perspectives there. But before that, I'd love to look at the current moment. And you had a conversation with Glenn Lowry and John McWhorter. And from there, it became clear to me, and John made clear how important to the conversation about race is policing in today's society. That's where a lot of African Americans feel is sort of the pinnacle of racism sits. The people that believe there's still racism in America. There's still a lot of racism in America. That's where it is. So to what degree do you think there's widespread institutional racism?
Yeah. Well, my first book was a book called Race, Crime, and the Law. And
1997.
1997.
Time flies.
Time flies. Unfortunately, the impetus behind that book stands. That book was propelled by a sense that with respect to the administration of criminal justice, African Americans feel deeply aggrieved, and they feel deeply aggrieved with good reason. And they feel deeply aggrieved with good reason in at least two dimensions. On the one hand, African Americans suffer from under protection. And in fact, in that book, the central theme of that book was that Black Americans suffer from under protection. You take a look at the broad, the broad trajectory of American history, and ask yourself, in what way have Black Americans been most oppressed? Well, take a look at the antebellum period before the abolition of slavery. Before the abolition of slavery, in the locales where most Black people resided, namely the slave states, in a lot of those areas, question, was there a crime called the murder of a Black person? Answer, for a long period, the answer was no. There might have been a tort, so if a white person killed a slave, that person could be sued because they had injured the property of another and would have to pay money to for that. But had they committed a crime? Answer: no. In the antebellum period, were black women protected against the crime of rape? In most states, the answer was no. There was no such crime. Let's go to after. Slavery is abolished. Thank God. Slavery is abolished. Then let's see, what happens. So we hear lynching. From 1890 until, let's say, 1930. Well, in 1890 there was probably, I would say there was probably on average a lynching every day in the United States. Well over 300 lynchings. It goes down. That was the case in the 1890s, probably the first decade of the 20th century, and then it starts going down. What was lynching about? Lynching was about black people being executed outside the law. Did the legal system do anything about that? Answer: no. You show me cases in which people were prosecuted criminally for engaging in lynching. You come up in most places with a null set. Black people suffered the under protection of the law. Do black people still suffer the under protection of the law? The answer is yes. And people talk about the Kerner Commission report, 1968. Black people were asked, with respect to the police, what's your main complaint? In many places, the main complaint was, we don't have police protection. When things happen to us, when our houses are burgled, when our businesses are encroached upon by robbers, when our businesses are robbed, when we're assaulted, nothing happens. The police protect white people. They don't protect us. Under protection. Our society right now, if you take a look at the statistics, who is most liable to be raped, robbed, the victim of assault, what have you? Black people. I mean, and it's not even close. Under protection. So that's one way in which the administration of criminal justice harm black people by not doing what government is supposed to do, which is protect us. The 14th Amendment. Equal protection, I underline protection of the law. So that was a big theme of race, crime, and law. Now, second, and this is the thing that gets most attention, and it's important. I think that the underprotection story does not get enough attention, but then there's a second story. The second story is that black people have historically and still today, black people are subjects of invidious racial discrimination when it comes to police action. So, walking down the street, you have a black person who's, let's say, 20 years old. You have a white person who's 20 years old. Let's make them men. Both is walking down the street. And question, attitude of the police towards these two. An attitude, is a complicated thing. It can show itself in various ways. It can show itself in a look. It can show itself in who gets the look. Black person's, walking down the street or running down the street. White person's walking down the street or running down the street. What happens with respect to the police? Let's suppose that, who gets the second look? Who is followed? Who is detained for a moment?
Well, some of it, just on a small tangent, I apologize to interrupt, but attitude is an interesting one because a lot of the interaction doesn't show up in the data.
Mm-hmm.
So detained, for example, starts showing up in the data. But before then, the second look, the third look, the first look, this is where the gray area of conversation happens because
Very much so.
culture and society happens in the stuff that doesn't often show up in the data.
Yep. So I tell you, this really came home to me several years ago. I was in New York City, and it was at a time when there was a lot of discussion over the stop and frisk, basically, racial profiling on the street. I was walking. I was in Harlem, walking down the street, and frankly, the police weren't bothering me. I'm just walking. No, the police weren't bothering me. But, I'm of a certain age. I did notice though. I was looking at the police and the way that the police attitude, it had to do with body posture. It had to do with, that's right, who got a second look. It had to, I noticed, I'm walking down the street, I'm walking in Harlem. There are white people in the street. Most of the people that were black, some Hispanic. The level of contempt, the level of animus, the level of unfriendliness that was pouring off the police. They didn't say anything. No, they didn't detain. They didn't say anything. It was palpable. I could feel the attitude that was being directed at the young black men. And the thing is, it's not as if this doesn't matter. It matters because the way I saw it, these young black men knew, they felt the contempt that the police were shedding. And this was going to have a consequence. The consequence it was going to have is, let's imagine that the police did say, excuse me, what are you up to? Now, if you have been feeling this contempt, if you feel like the officer who is asking this question doesn't like you, doesn't know anything about you, but just doesn't like you on sight, you might answer in a certain sort of way. You're not going to give the cop the benefit of the doubt and basically think, well, policeman's just, asking me this, probably just trying to make the neighborhood safe. Well, if that's your feeling, policeman's just asking me this, trying to make the neighborhood safe. Well, officer, the reason why I'm here is such and such. And, thanks for your service. That's one response. Another response is, I'm not going to tell you anything. I'm not going to tell you anything. I know that you don't mean me any. I know that you don't mean me any good. I'm not going to tell you anything. Am I free to leave? And then the cop, having heard that, then says something back. After 5 minutes, what do you have? You have an altercation on your hands. And I felt that. And that is hard. And you're absolutely right. That's not written down. It doesn't get to court. It's there. but it's an important part of street life. It's an informal part of street
And
life.
it has ripple effects because that young black man will probably talk shit about that cop later that day, so the narrative persists, and then the cop will also talk shit, and then there's these narratives.
Yep.
And I think the contempt is such a powerful thing.
It's so hard to disentangle because you're absolutely right. The young man, let's suppose that the story ends, quote, well.
Right.
He's going to go and he's going to be talking with his friends and he's saying, let me tell you what just happened to me. And his friends are going to say, oh, yeah, that doesn't surprise me. Let me tell you what happened to me. And, you know, for 2 hours, this goes on. The anger, the feeling of humiliation, the feeling of aggrievement grows. It's disseminated. And that's part of what we have. But that's not all of it. That's you know, that's an important part of what we have. But we have even worse than that, because then you ask the question, you know, what about things we do know? I know this from my teaching. This was brought up. You know, there's a lawsuit in New York City. And notice I didn't say, I didn't say Birmingham, Alabama. I didn't say Atlanta, Georgia. I didn't say Tallahassee, Florida. I didn't say, the Deep South. I didn't say Montana. I didn't say Idaho. New York City. Cosmopolitan place, metropolis. In New York City, the police were challenged with respect to their policies. The judge wrote a very lengthy opinion, and the facts were rolled out, and the facts were really quite horrifying. People, there were black men who had been stopped many, many times. It wasn't just once. Over and over and over again, under circumstances in which they ought not to have been stopped. And, this has real consequences. It doesn't just show up here, though, of course. It also shows up in other places with respect to the administration of justice. And we still have, a big problem. As you mentioned, the police. If you ask yourself, who are the state agents that are most consequential? The police. I mean, you walking down the street, what other agents have guns on them? What other agents are authorized by the law to shoot you under certain circumstances? It's the police. The police are the most consequential agents of the state that most people interact with.
I mean, there's push back a little bit of consequential in the physical sense, but if you return to the power of the psychological sense of contempt, I would say store clerks and stuff like that can also be a source of
They're
contempt.
not agents of the state.
Right. But if we look at the landscape of contempt, which throughout the 20th century, or the bus, right, you could experience the same kind of contempt
You can
in other aspects of society. But yes, the cops
I would
have consequences.
still put the policeman or the police person is a person walking down the street with a gun. And if you think about the way in which the law, the extent to which the police are authorized to use their force, the police have extraordinary authority.
Mhm.
You look, you're driving your car and you're speeding. The police can arrest you right then and there and take you to jail. That's an extraordinary power.
But they also have, because of that, the leverage, one human to another, they have more leverage to be an asshole and show contempt to you.
They certainly do.
to be the lesser, to lean into the lesser aspects of their nature as all humans can, just to be an asshole, to show contempt. You had a bad day. They have the more freedom to do that.
Yes, and that's why police officers are very important. I recognize. I mean, I know police officers. They have a very difficult job, a very important job. Very important. Again, remember what I talked about unprotection. I want the police to protect me. I want the police to protect me from the rapist, the robber. So the police, I'm with the police. We need good policing. But we need good policing. And for good policing, we need accountability. And one of the just absolute scandals of American law is the extent to which the police are not held accountable. It's absolutely remarkable the degree to which American law fails to properly hold police accountable. They have an important job, a difficult job. I want them to be very well paid. And as far as I'm concerned, the police should make more money. They should be given the importance of what they do. They should have more respect, more prestige, more money. With all of that, they should be held accountable. And the way things are now, they're not held accountable. And every day we see the consequences in our newspapers or just talking to people.
So, what do you make of the different perspective on this? To bring up a person that I'll probably speak with, Heather McDonald, who wrote a book called War on Cops, and will often bring up the stuff that does show up in the data to show the disproportionate amount of homicides committed by African Americans. And will also justify racial profiling on that basis in stop and frisk programs. And we'll also bring up things like the Ferguson effect, saying that because of this pushback and all the stuff we've been saying about police, in those areas, the police will step back and crime will increase.
I was in one debate with them. And one of the things that I said is it was a debate that was sponsored by the Federalist Society, conservative legal group. These were conservative law students at Harvard Law School. And she made a presentation and they asked me to respond. And one of the things that I said was, when we're talking about the police, I'm disappointed with the reaction of some of my conservative colleagues, and I would consider her to be one of my conservative colleagues, because what are some of the important precepts of conservatives? One very important precept of conservatives: limited government. Limited government. What if conservatives talk about the tendency of government to overreach itself and governmental agents to overreach themselves? And I say, you're right. You're right. I right on. Why is it that you somehow forget that when you're talking about the police? When you're talking about the police, you seem to be unaware of this tendency that is so much in your consciousness in other places. But now, when you're talking about the police, you make it seem as though other people are being paranoid when they talk about the danger of overreach. We need to be very careful about the danger of overreach. Another thing with respect to the police, what do conservatives? Transparency in government. Right. It's absolutely right. We need transparency in government. So why is it that so often when we're talking about policing, why is it that conservatives actually embrace police unions and are the enemies of transparency? Why is it that you want to prevent the citizenry from knowing that officer so-and-so has, there have been 10 incidents in the last year in which citizens have complained about officer so-and-so? Don't you think that the citizenry ought to know that? Why is it that you want to keep that under wraps? So overreach, transparency, the tendency or the problem of governmental agent corruption. Why is it that those sorts of things are forgotten about when some conservatives, by the way, not all conservatives, there's some conservatives who have stuck, and appropriately so, to their guns and have said, hey, we need to make sure that the police stay in their lane. We need to make sure that the police do not overstep constitutional bounds. We need to insist on transparency. There are some conservatives who have taken that line, and I salute them. But there are a lot of conservatives, and I would say Heather McDonald was one of them, who all of a sudden become just, totally uncritical statists when they're talking about the police.
So the overstepping, overreach, the lack of transparency. Of course, we see this kind of stuff in foreign policy as well, which is starting military conflicts, and a lot of the supporters, at least with the Iraq and Afghanistan wars, were conservatives and hawks and so on. So there's a lot of hypocrisy in terms of principles and so on. But maybe one question is, in this discussion about racism and policing, there was a lot of cops that might listen to this and feel like their profession is not being respected. They're not being heard, not being respected to the difficulty of the problem they're facing. And
can I just interject? Remember a few moments ago, I mean, if I were in charge of things, I'd pay police more, in fact, much more than they receive. Police have a very difficult job, extraordinarily difficult job. I mean, for one thing, sort of maintaining the law. The law, that's a very complicated thing, the law. That's not an easy thing. I mean, I teach law. I spend a lot of hours with very smart people trying to understand the law. Very difficult. Here we expect people to understand the law at the same time that they are grappling with people, some of whom are violent. It's very difficult. I respect police officers. And I said, we need police officers. You did not hear me say, by the way, so let's get down to brass tacks. You did not hear me say, defund the police, did you? In fact, to the contrary, I said, defund. Actually, I want more funds for the police. I want to hold them accountable. I understand the difficulty of their job. I respect the police. I want people to respect the police. I also want the police to respect civilians and demand that they do. I am not a police abolitionist. Far from it. Far from it. Again, we need good policing. For good policing, we need good people.
to what degree, it's almost philosophically, maybe practically, do you think police should be doing racial profiling? Profiling in general.
Mm-hmm. Okay.
It's a very difficult philosophical, moral human question.
So first thing we need to do, and here we get back to the early part of our conversation, because we focus so much on first part of a word. Here we have another word, profiling. Question: what is racial profiling? Now, here we have in the weeds, we have people talking past one another. I've been in conversations with police officers and debates, and we talk past one another because we are defining racial profiling very differently. If you ask, I've been in conversations with police officers, and they say, "Oh, I'm totally against racial profiling." And I say, "Well, sir, what do you mean by racial profiling?" And here's what they say: racial profiling is when police officers act against somebody wholly on the basis of race. That gets rid of the issue, because most police officers don't act against anyone wholly on the basis of race. You could have the most racist police officer, and that police officer is not going to act adversely against the 90-year-old black woman walking down the street with a cane. Okay, so it's always if you define racial profiling that way, you're getting rid of the issue. The issue is, the proper issue is this: should the police be able to act against someone taking race into account as a factor? So let's imagine that a black person who's 25 years old is walking down the street right next to a white person who's 25 years old. Some people would say, you know what, under those circumstances, it's okay for the police officer to give 2 looks at the black person and only 1 look at the white person. Why? Because the statistics tell us that the black 25-year-old, there's much more risk of that person acting in an unlawful way. You take a look at crime statistics and ask the question with respect to homicide, with respect to robbery, with respect to various crimes. Is there a difference between the white 25-year-old and the black 25-year-old? With respect to certain crimes, the answer is, in certain places, the answer is yeah, there's a difference. And there is a greater risk that the black 25-year-old has engaged in various forms of criminality. I'm not that. Okay. Under those circumstances, what do I say? Should the police officer therefore be allowed to take action vis-a-vis the black person as against the white person? My answer is no. I'm fully willing to concede. Let's concede for the point of discussion that there is more risk. There might be, but for reasons of constructing the sort of society I want, we should not empower agents of the state to act towards certain people in a way that's adverse to them. Let me try to break this down into a group of things. Let's go back to let's talk about what happens when you want to get on an airplane. It wasn't so long. 9/11 wasn't all that long ago. It was a while ago, but it wasn't all that long. This very issue came up with respect to the profiling of Muslims. And there were some people who said, geez, in the aftermath of 9/11, profiling of Muslims makes sense. No hard feelings, but, the 11 people who were on those planes were all Muslims. Now, there is a rationale. You could just simply say it's not prejudice, it's not animus, it's not invidious, it's just, the facts take us this way. Well, the facts never take us this way. There are facts, and then there is our choice of how we want to respond to those facts. Now, you could respond by saying, well, we perceive Muslims to be more likely to, do bad things on an airline. You could respond in that way. On the other hand, you could say, no, we want a society in which people do not have to grapple with prejudice on the basis of their religion, on the basis of their race. And to deal with that, we're going to demand that agents of the state act towards people in the same way. And so if that means that everybody getting on the airplane, before they get on the airplane, has to open up their luggage, and it slows things down, but everybody has to open up their luggage. I would prefer that over a system in which we focus on people who are Muslim. And one of the reasons, and I'm going to bring this back to the racial thing, one of the reasons why I want to insist upon that is because if, we all have to open up our luggage. What that means is we're all paying a tax for more security. And we're all likely to ask ourselves, do we want to pay this tax? Whereas if we focus simply on the Muslims and allow the Muslims to be the only ones who are sort of paying the tax, we'll foist that on them. Same in the, black person, white person, 25 years old walking down the street. Do we want to impose a racial tax on the black 25-year-old? Some people would say yes. I say that's a mistake. Black people aren't stupid. They know that they're paying this tax. It is a violation of, it seems to me, the rules that we ought to want to have to govern our society. I say spread the costs, make the police deal with everybody the same, and don't allow a situation to develop in which a group of people can accurately say, we are paying more of a cost than these other people.
So it's a better avoiding profile is while it may have costs on security in the short term, in the long term, it's the embodiment of the principles that all men are created equal. So it has a much bigger benefit
Yes.
in representing the fairness
Yes.
that is at the core of the ideals of this country.
Yes.
Let me ask a big philosophical question. Why do you think there is racism in the world?
Okay, fine. You've asked me a question in which I throw up my hands and I don't know.
Will there always be? Why is there tribalism? Are humans always finding this way to divide ourselves? And how bad of a problem is that?
It's a huge problem. I don't, I'm not going to pretend that I know enough to grapple in a satisfactory way with such a question. I mean, to really grapple with that question, one really has to have a very broad knowledge base in which they can make comparisons. And the world's a big place. From the little bit I know about the world, and I read as much as I can. I'm a very privileged character. I mean, I live in a university, so I'm reading constantly and listening constantly. From what I gather, the problem of divided societies is a problem that is worldwide. There's, and it seems as though it seems as though human ingenuity is such that humans will find something to divide over. You know, it might be texture of hair, it might be complexion of skin,
Political ideology.
political ideology. If the texture of skin is the same, it'll then be, well, you wear these sorts of clothes, you speak in this sort of way, you believe this, whereas I believe that. I mean, it seems like a human ingenuity is such, humans will find some way of distinguishing themselves, and then they seem to want to embellish the distinction. It's not just the distinction. It's not just you believe this and I believe this. Okay, that makes the world interesting. Let's talk about what you believe and what I believe. No, it's usually associated with you believe this, I believe this. Of course, my belief is superior to your belief, and I want to put you down. And now we're headed towards war.
The interesting thing is, if I were to step outside of this whole thing from an alien perspective, visiting Earth, I think America is one of the greatest, if not the greatest, countries in the history of human civilization. And I think that the line between white and black, the racial struggle, is the thing that in part made it a great nation. There's something about the division and the way you alleviate that division through the struggle for human rights that makes for a great nation. And so it's interesting that the division is almost the fuel for the greatness, for our discovery of what it means to be human, what it means to be, what justice means. And it's interesting that it seems like there's this struggle that you're elucidating now, but that struggle itself is our search, and man's search for meaning and justice and freedom.
I think there's something to that. As you were speaking, I was immediately thinking of the person who most jumped to mind was the great Frederick Douglass. So, I mean, here you have a person who, in my view, is one of the great people in the history of the world. And, one of the things that ironically enabled him to become one of the great people of the world, he was born into slavery. His overcoming was the very thing that, in a sense, made him this larger-than-life figure. And I think there's something to you. I will say this, because a minute ago you mentioned optimism and pessimism. And I'd say in the last few years, my feeling about the United States has changed. And it's changed in a somber way. For most of my life, I've been in the optimistic camp with respect to my view of American race relations. The optimistic camp. That's the camp that believes we shall overcome. That's Martin Luther King's camp. I mean, Martin Luther King, hours before he's killed, I've been to the mountaintop. I might not get there with you, but I've glimpsed the promises. That's optimism. Frederick Douglass would be in that tradition. There would be other people, wonderful, good people who would be in that tradition.
Would you, sorry to interrupt, put in the pessimist camp? Would you put Malcolm X in?
On the pessimistic camp is the more interesting camp. It's the more interesting camp, because in the pessimistic camp, you have, if I was going to list some of my pessimists, pessimist number one, Thomas Jefferson. Thomas Jefferson, the author, principal author, Declaration of Independence. He was also the author of Notes on the State of Virginia. And he said in Notes on the State of Virginia, basically, we shall not overcome. He said, the black people will always know that their forebears were enslaved. And they will always be resentful of that, always be aggrieved by that. Jefferson did not think that we would ever have in the United States a multiracial democracy. He was very critical of slavery. Now, he was a hypocrite. He had slaves. He sold slaves. He was terrible in that way. But he did understand that slavery was horrible. But he did not want he did not want to free the slaves for a variety of reasons. And one reason was because he thought that it would be impossible to have a society in which blacks and whites were equal neighbors. He was thoroughly pessimistic. Another pessimist, Alexis de Tocqueville, thoroughly pessimistic. So who were some of the other pessimists? Abraham Lincoln, pessimistic. That's why he was so interested in colonization. He basically said, I don't like slavery, but blacks and whites are not going to be able to share the United States. Maybe the best we can do is just, put blacks, ship blacks someplace else.
Can you elaborate on that? I think people would be surprised to hear
Oh, yeah.
that you will put Abraham Lincoln in the pessimist camp.
Oh, Abraham Lincoln was thoroughly pessimistic. He believed he was anti-slavery, but he did not believe that blacks and whites would be able to share the United States together. And he was always very interested, therefore, in colonization. Even during the Civil War, he was interested in, maybe all black people. Would all black people be interested in maybe going to Panama? Would they be interested in going someplace else? Because, Lincoln was aware of how racist white people were, including himself. And he did not think that black people and white people would be able to share the United States. Now, there's a black nationalist tradition. You mentioned Malcolm X. Before Malcolm X, Marcus Garvey. My father was a thoroughgoing pessimist. His view was, the United States was born as a white man's country. It's going to remain a white man's country, and that's the way it is. He was thoroughly pessimistic.
You mentioned, just a brief aside about your dad, that when you moved to South Carolina to Washington, D.C., and you asked him why, his response to you was because either a white man was going to kill me or I was going to kill a white man.
Yes.
So he saw race as an important line that divided people in the United States.
He certainly did, and he thought that the line. My father did not. My father had passed away before Obama was elected. I would have loved to have talked with my
What do
dad.
you think he would have said? You wrote a book about the Obama presidency.
I did, and I never. What would my father have said? My father would have been delighted. My father would have been happy about this election. I do think, though, that my father would have said, I'm happy that Barack Obama has been elected. Hold on to your seats. Let's see how the white people respond.
So he would have predicted down.
I think that in 2016,
He would have said, I told you.
Yes. I think that in 2016, my father would have said, all of you people who are talking about, I don't know what's happened to America, and how could this have happened, and, no. I think my father would have said, this is America being America, and what has happened is that America has been put off kilter by a black family being in the White House. It has deranged millions of white people, And now this is coming home to roost. So I think my father would have absolutely said in 2016, I told you so.
In 2016, as you're saying, is the reason that you have at least dipped your toe outside of the optimist camp into the pessimist camp.
I want to be careful here, and I don't want to.
Give up on the optimist camp.
I don't want to. I don't. You're right. I don't want to give up on the optimist camp. I don't. I have been. My optimism has definitely been dampened. Has definitely been tested. I am certainly no. I am not as triumphalist as I once was. I am not as indignant as I once was in my criticism of pessimists. But at this moment, as we speak, am I more in the optimist camp than I'm in the pessimist camp? I'm still probably more in the optimist camp, but my optimism has been dampened. But as I speak, I have to say the following things. And I say the following things of my father, but again, whom I revere, great man. But if my father was sitting here with us, I would say, listen, Pop, it's absolutely true that the country is more racist than I had thought. That is true. It's also true, Pop, that the Vice President of the United States, as we speak, is a black woman. As we speak, it's true that the Secretary of Defense. Now, the Secretary of Defense is the head of the Pentagon. The Secretary of Defense knows where the button is, okay? This is not this is not a small, out of the way thing. This is the Secretary of Defense is a black man. There are a slew of black generals. There have been black secretaries of state. There are black people who are the heads of police forces. There are black mayors. There are black people who are the heads of some of our foremost foundations. There are, the president-elect of Harvard University is a black woman. And we could go on and on and on and on. This is not, we're not, when I was growing up, when I was, let's say, 10 years old, we got a magazine, Ebony magazine, every month. And in Ebony magazine, you could turn to the middle of Ebony and they would have black firsts. The first black person to do this, the first black person to do this. You could read Ebony, and frankly, I could tell you all those. I knew their names. Now, I read stuff. The leading cadet, the chief cadet at the United States Naval Academy. I'm reading. Then I see a picture. Black woman. I didn't know that. Back in the day, I would have known that. Now, has the United States changed? Yes. Is there racism? Yes. Is it, a substantial force in American life? Regrettably, tragically, yes. Has the United States changed? Yes. And again, if we want to go international, the United States is not the only country that is a country that has wrestled with deep division. You think about, think about India. Think about, the United Kingdom. Think about practically any rich nation state. They've all grappled with divisions. If one asks about the United States and the race question, and one puts on the table that, in 1865. Now, you know, when I talk to students, I say 1865, they think, oh my God, you know, isn't that when dinosaurs roamed? No, it wasn't when dinosaurs roamed. 1865, frankly, is not all that long ago. In 1865, the great mass of black people in the United States had recently been released from chattel slavery. The great mass of black people in the United States in 1865 were illiterate. Now, I mean, it's an absolutely extraordinary story. And so one of the difficulties I have at this moment is wrapping my head around two stories that are in such tension with one another. One is the continuing story of racism, which is an awful story. But the other story is a story that is encapsulated in the title of a great book of history by John Hope Franklin, From Slavery to Freedom. And, you know, those are two stories in American life, and it takes an awful lot to put your mind around both stories, and I'm trying to.
Well, as an optimist, I think you put more value to the overcoming side of the story, the overcoming of hardship, the overcoming of slavery, of discrimination. Well, since you mentioned illiteracy from, 150 years ago, let me ask you about affirmative action. You wrote a book on the topic titled For Discrimination, Race, Affirmative Action, and the Law. First, what is affirmative action? And maybe we could talk about what your view is on it today.
Sure. Well, affirmative action refers to racial affirmative action, because there's various sorts of affirmative action. You can have affirmative action for veterans. You can have affirmative action for in-state residents. Let's suppose you have a school, you know, the University of, you know, blah blah blah, and we want to reach reach out a hand to boost help people who live within the state. We're going to have a boost for veterans. We're going to have a boost for, you know, for women. We're going to have a boost for men in certain circumstances. Well, we're the type of affirmative action that gets most attention, and that's worth noting as well. Lots of different sorts of affirmative action, but when you say affirmative action, the type of affirmative action that immediately people are thinking about is racial affirmative.
Seems like race is at the core of this American experiment, in every part of its
Bingo.
culture.
Bingo. You know, why is it that, you know, we, again, you know, there's various ways in which institutions reach out to help various sectors of our population. Why is it that this is the one that generates all of the pulling out of hair and gnashing of teeth? We can put that to the side for a minute. Racial affirmative action refers to efforts in which institutions reach out to provide assistance to racial minorities. Now, the reaching out can happen in different ways. A light form of affirmative action might be reaching out in terms of recruiting, making a special effort to make sure that young people, let's say, in racial minority neighborhoods know about your college. You know, that's, you know, recruitment. On the other hand, racial affirmative action might take more, you know, might take a stronger form. It might take the form of saying, okay, we have a competition, and we think that there will be too few racial minority kids who do well enough in this competition to be admitted to our school. So what we're going to do is we are going to, in various ways, give a boost to the minority kids. If it comes down to you have two kids, they both, I don't know, have 99 on the test. There's one place left. We only have one spot left. Two kids. One's a black kid, one's a white kid. They both got 99. We're going to give it to the black kid. Why? Well, black kid. That's all there is to it. The black kid, we want to, maybe, and then our theory, maybe our theory is that black people have been wrong in the United States, and we want our institution to contribute to making amends. That might be a theory. Another theory might be, we think that we'll have a more interesting student body. We'll have a better student body, a more, better discussion if there are more black kids on campus. And unless we make a special effort to bring more black kids on campus, our student body will be overwhelmingly monoracial. We'll just have, white kids, a few Asian kids, a few Latino kids, if there are no black kids here. I don't know, it'll be lacking an important aspect of American life. Some sort of, the so-called diversity. So anyway, there are various theories. Some are grounded, like I said, in reparative justice. Some might be grounded in distributive justice. So, for instance, when people say nowadays, we want a cabinet, we want a team, we want a student body that looks like America. That might be a distributive justice theory for why you want affirmative action. Unless we reach out and give a boost to certain groups, they won't be here. And we want a campus that looks like America. And we won't have a campus that looks like America unless we give a special boost to, the Latino kids, unless we give a special boost to black applicants. So reparative justice, distributive justice, or third, diversity. We just want to have an interesting student body, and to have an interesting student body, we want, kids from a wide array of places. We think that that'll make for a better campus, more interesting campus. Those are three justifications, all of which, however, are justifications for, in a competition, giving a special boost to some people based on their race.
What's your sense? Can you make the case for affirmative action? Can you make the case against it?
Yeah, I can make the case for and I can make the case against. The case for, I won't spend much time on this. Like I said, there's three main justifications. Your audience should know that the justification that actually led to affirmative action is a justification that you don't hear about in the courts, because the courts have said that justification is insufficient. So the real justification behind affirmative action was, in the late 1960s, in the aftermath of the Civil Rights Revolution and the aftermath of the Civil Rights Movement, there was a feeling that, well, okay, fine, we're not discriminating against black people anymore, but black people have been disadvantaged by the discrimination that has been put upon them. And this discrimination that was put upon them has disabled them. And so they go into competitions and it's unfair. Yeah, they score less well on the standardized test, but, surprise, surprise, what the heck? They went to schools in which they got the leavings of the white folks. The white folks gave the black folks the old textbooks. That's what the black kids read. The white kids read the newest textbooks. On and on and on. So reparative justice. We're going to try to repair the scars left by past racial injustice. And so it's sort of an effort to overcome the vestiges of past misdeeds. That was one justification for affirmative action. And frankly, I think that's the justification that has always been the predominant justification, whether people owned up to it or not. But that's one justification. The distributive justice justification is there. Like I say, people, we want an integrated America. We want an America that looks like America. In that justification, legitimacy is sometimes mentioned. So, for instance, people will say things like, well, if we're going in the armed forces, you can't have an armed forces in which the people on the ground you have a lot of people on the ground who are people of color, but none of the people calling the shots, none of the generals, none of the colonels are people of color. No, and then the people on the ground are not going to stand for it. So for purpose of legitimation, we need to, for purposes of buy-in, we need to have a situation in which people get the sense that even if they're sort of low down, they're still part of the story. They're part of the team. So that's part of the sort of, distributive justice notion.
Do you think there's power to that? I mean, do you think there's value, there's correctness to that kind of idea?
I think there's some.
Because for the application process for different universities, I think that there's probably a driving narrative, the justification for affirmative action. I don't know where we put DEI efforts because they overlap, but they're not perfectly overlapping.
The reason that the school, as you know, there is a case, we'll know about it. It'll be announced sometime in the next month. Month and a half. It's a case at the Supreme Court of the United States in which the affirmative action program at Harvard and the affirmative action program at the University of North Carolina are being challenged. Most people think, including me, that the Supreme Court of the United States is going to limit, if not totally seek to abolish affirmative action. So this is a very burning issue. As things currently stand, my university and other universities embrace affirmative action on the third ground, the diversity ground. And what they say is, we need affirmative action because affirmative action is good for pedagogical reasons. Now, frankly, do I think there's something to that? I think there's a little something to that with respect to some subjects. I don't think that's what's really going on for the most part. I mean, if that's what's really going on, why don't we have more foreign students? Why isn't there a greater effort to bring in more foreign students? Why isn't there a greater effort to bring in more, religious fundamentalists? Why isn't there a greater effort to bring in, and you could just name various groups that are, you hardly ever see them on here.
So you don't think this kind of effort of driving towards diversity is rigorous enough?
I think it's often pretextual. I think, frankly, the real reason has to do with the belief, and I think it's a good belief. I associate myself with the belief. It's just that because of the legal rules, the authorities can't say this belief out loud, but it's still the case that a lot of institutions want to help American society overcome its racial past. That's the real animating force. Now, this thing about, we'll have better classroom discussions, some discussions. I mean, with some subjects, listen, I'm an ignoramus when it comes to physics. My sense of it is, however, that if you're talking about physics, You're talking about physics, and frankly, it doesn't much matter in terms of mastering physics what the demographics of that classroom are.
Well,
You either know physics or you don't.
the interesting thing I've noticed since doing this podcast is one way it does matter. It's really lonely when you do a thing and you don't see somebody that looks like you doing that thing.
Okay.
And it's such a seemingly stupid thing. Why does it matter if there's another person that looks like you in this very shallow sense? But it seems to matter to people. And when I talk to, for example, women on this podcast, a lot of women reach out saying how inspiring that is. And that's interesting, right? Like, I think we're still human, and we see people that look like us. And this kind of narrow, shallow definition of diversity still matters.
Okay. Well, I think you've made a good point, and maybe so. So let's go back to the physics. I mean, let's suppose that under one scenario, there's a classroom and a kid sticks his head in, a black kid sticks his head in the classroom and doesn't see anybody else black there and has to make a quick decision and says, nah, this ain't for me. Versus they stick their head in the classroom, they see a smattering of other black people in the classroom, they say, let me try this. And then they try it, and it turns out, damn it, they're, Albert Einstein. So, to that extent, I can see, under that scenario, maybe it does matter. So, I'll have to recalibrate. Still, those are the three leading justifications for affirmative action. You asked me, where do I stand with respect to affirmative action? Oh, no. Before we get to that, are there criticisms? The answer is yes. There are criticisms of affirmative action. Affirmative action is a policy like, any policy. Any policy is going to have some downsides to it. And affirmative action is no different. Does affirmative action have some downsides? Yes, it does have some downsides. What are they? Well, let me mention a couple. One, stigma. So if you have an institution that says that it reaches out to give a boost to certain people on a racial basis, there are going to be people who observe that and who are going to be thinking to themselves, if so-and-so is here and they were given a special boost, doesn't that mean that they were not as proficient as the other people who were here and who did not have that boost? So if they are not as proficient, that means that they might not be as good. They might not be as up to snuff. Is that part of our affirmative action world? Yes, it's part of our affirmative action world. Yes. I'm a professor at Harvard Law School. One of the subjects I teach is contracts. Actually, that's probably the subject I most enjoy teaching. I think I most enjoy writing about racial conflict and the legal system. But as far as teaching, I most enjoy teaching contracts. Well, on that very first day, when 80 students come, especially they're first year students, they're nervous, I show up. I'm quite sure that there's some students there who are thinking, okay, well, is this guy as good as my other teachers? Because, I know that, institutions like Harvard have made a special effort to bring in people like this guy, Kennedy. Is he as good? Well, I'm sorry. If you have an affirmative action regime, people are going to think that. And are they crazy to think that? No, they're not crazy to think that. No. That's a perfectly logical thing for somebody to think. Does it have an effect on me as the teacher? Yeah, actually, it does have an effect on me. Sure. I'm aware that some people are thinking that. It doesn't. I'm not. It doesn't. Make me shake in my boots. Am I aware of it? Yeah, I'm aware of it. Does it have an effect? Yeah, it probably does have an effect. It probably does. It probably makes me redouble my efforts because I don't want anybody to think justifiably that I'm less able than my colleagues. So, it's funny. When I was growing up, my father used to tell me over and over again, tie, you lose. Okay, brother, let me just tell you that. And he was telling me that because when he was, in an earlier time, tie, you lose, it was, if it's even and there's a choice to be made, the white person is going to get the benefit of that. Now, under affirmative action, there's been a switcheroo. Oftentimes, it's the black person who gets the benefit of the doubt, but I'm still in a situation in which
have to work hard.
yes, to avoid the stigmatization that is imposed by affirmative action. But is that stigma there? Yes, it's there. It is there. I'll tell you another way in which it comes up from a student's point of view. I'll never forget this. It was in my second year of law school. It was in tax class. We had a very famous tax teacher, wonderful tax teacher, on the very first day of class. Professor Bittker, wonderful man, wonderful teacher, Boris Bittker, called on, the very first person he called on was a black student. I remember this as this was yesterday. Called on a black student. It was a black woman student. And I remember when he called on her, I remember just, I felt as if the room got quieter. Really, I felt as if the room got quieter, and I know there was a real tenseness within me. He didn't call on me because he was calling on somebody else. It was a black woman student. And I felt different. I felt as if I was somehow at issue. I felt as if my place, I felt as if my status was, some small degree at issue.
In the positive direction or the negative?
Just at issue.
At issue.
And so now all of this is happening really quickly. He calls on the student. This is, happening like in seconds. And she responded, really strongly. So he asked her a question. She answered the question. Beautiful. Very strong, comprehensive, wonderful response. Now you might say, okay, well, smart student. Okay, fine. Next. After class, I went up to her. And I clearly remember I said, that was great. Thank you. Why? Because I'm a black student, predominantly white institution, Yale Law School, and I felt some of the, again, affirmative action. I felt some of the burden of this affirmative action stigma.
So it was almost like a thank you for showing that we belong here.
Yes. Perfect. Boom. Yes, that's exactly what the situation. And by the way, I wasn't the only one. I wasn't being idiosyncratic. I wasn't the only one. There weren't many black people in that class, but all of them. And we laughed about it later.
Yeah.
We laughed about it, but that was there. So there's the stigma issue, and some people have made a lot of this. Some people have really made a lot of the stigma issue. My attitude towards the stigma issue, yeah, it's there. It's, again, it's part of, it's part of the situation, but I think that the benefits outweigh the burdens. That is that a burden? That's a burden. What are some others? resentment in society. And that's so in the fancy schools. And by the way, remember when we're talking about affirmative action, most colleges and universities in the United States, there is no affirmative action issues because they're not selective. Hell, they'll take anybody, you can pay, come on in. It's only a fairly small set of schools that are selective. But of course, those are the most elite schools. Those are the schools that people most want to get into. And that's one of the reasons why we have all this, fighting over those schools. Now, there's a whole, how many millions of people are there in America who have applied to various places? They didn't get in. What do they say? The white person who applied to Harvard, applied to Yale, applied to Columbia, applied to Georgetown, applied to NYU, didn't get in. What do they say? I would have gotten in if it hadn't been for that racial affirmative action. They're resentful. Well, should they be resentful? No, they shouldn't be resentful, but they are resentful. Does that have a consequence? Yeah, it has a consequence. It has a consequence on how they act towards other people. It has a consequence on how they vote. It has a consequence. And, that's something. Are there other things? Yeah, and, in my book, I have, I go through various, I think that there is a certain sort of denialism that has accompanied the affirmative action debate. So because, Black people like myself want to avoid the stigmatizing version of affirmative action, there's some people who deal with that have said, oh, actually, there is no difference between, the beneficiaries of affirmative action and the other kids. There is no difference. If the affirmative action kids got, let's say, a 500 and the other kids got a 750, that doesn't make any difference. That's just BS. They're, the only reason the kid who, the 550 kid didn't get 750 is because the test asked all sorts of, biased, culturally biased things like, what is a yacht? Well, sorry. Yes, there is a difference. There's a 200-point difference. Does the difference matter? Yes, the difference matters. And by the way, if you don't know what a yacht is, you can know what a yacht is without owning a yacht, okay? And there's this denialism that I think has really seeped into not just into various conversations.
That can have a slippery slope effect that's beyond just this.
Yes, and we see it in various ways. So this attack on testing. It's not like I'm holding the some tests are not good tests. I think we should be skeptical of everything, but there are a lot of tests that they tell us something. They tell us who knows what, and there's some people who are really, dead set against testing because they're dead set against anything that might show a gap. Well, I think, by the way, are there gaps? Yeah, there are gaps. And what we need to do is be cognizant of those gaps and do things to make it so that if there's a gap, if you're deficient, no shame in being deficient. Heck, I'm deficient about a lot of things. Let's learn so that I catch up. But others, but I think sometimes there's been people who've been afraid of even acknowledging the gaps.
Of course, there's, I guess, a colleague of yours, Michael Sandel, with Tyranny and Merit. There's interesting, rigorous ways to kind of challenge ways. On the flip side of that, where obsessing with merit can go wrong also.
Yes, you mentioned Michael Sandel. He's a wonderful colleague and he's a wonderful friend. I've known him for a long time. I think he makes very important arguments about meritocracy. I disagree with some of the points that he makes
You
about
do.
meritocracy.
So you lean towards the meritocracy.
I think that yes, I think that there are values in meritocracy extremely important. That in fact, the movement from feudalism, the movement from status, the idea of I don't care who your father or mother was. I don't care from what part of town you come from. I don't care what your last name is. I don't care what your color of your skin is. Show me what you can do. And then somebody sits down. Okay, I'll show you what you can do. What I can do, and they show it. You're in. I think there's a lot to that, and the impulse, the sentiments behind that. I resonate with that. I think that there's a lot there. What I want to do is I want to get rid of those features in society that deprive people of the what you need to develop yourself. Sometimes those are psychological. Sometimes it's you're not around people who've done things that give you the idea that you can do things. I want to get rid of that. But the idea of people, the idea, by the way, of distinguishing. This is excellent, and the people who are excellent. They're here. And then there are people who are good. Are they excellent? No, they're not excellent. They're good. I'm not gonna, close my eyes to that distinction.
And highlight that distinction, and yet at the same time maintain a sense that their basic worth as a human being is equal.
Yes. So, is it Run DMC, one of the rap groups? We're all written down on the same list. We're all written down on the same list. Yes, we're, so I want to recognize our fundamental humanity. I don't think I think that one can recognize our fundamental humanity, and one can also recognize, as far as I'm concerned, that we all collectively should make sure that we do all that we can to prevent people from sinking below a certain level and being, in misery. I'm, all for that. But I want to be careful about some of the attacks that I hear on meritocracy. So some of the people, including, again, I have all the respect in the world for Michael Sandel. He talks about the arrogance of the winners. Mm-hmm. Okay, I want to be, I don't want the winners to be arrogant. That's right. Luck has a lot to do with things. You didn't have any control over the circumstances in which you were born into. You were lucky that you were born healthy and that you were born with a well-working mind. You didn't have anything to do with that. That was pure luck. There's some people who don't have that luck. So don't be Mr. Big Stuff. Okay? So I'm against that sort of arrogance. I'm entitled, as if I taught myself how to read. No, you didn't teach yourself how to read. There were people who did all sorts of things for you. You don't even know it. Okay, so I want to get rid of the arrogance. Have decent humility. I'm all for that. At the same time, I want to be careful about the problem of envy. I want to be careful about the problem of resentment. I want to be careful about, I've heard, so let's not give a trophy to the person who wins the race, because to give a trophy to the person who wins the race will make the person who they defeated feel bad. No, I don't want that. I want to give a trophy to the person who wins the race, because I think it's a good thing to valorize the best.
Yeah, it's a kind of celebration of this whole human project that we're on.
Yeah.
Is celebrating the best. You mentioned your father several times, so let me just linger on that. What have you learned from? What have you learned about life from your father?
I have been just such a lucky person. I mean, I feel like I've just lived an absolutely charmed life, and I live the work that I do is what I love doing. I would pay to do what I am paid to do.
Yeah,
And it's great. And I've been fortunate in so many ways. And one way in which I've been fortunate is my parents. My parents, Rachel Spann Kennedy, Henry Harold Kennedy. My mother, born in Columbia, South Carolina. My father from New Orleans, Louisiana. They were refugees from the Jim Crow South. They were people who put their all into their children. I have an older brother, I have a younger sister. All three of us know beyond any controversy that we were loved and dearly loved by our parents. And they were great people. My father, very interesting man, very independent-minded. He was perfectly willing to go his own way. And I learned much from him, including I learned things from him even when I ultimately disagreed with him. So, for instance, again, to go back to his pessimism, yeah, he was pessimistic, thoroughly pessimistic. But he was also willing to change in certain ways. In fact, both my parents. I mean, one of the most important things that happened to my parents was that I'd say when I was, let's say, 10 years old, I was born in 1954. So in 1964, I think my parents would have taken the position that you definitely never, under any circumstances, trust a white person. If a black person trusts a white person, that person is a fool. Do not trust white people, all right? They are not to be trusted. And it's the highly, highly, highly unusual one who is not prejudiced. Okay, so white people are not to be trusted, and by and large, are going to be your enemy. All right, so let's just face it. That's their point of view. I'd say that 10 years later, that point of view had been leavened somewhat. I think, and you say, well, what happened in those 10 years? Well, certainly in my life, one of the things that happened in those 10 years is I was a student in various schools, and I had a series of teachers. I've had wonderful black teachers. I've also had wonderful white teachers. And my parents paid attention to who my teachers were and how my teachers treated me. And I think that they were affected by the way in which there were white people who really helped me and were on my side and were thoroughly on my side. And I think that that experience changed my parents in their general view. They, skeptical, yeah, but they were the possibility of a white person genuinely being the friend of a black person, that that became alive to them, and I give them a lot of credit because they were adults, and for an adult to change, that's a big deal. But my parents did change.
In that transformation, that was inspiring to you, was formative to you in terms of joining the Alchemist camp.
Hugely. And the school, I mean, I said a moment ago how lucky I've been. Heck, I teach at Harvard Law School. I attended Balliol College, Oxford. I got my law degree from Yale Law School. I got my undergraduate degree at Princeton University. Those are some pretty good schools. They all were. The most important school, however, that I attended, the school that made the most difference in my education, was my high school, St. Albans School for boys. And at St. Albans, I encountered a cadre of teachers. And by the way, St. Albans, when I went to St. Albans, all these teachers were white. All these teachers. So there was one, the head of athletics, very important man, very impressive man, Brooks Johnson, black. Otherwise, white teachers. And these teachers made a huge difference in my life. And, I can call their names. Boom, 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 boom. The greatest of them all was a man by the name of Jack McKeon. Yeah. We called him Gentleman Jack McKeon. And
What subject did you?
he taught me history. He was my advanced placement history teacher. But John F. McKeon, and we shared a birthday. John F. McKeon was a fabulously good teacher. And we developed a deep, lifetime friendship. I was with Mr. McKeon the day before he died. And, he was a white man. And I've had other teachers, some of whom have become colleagues of mine. Sanford Levinson. Sanford Levinson was a teacher of mine at Princeton. He's become a colleague of mine. I mean, it would be impossible for me to, I can't make some sort of blanket condemnation of white people with Sandy Levinson in my life. I mean, it'd be seriously. John F. McKeon in my life, with Eric Foner in my life, with my colleague Martha Minow in my life, my colleague Cass Sunstein in my life. Impossible.
That speaks to the power of teachers and mentors.
Oh yeah.
And you're that for a lot of people.
Well, I've taken that to. I hope. Listen, I I would be absolutely overjoyed if there was a student who thought of me in the way that I think of Gentleman Jack McKeon. If that's the case, just one. If that's the case, I'm overjoyed.
That's a life well lived. What do you think of Martin Luther King's "Have a Dream"? Do you still share that dream?
I think that Martin Luther King Jr.'s "I Have a Dream" speech is one of the great speeches, not only in American history, but in the history of the world. You know, there's a tendency now for people to sort of poo-poo that speech. I think, unfortunately, the speech, has been embraced by, advertisers of corporate America. It's been so, it's been heard so many times that it sort of has been made to suffer from what some people might view as overexposure.
It's so unfortunate. I mean,
It's too bad.
when especially when Hollywood rolls in, they did that with John Lennon's "Imagine" recently, which I think is one of the greatest songs ever. And actors and actresses ruined it by trying to sing along and do this kind of cliche Hollywood thing.
It has, but people have tried to make it into a cliche. The fact of the matter is, it's the sentiment behind "I Have a Dream." Yeah, I'll associate myself with that. And anybody wants to see some great oratory, go watch. And Martin Luther King Jr. I mean, he gave several great speeches. His the first speech that he gave as a civil rights leader, the Holt Street Baptist Church, 1955, at the beginning of the Montgomery bus boycott, which was virtually an extemporaneous speech. It's one of his greatest. And he was, I think, 26 years old. Great. His last speech, his mountaintop speech, great speech. But "I Have a Dream," I love it. I will associate myself with those sentiments any day of the week. Absolutely.
So you still hope for a deep kind of multiracial, a deep unity in the 21st.
I have that hope, and I think that the sentiments that Martin Luther King Jr. expressed in August 1963, that represents the best of American life. And I think it's do I want to see that come to pass? Yeah, I want to see that come to pass, and we'll work to push that project along as far as it'll go.
Well, thank you for carrying his spirit of optimism forward, the spirit of your mother and father. Thank you for all the amazing work you've done, and thank you for just this conversation. It's a huge honor.
Thank you. Really
Thank you.
appreciate it.
Thank you, Randall. Thanks for listening to this conversation with Randall Kennedy. To support this podcast, please check out our sponsors in the description. And now, let me leave you with some words from Martin Luther King Jr. Darkness cannot drive out darkness. Only light can do that. Hate cannot drive out hate. Only love can do that. Thank you for listening, and hope to see you next time.
I would run outside, right, and just lay on the ground under the southern Milky Way, beautiful right up there. And I would just lay there like a snow angel and just kind of let my thoughts sort of pass through my brain. And this is when I personally have a feeling that I'm a part of it. I belong here, rather than feeling kind of small. Yes, I'm small, but there are many other small things, and lots of small things make one big.
The following is a conversation with Anna Frabel, an astrophysicist at MIT, studying the oldest stars in the Milky Way galaxy in order to understand the chemical and physical conditions of the early universe, and how from that our galaxy formed and evolved to what it is today, the place we humans call home. This is the Lex Friedman podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Anna Bell. Let's go back to the early days. What did the formation of the Milky Way galaxy look like? Or maybe we want to start even before that. What did the formation of the universe look like?
Well, scientists believe there was the Big Bang, some big beginning. But what is important for my work, and I think that's what we're going to talk about, is what kind of elements were present at that time. So the Big Bang left a universe behind that was made of just hydrogen and helium and tiny little sprinkles of lithium. And that was pretty much it. And as it turns out, it's actually quite hard to make stars or any structure from that. That's very hot gas. And so the very first stars that formed prior to any galaxies were very massive stars, big stars, 100 times the mass of the sun. And they were made from just hydrogen and helium. So big stars explode pretty fast after a few million years only. That's very short on cosmic time scales. And in their explosions, they provided the first heavier elements to the universe, because in their cores, all stars fuse lighter elements like hydrogen and helium into heavier ones, and then that goes all the way up to iron, and then all that material gets ejected in these massive supernova explosions, and that marked a really, really important transition in the universe, because after that first explosion, it was no longer chemically pristine. And that set the stage for everything else to happen, including us here talking today.
What do you mean by pristine? So there's a whole complex soup of elements now, as opposed to just hydrogen, helium, and a little bit of lithium.
Yeah, so after the Big Bang, just hydrogen and helium. We don't really need to talk too much about lithium because the amount was so small. And after these very first stars formed and exploded, the heavier elements like carbon, oxygen, magnesium, iron, all of that stuff was suddenly present in the gas clouds, in tiny amounts only, very tiny amounts. But that actually helped, especially the carbon and the oxygen, to make the gas cool. These atoms are more complicated than hydrogen. That's just a proton, and so it has cooling properties to send out photons outside of the gas cloud, so the gas can cool. And when you have gas that gets colder and colder, you can make smaller and smaller stars. So you can fragment it and clump it and turn it into stars, like the sun. And the cool thing about that is that when you have small stars like the sun, they have a really long lifetime. So those first low mass stars that formed back then are still observable today. That is actually what I do. I try to find these early survivors because they tell us what the gas looked like back then. They have preserved that composition of these early gas clouds, the chemical compositions, until today. So I don't need to look very far into the universe to study all the beginnings. I can just chemically analyze the oldest stars, and it's like unpacking everything that happened back then. It's very exciting.
So to just reiterate, so in the very early days, in the first few million years, there's giant stars that's mostly hydrogen and helium, and then they exploded in these supernova explosions, and then they made these clumps.
Yeah, so the first
Not
stars...
not pristine clumps.
Yeah, pretty much.
Fun.
So it took a few 100 million years for the first stars to emerge, and then they exploded after a few million years. Kaboom. And then it's like, I always consider the universe like a nice soup.
Mm-hmm.
And then these first supernova explosions kind of provided the salt, just a little sprinkle of heavier elements, and that made it really tasty. It just changed it completely, right? And that changed the physics of the gas. So that meant that these gas clouds that were surrounding the former first stars they could now cool down and clump and form the next generation of stars that now included also little stars. And as I just mentioned, the small stars have these really long lifetimes. The sun has a lifetime of 10 billion years. Any star that is even less massive will have an even longer lifetime. So that gives us a chance to still observe some of the stars that formed back then. So we are testing the conditions, the chemical and physical conditions of the early universe even before the galaxy formed.
So what's the timeline that we're talking about? What is the age of the universe, and what is the earliest time we got those salty, delicious clump soups with heavy elements?
Well, the universe is 13.8 billion years old.
Allegedly, yeah. Is it
yeah.
so? Okay, 13.
Well, when I was in high school, the universe was 20 billion years old.
Oh, yeah. So the estimate. Do
Things have changed.
you think that estimate will evolve in interesting ways, or no? Is it
I think
pretty
we have
stable at this point?
mostly converged, yes, because the techniques are very different now, much more precise. And the whole business of precision cosmology by mapping out the cosmic microwave background, that's a marvelous feat. Maybe, the digits will still move around a little bit, but that's all right.
Plus the gravitational waves and all that.
Yeah.
So all the different sources of data,
Yeah,
and it's
yeah.
mapping out this detailed picture of the
Yeah.
early universe. Yeah.
Totally. And so we think the earliest little stars formed, I don't know, maybe 500 million years after the Big Bang, right? Again, a few 100 million years for the first stars to emerge, and then, took some time. So give or take 500 million years. And that was the time when sort of the very first proto-galaxies formed, early stellar structures, stellar systems, from which the Milky Way eventually formed, right? So the Milky Way was probably slightly bigger one, and we know today that galaxies grow hierarchically, which means they eat their smaller neighbors. So if you're the bigger one and have a few friends around, you're just gonna eat them, absorb them, and then you grow bigger. And so all these little early stars, kind of came into the Milky Way through that kind of process, and that's why we find them in the outer parts of the galaxy today, because they're just they've been just left there since.
So the old stuff is on the outskirts of the galaxy, and the new stuff is closer to the middle. Is there?
Broadly speaking, yes.
So that's where you would look for it. So maybe just to step back, like what is a galaxy? What is a protogalaxy?
I love that question. So the galaxy is a huge assembly of stars. The Milky Way contains something like 200 to 400 billion stars. And most of the material and the stars are in the disk. And when we look at the night sky, what we see as the Milky Way band on the sky, that is actually the next inner spiral arm, because we actually live in a spiral disk galaxy. So the Milky Way is a spiral disk galaxy, and we're looking. Actually, it depends a little bit. In the northern hemisphere, we're looking out of the galaxy, so we're seeing the next outer spiral arm. And as you can imagine, there's only dark space behind that, so we don't see it all that nice on the sky. But if you travel to the southern hemisphere, let's say South America, you see the Milky Way, and it looks so different on the sky because that's the next inner spiral arm, and that's backlit by the galactic center. The galactic center is a very big, puffy, region of gas. There's a lot of star formation. The galactic party is happening there, so it's very bright, and it makes for this very beautiful Milky Way on the night sky that we see. So actually, if you ever get the chance to experience that, I encourage you to almost like close your eyes while seeing this and imagining that you're sitting in this kind of disk, in this pancake, and you're just kind of looking right into it, and you can really feel that we're in this 2D disk. And then you can imagine that there's a top and a bottom, and that we're really part of the galaxy. You can really experience that. But we're just not just lost in space somewhere, but we're really a part of it. And knowing a little bit about the structure of the Milky Way really helps.
Do you feel small when you think about that? When you look on the spiral on the inside of the Milky Way, and then you look out to the outside, how are we supposed to feel?
I don't know. I don't feel small necessarily. I feel in awe and I feel I'm a part of it because I can really feel that I'm a part of it. I think for many people, they think like, oh, there's just the planet and then there's nothing. And that's almost a little bit sad, but that's really not the case, right? Because there's so much more. And I really like to imagine how I'm sitting in this big galactic merry-go-round and we're going around the center and I can see the center above me, right? And I can almost feel like we're going there. Of course, we can't really feel that, but the sun does circle the galactic center.
But there's a kind of sadness to like looking pictures of a nice vacation place. All we get is that light and cold light. Do you feel like sad that we don't get to travel, or you and I will not get to travel there, and maybe humans will never get to travel there?
Yeah, I always wanted to travel into space and see the Earth and other things from up there. There's certainly that, but I don't know. It's also okay to just be at our vantage point and see it from here.
With the sensors, with the telescopes that we have, and explore the possibilities.
Yeah.
I mean, there is a kind of wonder to the mystery of it all. What's out there? What interesting things that we can't possibly imagine. You know, there could be all kinds of life forms, bacteria, all this kind of stuff. I tend to believe that, you know, it depends on the day. I tend to believe there's just a lot of very primitive organisms just spread out throughout. And they build their little things like bacteria type organisms. And just to think what kind of worlds there are. Because they're probably really creative living organisms. Because the conditions, I guess the question I'm wondering to myself when I look out there to the stars, how different are the conditions on the different planets that orbit those stars?
It will definitely be very different. I mean, the variety out there is huge. We know now that I think it's about every other star has at least one planet. I already mentioned the number of stars in the galaxy. I mean, you know, it's a huge number of planets out there. So who knows what that looks like? All we know is that there is a lot of variety. We don't quite yet understand what drives that, what governs that, why that is the case. Why is it not all one size fits all?
Maybe the dynamics of planet formation, like exoplanet formation or star formation, the whole
All of
thing.
it. All of it. Star formation remains a much researched topic. We definitely know that it works because
Sure.
all the stars are there. Same for the planets. But the details are so varied per gas cloud, right? It's very hard to come up with very detailed prescriptions. Broadly, we have figured it out. You need a gas cloud, you need to cool it, something clumps and fragments, and somehow it makes a star with planets or without.
But the dynamics of the clumping process is not fully understood.
No, and the local conditions are so varied, right? I mean, it's the same with, you know, all people look like people, but individually we look very different.
So even the subtle diversity of the formation process creates all kinds of fun.
Yes. So
Differences.
we just don't know how this turned out in an individual case, and it's kind of hard to figure it all out and to take a look. Certainly with planets, right? The chance to ever actually take a picture of a planet is minuscule because they don't shine, so they're really dark.
Yeah.
So I'd say there's a lot of possibility out there, but we have to be a little bit more patient.
Yeah, or come up with technologies where patience becomes less necessary by extending our lifetimes or increasing the speed of space travel, all that kind of stuff. Humans are pretty intelligent. They're pretty
Sometimes, yeah.
for the most part. I hope. When I'm on the optimistic days. Well, maybe just to linger on the what a galaxy is. What should we know about our understanding of black holes and the formation? Is it an important thing to understand in the formation of a galaxy? So all the orbiting, all the spiraling going on, how important is that to understand?
All of the above. That's what makes astronomy really hard, but also really interesting, right? No day is like another because we always find something new. I want to come back to the idea of the proto galaxy because
Yes,
it actually
yes,
matches or relates to the black hole formation. So most pretty much all large galaxies have a supermassive black hole in the center, and we don't actually know we don't really know where they come from. Again, we know that they're there, but how do we get there? So if we go back to the early universe, right? We had a little galaxy that just sort of, I don't know, had some small number of stars. It was the first gravitationally bound structure that was held together by dark matter, because dark matter actually kind of was structured up, first before the luminous matter could, because that's what dark matter kind of does. And it started to hold gas and then stars sort of together in these first very shallow, what we call potential wells, so these gravitationally bound systems. And then the Milky Way grew from absorbing neighboring even smaller systems. And somewhere in that process, there must have been a seed or one of these supermassive black holes. And I'm not actually sure that it's clear right now kind of what was there first, the supermassive black hole or the galaxy. So lots of people are trying to study that. And of course, the black hole wasn't as massive back then as it is these days. But it's a big area of research. And the new James Webb, the JWST, the telescope, the infrared telescope in space, is working on. Many people are working on that to figure out exactly what happened. And there's some surprising results that we really don't understand right now. So
to solve the chicken or the egg problem of do you need a supermassive black hole to form a galaxy, or does the galaxy naturally create the supermassive black hole?
Yeah. I mean, I think to some degree we can answer that, because there are lots of little dwarf galaxies out there. The Milky Way remains surrounded by many dozens of small dwarf galaxies. I have studied a bunch of them, and to the extent that we can tell, they do not contain black holes. So there certainly were gravitationally bound structures. So either you can call them proto-galaxies or dwarf galaxies or first galaxies. They were definitely there. But there must have been bigger things, like the proto-Milky Way, where something was different, right? What made them more massive so that, they would gravitationally attract these smaller systems to integrate them. So we'll have to see.
How do we look into that, into the dynamics of the formation, the evolution of the proto galaxies? Is it possible? Do they shine? I mean, what are the set of data that we can possibly look at? So we've got gravitational waves, which is really insane that we can even detect those. There's light. What else can we?
So that would fall into the category of observational cosmology, and the JWST is the prime telescope right now and it promises big steps forward. This is in its early days because it's only been online like a year or so, but that collects the infrared light from the farthest, like literally proto galaxies, earliest galaxies. That light has traveled some 13 billion years to us, and they're observing these faint little blobs. And folks are trying to, again, study the onset of these early supermassive black holes, how they shape galaxies. So they're seeing that they were there, surrounded by already bigger galaxies. Ideally, I'd like for my colleagues to push a little bit further. Hopefully that will eventually happen.
In terms of looking towards older and older.
Yeah, and more and more sort of primitive in terms of the structure. But of course, as you can imagine, if you make your system smaller and smaller, it becomes dimmer and dimmer, and it's further and further away. So we're reaching the end of the line from a technical perspective pretty quickly.
But it's dimmer and dimmer means older and older.
Yes, in a sense, because it all started really small, right?
Because it's smaller and smaller,
Yeah.
which correlates to older and older.
In that phase of the universe, it would. Otherwise, it doesn't. Yeah.
Just to take a small tangent about black holes, and because you do quite a bit of observational cosmology and maybe experimental astrophysics. What's the difference to you between theoretical physics and experimental? So there's a lot of really interesting explorations about paradoxes around black holes and all this kind of stuff, about black holes destroying information. Do those worlds intermix to you when you, especially when you step away from your work and kind of think about the mystery of it all?
Well, at first glance, there isn't actually much crosstalk. Personally, I mostly observe stars, so I don't usually actually think too much of black holes.
And stars is a fundamentally kind of chemical, physical phenomenon that doesn't.
That's right. The physics is kind of different. It's not extreme. I mean, you could consider nuclear fusion sort of be perhaps extreme. You need to tunnel. There's some interesting physics there, but it's a different flavor, and I don't do these kinds of calculations myself either. I very much like to talk with my theory colleagues about these things, though, because I find there's always an interesting intersection, and often it's just I've written a number of papers with colleagues who do like simulations about galaxies, and so they're not quite as far removed as, let's say, the black hole pen and paper folks, but even in those cases we had the same interest in the same topics, but it was almost like we're speaking two different languages, and we weren't even that far removed, both astronomers and all, and it was really interesting just to take the time and really try to talk to each other. And it's amazing how hard that is. Even amongst scientists, we already have trouble talking to each other. Imagine how hard it is to talk to non-scientists and other people to try, we're all interested in the same things as humans at the end of the day, right? But everyone has sort of a different angle about it and different questions and way of formulating things. And sometimes it really takes a while to converge and to get to the common ground. But if you take the time, it's so interesting to participate in that process, and it feels so good in the end to say, like, yes, we tackled this together, right? We overcame our differences, not so much in opinion, but just in expressing ourselves about this and how we go about solving a problem. And these were some of my most successful papers, and I certainly enjoyed them the most.
It could also lead to big discoveries. I mean, I think you put it really well in saying that we're all kind of studying the same kind of mysteries and problems. I mean, I see this in the space of artificial intelligence. You have a community, maybe it seems very far away, artificial intelligence and neuroscience. You would think that they're studying very different things, but one is trying to engineer intelligence, and in so doing, try to understand intelligence, and the other is trying to understand intelligence and cognition in the human mind, and they're just doing it from a different set of data, different set of backgrounds, and the researchers that do that kind of work. And probably the same is true in observational cosmology and simulation. So it's like a fundamentally different approach to understanding the universe. For simulation, let me use the things I know to create a bunch of parameters and create just play with it. Play with the universe. Play God. create a bunch of universes and see in a way that matches experimental data. It's fun. It's like playing Sims, but at the cosmic level.
Yes.
And then probably the set of terminology used there is very different. And maybe you're allowed to break the rules a little bit more. Let's have, like the Drake equation. Yeah, you don't really know. You kind of come up with a bunch of values here and there, and just see how it evolves, and from that kind of intuit the different possibilities, the dynamics of the evolution of a galaxy, for example. Yeah, but it's cool to play between those two. Because it seems like we understand so little about our cosmos. So it's good to play.
Yeah, it's like a big sandbox, right? And everyone kind of has their little corner and they do things, but we're all in the same sandbox together at the end of the day.
But in that sandbox does have super powerful and super expensive telescopes that everybody's also... All the children are fighting for the resources to make sure they get to ask the right questions using that big cool tool. Well, can we actually step back on the big field of stellar archaeology? What is this process? Can you just speak to it again? You've been speaking to it, but what is this process of archaeology in the cosmos.
Yeah, it's really fascinating. So I mentioned the lesser the mass of a star, the longer it lives. And again, for reference, for the next dinner party, the sun's lifetime is 10 billion years. So if you have a star that's 0.6 or 0.8 solar masses, then its lifetime is going to be 15 to 20 billion years. And that's an important range for our conversation, because again, if you assume that such a small star formed soon after the Big Bang, then it is still observable today. You mentioned old light before. Yeah, that light is like a few thousand years old, but compared to the age of these stars, it's nothing.
Mhm.
So to me, that's young. Comes straight from our galaxy. Oh, it's not far. These stars are not far away. They're in our galaxy, in the outskirts. They probably did not form in the galaxy because, again, hierarchical assembly of a Milky
They were
Way
eaten.
meant exactly. They formed in a little other galaxy in the vicinity, and at some point the Milky Way ate that, which means it absorbed all the stars, including these little old stars that are now in the outskirts of the Milky Way that I used to point my telescope to. So, what can we learn from these stars? Why should we study them? Now, these little stars are really, really efficient with their energy consumption. They're still burning, for the experts, just burning hydrogen to helium in their cores, and they have done so for the past 12, 13 billion years, however old they are. And they're going to keep doing that for another few billion years, same as the sun. The sun also just does hydrogen to helium burning and will continue that for a while, which means the outer parts of the star, well, pretty much actually most of the star, that gas doesn't talk to the core. So whatever composition that star has, in its outer layers, is exactly the same as the gas composition from which the star formed, which means it has perfectly preserved that information from way back then all the way to today and going forward. So I'm a stellar archaeologist because I don't dig in the dirt to find remnants of past civilizations and whatnot. I dig for the old stars in the sky, because they have preserved that information from the first billion years in their outer stellar atmosphere, which is what I'm observing with telescopes. So I'm getting the best look at the chemical composition early on that you could possibly wish for.
What kind of age are we talking about here? Talking about something that's close to that, like a 13 billion, 12, 13 billion
Yeah.
age range?
That's what we think. Now, as a small caveat here, we cannot accurately date these stars, but we use a trick to say, oh, these stars must have formed as some of the earliest generations of stars, because we need to talk about chemical evolution of the universe and Milky Way for a second. So, I already mentioned the pristineness of the universe after the Big Bang, right? Just hydrogen and helium. Then the first stars formed. They produce a sprinkle of heavier elements up to iron. Then the next generation of stars formed. That included, again, massive stars that they would explode again, but also the little ones that keep on living, right? So, and then the massive ones, again, explode as supernovas, so they provide, again, another sprinkle of heavier elements. And so over time, all the elements in the periodic table have been built up. There have been other processes, for example, neutron star mergers and other exotic supernovae that have provided elements heavier than iron, all the way up to uranium, very early on. We're still trying to figure out those details, but I always say pretty much all the elements were done from like day 3.
So iron is where, once you get to iron, you got all the fun you need. Most of the fun.
Yes and no. I really like the heavier elements, gold, silver, platinum, that kind of stuff.
For personal reasons or for star formation?
Well, both.
What's the importance of these heavier metals in the evolution of the stars?
So they're the spice of life. right? So every supernova gives you elements up to iron. That's cool, but at some point it gets a little bit boring because that always works. But that's the baseline. We need that. And that's certainly what came out of the first stars, and then all the other supernova explosions that followed with every generation. And it took about 1,000 generations, give or take, until the sun was made. So the sun formed from a gas cloud that was enriched by roughly 1,000 generations of supernova explosions. And that's why the sun has its the chemical composition that it has, including, and somehow the planets were made from that as well.
So the supernova explosions, the many generations, are creating more and more complex elements.
No, it just goes all the way up to iron,
Yeah.
and then it's a little bit more of all of these elements.
Just more.
Yeah, it's one sprinkle, then another, and it just kind of adds up, right?
Mhm.
Now, the heavy elements form in very different ways. They are not fusion made. They are made typically through neutron capture processes, but for that you need seed nuclei, ideally iron or carbon or something. So the supernova-made elements are very good seed nuclei for other processes that then create heavy elements. And because they cannot be made everywhere, some of my stars have huge amounts of these heavy elements in them, and they tell us in much more detail something really interesting happened somewhere.
Well, wait. I thought the really old ones would not have. So what does that mean if the old?
Yes, important clarification. So the stars that we are observing today, these old ones, they formed from the gas. And the question is, what enriched that gas?
Oh.
So it could have been just a first star dumping their elements into that gas all the way up to iron. And we have found some stars that we think are second generation stars. So they form from gas enriched by just one first star. That's super cool.
Yeah.
Then we find other old stars that have a much more complicated heavy element signature. And that means, okay, they're probably formed in a gas cloud that had a few things going on, such as maybe a first star, maybe another more normal supernova, and maybe some kind of special process like a neutron star merger that would make heavy elements. And so they created a local chemical signature from which the next generation star then formed. And that is what we're observing today. So all these old stars basically carry the signature from all these progenitor events. And it's our job then to unravel, okay, which processes and which events and how many, may have occurred in the early universe that led to exactly that signature that we observed 13 billion years later.
Is it possible to figure out like the number of generations that resulted in this, in these stars?
Well, we think we can sort of say, okay, this was like second generation or third, because the amount of heavy elements in the stars that we observe is so tiny. One normal supernova explosion is actually already basically too much. It would give us too much of it. And the thing is, you can never take away things in the universe. You can only add. There's no cosmic vacuum cleaner going around sucking things away. The black holes are probably the closest to that, but they would have taken the whole star.
Yeah, they take the whole thing. Not just
They wouldn't take stuff out of the gas, So we have maybe 10 stars or so now where we are saying that they contain so little of these heavy elements that there must be second generation, because how else would you have made them? And again, I want to stress that the elements that we observe in these stars were not made by the stars themselves that we observe. That's just a reflection of the gas cloud. So we don't actually, I had to say that because I love stars. We don't, at the end of the day, we don't really care for the stars that we're observing. We care for the story that they're telling us about the early universe.
So the stars are kind of a small mirror into the early universe.
Yeah.
And so what are you detecting about the stars? Can you tell me about the process of archaeology here? Like what kind of data can we possibly get to tell the story about these heavy elements on the stars?
Yeah, it depends really on what star you find. There are many different chemical signatures. We actually pair up these days our element signatures with also kinematic information, how the star moves about the galaxy. That actually gives us clues as to where the star might have come from. Because again, all these old stars are in the galaxy, but they are not of the galaxy. That's a small but important distinction. So they all came from somewhere else.
So you can rewind back in time, kind of estimate where it came from.
Yeah, so we can't really say, oh, it came from that and that dwarf galaxy. But interestingly enough, so I just a few days ago, I submitted a paper with 3 women undergrads. It was so good to work together, and we found a sample of stars that have very, very low abundances in strontium and barium, so very heavy elements. And I had a hunch for a while that these stars would probably be some of the oldest, because, as I said, heavy elements give you extra information about special events. And again, finding something that's really low means that must have happened either really early on or in a very special environment, right? Because we can only ever add. So if you find something that's incredibly low in terms of the abundance, maybe just one event contributed that max. So we looked at the kinematics, how are these stars moving, and they're all going the wrong way in the galaxy. How is that possible? Well, it is possible because now we come back to the protogalaxy. The protogalaxy was like a beehive. It just didn't really know what it was or what it wanted to become when it grew up. So, and it was absorbing all these little galaxies to grow fast. Some absorbed galaxies were thrown in going the main way, and some came in the wrong way. Happens.
Yeah, it happens.
But this could only happen early on when, it wasn't left and right and up and down. So stuff would come in from all ways. So now, 13 billion years later, we're looking.
Doing it.
Yeah, they're still doing it. And B,
Yes.
we just looked for stars that have low strontium and barium abundances. And then we look at the kinematics, and lo and behold, they're all at hundreds of kilometers per second going the wrong way. It's like, dude, you must have come in really early on from somewhere else. So we call this retrograde motion. That's a clear sign of accretion. So something that has come into the galaxy. And because they are so fast, and it's really all of them, that must have happened early on. You can't throw a galaxy into the Milky Way right now the wrong way. It eventually will turn around.
Can you actually just, in a small tangent, speak to the 3 women undergrads? Like it's pretty cool that you were able to use a hunch to find this really cool little star. Yeah, what's the process like, especially with undergrads? I think that would be very interesting and inspiring to people.
Yes, it was a wonderful little collaboration that actually emerged in the fall. I really like working with undergrads and grad students, postdocs, and I came up with a new concept for a class at MIT where I wanted to integrate the research process into the classroom, because sometimes people find it really hard to email a professor, hey, I'm this and that person, and I'm interested in your research. Could I possibly, come?
Yeah.
And I wanted to streamline that and give, just trial how it would work to provide a sort of the safe confines of a classroom where you just sign up and do research in a very structured way. And I developed it. It was a lot of work, a little bit more than I thought, to map up an entire research project basically from scratch in 10 worksheets so that they could do it, again, in a very structured and organized fashion.
Also, you created this whole framework for
Yes,
them to do
the
it.
whole thing. But the promise was, you come sign up for my class in teams of 2. You each get your own old star that has not been analyzed before. I don't know what the solution is, because in research, we don't look up the solution at the end of the book. We do not know what we're going to find. Our job is to do the work and then to interpret the numbers because our job as scientists is to find the story. Anyone can crunch numbers. Anyone.
To
It's
find this-
complicated sometimes, but it's
Yes.
doable, right?
Yes.
But coming up with a story, when you only have 3 puzzle pieces, what does a puzzle look like? That you have to be a little bit bold. You need to have some experience, and you need to kind of see the universe in 3D. You just need to kind of go for it, and that's the beautiful thing. I really love that.
And so this was a story of weird kinematics going the wrong way, combined with this particular weird signature in terms of the
Yeah.
heavy elements.
Exactly.
And you have to come up with a story.
Yes. And so the story of that paper is now, usually I don't say I find the oldest stars. You know, when I talk to my research colleagues, I talk to them about we find the chemically most pristine stars because that's actually what we measure, the chemical abundance that tells us, okay, it must have been 2nd or 3rd or 5th generation of stars, right? But these low strontium stars that go in the wrong way, like they're getting paid for it, they must be the oldest stars that came into the galaxy because they formed before the galaxy was the Milky Way, right? And it's so cool and it was so wonderful. So this class, it went so well in the fall. I had 9 people sign up. That's not unusual for a class, a specialty class at MIT, so small number. It was 8 women, and they were so into it that I said, okay, let's use this opportunity. You're going to do some extra work with me, and we're going to publish this.
Trying to publish.
Yeah.
I also like that you're using the terminology chemically more pristine. When I'm talking to younger people, I'll just say that I'm more chemically pristine than that. I like that description of age. So there's this term of metal poor stars. So
Yes.
most of these old stars are going to be metal poor.
Yes, I search for the most metal poor stars.
And what is that? Can we just define?
Yeah, what does it mean? I don't know who came up with this. I would love to know, but the universe is a complicated place. So many decades ago, someone clever came up with the idea to say, let's simplify things a little bit. Let's call hydrogen X, helium Y, and all the other elements combined metals, Z. When I give public talks, I always ask, is there a chemist in the audience? Let me just tell you, neon is a wonderful metal. And they're like, oh my God, what's he saying? I'm an astronomer, I'm not a chemist, so I'll get away with it. So if you just roll with it for a moment, all the elements except hydrogen and helium are called metals. Now, if we look again at chemical, or the concept of chemical evolution, that means more and more of all the elements, everything heavier than hydrogen and helium, gets produced slowly but surely by different types of stars and events. So that's a monotonously increasing function. And so we look for the stars that have the least amounts of heavy elements in them, because that means we are going further and further back in this process, in that function, almost all the way to the very beginning, and that is the first stars, right? They started that process. That's why I said it was such an important transition phase, because if things were, we call the post Big Bang universe pristine, just hydrogen and helium, and after that the mess started. As soon as you add elements to it, things kind of get a little out of hand. That ends in this beautiful variety that we have everywhere these days.
Yeah, and you're looking at the very early days in the introduction of the variety.
Yes, exactly. When it was still a little bit more organizable. But the variety of different types of metal poor stars we have is stark. Many different types of stars, many patterns we have sort of identified, but there are still crazy ones out there that we're still trying to kind of fit in.
So what kind of stars have been discovered? So you've already a while ago helped discover the star HE 1327 2326. Great name.
Yes.
And HE 15230901. What can you say about these stars and others that have been found?
I love them.
Okay.
They're my baby stars.
What do you call your baby stars? Is there
I'm probably the
cute
only
names?
one who can spit out these names without cheating.
Are there nicknames? Are there nicknames?
But no, that's
It's not allowed. Okay.
Well, some colleagues at conferences have just called them Anna Star, Friebel Star, because
Yes.
they didn't want to learn the phone number. You know, I get it.
Phone number.
And these
Yeah.
numbers are actually based on older sets of coordinates for these stars. So
Wow.
they yes, the minus in the middle means that they're in the southern hemisphere. So negative is in the southern hemisphere, positive is in the northern. And then 13 and 15 means they're sort of observable in the middle of the year.
Okay, so it's to do with the observation of whoever's observed.
Yes. But they have very different stars. Both absolutely significant, career-defining actually for me, but really pushed the envelope in very different ways. So HE 1327, the first one that you mentioned, that was the second generation star that we found.
Mhm.
And you know, usually people say like, oh, the first one is the big one and the rest is nobody cares. But to us, it proved that yes, we can do it. Because one, astronomers live in this sort of way of, you know, there are a lot of serendipitous discoveries and that's really great. But we need to show that we can do it again.
Reliable.
Because then we're onto something. It's not just some kind of weird quirk. And there are a lot of quirks in the universe. But we want to know, is that a real thing? Does that happen regularly? Is there something that we can learn? Is that a piece of the story? And so finding the second one that was even a little bit more extreme than the first one really showed, yes, our search techniques work. We can find these stars. They provide an important part to the story in the sense that if we had more than 2 stars, and by now we have about 10-ish or so, what do they tell us about the nature of the very first stars? And what we found, again, working with the theorists, of course, who run these supernova models, is that, so actually, let me, before I get into this, these 2 stars had huge amounts of carbon relative to iron. So we usually use iron as a reference element for what we call the metallicity, so the overall metal content, the overall amount of heavy elements in it.
So that's why it's called iron deficient.
So that's right. So these stars are incredibly iron deficient, which means they must be of the second generation, because there was, and interestingly enough, there was this discrepancy. A normal supernovae, until then, we thought would get us so much iron, you know, you would distribute that in the gas plug, and then you would form this little star that we're observing. But the iron abundance that we measured was actually much lower than that. And I already mentioned, you can't take things away. That must mean these early massive POP3, we call them population 3, the first stars, they must have exploded in a different way than we previously thought. They can't output as much iron because they just can't. Otherwise, it wouldn't match our observation.
Got it.
And so that's when we started to work with several theory groups on supernova yields. So what comes out of
From the explosion of the supernova.
Yeah.
That's cool. Supernova yields. And so this one was not yielding much iron.
Well, we needed to concoct a theoretical supernova that made less. And it's actually surprisingly difficult because you can always add more in the universe, right? But you can't take stuff away. So Japanese colleagues kind of came up with the idea of a fainter supernova that just doesn't have enough oomph, you know, when it explodes. So somehow there's less iron coming. But at the same time, then these stars show huge overabundances of carbon, you know, 1,000 times more carbon. So how do you now get 1,000 times more carbon out of these 4 first supernovae? That was the theoretical challenge. And because we didn't have just 1 star, but 2, that really spurred the field to think about what was the nature of the first stars? How did they explode? What are the implications? Because if they are not as luminous and bright and energetic, that has consequences for these early proto-galaxies in which, you know, they must have been located in terms of, you know, blowing the gas out, let's say, and disrupting the system. So much higher chance for the earlier system to stay intact for longer, right? So there's a whole tail of consequences. And this is what I mean with we need to find a story, because you one thing and it's like the dominoes, the consequences everywhere, and then you have a different universe, right?
What could possibly be a good explanation for something that yields a lot of carbon and doesn't yield a lot of iron?
Well, it's not so much an explanation, more like finding a mechanism for what happens in supernovae. And the official term, what was sort of, as I said, cooked up in order to explain the observations. And we have, by the way, found a whole bunch more of these stars, so that holds. And it's called a fallback mechanism. So actually, in the supernova, during the supernova explosion, a massive black hole emerges, and so some of the material falls back onto the black hole. So here is a vacuum cleaner now plopped into the middle, right?
Like a temporary one that just cleans up some of the
Well,
elements?
sort of, right? Because if you think of we haven't talked about this yet, but if you know what a star looks like, a massive star looks like in its interior before it explodes, you have hydrogen, helium still on the outskirts, and then you have heavier layers of heavier and heavier elements all the way up to iron. So you have an iron core in the center. And because you can't get any energy out of iron when you want to fuse to iron atoms anymore, right? That's when the supernova explodes, or what occurs really. It's actually an implosion first, and then you have a bounce of the sort of neutron star phase that occurs in the process, and then
So awesome.
Gets disrupted. Yeah, it's like this giant, basketball, and then whoa, it all goes out.
Explosion first, explosion after.
Yeah. And so in the process, right, if you make your black hole basically big enough, it will suck away some of the iron, because that's the closest in terms of the layers. You hold on to it. You don't let it escape. And carbon is much further out. You let it all go.
Nice.
And so
that explains why you can have a big moon and not much iron yield.
yes.
So is this explained HE 1327?
Correct.
And others like it.
Yes. So it's well established now that the lower the iron abundance of the stars are, the higher the carbon sort of gets. And carbon is such an interesting element in that regard. If we come back to the formation of the first low mass stars, right? So we had the hotter gas, just hydrogen and helium, that made the first stars. They were 100 solar masses or so, because the gas couldn't cool enough. So they were big and puffy. Carbon then, coming from the first stars, probably led to enough cooling in these gas clouds that enabled the formation of the first low mass stars. So think about what happened if there wouldn't have been any carbon, or the properties of the carbon atom would be different. It would not have cooled the gas in such significant ways, perhaps. There wouldn't be any low mass stars. We wouldn't be here today, right? And we're carbon based, and so I think carbon is really the most important element in the universe for a variety of reasons, because it just enabled this whole evolution that we're now observing and literally seeing in the sky. And it's really fascinating.
So combined with the fact that you have the iron deficient, so all of that is probably important to creating humans.
Yeah, we need all the elements, but if you don't have stars, like the sun, small stars that can actually host planets that have long lifetimes, you need long lifetimes if you want to have a stable planet and develop humans.
So carbon is kind of important in many ways.
Yes.
This is perhaps a interesting tangent. If I could just mention that you interviewed Mildred Dresselhaus, Carbon Queen, the remarkable life of the nanoscience pioneer. Is there something you could say about the magic of carbon and the magic of Millie?
Well, Millie was certainly magic. She was a professor at MIT for many decades. I met her a number of times. Her photograph, actually a young and an older Millie, is still on the wall every time I step out of the elevator in one of the buildings. I see it. She pioneered all sorts of carbon nano work. So she was a material scientist, very far removed from what I do on a daily basis. But yes, carbon has amazing properties when you study it. And again, that's indeed another aspect of why carbon is so fascinating. Not just in the cosmos, but also for us, making us, creating us in the way that we can use it. It's wonderful.
You sometimes think about this chemical evolution in this big philosophical way that we're the results of that chemical evolution. Like we're made of this stuff. We're made of carbon.
Yes, we're made of sources.
Yeah, and it came.
All right.
I mean, it's almost like a cliche statement, but it's also a materials, a chemical, a physics statement. We came from hydrogen and helium, and somehow this formation has created this interesting complexity of soup that made us. What are we supposed to make of that? Like, what? Did we just get really lucky? Why did we get all this cool stuff?
Yeah, that's a good question.
I don't think it's a question that has an answer. I keep just asking why.
Yeah.
But it's just this incredible mystery. So much cool stuff had to happen. Hot stuff had to happen to create
right.
us.
And so much could have gone wrong, and there would have been another outcome, And it's actually amazing how many things kind of fell in place. I mean, maybe that's all sort of self-deterministic in some ways, right? We are who we are because that was the path. Maybe we would have ended up being robots. I don't know. But it's certainly wonderful to, as scientists, for us to help contribute unraveling our cosmic history, right? I always say the biological evolution on Earth was absolutely facilitated by the chemical evolution of the universe, right? And one doesn't go without the other.
And that evolution,
from a human perspective,
that evolution seems to be creating more and more complexity. The kind of interesting clumping of cool stuff seems to be accelerating and increasing. And it's hard not to see as humans that there's some kind of purpose to it, like a momentum towards complexity and beauty,
Well, beauty's in the eye of the beholder. But yes, everything gets more complicated.
But there's also beauty to the chemically pristine universe in the early days.
Certainly is, yes. I love the desert with its nothingness.
Yeah.
It has so much aesthetics and appeal.
We came from nothing when we returned to nothing. So what about HE 1523? What's exciting? A red giant star.
Yes.
That's another one of your babies.
Yes.
13.2 billion years old.
So that one isn't quite as iron deficient as the other one. So probably not a second generation star, but easily second, third, fourth, fifth or so. We can't really pin it down, but it's also not super important for us. What is important is that star has a very different chemical composition, in the sense that, yes, we have all the elements up to iron there. They have sort of normal ratios, which means kind of the same as most other old stars and not too different from the sun, or at least, different in quantifiable ways. But it has this huge overload of very heavy elements. And what was so nice about that star in particular was that I could measure the thorium and the uranium abundance. And again, that was the second of its kind. But the uranium abundance could be more well determined, so we had a better grasp on that. Now, why are thorium and uranium interesting? They are radioactive elements. They decay. Thorium has a half-life of 14 billion years, I believe, and uranium of 4.7, which, to folks on us on Earth is a really long time, but those kind of timelines are really good when you want to explore the early universe. So there are two questions now that kind of come to mind. Where do these elements come from? And what do they tell us, right? And these, as we know, these heavy elements are made in a specific process. It's a neutron capture process, usually referred to as the R process, for rapid neutron capture process. We talked about seed nuclei before, right? So we still don't exactly know where this process can occur. So you have, let's say, a lone iron atom somewhere, and it is in an environment where you have a strong neutron flux, which means there must be lots of neutrons around. And again, when we talk about the site, we can surmise and ponder where that might be the case. But you have this iron atom and you bombard it with neutrons, and you do it incredibly fast. Now, what happens in the process? That iron atom, you collect lots of neutrons, it becomes really big and unstable. So it's a heavy neutron-rich nucleus that wants to decay because it's not stable, it's way too big. And so let's say you add only one neutron to it, that would already make it unstable. So it has a characteristic decay time that's called the beta decay time scale. So it will decay to a stable nucleus. So the neutron will convert to a proton, and that makes it stable. If you bombard lots and lots and lots of neutrons onto that seed nucleus within that time scale of the beta decay, that's how you get to this huge, fat, neutron-rich nucleus that then wants to decay, right? So the rapid process is you have your seed nuclei, they get bombarded, you create these really heavy neutron-rich nuclei. They're heavier than uranium even. The neutron flux stops, and then all these heavy nuclei, they decay. And they make all these stable isotopes that we know of, all the way up to thorium and uranium.
So that rapid nuclear
Yes.
decay is what creates all this stuff.
Correct. And the whole thing is done within 2 seconds. So just to add to the rapid here, it literally the snapping of my hand, it's all there. In my talks, I have this nice simulation that illustrates this creation of these heavy nuclei, and I always say this is the only simulation you'll ever see that's slower than real time. Because in astronomy, we show, this is how a galaxy forms, 13 billion years and 30 seconds. And really short, right? This is the opposite. Me showing you this, the elements are already long made.
So where and when does this happen?
So you need the strong neutron flux.
That's the pumping of the neutrons.
Yes, that's right. And so there are not that many options, right? So where do you find lots of neutrons in the universe? Well, it's neutron stars, right? Neutron stars form in the making of supernovae, of the explosions. Okay, so maybe some of this heavy material gets sort of made in the making of the supernova explosion and then gets expelled. Or you have neutron stars. So if the neutron star usually that's the leftover of a supernova. If you have two from a binary pair, so stars usually actually show up in pairs, and so it's not too unusual to create a pair of neutron stars that will still orbit each other after both of their progenitor stars have exploded. And those two neutron stars will orbit each other diligently. But as we know now, thanks to LIGO, the Gravitational Wave Observatory, we know already that before, but now it's been measured by LIGO, is that these two neutron stars, they will orbit each other for forever, but in the process they will lose energy. So that orbit is what we call it, the orbit decays, and eventually the two neutron stars will merge, and that results in an explosive event that has roughly the energy of a supernova, but the process is completely different. And the cool thing is, when these two neutron stars collide, they produce a gravitational wave signature, because neutron stars are super dense objects. They're like giant atomic nucleuses. So there's a lot of interesting physics happening already. And so if you basically form a super neutron star by smashing two into each other, more interesting physics happens. And that means that there's this ripple sent out, into the space, the space-time continuum, basically, what do people say, the ripples of space-time, it's like,
Yes.
It's like you drop a rock into water, right? You see the waves coming. So that's exactly what happens when two neutron stars merge. And this is neutrons galore, right? It's really violent to smash two neutron stars, so they're dense already into each other. And they in 2017, one of these events occurred, and the LIGO and Virgo gravitational wave observatories, they detected that. And then the astronomers pointed their telescopes in that direction, and they indeed observed what we call the electromagnetic counterpart. So there was something seen in the sky that faded over the course of 2 weeks. And that light curve, that light, was exactly what you get when you create all these heavy neutron-rich nuclei in the R process, and then the neutron flux stops, and then it takes about 2 or 3 weeks for most of them, of these nuclei, to decay to stability. So the astronomers saw in this electromagnetic counterpart the nucleosynthesis of heavy elements occurring. And that's just
That's amazing.
awesome.
So
So awesome.
that's electromagnetic counterpart to the gravitational waves that were detected with
Yeah.
two neutron stars
Yeah.
colliding aggressively, violently to create a super neutron star, and that's where you get all the neutrons and neutron flux somehow, and
Yeah.
that
Yeah.
the whole shebang that happens in 2 seconds and
Yeah.
creates a bunch of.
So that confirms that one of the sites, for sure, is for the R process to occur is neutron star merger. Interestingly enough, I have to mention this here, a year prior, in 2016, my former grad student Alex G and we discovered a small dwarf galaxy that is currently orbiting the Milky Way. It's called Reticulum 2, that was full of ancient iron deficient stars that also had a strong signature of these heavy elements, exactly like HE 1523. We weren't looking for that. I actually wanted to prove that they had really low levels of heavy elements, because that's what we had seen in all the other dwarf galaxies. And I was dead set on showing that is yet the case again, and that is the typical signature of early star formation. We already talked about low strontium and barium abundances and the oldest stars, right? This is what we had seen anecdotally in the ancient dwarf galaxies that are surrounding us.
So that's an ancient dwarf galaxy. That dwarf galaxy has a bunch of ancient stars in it.
Yes. And so now we find Reticulum 2, and it has the stars show the signature of the rapid neutron capture process, the R process, and we are like, okay, these stars are located in a dwarf galaxy right now. We have environmental information. They are not lost in the galaxy where we don't know where they actually came from. No, we know these stars were formed in that galaxy because they're still in it. And that we already deduced from that it must have been a neutron star merger that went off in Reticulum 2 at early time, that polluted the gas from which all our little stars formed.
Can you speak to what a dwarf galaxy is? Can you speak to what this Reticulum 2 dwarf galaxy is that is orbiting the Milky Way galaxy?
Yeah.
It's going to be eaten by it, presumably.
It totally is going to be eaten.
Okay.
I can't tell you exactly when. The Milky Way remains surrounded by dozens of small dwarf galaxies. They are collections of stars. Some of them, we call them ultra-faint dwarf galaxies because they now only contain, a few thousand stars. Very, very faint.
It's still detectable?
Yes, because they're fairly close, and we detect actual individual stars now. So I've observed some of the faintest stars, you possibly observe with current telescopes in these dwarf galaxies, because I was like, I need to know what the chemical composition is, because there are leftovers from the early universe, right?
Yeah.
They did not get eaten, so they're still in their native surroundings. It's like getting the lions in the wild, right? I got to study those and compare to the counterparts that got eaten and are now in the Milky Way. And so
presumably most of those stars, not all those stars in that dwarf galaxy, are really ancient.
They're all really ancient, because actually, as it turns out, if you have a small galaxy, there was a process early on in the universe called reionization that kind of heated up everything. And together with some supernova explosions in an early shallow, bound system, all these little systems lost the gas. It was sort of blown out, or it simply evaporated, or both, probably both. And so these systems have been unable to continue to form stars since. So it's the best for us stellar archaeologists that you could hope for, because it's a whole bunch of stars still sitting there. It's not just one, it's a whole bunch of them still sitting there ever since, and literally nothing has happened to them. They've just been waiting there for us.
So from the archaeology perspective, what is like juicier and more interesting? The old stars in the outskirts that have been eaten, or the outskirts of Milky Way, or the stars in the dwarf galaxies? What's of all the things you love about the world? You said you love stars, so which do you love more? Of
That's a hard one. I mean, I love them all, of course. They serve different purposes. The stars in the Milky Way, I can get much better data for them because they're brighter, they're closer, so they're brighter, and that tickles my fancy.
And they have interesting kinematics, presumably.
Yes, and we can get that. And so HE 1523, for example, that one is really bright. Only it's a red giant, so it's intrinsically bright and it's fairly close. And so the data I got for that was insanely good, and that yielded this uranium detection and thorium detection. I can never get that kind of data for dwarf galaxies, though. So that's a big trade-off. But the environmental information that we get along with the basic information about these stars in each dwarf galaxy is really, really valuable in establishing, these, for example, these site information, right? Because the galaxy is still there, so nothing crazy could have happened. So actually, to close that loop, probably some heavy elements come out of supernovae here and there, but somehow my theory colleagues tell me that the normal supernova just doesn't have enough oomph to really get the R process going and doing it all.
So you need these orbiting supernova.
We need probably the neutron star mergers, or we need a special kind of supernova that's maybe extremely massive or heavily rotating or does something else funny, right? To really kind of get that particular process going. But the normal supernovae don't do it, right? So only a little bit comes out. But you could come along and say, Anna, why don't you just take 100 supernovae together to build up the yield, right? But then I come along and say, look, this dwarf galaxy is still intact today. If you would have plugged in 100 supernovae into this little system early on, it would have blown apart. It would have blown apart past 5 supernovae or 10. So that's a really important constraint that we have, that these systems are still alive. Right, so it helps us to pin down where certain processes could have possibly happened, and so it's just a different type of information that we get.
It'd be amazing if we could talk about the observational aspect of this, the tools of observation. So, what telescopes do you use, and what does the data look like? And I think I've read a few interesting stories about the actual process of day-to-day observation. A bunch of probably late nights.
Well, yeah, astronomers are doing it all night long, so
Lots
of late nights.
Can you explain the all night long aspect of it?
Well, let me start by saying I mostly these days use the Magellan telescopes in Chile. They're a 6.5 meter telescope, which means the mirror diameter is 6.5 meters. That's not the largest that is out there, but it's among the largest, and I use a spectrograph because I'm a spectroscopist. I don't take pictures. And that particular spectrograph at that telescope is actually unusually efficient, so it kind of makes up for the fact that the mirror isn't as large, let's say the 8-meter telescopes from the Europeans or so. So I'm very happy with that.
Efficiency meaning?
How many photons get collected sort of per time unit, because that's always the limiting factor. Prior to the pandemic, we would travel to Chile to do our observations. Those telescopes that's the last observatory where people were sort of supposed to travel there and take their own observations. Most other observatories basically have staff there by now who take the observations for you.
So there's the scientists are specifying where to point the telescope, and they're sitting there and collecting the data, making sure the data is collected well, the cleaning of the data, the offloading of the data, all that kind of stuff.
Yeah, so it's mostly done for them.
Yeah.
Obviously, that's super convenient, but it also takes takes away a central part of what the work of an astronomer is, which is data collection. Right? We don't have an experiment in the basement where we can go day and night or whenever we please and ask a certain question of the apparatus, right? Let's turn this knob and see what happens. Let's turn that knob and see what happens. No, we only have one experiment, which is the universe, and what we see is what we get. And I think it's so important to take an active role in that. I really love going to the observatory. I've taken many students there over the years to teach them and to just show them what it means to be an astronomer, because you go to these remote mountaintops and it's such a magical environment, and you wait there, for the sun to go down, and then you get ready and you look outside, and it's such a serene environment, and it's a little bit out of this world.
You're sitting there to the sun down. It's evening, late evening, and what does it look like? What are some of the most magical experiences of that process?
Well, when you're on top of a mountain, climbers, I guess, get to see that probably. Otherwise, it's very calm, and the colors are so beautiful, and I always become much calmer when I'm there. Because I'm just there for one purpose only, and that's data collection. I can say no to my emails. I can say no to everything else because I'm observing. So there's literally less distractions because you're just there to do one thing.
And also the emails somehow seem less significant.
Yeah. It's just you can afford to focus on this one thing, and it just kind of does something to you. It's a little hard to describe, but if you then fast forward, maybe I can speak a little bit about that. And I have done a lot of astrophotography there as well. So and I observing faint dwarf galaxy stars. These are like 45 minutes, 55-minute exposures. So you actually have a lot of time. So I would run outside and just lay on the ground under the southern Milky Way, beautiful, right up, there. And I would just lay there like the snow angel, and just stare up there and just kind of let my thoughts sort of pass through my brain, and just like I'm one of it, right? We talked about this in the beginning. This is when I personally have the feeling that I'm a part of it. I belong here, rather than feeling kind of small. Yes, I'm small, but there are many other small things, and lots of small things make one big whole.
Yeah,
right?
we're part of that big whole.
And
so that's looking at the inner spirals.
Yes.
Nuclear galaxy.
And just this dark sky with the bright stars. And I have described this in my book years ago. If the Milky Way is all bright above you, you don't need a moon or anything. You can walk in the starlight and you will find your way. There are no trees there for safety reasons, but you wouldn't even run into a tree, right? I mean, you can almost see the shadow, from the starlight, because it's such a dark sight, and the stars are so bright. And these are kind of moments that kind of change you a little bit. And
you see the unity of it all.
Yeah, and it's just you and nature, and with modern civilization and all of that, I think we often try a little bit too hard to be removed from nature, to be independent of it and figuring it all out. But at the end of the day, we're just a part of it, and that really helps me to remember that we're one and the same.
Well, that fills me with hope that I tend to think of us humans as in the very early days of whatever the heck we are. So that makes me think thousands, tens of thousands, hundreds of thousands of years from now, that we'll be whatever we become, we'll be traveling out there to explore more and more and more.
Yeah.
So what you're doing is the early days of exploration with the tools we have.
Yes, the early seafarers looking at the sky for navigation.
Coming up with different theories of what's on the other side with the Earth. It's starting to gain an intuition that the Earth may be round, and then we might be able to navigate all the way around to get to financial benefits of getting spices from India, whatever the reason, whatever the grant funding process is all about, but ultimately actually results in a deep understanding of the mystery that's all around us. And, I mean, it's just to travel out there. Like, to me, the discovery of life in the solar system, I really hope to see that in my lifetime. Some kind of life, bacteria, something, maybe dead, because that means there's life everywhere, and that just the kind of stuff that might be out there, all the different environmental conditions, chemically speaking, that are out there. And it just seems like when you look at Earth, life finds a way to survive, to thrive in whatever conditions. And so maybe that process just kind of humbles you. Is super exciting to know that there is life out there of different forms. And of course, that raises the question of what is life even? We tend to have a very human-centric perspective of what is a living organism and what is intelligence and all this kinds of stuff. And all the work in artificial intelligence now is trying to challenge our ideas of what makes human beings special. And I think we're doing that through all kinds of ways. And I think you're working some part doing that as well. Like the unity you feel is realizing we're part of this big mechanism of nature, whatever that is, that's creating all kinds of cool stuff, from the humble, pristine origins to today. So what is, if you could just kind of linger on the process of the data, what does the data look like? And how does the raw data lead to a discovery of an ancient star?
Well, as a spectroscopist, we have to, I guess, talk for a brief moment about what a spectrum is. Everyone, I hope, has seen a rainbow in the sky. That is basically what we're doing. We don't send the starlight through a rainbow that then gets bounced around and splits up the light into the rainbow colors. We do it with a spectrograph, so basically a prism. So we send the starlight through a prism of sorts, and that splits it up, and then we record exactly that. So it's a little 2D picture, actually, of a spectrum. Now, it's not going to look colorful. It's just black and white. Different colors have, of course, different energies. That's what we record. More specifically, we record it as wavelengths. So wavelengths and frequency and energy is all the same at the end of the day. We process that little image in a sense that we do a crosscut and then sum up a few columns so that we get all the data that we recorded. And what we see is it's a bit funny to describe just with words, but a wiggly line with lots of dips. So the 2D processed spectrum, we call it continuum. So it's just a flat line, basically, and then there are dips. So the interesting things are the dips. If you think back of the rainbow, what we actually see in our stars is not just a rainbow, but it would be a rainbow with lots of black lines in it, which means certain little pieces of color have been eaten away by a certain amount. And so we can no longer see it as well, or not at all. Why is that happening? So if we come back to our stars, what we're observing the stellar surface. We can actually never peer with our telescopes inside. We only ever can go after the surface. And the surface contains, or the surface layer contains, different kinds of elements. Okay, every one of those types of atoms, so elements are just different types of atoms, they absorb different photons that are coming from the hot core where the fusion is occurring. And so that means that if you were the observer, with a spectrograph or without, you will see the starlight, but certain frequencies, certain energies of that light will have been absorbed by all the different atoms in the gas. So you see less of them. And so those are the dips. And the strength of the dips tell us, which element was it, and how much of that element was or is in the star. So we have many, many, many dips. The solar spectrum, for reference, all the dips are overlapping because the abundance of all the elements is so high. It's actually a very complicated spectrum. My spectra really look like a straight line, and then there's a dip here, and then there's a straight line again, there's a dip there. The sun doesn't have straight lines. I mean, it's just all absorbed in some form or another. But the old stars have so little of all the elements that there are only occasionally these dips that then indicate, okay, that one at that wavelength was iron, and here we have carbon, and there's magnesium and sodium, and there's a little strontium line here. So we have a much easier way to map out this barcode that the spectrum, pretty much is at the end of the day, and to then measure the strength of these, we call it absorption lines, to then calculate with existing codes that mimic the physics of the stellar hemispheres, like how much was absorbed, what kind of elements were present in the stellar hemisphere. And so this is how we get to our abundance measurements, and then altogether that gives us the chemical composition and that particular signature in that star.
If you ever look at like the raw spectrograph and the absorption line, and they're able to see, intuit some interesting non-standard outlier kind of patterns, or does this have to do heavy amount of processing?
We actually process it's fairly straightforward to do our processing. We do it at the telescope, so I often take a shorter exposure first, let's say 10 or 15 minutes. So mostly when I do discovery work, we would just take a quick look spectrum, then we process it while we observe the next star. Then we take a quick look. We have what I call the summary plot. It's a collection of little areas in the spectrum that have the key positions, the positions of the key elements in it. And it's kind of like reading the tea leaves. I have stared at so many spectra. I just need to know, I just need to see our summary plot, and I can tell you exactly what the numbers are going to be.
And also to tell if it's going to be promising to get further.
Exactly. And so that's a thumbs up, thumbs down. You're worth my time or not. In most cases, it's not, or it's good enough. We can do a basic analysis, maybe publish this as part of a larger sample, just so, we output that we have observed the star and their basic nature. That's an important part to publish as well. I had a run. So now we do remote observing. I do all of this now from my home, from my living room, all night long. I often work with colleagues, so we do it over Zoom, and we process the data. We look at it, same thing still, and we just found a star that had a very low iron abundance, and then we decided, okay, that looks interesting. We're just going to keep exposing. So we took more data on it on the spot, and we're writing up the paper right now.
How do you know where to point the telescope?
It's not random. There's a lot of work that goes into that. I began my career by trying to answer that question, as in like doing the search process. That's why I called my book that I've written some time ago, Searching for the Oldest Stars, because searching is one thing, it's very time consuming, and then on top of that, not everyone finds, right? And I often don't find, but I keep searching because our techniques have established that yes, we can do it if we're just patient enough and keep going, because it's a numbers game, and that's often the case in science, and that's something that not enough is talked about, how tedious it is and how long it takes to get to that one discovery, right? That moves the field further.
And how difficult it is to believe that there is a thing to be discovered.
Yes. If we have the saying, I learned this, I think, from my supervisor. 1 star is a discovery, 2 is a sample, and 3 is a population. So as soon as you found 3 of roughly the same kind, you're done. But you need to get there.
Yeah, probably the first is the first, right?
Yeah, but it kind of remains really hard. But the thing is, then at past 3, many of us are, okay, we solved that problem. We've shown it 3 times. We can do it. That's a thing, right? That's a population. 3 iron deficient stars, let's say, right? That's one puzzle piece. Now we can move on to the next thing.
That's an indicator that there's many more.
Yes.
Potential.
Yes. So to cut a long story short about the searching, we started early on with what's called low resolution spectroscopy of many stars. So for example, my thesis work almost 20 years ago was piggybacking off a quasar survey that had collected. So quasars are basically giant supermassive black holes that are really far away. So you only see one big bright light point. So it looks like a star, but it's actually just a giant supermassive black hole that outshines its own galaxy. And people had been trying to study those, and they had taken little spectra of all things in the sky. And it turns out, you can fish out the actual stars from that and look for certain signatures that might indicate low metallicity stars, so stars with low abundances. And so it was painstaking work to then take medium resolution spectroscopy to get a little bit more information and to use approximations and to kind of get candidates that we can then eventually take to the big class like Magellan to get a high resolution spectrum. So we really see the dips of all the individual elements that then give us the final answer. Is it yay or nay? These days, with another grad student, I developed a new technique to use images actually of all the stars in the sky taken with very narrow filters. So it's like you're wearing very specific glasses that only let so much light through. And so we can do similar things through having several narrow band filters, what we call it. To fish out things that have no absorption over here, so just the straight line, and then a little dip here, so a little something there, and that has proven fairly successful in recent years.
So looking at broader regions of space.
That's right, because these stars are a little bit like a needle in the haystack, right? There are not that many left over, and certainly the galaxy has made plenty of stars in between. We need to comb through all of those to get to the goods. So we always start with millions and then work our way down, and in the end we have like 3 good candidates.
I wonder how those ancient stars feel that they were noticed. They probably know that nobody pays attention.
Well,
no, I'm just kidding.
we're all special, right? So are the stars.
It's good. It's inspiring, even if you're the outcast. In your pristine nature, you still might nevertheless be noticed. I'm hoping the same about humans and these observers. Is there something else you could say that's about the challenges of this kind of high precision measurement that you're doing? So this kind of collection of data, trying to kind of pull out the signal from the noise out there.
Well, that's literally what we're doing in multiple ways, actually. So we're trying to find the needle in the haystack, and then we find something, and then it turns out it's just a little bit too faint to actually get the kind of data quality on it that we would like, or that would be warranted given the potential of the star, right? It's like, ugh.
So there's always noise. There's always a little bit of noise, and you have to try to say, like, what, how special is this when you're looking at the absorption line?
Yeah. So the most iron poor stars, their iron lines are so tiny that they're literally, almost in the noise. So you need incredibly good data to make detections. And the funny thing is, we're looking for the nothingness of, let's say, the iron lines, but then we don't want nothing, because if there's nothing in the spectrum, we can't measure anything. We can only get an upper limit. But we'd really like a measurement. So we are looking for the last little bit that you could possibly detect. And that's the strong function of the brightness of the star, because the telescopes have the size that they do. That's not going to change for a while. Hopefully, eventually it will, but it's going to be at least 10 years out. And so, yes, we're often literally stuck in the noise because we can't make the measurement. So actually, the record holder for the most iron poor star only has an upper limit. We can't get enough data on this to actually pinpoint a measurement, to then take it to our theory colleagues and say, like, give me this little iron out of your first star. So it's a bit frustrating, but also super exciting at the same time.
let's go to both sides of that spectrum. What's like the most exciting discovery to you personally? Where is there a moment you remember that you saw a piece of data and your heart skipped a bit?
Yeah, of course.
Is it HE 1327?
That was definitely one of those moments. I wasn't actually present at the telescope, but we were sent the data immediately from our colleague, and we just looked at it, and our eyes got really wide. And was like, "Oh my god, is this really what we think it is?" So we had to run some numbers, and it was, and it these are magical little moments. The thing is, often we have false positives,
Yeah.
and so there's always this kind of period, and often it's I don't know, 10, 15 minutes where you need to make some tests to kind of make the decision. Is this really something I should keep observing now? Is this really as good as I think, or am I being fooled by something, right? So actually, if you take a spectrum of a white dwarf is the leftover core of a star like the sun that has gone extinct. And white dwarfs have lost all their outer atmosphere, so it's just the hydrogen-helium core. So they look like a metal core star because that's only hydrogen-helium left, right? But the hydrogen lines that you can see in the spectrum of our stars and of the white dwarfs are a little bit wider than normal. So you need to have a good eye just to check, does this look a little bit wider than us? Is this a white dwarf who's fooling me here, right?
Yeah.
And so it's like this moment, it's like, oh my God.
It's just minutes of nervousness.
Yes. And sometimes, it's a dud, and sometimes not.
What's been a big that you remember heartbreak, like a painful low point? Is it all leading up to the first? Is it all about HE 1327 again? Just the leading up to it, or has there been like a? Has there been like low points in this search?
That's a good question. I mean, it starts with mundane things, as in like you won your telescope time, you traveled there, and the weather is completely cloudy, it rains, and you had 3 nights, which is a lot, and you go home empty-handed. So that's definitely a low point. Probably not what you were thinking of, but there is a certain occupational hazard to it.
Which requires resilience and patience.
Yeah, and you just gotta learn to live with it. Coming back to Reticulum 2, actually, that little dwarf galaxy, that was a run that we had, and the weather was incredibly bad. And I had sent my student there, and I was at home, and he calls me at 2 a.m. and he was like, Anna, I think I observed the wrong star. I'm so sorry. There is this line there, this Europium line, and it looks like a metal-rich star. And I was like, it's cool. We all make mistakes. Send me the data. Send me that summary plot. And so I look at it, I was like super tired. It's like, I can't really tell. It doesn't look wrong, but I can't tell you right now that it's right either. So why don't you go to the next target? And he calls me back an hour later. Anna, it looks just the same. What am I supposed to do? And then I joke, well, maybe we found an R-process galaxy. Let's go to the next one. And the weather was degrading. And so to cut a long story short, we had to come. So he was observing the right stars. It was an R-process galaxy, the first one we had ever discovered, totally unpredicted. We had no idea that this was a thing. I mean, of course, we thought that, such a thing might possibly exist, because why not, right? Neutron star mergers happen somewhere. Crazy supernovae probably too. But we were not prepared in that moment to find this thing. And in the end, the weather was getting worse and worse, and we wanted to see how many R-process stars are in this galaxy. So we managed by a hairline to observe the 9 brightest stars, but the data quality was atrocious.
And the weather affects the data quality.
Yes, absolutely, because these were really faint stars. And so we were really lucky by making a very tight strategy of getting the absolute bare minimum for all the stars, so we could at least take a very crude look. Is it a yay or is it a nay? We couldn't even say yes or no, just to get an idea, because we needed to know. Why was that important? Because we could only observe this system again 9 months later.
So there's always a window of observation.
Yeah, it was setting. This was our chance. It was going away with the clouds, you know. Yeah.
That was super high stakes.
But we just made it. Like, really, it was almost impossible, and it was just. And the thing is, this is such a serendipitous moment. In a serendipitous moment, the enhancement of these heavy elements was so strong that even in this really crappy data, we could still see the enhancement. Right? The absorption was so strong that it stuck out of the noise. If the enhancement wouldn't have been as strong, we would not have been able to say anything, because we wouldn't have been able to tell. But because it was so extreme, it lent us a hand, despite the weather and all, to say, like, yes, this is it. So that was quite the night.
Luck. I mean, a lot of this is just luck. So that was the first Our Process galaxy discovered.
Yeah. I didn't sleep all that much
Do you have hope? Are you excited about James Webb Space Telescope and other telescopes in the future that increase the resolution and the precision of what can be detected out there?
Absolutely. JWST is fantastic already. I am not planning to use it personally, although I think I'm on 1 or 2 observing proposals, actually, because similar to what we already spoke about, we're interested in the same thing. We're just kind of looking at it different sides of the fence, right? I have my old surviving stars, and I concoct these little stories about what the earliest galaxies may have looked like, what the objects were that contributed, you know, energy and elements and all these things. And my JWST colleagues, they try to detect some of these earliest photons from these earliest systems to look at the energetics and other things, you know, what was there, how many, these kinds of things, right? So together we're trying to explore this first billion years, but we do it in very complementary ways. And so I'm very excited to see what they can come up with, and how that helps me to inform my stories better and more comprehensively.
What do you think is the future of the field of stellar archaeology? How much can we, maybe what are the limits of our understanding of this first billion years of our universe?
Well, obviously, lots of limitations in the sense that I always say, I have a metal core star for any of your questions. Because there are so many different kinds out there. And we still find new patterns sometimes, right? And there needs to be an explanation. The question is it ultimately just one quirky star? Is it 2? Is it 3, right? Is it a sample? Right. Is it a population? So we haven't concluded that kind of work yet.
So every metal core star is a kind of data point that you can use to improve the quality of your model of how is the evolution of the early universe.
Yes. And I would say we've made huge progress over the last 20 years. When I joined that field, it was in its infancy, and there was this serendipitous discovery of that first, second generation star. And we have filled in the canvas a great deal since then. And this is what I have greatly enjoyed about doing so, because there was so much discovery potential, and it's been dying down a little bit because of all the progress. It's on the up and coming again, because there's so many large spectroscopic surveys in the works now that will just provide a different level of data that we haven't had before. I'm sort of these older generation. I have only very few colleagues. I work in small teams, and I observe every single star myself. That, you know, whatever I can, I do myself. I don't generally take other people's data, or at least certainly not in the end stage. And you know, I'm not a big data kind of person, although we all headed that way. I certainly use data from Gaia, astrometric satellite for the kinematics, for example. But that's personally a new thing for me to use sort of big sky surveys that are available. So it's still very sort of hand-grown field, where we do our individual observations. I have enjoyed that a lot, but that's about to change.
So one star at a time.
Yes,
I mean, there's power to that, to build up intuition of the
Absolutely.
early universe by looking one star at a time.
yeah. And this is how you can really drill down on the questions that you have, right? Because you control what data you get. Otherwise, you have the data that you have, right? You get what you get, and you don't get upset. I don't like that. I'm a little bit snobby. I really like to formulate my questions, go to the telescope, and then come what may, I will try to get it.
And also develop the intuition of where the data can be relied upon and where it can't, and all the different quirks of the data and all that kind of stuff.
Yeah,
Sometimes a lot is lost in the aggregation of the noisy data.
yeah. And there's always the danger if you have someone else's data that you just don't really understand the limitations, completeness things, how certain things were set up, and you get out what you put in. So I'm really particular about that, and it certainly paid off for me. That's one of the main notions that I try to teach in my classes and to my students, that you need to be able to formulate your question really well, because otherwise you're going to get an answer to a different question, but you won't notice that that the goalpost has shifted in the meantime, right? So your interpretation can only be as good as the question. If you need to change your question, that's cool, do it, but then it needs to pair up with your interpretation again. And so really being in the know about every step of what happens, that leads to quality results, I think. That's why I have sometimes little trouble with sort of big data and statistical analysis. Yes, on average, that's true. I'm not debating that. But I'm the kind of person, I like to look at the outliers, so not the bulk, but the special ones. And they just need to be treated in a different way. And there needs to be an acknowledgement of that, different ways for different things.
So big data can look at divorce rates, and perhaps you and I are more interested in the individual love stories.
Yes, that works for me.
So I don't know if it's possible to say, but what do you think is the big discoveries that are waiting? Is it on the different dynamics of the yield, the common narrative, the common story of how some of these metal poor stars are formed? Is it where the discoveries that you think will come?
I think the individual discoveries are actually, we've made most of those, certainly through individual stars. Finding yet another second generation star is incredibly important for me, but isn't really going to move the needle. Finding 50 of them or 100 of them, that would move the needle, but that's in order or two magnitudes up. And new search techniques and new surveys may enable that, but would you still call that a discovery? Right?
So that's just a scale. It's a scale.
Yeah. So I think about it more like literally of the puzzle. Let's say you have 1,000-piece puzzle, and you have 900 pieces in there. If you're a person like me, I want to get to the last one. I'm not going to leave it. It's like, okay, I see broadly what this is going to look like, right? I'm done now. No, I want to get to the last one. Is the picture globally going to change? No. Are we going to figure out all the details and how it really works? Yes, right?
So really careful,
Getting
detailed map
into
out
it.
the ancient stars of our universe.
Yeah, because I think that's what many of us scientists are little bit detail obsessed. But I think that's our job too, right? To really kind of make it airtight, to really walk away saying, I fully understand this. Not just broadly, but we really know now. And so more and more of that is going to happen. And so I think this is probably true across astronomy. These individual 10 sigma discoveries become less and less. If they were easy, we would have made them already, right? Which means we have made many of them. But really filling in the details is the next sort of level of discovery. Maybe we need to find a new word for that. The hopes and expectations that go along with the word discovery are so enormous we may not always be able to live up to that. But it doesn't mean that we're not finding out new things. It's just a different kind of quality because the questions have shifted. You close one door, suddenly there are 10 new open doors that we want to explore and march through. And that's finding these last puzzle pieces here and there that really make it airtight.
And so there's a lot of value and a lot of power and beauty to the discovery in the big picture of our universe and in the details.
Yes,
So both
we need both. Absolutely.
Perhaps drifting into the philosophical, let me ask about the Big Bang as we kind of encroach onto it. So your work is kind of taking steps back through time in a weird way. Do you think we'll get to deeper and deeper understand the really, really early days of the Big Bang? And the philosophical question, do you think we'll be able to understand what was before the Big Bang or why the Big Bang happened? Do you think about that stuff?
Not with stars, for better or for worse, because stars only probe the time when they were formed, and the Big Bang is surely before then. I mean, I often talk to my students about the difference between math and physics. Let me give you an example. We talked earlier about HE 1523, and I was happy to share with you that I measure thorium and uranium, but I actually didn't quite close that loop. So we did this to try to attempt to calculate an age for these stars, right? But they rely on us knowing how the R process works, how these elements are created, where it happens, and then how those elements get dispersed into the gas and end up in the next generation star. So quite a few question marks. So that's how we got to the age of 13.2 billion years. This is probably not accurate, but this is the best calculation we could do. And the reason why I'm bringing this up is that was actually the average of multiple elemental ratios that each gave a certain age, and then we averaged that because for better or for worse, this is the best we can do. So some of these numbers said, oh, this star is 15 billion years old. And then others said, oh, this is 10 billion years old. And so I often use that in my class to say, like, what's the good news and what's the bad news here? Some ratios said 15, sometimes 10, right? Is 15 correct? And then I ask them, some people will say something. And so the thing here is that it's an absolutely correct calculation given the mathematical and physical model that we constructed. But does it make sense? No, it doesn't. If we believe the universe is 13.8 billion years old, 15 is ridiculous, yet it is correct. Isn't that interesting?
From a mathematics
Yes,
perspective.
it is not incorrect because this is what I calculated. Nobody made a mistake. Now, we can question whether that's a good model, but that's a separate issue.
So you're saying physicists are much closer to truth than mathematicians?
Well, it depends. It depends. Sometimes yes and sometimes no, right? So what our job as physicists is to take the mathematical model, calculate our numbers, and then ask the question, does this make sense, right? Now, in the case of 15, it doesn't, but we took the average anyway because that was the best we could do, right? So, all right, let's put that aside. Let's apply the same sort of thinking to the Big Bang, right? Math can tell us things that we as physicists cannot grasp because it doesn't make sense to us. Now, in the case of the Big Bang, that's a special case because we don't actually know what's supposed to make sense.
Yeah.
And this is where things get interesting. But this is where math will ultimately be the winner because we can no longer say this makes sense or this doesn't make sense because the physics is broken down.
But math breaks down too in the singularity of things.
Well,
Or no?
depending on who you ask.
Okay. Sure.
This is the current question, right? How much further can we push math, let's say, to the front of the Big Bang, if there is such a thing?
What's the front and the back? What's the front?
Well,
The front is the
before the Big Bang.
Oh, before
right?
the Big Bang. The front. Okay. To clarify,
Right,
all the doorways
yes,
and
yes.
the entrances.
So how far can we let the math go before that stops to make sense, right? And I don't know what the answer is to that, but it's really cool that because math doesn't have it's not limited by our physical nature, it can probably go a little bit further than the physics,
Yeah.
right?
And math can go into more dimensions than 4 dimensions
Yeah.
comfortably.
And it's judgment free because it just calculates things on its own. Whereas as physicists, we are so judgmental.
Yeah.
This makes sense. This doesn't make sense, right? It doesn't get any worse.
It's such a beautiful dance. And it's such a, it's so amazing that through this dance, you get to explore the origins of the universe. Like, doesn't the Big Bang just blow your mind? That this thing is just started from a point.
Yeah,
Now we're here.
yeah.
Hydrogen and helium. And then all the stuff you're studying. I mean, like, this evolution of chemistry created humans. We're here talking. And there's a lot more to the story. It's amazing.
Yeah.
And this kind of march that you're doing is observing data. And is there, you're looking at old light and old data.
But only a few thousand years, right?
Just a few thousand.
That's the difference between me and my JWST colleagues.
Yes.
Their objects, that light has traveled 13 billion years or whatever it was to us, and they're observing that now. My light has only traveled a few thousand years. It's nothing.
So whatever you observe now is likely still going on.
Yes, these stars are alive and kicking and having a blast.
1,000 years. Just a few thousand years. It's all it takes. If we can travel close to the speed of light,
Yeah,
maybe we can reach out there.
we wouldn't have any planets around those stars.
So is that a definitive intuition?
Well, what are planets made of? Elements, right? To take the Earth, it was all heavy elements, right? The universe needed to reach a certain stage first to have produced enough of all these elements to actually make a planet.
So on average, okay, right.
So that took quite a few billion years.
So they're not going to have a mechanism for forming planets. You could have visitors probably, but the kinematics of that are weird, are unlikely.
Yeah, I would say so.
So they're interesting in that they reveal the early chemical evolution of the universe.
Yes.
Not that they could be good vacation spots, but not.
Well,
there's
it would
not
be like
much-
a worm. Just
Fair
no,
enough.
no planet islands to go to chill.
In your book, you highlight the major contributions in the field by many women. Some of these women were not, as you describe, immediately credited for their discoveries. So for me, from a computer science perspective, the story also tells Harvard Computers. Who are these women, and what can you just say about the nature of science and humanity?
Discovering things is part of the human nature, right? And so it has happened for the longest time, not just by men, but also by many women. The field of stellar astronomy, which is my field, has particularly benefited from many discoveries made by women. You mentioned the Harvard Computers. That's a term used for women who worked about 100 years ago at the Harvard College Observatory, and they were hired for their low wages and willingness to do diligent and patient work to comb through the big data of the day. So the observatory director, they were carrying out large sky surveys at the time, and they needed that data needed to be processed and looked at and analyzed. And so many women, or several dozens, or 1 or 2 dozen women over the years, were hired to do this work. And in the process, because they were looking at the actual data and they were smart, even though they had often no formal education, they made a lot of discoveries simply by being in tune with what they were doing. So they weren't robots, as you know, the term computer would perhaps lead on. So Annie Jump Cannon classified thousands and thousands of spectra and found out that you can, stars have different temperatures and their spectra look according. We still use that classification sequence today. Cecilia Payne-Gaposchkin later on in, I think, 1925 was one of the first women to obtain a PhD in stellar astronomy, and she calculated that the sun is mostly made of hydrogen and helium. That seems normal to many of us these days, but at the time it was thought that celestial objects are made of the same thing as the Earth.
That's a gutsy, amazing discovery.
Yeah. It was later termed the most important thesis of humankind or something like that. What a revelation to realize that stars are made of hydrogen and helium, right? And this was exactly the time when people figured out why stars are shining, namely because of nuclear fusion, and that it's protons and the tunneling effect that leads to the actual fusion. Otherwise, the protons repulse each other; they don't come together. And so, what an incredible time it was back then. And so, stars and nuclear physics were very closely related, and it remains. Now it's called nuclear astrophysics. And so, many women had many contributions to that. Of course, prior to that, Marie Curie discovered 2 new elements. So awesome. Radium and polonium. Lise Meitner discovered nuclear fission. That is the basis for understanding the R process. This is exactly what happens in the R process. The heavy nuclei, let's say uranium, if you bombard it with a neutron, we talked at length about it, it will decay, it will fission, it will split into barium and krypton, let's say. So 2 lighter elements. That's exactly what we observe. I have always a higher abundance of barium than the heavier elements because of this fission cycling that she calculated in 1938 and 1939. So many contributions, and it's just so remarkable. If you just take that body of work, that changed how we do things, how we see the universe, how we understand things. Has led to so many subsequent discoveries, good ones and bad.
Well, all of it is taken together.
That's progress. Right? It's ultimate. Science is what it is. We have to decide what we do with that knowledge. Right? We can always use things for good or for bad. That's part of the human endeavor as well.
And also part of the human endeavor and the human nature is the issues with corruption and credit assignment and all these kinds of things that make this whole ride so damn interesting about what's right and wrong and about the nature of good and evil. That seems to surface itself in all kinds of places all the time.
Yes. Still. Lise Meitner was nominated for the Nobel Prize 40 times. More than that even. It's amazing. She holds the record for that. She never received it. Case in point.
And of course the Nobel Prize has its complexities. One is the credit assignment, but 2, even in astronomy, sort of assigning credit to a handful of folks when so many more contributed is a complicated story also.
Yeah, it's very complex.
Okay, sorry for the romantic question, but what do you is the most beautiful idea in astronomy, in stellar astronomy?
Well, so early on, when I was in high school, I was thinking like, okay, well, what do I want to do when I grow up, right? I knew I wanted to do astronomy, but I was a little bit torn because my interests were definitely stars, stellar astronomy, but also chemistry. I always had a fascination about the elements, so Marie Curie was a big role model. My friend actually produced a beautiful movie about the discovery of the elements. This is a theater play, but digitized, where when I saw it, I could actually kind of relive this sort of discovery moment that Marie Curie had. It sent shivers down my spine. It was fantastic. I mean, this is the kind of thing that I wanted to experience. But yeah, so nuclear physics and element creation and formation was really interesting to me. Chemistry, the elements, stars, and all of that. And I was like, I don't know if I ever find something that combines all of these things. And then I ended up in Australia, and I met this person, and he was working on all stars. And as I was sitting in his talk, hearing about this for the first time, it clicked all over my head. I was like, oh my God, it all fell in place, because we can use these old stars to study the elements, to learn how they're formed. We can get these clean signatures that help us inform the nucleosynthesis processes, and I know, of course, I need to know a lot about stars too. So it's like all together. And that was sort of a moment of magic. And then the fact that I have now done that for 20 years is just like I won the lottery.
It all clicked into
And
place.
so in some sense, it's an ongoing love story for me, if I could say it like that, where, I found my stars, my thing. And I'm fortunate enough to be able to keep doing that. And I'm happy to see where it will take me. It's an evolution, as with every relationship. You have to, if you don't march forward, you move backwards. I'm not interested in moving backwards. So I'm letting the field and the discoveries and the findings lead me to, and I'm often, it's not hard for me to follow sort of my hunches, and sometimes even at the telescope and say, let's take a look at this one. I have a good feeling, and then usually something good or not bad pops out at the end, and I really like that. That I have the freedom to do that I'm allowed to follow my hunches. Too many people, I think, are sort of boxed in with their job or their life. They don't have that kind of freedom. That's really important to me, and I certainly try to make use of that. I also try to teach that to others, to trust them, to learn. You need to learn your things, but then you need to also trust that knowledge, and you have a grasp on it, right? You get out what you put in. And being able to contribute in meaningful ways to our knowledge about our cosmic ancestry, our cosmic history, that's a wonderful thing.
And in this way, your personal love story with the stars evolves. What advice, you've already spoken to it a little bit, but what advice would you give to young people that are trying to find the same kind of love story in their career, in their life?
It seems increasingly hard for folks to find that. Sometimes I feel that young people have all the opportunities these days, and that's wonderful. But it's almost like that leads to some, what's the right word? They're a little bit too tired to make all the decisions, because at some point you need to put your eggs in a basket, and you need to be okay with that. We can't do all the things, even though we're often told you can be president too. And I think that's really important to convey. But at the end of the day, we can only have sort of one job or one type of profession. I'm not saying, you need to be locked in, but it's hard to change 180 degrees. And so lots of people, I think, are often afraid to really dig in, at least for some time, and get their hands real dirty and really learn from the bottom up.
On one thing.
Because they're afraid they're missing out on 99 other things. But life is a little bit missing out on 99 other things, because we only have 24 hours in a day. I have that feeling very often. There are so many things I would like to do, many things I would like to try to be good at. Sometimes I wish I had a different job, because I have other interests too, but I realized, okay, I can only do one thing. So I have no regrets. But this is a general feeling that I think I would think most of us have. But if it stops you from really digging and drilling down on one thing, to become an expert in one thing, to become really good at one thing that you call your own, then it just makes it difficult.
And so a fulfilling life is in part likely to be discovered in a singular pursuit of a thing, of one thing,
Well, yeah, or
for at least for a time.
yeah, for some time with your heart and your hands, because I think most people long to own something. You know, we all, I think, want to leave some legacy of some sort. You know, for our children, for humanity, for the planet. And I think it's really important for young people to strive for that and not lose sight or trade that for all the opportunities, because an opportunity is nothing if you don't do anything. You need to do something at the end of the day. So I chat with lots of people about this, and I often start by just saying, hey, tell me what you don't like. Because it's often much easier to you know,
narrow down.
let out what's not on your plate.
Yeah.
And then this way we get a little bit closer, and then it's like, why don't you take a risk and just sign up for something for 3 months?
But that's
You
what it
can
feels
afford
like.
that.
That's what it feels like, and it is that is a risk. Commitment is a risk
Yes.
because you're basically sacrificing all the other possible options. And then I guess you have to trust the magic you noticed in that thing.
Yeah.
If you notice one thing, stick with it, and then maybe there's something there.
Right. And this moment of kind of feeling it in your entire body and mind that this is the right thing, you know, getting there is probably really hard. But if you don't try, you won't find out.
The hard stuff is the fun stuff. That's also another thing you find out.
And then there's that, yes.
Somehow it doesn't make sense. You also mentioned that you have taken a little stroll into the artistic representation of yourself. Can you speak to that for a little bit?
Yes. Well, I already just mentioned. Sometimes I wish I had more time to do other things. So I find little sideways, I guess, to pursue things that I like besides astronomy, or at least I try to find connections. And so some years ago, I again, with the help of my friend who made this Marie Curie movie, she and I wrote a one-woman play where I actually portray Lise Meitner, who was an Austrian-German nuclear physicist. I'm from Germany, so I have the right accent for that. And we wrote this play about this moment of discovery of nuclear fission. Again, this is an absolutely critical piece that explains my work today. And we all stand on the shoulder of giants. She was one of those giants. And in some ways, it's of course a way for me to acknowledge other people's work that have come before me. It's a wonderful way to highlight the contribution by a prominent woman. And the way I do it is it's a 25-minute play in costume where I relive for people the moment of discovery. Then I turn into myself, and then I give a 30-minute presentation on the art process and the creation of heavy elements, because the audience can now perfectly understand that, the public audience, given the historic backdrop of this discovery that they just lived through my presentation. And it's a wonderful compliment that almost spans 100 years from one woman to the next, passing on the torch. And, you know, when we write up our results in, let's say, you know, magazines like Nature and Science, it's always about the results on the golden platter, perfectly prepared. The discovery is never described, only ever the results. You asked me beforehand, right? What does it feel to be at the telescope in this moment, right? I'm happy to talk about this, but it's nowhere written, ever. Nobody really talks about this. And so having a form of, theater of the arts to bring this exciting moment that is what we all want to experience as scientists to a wider audience is so profound and so rewarding. And they all love it because everyone can understand a moment of discovery. I was looking for something and then I found it. It's like you misplaced car keys, right?
Or love.
Yes. Everyone can
What the
understand
glorious
it.
experiences, yes.
The implications and the findings, that is much harder to understand for anyone. This is where the scientists' work truly lies. This is our job. But the moment of discovery is easy and it's beautiful and it needs to be said. And so taking my audience on this journey, what is the perils? What are my worries? And then, oh, here is the moment of discovery. Let me tell you about it. It profoundly transformed me. And here's how it went, right? It's so good.
And art is a way to reveal this fundamental human side of science.
Yes. The problem with science is that it's people doing it.
That's
Maybe
also
not a
the,
problem, but
that's
that
that's
is
also
it.
what makes it beautiful, right?
Yeah.
I mean, humans are fascinating. You know, we're able to come up with these ideas through all the struggle, through all the hardship, through all
Yes,
the hope,
yes, yes.
through all the search.
And
We
so
find-
the art's a great way to portray that and to broadcast that, right? I think this is how the audience really should be interacting with scientists. Much less about the findings, but really more about this yearning for answers, right? I need to find these copies. I need it because I need to go, right? It's like now. And then, oh God, here it is. Now I can go my merry ways. It's so relatable. We just need to find more and better ways to do that. So I hope to turn this into also a digitized version at some point to again make it more accessible.
I hope so too. I'd
So
love
far,
to see
I'm
it.
just doing it in person, but it's
I would
nice.
love it. I think a lot of people would love to see it. So I hope you do just that. Let me ask you a big, ridiculous question. You look up at the stars. You look up at the early stars. So let me ask the big question that we humans often ask and struggle to answer. What's the meaning of this whole thing? Why are we here?
We talked about, the biological evolution requires the chemical evolution for all of this to kind of play out, and carbon played this important role. And in some sense, we're just a consequence of all of these things being the way they are, right? So maybe this is just where we are supposed to be, because the laws of physics sort of work the way they do, and we talked much about the variety of everything really, and certainly from over here to over there, and things in the vicinity of where the sun and the solar system formed, they were the way they were, and life maybe was a necessary consequence of that. In some sense, I like to believe that, because then it becomes reproducible and we can apply that same argument elsewhere. If it's total chance, right, that makes it harder, and that's not truly satisfying to a scientist.
So it's a consequence of psychological evolution, which is the consequence of biological evolution, which is the consequence of chemical evolution, consequence of physical evolution, whatever disciplines. It's turtles on top of turtles.
Turtles all the way down, yes.
And you would have studied some of the most ancient turtles.
Yes,
At the
yes.
very bottom of the thing.
That's right. They live for quite a while.
Yeah, they do. Well, thank you for your incredible work. Thank you for highlighting both the human side and the deep scientific side. It's just, I'm a huge fan of your work, and thank you for everything you do. And thank you for talking today. This is awesome.
Of course, it was wonderful. Thank you.
Thanks for listening to this conversation with Anna Frabel. To support this podcast, please check out our sponsors in the description. And now, let me leave you with the words from Douglas Adams in Hitchhiker's Guide to the Galaxy. Far out in the uncharted backwaters of the unfashionable end of the western spiral arm of the galaxy lies a small, unregarded yellow sun. Orbiting this, at a distance of roughly 92 million miles, is an utterly insignificant little blue-green planet whose ape-descendant life forms are so amazingly primitive that they still think digital watches are a pretty neat idea. Thank you for listening. I hope to see you next time.
It is the most important right that Americans have. It's not a coincidence or an accident that it's named in the First Amendment to the Constitution. Without it, no democratic society can be democratic for long. And I'm an absolutist. That is, I believe that, for example, people say to me, but what about hate speech? Well, hate speech is much more important than love speech. And the reason is, I'm much more interested in knowing whom I should not turn my back on than I am interested in figuring out who loves me.
The following is a conversation with Harvey Silverglate, a legendary free speech advocate, co-founder of FIRE, the Foundation for Individual Rights and Expression, and the author of several books on the freedom of speech and criminal justice, including The Shadow University, the betrayal of liberty on America's campuses. Harvey is running to be on the Harvard Board of Overseers this year with the write-in campaign. So you have to spell his name correctly, Silverglate, promising to advocate for free speech and to push for reducing the size of Harvard's administration bureaucracy. Election is over this Tuesday, May 16th, 5 p.m. Eastern. To vote, you have to be Harvard alumni. So if you happen to be one, please vote online. It's a good way to support freedom of speech on Harvard campus. Instructions how to do so are in the description. As a side note, please allow me to say that since there are several controversial conversations coming up, I tried to make sure that this podcast is a platform for free discourse where ideas are not censored, but explored, and if necessary, challenged in a thoughtful, empathetic way. It's by having such difficult conversations, not by avoiding them, that we can begin to heal divides and to shed lights on the dark parts of human history and human nature. This is the Lex Friedman Podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Harvey Silverglate. You co-founded the Foundation for Individual Rights and Expression, also known as FIRE, a legendary organization that fights for the freedom of speech for all Americans in our courtrooms, on our campuses, and in our culture. So let's start with the big question. What is freedom of speech?
First of all, the organization, when I co-founded it in 1999, was called the Foundation for Individual Rights in Education. It focused on free speech issues on college campuses in academia. And only earlier this year did we decide to expand our reach beyond the campuses, which is why the name or the acronym FIRE remains. It's now the Foundation for Individual Rights and Expression.
The E used to be education.
The E used to be education, it's now expression. And we basically do a lot of the cases the ACLU used to do. The ACLU now more is they're a progressive organization rather than a civil liberties organization. And we've taken the role of dealing with free speech in the society generally. And now this is a particularly an era prone to censorship. Everybody thinks they're right and that people who disagree with them should not be able to voice their views. It's a very difficult period right now, both on campus and off campus. It's about as intolerant an era as I can remember. And I'm going to be 81 May 10th. I was born on Mother's Day, 1942. And I can't remember it being this bad. I was born during the McCarthy era.
So that says a lot.
And it sort of reminds me of that.
Well, let's start with that almost a philosophical question, a legal question, a human question. What is this freedom that you care so much about, that you fought for so much, freedom of speech?
It is the most important right that Americans have. It's not a coincidence or an accident that it's named in the First Amendment to the Constitution. Without it, no democratic society can be democratic for long. And I'm an absolutist. That is, I believe that, for example, people say to me, but what about hate speech? Well, hate speech is much more important than love speech. And the reason is, I'm much more interested in knowing whom I should not turn my back on than I am interested in figuring out who loves me or who likes me. So hate speech is the most important, in my view. and yet it's banned in, for example, schools. It's unbelievable. Kids are not schooled into understanding the glory of the First Amendment when schools say to them they shouldn't say things that are going to make somebody feel bad. The purpose of speech is to express honest views that people have, and so I believe hate speech is as important as love speech, and my view is more important.
So it should be brought to the surface rather than operate in the shadows.
Absolutely. Absolutely.
What is the connection between freedom of speech and freedom of thought?
Well, in a free society, thoughts start in the brain and then they come out the mouth. So they're different ends of the same spectrum.
So to you, the censorship of speech eventually leads to a censorship of thought.
Of course, censorship of the mode by which other people know what you're thinking.
So there's some aspect of our society that is the thinking is done collectively, and without being able to speak to each other, we cannot do this kind of collective
Correct.
thinking.
And out of speech, the theory is that ultimately out of speech comes truth. That isn't necessarily so, but I do think that when there's free speech, better decisions are made because people put their views on the table in a frank, accurate way, and then those views mix together and clash, and out of that usually comes the better decision. Not always, but usually, more often than not. But if somebody is not allowed to be sit at the table of decision making, then the decision making process is poorer, less robust, less diverse, and ultimately less successful.
Can you elaborate on the idea of free speech absolutism? So hate speech can be quite painful to quite a large number of people. Does this worry you?
Yeah. Living in a free society requires that you expose yourself to some discomfort. We call it pain. It's maybe emotional pain. It's not physical pain. But it's the price we pay for living in a free society. Every so often we're insulted. We're emotionally hurt. Think of the alternative. All the alternatives are worse. Nobody ever promised us a rose garden. We're lucky to be in a country that has the First Amendment. It's also it's the most diverse country in the world because of immigration. I mean, my grandparents, my father's side came over from Russia. My mother's side came over from Poland. I'm very happy that my grandparents came in from Russia. I would not want to be in Russia today. I'd probably be sharing a cell with a Wall Street Journal reporter. I'm thankful that they came in, and this is a great country. It's got troubles right now, but our country doesn't. And we had a civil war, we had segregation, we had the decimation of the Indians. We're not perfect, but it's the best place in the world for somebody who values liberty.
So you don't think that hate speech can empower large groups that eventually lead to physical action, to physical harm to others?
No, I don't. I think that we have developed a culture in which it's understood that if you don't like what you hear, you talk back. You write something. We don't punch each other. We insult each other. Is insulting great? Well, I don't know. It's okay. I used to, as a kid in Brooklyn, where I was born and raised in Bensonhurst. We used to say, sticks and stones can break my bones, but names can never harm me. And it's absolutely true. It was true when I was 5. It was true when I'm almost 81. So I've lived a long time. I've seen it all. And I'm talking from experience as well as theory. It's what happens when you reach your 80s.
I read that you had this line that you cannot be protected from being called an asshole.
Correct. Especially if you're an asshole.
Well, that's but you don't have to be an asshole to be called an asshole.
That's correct.
And I think the internet has taught me that.
Well, the internet has posed a particular challenge to free speech absolutists because of some of the stuff that's on there is god awful. But I have no different rule for freedom of speech on the internet than I have in newspapers or lectures or in classrooms or conversations among people.
What do you think about the tension between freedom of speech and freedom of reach, as is kind of sometimes termed? So the internet really challenges that aspect. It allows speech to become viral and spread very quickly to a very large number.
Yeah, but you know we've had revolutions in the modalities of communication. After all, newspapers were the first challenge. Radio and television posed a new challenge. The FCC tried, but ultimately gave up the attempt to control obscenity, for example. And the Supreme Court has been pretty close. The one thing that liberal and conservative Supreme Courts, right now we're in a conservative era due to Trump nominations. During much of my life, it was the Warren Court, it was William O. Douglas, Brennan, it was the liberal court. One thing they agree on is free speech. They don't agree on much else, but they do agree on free speech. And I think the reason is that they recognize that, well, my group is in the ascendance today, but it may not be tomorrow. And I want to have objective, clear rules so that when I'm in the minority, I'm able to voice my opinion. And so it's one of the few things that both sides of the political spectrum agree on. The only people who don't are the people way over on the right that I call the fascists, and the people way over on the left who are the communists. But with respect to most people in this on the political spectrum, Republicans, Democrats, socialists, libertarians, they agree on the primacy of free speech because it protects them when protection is needed.
So to you, even on the internet, free speech absolutism should rule.
Yes. Nobody's going to die. Remember, death threats are not law. They're not protected. Nobody's going to die. Though people are going to be a little bit insulted, that's the price you pay for living in a free society. And it's a small price, in my view. Some people don't have as tough a hide as others. Well, then develop it. I don't mean to sound cruel, but you're living in a free society. You develop a tough hide.
So that's the cost of living in a free society.
Yeah, there's a cost.
The thing is that it can really hurt at scale to be cyberbullied, to be attacked for the ideas you express, or maybe ideas you didn't express, but that somebody decided to lie about you and use that to attack you.
Well, first of all, there are some exceptions to this. Libel and slander is an exception. Direct threats are an exception. If you say such, I will murder you. That is not lawful. If you say to somebody, if you say about somebody, you beat your wife, that is not lawful. In fact, the person knows you don't beat your wife. There are some limits. Defamation is one. Direct threats are another. So it's not absolute. The First Amendment is not absolute. But it's more absolute than it is in any other society, and it's pretty near absolute. For example, fraud. If you sell somebody a car and you say, "Oh, this is in great running shape," and in fact it's an old jalopy and it's not going to make it more than 10 miles, that's fraud. That's not free speech. Free speech is not absolute. There are these limits, but they're very narrow, specific categories of limits.
But there's gray area here because while legally you're not allowed to defame a person. In the court of public opinion, especially with the aid of anonymity on the internet, rumors can spread at scale. Thousands, hundreds of thousands of people can make up things about you
You have to defend yourself.
using more speech.
We're through freedom of speech. We're big boys and girls. You have to defend yourself. In some societies, if you say something, if you say something nasty about Putin, you'll end up in the gulag. Say something nasty about Biden, you end up in the New York Times. Where would you rather be?
Well, let's talk about the thing you've done for over 20 years, which is fight for the freedom of speech on college campuses. So why is freedom of speech important on college campuses?
Well, it's everywhere in the society, but it's most important on college campuses. Why?